The Ultimate SAP S/4HANA EAM and PM Migration Masterclass. 275 Migration Incidents.
Welcome to the most comprehensive and production-realistic SAP EAM and PM Migration Masterclass ever created. Across this series, we will dissect 275 real-world incidents that commonly occur during the conversion from SAP ECC to SAP S/4HANA. Designed strictly from actual enterprise war rooms, this survival guide spans the entire project lifecycle, from strategic scoping and discover to high-intensity troubleshooting and hypercare and post-go-live optimization. Whether you are an enterprise solution architect leading a multi-plant transition, a senior functional consultant preparing for a critical project, or preparing for an architect-level interview, this series provides the deep, cross-functional knowledge needed to identify and resolve critical conversion risks before they disrupt your business.
Here is how those 275 migration incidents are structured across 6 parts.
We divide the complete migration lifecycle into 6 focused, phase-aligned parts. Part 1 this video. Discover and prepare phases related migration incident strategy, CVI and technical readiness checks. Part 2. Explore and early realize phases related migration incident sandbox conversions, SUM and DMO bottlenecks, and technical dictionary activation. Part 3. Realize phase-related migration incidents UX and security ABAP custom code remediation, Fiori adoption, and security role redesign. Part 4. Realize phase-related migration incidents data and integration cross-module middleware, external interfaces, and data migration cockpits. Part 5. Deploy and cutover phases related migration incidents cutover strategies, downtime optimization like NZDT, and go-live rehearsals. Part 6. Run and hypercare phases related migration incidents hypercare support, HANA performance tuning, and critical production outages. Let's deep dive into Part 1. Discover and prepare phases related migration incident strategy, readiness, and pre-checks.
Part 1. Discover and prepare phases related migration incidents, strategy, readiness, and pre-checks.
Welcome to Part 1 of our Masterclass series. This segment covers the most critical early gating phases of the project. Discover and prepare. Here, we tackle the first 44 incidents of our catalog. These scenarios represent the strategic, assessment, governance, and technical preparation failures that happen before the actual system conversion even begins. Understanding these first 44 incidents is mandatory to secure your project's foundation and prevent catastrophic downstream delays.
Part 1 Migration Incidents. Discover and prepare incidents 1 to 44.
In this part, we systematically analyze 44 real-world integration, data, and architecture-related migration incidents. 1. Discover phase migration incidents 1 to 22. Strategic failures, incomplete sizing, missed integrations, and underestimated CVI data cleansing requirements. 2. Prepare phase migration incidents 23 to 44. Hard conversion blockers, failed SAP readiness checks, custom PM code ATC dumps, and unremediate LIS reporting. Let's deep dive into Discover Phase Migration Incidents. Discover Phase Overview. Understanding where migration failures begin. The Discover phase is the foundation of an SAP ECC to SAP S/4HANA transformation. During this stage, organizations assess their current ECC landscape, evaluate business processes, identify technical debt, analyze integrations, assess data quality, review custom developments, and determine the most appropriate migration strategy. The objective is not to perform the migration itself. The objective is to fully understand what is being migrated. Every major architectural decision made during Discover influences every subsequent phase of the program. Decisions regarding migration strategy, system scope, custom code remediation, master data cleansing, integration treatment, infrastructure sizing, and organizational readiness establish the baseline for the entire transformation. Most Discover phase incidents occur because organizations underestimate the complexity of their existing environment. Hidden customizations, undocumented interfaces, obsolete technologies, poor master data quality, unsupported add-ons, and overlooked business dependencies often remain invisible until later phases, where remediation becomes significantly more expensive and disruptive. Simply put, the further a problem travels beyond discover, the more expensive it becomes to fix.
Here are the functional activities that are performed.
During the discover phase, functional teams focus on understanding how plant maintenance PM processes currently operate and how they will be affected by the S/4HANA transition. 1. Business process review, assessing current plant maintenance PM and EAM business processes. 2. Operational life cycles, reviewing maintenance order life cycle and notification processes. 3. Master data hierarchy, analyzing equipment master data and functional location structures. 4. Maintenance typologies, assessing preventive, corrective, and breakdown maintenance processes. 5. Planning and scheduling, evaluating maintenance planning and scheduling procedures. 6. Financial cross-module links, reviewing asset accounting dependencies with maintenance operations. 7. Shutdown operational windows, identifying business-critical maintenance periods and shutdown windows. 8. Analytics and reporting, assessing reporting, analytics, and key performance indicator requirements. 9. Customization scans, identifying custom PM enhancements and workarounds. 10. Data quality profiling, assessing equipment and functional location master data quality. 11. Process standardization, documenting future state business requirements and identifying process standardization opportunities. 12. Capability scoping, executing high-level capability scoping and simplification item impact assessments.
Here are the technical activities that are performed.
Technical teams focus on understanding the existing ECC landscape and identifying risks that could affect conversion readiness. 1. Z development inventory, inventorying custom PM developments, user exits, enhancements, and Z programs. 2. Technical object sizing, assessing technical object volumes and historical maintenance data growth. 3. Interface architecture mapping, analyzing interface landscapes including GIS, IoT, mobile scheduling, and external systems. 4. Middleware and add-on audit, reviewing active add-ons, middleware components, and integration technologies. 5. Archiving analysis, assessing legacy archiving status and data retention requirements. 6. Batch job profiling, analyzing batch jobs, background processing, and operational dependencies. 7. HANA footprint sizing, reviewing infrastructure sizing assumptions and expected HANA footprint. 8. Obsolete tech identification, identifying obsolete technologies that may not be supported in S/4HANA. 9. Standard readiness scans, performing standard SAP readiness check assessments. 10. Simplification item assessment, running simplification item analyses across the entire ECC database. 11. Code remediation scans, assessing custom code inventory. 12. Custom enhancements analysis, evaluating ABAP modifications and enhancements. 13. Security and authorization audit, assessing security and authorization architecture. 14. Database growth analysis, reviewing database health and growth trends. 15. Hardware readiness, assessing infrastructure readiness.
Here are the most critical business stakeholders that should be engaged.
Key business and operations stakeholders must be engaged early during the discover phase. Cross-functional leaders define integration, financial, and compliance boundaries. 1. Program sponsors, provide executive sponsorship, funding approval, and strategic direction. 2. Maintenance operations managers, represent operational maintenance teams and validate business process impacts. 3. Plant supervisors, assess operational impacts on technicians and field maintenance teams. 4. Reliability engineers, validate equipment history requirements, asset criticality models, and analytics dependencies. 5. Maintenance planners, provide insight into maintenance planning, scheduling, backlog management, and reporting requirements. 6. Finance and asset accounting teams, assess maintenance cost reporting, asset accounting impacts, and budget considerations. 7. Operations leadership, approve operational maintenance change management and deployment strategies. 8. Enterprise architecture team, map the target S/4HANA landscape and establish system integration parameters. 9. Procurement leadership, validate integration requirements between PM, MM, and external service providers. 10. Compliance and audit teams, Define regulatory retention requirements and data governance expectations.
Here are the key deliverables to be produced.
The foundational deliverables generated during the discover phase to establish the program baseline. These deliverables establish the definitive business case and technical roadmap. 1. Migration strategy recommendation. Defines the optimal path brownfield, greenfield, or selective transition. 2. Current state architecture assessment. Documents the legacy ECC landscape, servers, and middleware. 3. SAP readiness check report. Summarizes active business functions, custom code footprints, and sizing. 4. Simplification item assessment. Maps legacy customizing against target S/4HANA requirements. 5. Custom code inventory. Catalogs all active legacy Z programs, user exits, and modifications. 6. Integration inventory. Maps every active inbound and outbound interface point. 7. Third-party application assessment. Documents non-SAP solutions requiring compatibility validation. 8. Data quality assessment. Profiles the cleanliness and consistency of legacy master data. 9. Master data readiness report. Outlines the cleansing scope for technical objects, equipment, and classes. 10. HANA sizing assessment. Projects target working memory and hardware footprint requirements. 11. Infrastructure readiness assessment. Validates cloud, hosting, or on-premise hardware viability. 12. Security and authorization assessment. Audits legacy roles against Fiori Launchpad security architectures. 13. Risk register. Consolidates all technical, functional, and program-level transformation risks. 14. Program roadmap. Establishes milestones, resources, and deployment phases. 15. High-level cutover strategy. Outlines the expected downtime window and business blackout requirements. 16. Executive business case. Establishes the commercial justification and projected ROI of the conversion.
Here are the key integration touchpoints that are going to be assessed.
Maintenance operations depend heavily on tight integration with core logistics and financial modules. Asset performance and field execution require modern digital integration touchpoints. 1. Materials management Maintenance orders depend on material reservations, inventory availability, and procurement. 2. Production planning Maintenance scheduling frequently interacts with production planning and plant shutdown windows. 3. Finance and controlling FI&CO. Maintenance costs, settlements, budgeting, and reporting depend heavily on financial integrations. 4. Asset accounting FIAA. Equipment and asset structures require synchronization across maintenance and accounting processes. 5. Human resources HCM and success factors. Workforce planning and technician assignment processes often depend on HR integrations. 6. GIS systems. Many utilities, transportation, and public sector organizations rely on GIS integrations for asset visualization. 7. Mobile maintenance platforms. Field service and technician applications frequently contain mission-critical maintenance functionality. 8. Document management systems. Maintenance records, drawings, manuals, permits, and technical documentation often reside externally. 9. SCADA and IoT platforms. Operational asset data frequently originates from industrial monitoring platforms. 10. External service providers. Maintenance execution may depend on contractors, vendors, and external workforce management solutions. 11. Enterprise data warehouses. Maintenance reporting frequently depends on BW, SAC, or third-party analytics platforms.
Why incidents occur during this phase?
Most discover phase incidents are caused by one or more of the following conditions. 1. Incomplete landscape. Failing to document legacy systems, obsolete technologies, and local shadow databases. 2. Siloed scoping. Missing cross-functional planning, procurement, and financial settlement dependencies. 3. Undocumented integrations. Overlooking background interfaces, local planning boards, and custom middleware. 4. Unidentified technical debt. Underestimating legacy custom ABAP programs, modifications, and obsolete user exits. 5. Data quality gaps. Ignoring legacy master data corruption, technical object loops, and invalid character sets. 6. Flawed sizing and strategy. Approving hardware specifications and conversion paths based on assumptions instead of evidence.
Here are the early warning signs of discover phase failure.
Organizations should immediately investigate these early warning signs of discover phase failure. These warning signs indicate major project risks months before they formally surface. 1. No agreed migration strategy recommendation after multiple assessment workshops. 2. Different technical and functional teams reporting conflicting system or table database inventories. 3. Large quantities of undocumented interfaces or untracked RFC connections discovered. 4. Significant legacy custom code with completely unclear business or technical ownership. 5. Missing or outdated technical architecture diagrams for key PM-dependent processes. 6. Incomplete integration inventories that omit local, plant-specific scheduling or mobile apps. 7. Unknown third-party applications found actively querying standard ECC database tables. 8. Inaccurate data quality metrics that fail to identify legacy master data inconsistencies. 9. Missing master data ownership across local plants and maintenance departments. 10. Inconsistent or disengaged stakeholder participation during cross-module assessment workshops. 11. SAP readiness check findings and critical simplification items not being assigned to specific owners. 12. Infrastructure sizing assumptions based on theoretical calculators rather than actual system measurements. 13. Significant reliance on tribal knowledge and undocumented legacy process workarounds. 14. Simplification item check or custom code scan warnings being downplayed by the technical team.
Here is the key message to the discover phase.
Most SAP S/4HANA migration failures are not created during the technical conversion. They are created during discovery when organizations fail to fully understand their existing landscape, customizations, integrations, master data, technical debt, operational dependencies, and business requirements. Every issue missed during discover becomes significantly more expensive to fix during prepare, explore, realize, deploy, or run. Organizations that invest heavily in assessment, validation, stakeholder engagement, and architecture analysis consistently experience smoother migrations, lower costs, shorter downtimes, and fewer production disruptions. A successful SAP S/4HANA transformation begins long before the first technical conversion. It begins with understanding exactly what exists today.
Discover phase. Strategic and assessment incidents.
We systematically analyze the first 22 core strategic and assessment failures identified in this phase. These incidents also represent key architectural, integration, and cross-functional scoping risks. 1. Incorrect migration strategy selected brownfield chosen despite highly fragmented ECC landscape, leading to massive remediation effort later. 2. Legacy PM custom developments underestimated during assessment phase. 3. Equipment master data volume not properly analyzed, causing future HANA sizing issues. 4. Maintenance order historical data growth ignored during storage estimation. 5. GIS integration dependencies missed during discovery workshops. 6. External mobile maintenance applications not considered in transformation scope. 7. Third-party maintenance scheduling tools not identified during interface inventory. 8. Custom PM notification workflows undocumented, causing redesign failures later. 9. Functional location hierarchy inconsistencies ignored during landscape assessment. 10. Large number of inactive technical objects not identified for archiving. 11. PM-specific batch jobs not documented during operational assessment. Dive into the second half of our Discover phase incident catalog. 12. Business users assumed GUI transactions would remain unchanged, Fiori impact not communicated. 13. Heavy Z table dependency for maintenance analytics discovered late. 14. Unsupported PM add-ons identified only after project kickoff. 15. No downtime estimation performed for PM-heavy transactional environment. 16. CVI impact on vendor-linked maintenance processes underestimated. 17. IoT sensor integrations excluded from initial architecture assessment. 18. Plant-wise data quality inconsistencies not identified. 19. Duplicate equipment numbering ranges discovered late. 20. Executive leadership underestimated business disruption during maintenance order freeze windows. 21. Mandatory finance simplifications, for example, Universal Journal, new asset accounting underestimated, severely impacting PM order settlement and AUC mappings. 22. Material ledger mandatory activation impact on PM spare parts valuation and reservations completely missed during discovery. Finally, let's deep dive into Migration Incident 1 in Discover phase.
Migration Incident 1. Incorrect migration strategy selected.
During the Discover phase of an SAP ECC to SAP S/4HANA transformation, organizations sometimes select a brownfield conversion approach despite operating a highly fragmented plant maintenance landscape with extensive custom developments, inconsistent master data, unsupported add-ons, and complex third-party integrations. The decision is often made based on perceived cost savings and faster timelines, rather than a comprehensive assessment of technical debt and business complexity. As a result, the project encounters significant remediation effort during later phases, causing delays, budget overruns, and increased transformation risk.
Incident classification and relevant SAP, note if applicable.
1. Complexity. Very high program-level strategic failure. 2. Migration phase, discover. 3. Frequency, common in large ECC landscapes. 4. Primary ownership, enterprise solution architect. 5. Supporting, PM functional lead basis architect, integration architect. 6. Business ownership, program sponsor or transformation steering committee. 7. Relevant SAP note, not applicable. Migration strategy and program governance failure.
How teams identified this issue, diagnostic dashboard, symptoms and evidence.
How an incorrect migration strategy typically reveals itself during the program lifecycle. 1. Symptom. Large numbers of custom developments require redesign despite selecting a brownfield approach. 2. Red flag. Discovery workshops continuously uncover undocumented business processes and integrations. 3. Business impact. Project timelines expand significantly as remediation scope increases. 4. Detection. Fit gap analysis and readiness assessments reveal technical debt far beyond original assumptions. 5. Technical proof. High volumes of ATC findings, unsupported add-ons, data quality issues, and obsolete integrations emerge during assessment activities. SAP Readiness Check reveals extensive simplification item impacts and custom code adaptation requirements. Insight. When remediation work starts to resemble a greenfield implementation, the original migration strategy should be questioned.
Incident analysis and root cause why this happens.
1. Migration strategy decisions are made before a complete assessment of the ECC landscape. 2. Organizations focus on minimizing cost and duration rather than evaluating technical complexity. 3. Custom developments, interfaces, and operational workarounds are underestimated. 4. Business stakeholders assume existing processes can be carried forward unchanged. 5. Architecture teams lack objective criteria for selecting brownfield, greenfield, or hybrid approaches. The root cause is rarely technical. It is usually a governance and assessment failure.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue exists only because an ECC landscape is being transformed to S/4HANA. 2. Migration strategy determines the level of remediation, redesign, and transformation required. 3. A poor strategy decision amplifies every subsequent migration risk. 4. The problem does not exist during normal ECC operations because no transformation path is being evaluated. A wrong strategy creates downstream failures across every future migration phase.
Business and program impact.
1. Project budgets increase due to unexpected remediation activities. 2. Implementation timelines expand significantly. 3. Business confidence in the transformation program declines. 4. Additional consulting, development, and testing effort becomes necessary. 5. Planned business benefits are delayed due to extended project duration. Migration strategy mistakes are among the most expensive errors to correct later in the program.
Strategic decision. Evaluating the migration path.
Answer. Selecting the correct S/4HANA transformation path requires balancing system complexity, data heritage, and long-term business goals. We must evaluate these 5 potential options. 1. Brownfield conversion. Proceed with full system conversion, accepting the high cost of custom code, data, and integration remediation. 2. Selective data transition. Prune legacy technical debt while selectively migrating only active business processes and required historical data. 3. Greenfield implementation. Completely rebuild the business processes using S/4HANA best practices, eliminating all legacy technical debt. 4. Strategic reassessment. Pause major delivery activities to perform a deeper readiness assessment and recalculate scope, budget, and risk. 5. Risk acceptance. Proceed with a standard system conversion under formal steering committee approval, documenting explicit accountability for future costs. Pro tip: if the projected brownfield remediation effort starts approaching greenfield implementation complexity, the strategy must be formally reassessed rather than forcing a legacy conversion to save temporary costs.
Governance and accountability, Ray C. model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the migration strategy and gets fired if the transformation direction is fundamentally wrong. 2. Responsible. Assessment team lead performs landscape analysis and strategy evaluation. 3. Consulted. PM functional lead, basis architect, integration architect, data migration lead. 4. Informed. Program sponsor, steering committee, business process owners. Strategy decisions must be driven by evidence, not assumptions.
Ownership, who actually fixes it.
Correcting a strategy failure requires reassessment rather than technical remediation. 1. Enterprise solution architect reassesses migration options using objective criteria. 2. Assessment teams perform a deeper analysis of custom code, integrations, and data complexity. 3. Business stakeholders re-evaluate transformation objectives and constraints. 4. Program leadership approves revised scope, timelines, and delivery approach.
Who gets blamed versus who owns it.
1. Blamed. PM functional team, business assumes process complexity was underestimated. 2. Blamed. Technical teams perceived as discovering issues too late. 3. Actual owner. Enterprise solution architect, accountable for selecting the correct migration strategy. 4. Root cause. Insufficient assessment and governance before strategy approval. Strategy failures are governance failures long before they become technical failures.
How this is actually fixed the right way by a role.
1. Perform a formal migration strategy reassessment using updated assessment findings. 2. Quantify technical debt, custom code complexity, and integration dependencies. 3. Evaluate brownfield, greenfield, and hybrid approaches against business objectives. 4. Obtain executive approval for any required strategy adjustment before entering later phases.
Common mistakes to avoid, what not to do.
1. Do not select a migration approach based solely on cost or duration. 2. Do not assume custom developments can be carried forward unchanged. 3. Do not ignore assessment findings that contradict the original strategy. 4. Do not delay strategy reassessment until realization activities begin. The cost of correcting strategy mistakes increases dramatically after discover.
Follow-up 1. When should a brownfield approach be reconsidered?
Answer: a brownfield system conversion should be reconsidered when readiness assessments reveal extensive technical debt, such as extensive custom developments requiring significant remediation and redesign effort, or a massive custom ABAP developments that are fundamentally incompatible with the target S/4HANA database. Additionally, if the legacy plant maintenance landscape is highly fragmented with poor master data quality, unsupported third-party add-ons, or undocumented integrations, the remediation overhead often negates any expected cost savings. Finally, if the business demands a complete process redesign, such as adopting the new standard 9-phase maintenance model, or centralizing highly localized operations, a clean slate greenfield restart, or a selective data transition becomes the only pragmatic path to secure long-term architectural stability.
Follow-up 2. Why do organizations frequently choose the wrong migration strategy?
Answer: organizations frequently choose the wrong migration strategy because their steering committees prioritize short-term project budgets and aggressive timelines over objective, data-driven technical assessments. They often sign partner statements of work during the early planning stages before executing deep custom code analyses, CVI validation checks, or comprehensive integration mapping workshops. Furthermore, business stakeholders frequently suffer from change fatigue and falsely assume that highly modified legacy processes can simply be pushed into S/4HANA as is without business disruption. This lack of objective gating criteria, combined with weak technical governance and a failure to confront legacy architectural complexity early, inevitably leads to choosing a conversion approach that becomes stuck during sandbox testing.
Follow-up 3 curveball. Can a project switch migration strategies after Discover?
Answer: yes. A project can switch migration strategies after the Discover phase, but the organization will face immense timeline, resourcing, and financial penalties. Pivoting from a brownfield system conversion to a greenfield implementation during the Explore or Early Realize phases requires throwing away all previous technical preparation work, completely renegotiating the system integrator's contract, and establishing a brand new data migration stream. This shift requires reallocating business experts to new blueprinting workshops and rebuilding all target integrations from scratch. However, while executing such a mid-project pivot is highly disruptive to program morale and budgets, making this difficult course correction early is always preferable to forcing a fundamentally flawed conversion into a live, high-volume production plan.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: establish strict, objective gating criteria, for example, max percentage of custom code, data cleanliness scores that must be met before a brownfield strategy is officially approved. Recommendation 2. What successful projects do? Reliability: elite projects run the SAP readiness check and ABAP test cockpit ATC in a sandbox environment before signing the final statement of work SOW with the system integrator. Recommendation 3. What should be validated? Revalidation: physically validate the assumptions of the PM functional team against the actual system usage logs ST03N to prove whether heavily customized legacy processes are actually still being used. Recommendation 4. What should be governed? Responsibility: the enterprise solution architect must own the technical debt register and force the steering committee to formally accept the remediation costs before the prepare phase begins.
Migration Incident 2. Legacy PM custom developments underestimated.
During the Discover phase of an SAP ECC to SAP S/4HANA transformation, organizations often catalog custom developments purely as simple lines of code without evaluating their semantic complexity. Legacy custom programs, direct database updates to standard tables, and heavily modified user exits written for plant maintenance are assumed to run seamlessly on the new architecture. However, underestimating the technical debt of legacy custom code creates massive development roadblocks during later phases, causing the custom code remediation workstream to stall and threatening the entire program timeline.
Incident classification and relevant SAP note if applicable.
1. Complexity: high critical technical debt failure. 2. Migration phase Discover. 3. Frequency: very common in older ECC landscapes. 4. Primary ownership custom code lead. 5. Supporting PM functional lead enterprise solution architect lead ABAP developer. 6. Business ownership program sponsor. 7. Relevant SAP note. SAP note 1912445. ABAP custom code migration for SAP S/4HANA.
How teams identified this issue. Diagnostic dashboard. Symptoms and evidence.
How underestimating legacy custom developments typically reveals itself during the program lifecycle. 1. Symptom: custom transaction codes and custom maintenance cockpits dump or fail to return data during early S/4HANA sandbox testing. 2. Red flag: finding legacy user exits that directly manipulate core databases instead of using standard enhancement points. 3. Business impact: remediation estimates for custom PM reports double, delaying the build phase. 4. Detection: ABAP test cockpit ATC identifies incompatible syntax, direct database access, obsolete enhancement techniques, and HANA optimization issues. 5. Technical proof: custom ABAP code scan logs reveal direct select queries on deprecated PM aggregate tables like S061 and S062. Insight: if legacy custom code was written to bypass standard SAP validation engines, S/4HANA will reject it immediately.
Incident analysis and root cause. Why this happens.
1. Legacy PM enhancements were written over decades without proper documentation or adherence to coding standards. 2. Assessment teams run simple line of code scans instead of executing semantic compatibility checks. 3. Custom developments bypass standard BAPIs and directly update standard databases to save development time in ECC. 4. Business stakeholders assume all custom transactions must carry over to S/4HANA without evaluating actual usage. The root cause is treating custom code as a simple migration task rather than a strategic technical debt cleanup.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migration due to the simplified core data model. 2. Many legacy PM aggregate tables and reporting structures used by custom developments become obsolete in S/4HANA and are replaced by CDS-based reporting models. 3. Syntax and database operations that executed successfully on ECC frequently require redesign or optimization to comply with HANA and S/4HANA development standards. 4. S/4HANA enforces a completely new extensibility concept, making direct modification techniques completely obsolete. S/4HANA database optimizations will not tolerate legacy database shortcuts.
Business and program impact.
1. Custom code remediation costs escalate rapidly as ABAP teams spend months rewriting legacy code. 2. The overall S/4HANA program timeline slips, delaying downstream functional testing and training. 3. High risk of post-go-live transactional data corruption if direct database updates are not identified and remediated. 4. Decline in program momentum as technical debt consumes resources meant for functional innovations. Unremediated custom code is a ticking time bomb for data integrity in S/4HANA.
Strategic decision. Evaluating custom code strategy.
Answer: managing legacy custom code complexity requires a clear, strategic evaluation of our current Z developments. We must evaluate these 4 custom code paths. 1. Remediate and cleanse. Retain and remediate legacy custom code to make it S/4HANA compliant, accepting the high redevelopment costs of legacy object modifications. 2. Retire and standardize. Decommission the legacy custom programs completely and adapt standard, out-of-the-box S/4HANA Fiori applications to handle business processes. 3. Rebuild as BTP extensions. Decouple custom logic from the core ERP by rebuilding mission-critical enhancements as side-by-side cloud extensions on SAP BTP. 4. Prioritize and phase remediation. Focus only on high-value custom developments required for go-live and defer low-priority enhancements to later releases. Pro tip: if legacy custom code does not provide a clear competitive business advantage, decommission it and adopt standard S/4HANA Fiori processes.
Custom code decision matrix.
A standard architectural matrix to categorize legacy custom code during the discover phase. 1. Unused custom code. Retire and decommission from the code repository based on SD03N usage logs. 2. Standard functionality exists. Replace with standard S/4HANA Fiori applications to minimize future technical debt. 3. High business value. Remediate and adapt legacy ABAP logic to be compatible with S/4HANA data model changes. 4. Strategic innovation. Rebuild on SAP BTP using side-by-side cloud extensibility to keep the core clean. Architect's rule: keep the core clean by pushing custom innovations out of the core ERP onto the cloud.
Governance and accountability. RACI model.
Remediating custom technical debt requires clear governance and ownership across all technical teams. 1. Accountable. Custom code lead, the person who owns the custom code remediation budget and gets fired if legacy ABAP syntax failures delay functional testing. 2. Responsible. Lead ABAP developer executes system scans and performs code correction. 3. Consulted. PM functional lead enterprise solution architect. 4. Informed. Program manager, steering committee. Do not let developers remediate legacy custom programs without functional business sign-off.
Ownership. Who actually fixes it?
Resolving custom code issues requires structured evaluation and programmatic cleanup. 1. Custom code lead categorizes all custom objects based on standard ATC findings and actual system usage logs. 2. ABAP developers execute code cleanup, replacing legacy database operations with S/4HANA compatible logic. 3. PM Functional Lead reviews custom code usage and identifies candidates for standard Fiori replacement. 4. Basis team configures the ABAP test cockpit checking variants in the sandbox environment.
Who gets blamed versus who owns it?
1. Blamed. ABAP developers accused of writing over complicated legacy custom programs that are too difficult to remediate. 2. Blamed. PM Functional Team business blames functional consultants for underestimating enhancement complexity. 3. Actual owner. Custom code lead, accountable for assessing the technical debt and defining the remediation strategy early. 4. Root cause. Failure to perform a semantic custom code assessment during the discover phase of the project. Do not blame legacy developers for legacy code. Blame current architects for ignoring it during discovery.
How this is actually fixed the right way by a role.
1. Custom Code Lead runs a comprehensive ABAP test cockpit scan with the S/4HANA Readiness Check variant in the early sandbox. 2. Lead ABAP developer cross-references ATC errors with transaction SD03N usage data to immediately decommission unused custom programs. 3. PM Functional Lead performs a formal fit gap analysis of the remaining Z code against standard S/4HANA Fiori apps to retire redundant custom transactions. 4. Senior ABAP developer remediates only high-value active PM developments, replacing direct database selections with standard baddies and CDS views. Scrubbing your legacy custom code repository can reduce your ABAP remediation scope by up to 60%.
Common mistakes to avoid what not to do.
1. Do not estimate remediation effort using object counts alone. Evaluate actual business complexity and technical dependencies. 2. Do not assume custom developments can be carried forward unchanged. 3. Do not ignore assessment findings that contradict the original strategy. 4. Do not delay custom code remediation activities until functional user acceptance testing begins. Remediating dead custom code is the fastest way to waste a project budget.
Follow-up 1. How does SD03N data help optimize custom code remediation scoping?
Answer. Analyzing SD03N transaction usage data is a critical best practice that allows the custom code lead to map standard ATC syntax errors against actual runtime execution. S/4HANA readiness scans often return thousands of syntax errors, but cross-referencing this footprint with historical usage profiles typically reveals that 40 to 60% of legacy custom programs have not been executed by any business user for over a year. By immediately identifying and formally decommissioning these unused or orphaned Z objects from the migration scope, the team can dramatically reduce the required ABAP remediation effort. This target scoping exercise ensures that project budgets and consulting resources are strictly focused on modifying high-value, active business enhancements rather than wastefully fixing obsolete legacy code.
Follow-up 2. What is the risk of using direct database table updates in S/4HANA?
Answer. Performing direct database table updates in S/4HANA represents a critical architectural risk that can lead to immediate transactional data corruption and system instability. S/4HANA utilizes highly simplified, columnar table structures and relies on complex CDS views to dynamically aggregate and reconcile operational data in real time. Legacy custom developments sometimes relied on direct table manipulation or unsupported update techniques that bypassed standard application logic. In S/4HANA, direct database modifications bypass the complex application logic layer, creating major inconsistencies across dependent financial and logistics ledgers. To prevent these catastrophic errors, architects must enforce a strict policy mandating the use of standard BAPIs, or modern OData services, for all transactional operations.
Follow-up 3 curveball. When should a legacy PM user exit be redesigned as an S/4HANA baddie?
Answer. A legacy plant maintenance user exit must be systematically redesigned as an S/4HANA baddie whenever the ABAP test cockpit identifies syntax obsolescence, or when standard enhancement tables are simplified. Standard ECC user exits such as those inside enhancement IW010009 for PM order checks often rely on direct table references and global memory variables that are no longer valid or supported in S/4HANA's modern architecture. BADIs offer a highly structured, object-oriented framework with clean, well-defined importing and exporting parameters that prevent direct memory manipulation. Moving to the BADI framework ensures that custom logic is decoupled from standard SAP code, preventing core enhancements from being accidentally overwritten during future FPS or SPS upgrades.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run standard ABAP test cockpit ATC scans and custom code analysis across the entire Z namespace before finalizing the functional remediation scope. Recommendation 2. What successful projects do? Reliability elite projects cross-reference ABAP test cockpit ATC findings with ST03N transaction usage statistics to systematically eliminate unused custom objects. Recommendation 3. What should be validated? Revalidation: formally validate whether each legacy custom enhancement still provides unique business value in S/4HANA before committing development budget. Recommendation 4. What should be governed? Responsibility: require local plant business process owners to formally approve and justify the retention of every single custom object before migration development begins.
Migration Incident 3. Equipment Master Data Volume Unanalyzed.
During the discover phase of an SAP ECC to SAP S/4HANA conversion, organizations often fail to analyze the physical storage and memory footprints of their equipment master data and its deeply nested classification hierarchies. Legacy systems running for decades accumulate massive volumes of technical objects, many of which are inactive or obsolete. Underestimating the memory sizing required for these database-heavy objects leads to critical in-memory sizing inaccuracies, directly causing severe performance degradation and unexpected hardware cost spikes during later conversion phases.
Incident classification and relevant SAP note if applicable.
1. Complexity: high critical technical sizing failure. 2. Migration phase discover. 3. Frequency: common in older ECC landscapes. 4. Primary ownership basis lead. 5. Supporting PM functional lead data migration lead infrastructure architect. 6. Business ownership program sponsor. 7. Relevant SAP note. SAP note 1872170. S/4HANA sizing report /SDF/HDB_sizing.
How teams identify this issue. Diagnostic dashboard. Symptoms and evidence.
How an unanalyzed equipment data volume typically reveals itself during the program lifecycle. 1. Symptom: the sandbox conversion run fails or suffers severe performance bottlenecks during database table conversion stages. 2. Red flag: execution of standard sizing reports reveals a massive memory footprint specifically allocated to the classification table AUSP. 3. Business impact: project costs spike unexpectedly due to the sudden requirement for larger, more expensive HANA appliance hardware. 4. Detection: /SDF/HDB_sizing, readiness check analysis, and database growth assessments reveal that equipment and classification data volumes exceed initial sizing assumptions. 5. Technical proof: memory consumption analysis reveals that equipment classifications and related technical object tables represent a significant proportion of the projected HANA memory footprint. Insight: treating master data sizing as a simple storage calculation instead of an in-memory optimization is a critical project risk.
Incident analysis and root cause. Why this happens.
1. Teams rely on standard legacy disk footprint calculations instead of executing memory-specific sizing reports. 2. Assessment teams treat PM master data as a simple static entity without scanning its attached characteristic values and classification tables. 3. Data cleanup and archiving opportunities are ignored during early project stages. 4. Infrastructure and business teams operate in silos, preventing technical objects from being sized against business realities. The root cause is treating master data as a static storage footprint rather than an expensive in-memory resource.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migration due to the shift from disk-based storage to in-memory computing. 2. Large equipment, functional location, and classification datasets that had minimal impact on traditional database platforms can become major memory consumers in SAP HANA. 3. Sizing assumptions that held true for decades in ECC are completely invalidated by HANA's strict working memory and compression models. 4. Under traditional ECC database architectures, inactive master data typically has a lower operational cost impact than it does in an in-memory HANA environment. HANA memory costs require organizations to treat technical objects with a strict data lifecycle strategy.
Business and program impact.
1. Program budgets are shattered by the sudden need for massive, high-spec HANA hardware appliances. 2. Conversion cycles during deploy and cutover phases are delayed because larger databases take significantly longer to migrate. 3. Decline in reporting and transactional performance if the HANA database is sized too closely to its physical memory limits. 4. Extended project downtime windows, increasing overall business disruption, risks during live plant migrations. Unoptimized master data volume directly inflates the long-term total cost of ownership in S/4HANA.
Strategic decision. Evaluating sizing optimization paths.
Answer: optimizing the target HANA hardware footprint requires evaluating the storage economics of legacy technical object volumes. We must evaluate these 4 sizing paths. 1. Hardware scale up. Accept the legacy data volume and purchase larger, more expensive HANA memory appliances, avoiding data cleansing and archiving efforts. 2. Active PM archiving. Execute a rigorous data archiving project in ECC prior to conversion to permanently remove inactive technical objects. 3. Historical transaction archiving. Archive closed maintenance orders, notifications, and historical measurement documents to reduce overall database growth while keeping active master data fully available. 4. Sizing scope reduction. Perform deep master data cleansing, filtering out legacy characteristic values and orphan classifications before technical migration. Pro tip: purchasing larger hardware is a temporary fix. A proper archiving strategy solves the root cause of database growth.
Sizing decision matrix.
Use this standard matrix to determine the correct technical or business action based on master data assessment findings. 1. Large inactive equipment population. Archive the historical technical objects in ECC pre-conversion using standard archiving object PM_EQUI. 2. Excessive classification records. Cleanse and prune orphan characteristics in tables AUSP and KSSK before committing to target database sizes. 3. Rapid future growth expected. Scale the target HANA hardware specifications upwards to secure a safe buffer for operational expansion. 4. Regulatory retention requirements. Retain the data in memory or map to an active cold storage archiving tier to satisfy regulatory compliance. Architect's rule: prune and archive legacy technical objects before finalizing cloud hardware contract commitments.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Basis lead, the person who owns the migration sizing assessment and gets fired if the target memory footprint is underestimated. 2. Responsible. Data migration lead executes data profiling and cleanup activities. 3. Consulted PM functional lead infrastructure architect. 4. Informed. Program sponsor steering committee. Business process owners. Sizing calculations must be verified by actual sandbox runs, not theoretical calculators.
Ownership. Who actually fixes it?
Resolving database sizing issues requires structured evaluation and programmatic cleanup. 1. Basis lead executes S/4HANA sizing reports and calculates the target memory requirements. 2. Data migration lead partners with functional teams to identify archiving candidates. 3. PM functional lead reviews master data usage and identifies candidates for technical object archiving. 4. Infrastructure architect maps the refined sizing requirements to the final hardware specification.
Who gets blamed versus who owns it?
1. Blamed. Infrastructure team accused of purchasing undersized hardware or blocking the conversion due to hardware shortages. 2. Blamed. PM functional team business blames functional consultants for not warning the project about massive master data volumes. 3. Actual owner. Basis lead, accountable for executing the exact sizing assessment and projecting realistic HANA footprints. 4. Root cause, failure to perform a memory-specific database assessment during the discover phase of the project. Hardware limits are absolute. Do not blame the infrastructure team when your database is bloated.
How this is actually fixed the right way by a role.
1. Basis lead executes the memory-specific sizing report /SDF/HDB underscore sizing in the legacy ECC environment to analyze table-level footprints. 2. Data migration lead runs comprehensive database volume scans to isolate high-volume PM tables such as AUSP, EQUI, EQKT, IFLOT, and IFLOTM. 3. PM functional lead reviews equipment, functional location, and classification usage to identify inactive technical objects eligible for archiving. 4. Infrastructure architect validates refined sizing outputs and aligns cloud or on-premise HANA hardware specifications with projected growth requirements. Scrubbing your legacy custom code repository can reduce your ABAP remediation scope by up to 60%.
Common mistakes to avoid what not to do.
1. Do not size the S/4HANA database based on legacy disk storage sizes using standard DB02 calculations. 2. Do not attempt to migrate millions of legacy classification records without verifying active business usage. 3. Do not delay the execution of the sizing report until after the production hardware has been purchased. 4. Do not skip the data archiving phase to meet a tight project timeline, as doing so permanently inflates cloud hosting costs. Relying on disk footprints to size RAM is a critical infrastructure mistake.
Follow-up 1. Why is legacy classification data particularly problematic for S/4HANA sizing?
Answer. Legacy plant maintenance systems frequently utilize the SAP classification framework to assign standard characteristics to equipment and functional locations. Over decades of operation, tables like AUSP and KSSK accumulate millions of records with highly unstructured, redundant entries. In legacy disk-based databases, this data volume was practically invisible from a cost perspective, but S/4HANA's in-memory database loads these tables directly into highly expensive RAM. If these tables are migrated uncleansed, the required memory footprint of the target database scales exponentially, forcing the purchase of much larger hardware appliances. Therefore, running deep classification profiling during the discover phase is a non-negotiable step to optimize long-term infrastructure budgets.
Follow-up 2. How does /SDF/HDB sizing calculate S/4HANA memory requirements differently from legacy DB02?
Answer. The legacy DB02 transaction measures physical disk storage block sizes, which do not reflect how data behaves in an in-memory database. The standard S/4HANA sizing report /SDF/HDB sizing evaluates the raw row count of tables and simulates how they will compress under HANA's column store database engine. Columnar databases compress repetitive values extremely efficiently, while non-repetitive long texts or unique classification values compress poorly. The sizing report analyzes these specific data structures to calculate the active working memory, the database footprint, and the temporary memory required for daily operations. Relying on DB02 disk space calculations instead of this simulated memory model inevitably leads to massive hardware oversizing or undersizing errors.
Follow-up 3 curveball. What is the risk of using data aging as a workaround for poorly sized PM master data?
Answer. While data aging is an effective S/4HANA standard strategy for reducing active memory footprints, attempting to apply it to PM master data represents a critical architectural mistake. Data aging is designed for high-volume, closed historical transactional data, such as completed maintenance orders or historical measurement documents. Master data objects, such as active functional locations, equipment, and classifications, must remain in the hot, in-memory database layer to support daily planning, scheduling, and searching operations. If an organization attempts to age out inactive equipment records to save on hardware costs, planners will suffer from broken hierarchy navigation, missing search results, and failed work order creations. Master data must be permanently cleansed or archived in ECC, rather than temporarily aged out in S4HANA.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run standard memory-specific sizing reports /SDF/HDB _ sizing and legacy ECC, and validate the output against actual PM table historical growth trends before establishing the hardware budget. Recommendation 2. What successful projects do? Reliability: perform complete sizing and simulation checks on a highly recent copy of the production database, rather than sizing on outdated or subset QA environments. Recommendation 3. What should be validated? Revalidation: physically validate the projected growth of equipment, classification, and other technical objects over the next 3 to 5 years to ensure the HANA database is sized to accommodate future operational expansion. Recommendation 4. What should be governed? Responsibility: require formal business approval and sign-off from plant managers before committing to migrate legacy, inactive technical objects that materially increase target HANA cloud hosting costs.
Migration Incident 4. Maintenance order historical data ignored.
During the discover phase of an SAP ECC to SAP S4HANA conversion, project teams often fail to analyze the physical storage footprint and historical growth trends of transaction-heavy maintenance order tables. Legacy systems that have operated for years accumulate millions of closed maintenance orders, order confirmations, and settlement documents. Ignoring this massive operational data growth during initial sizing assessments results in severe database expansion, inflated HANA hardware memory costs, and elongated conversion runtimes during sandbox trials.
Incident classification and relevant SAP note if applicable.
1. Complexity: medium strategic data volume management failure. 2. Migration phase discover. 3. Frequency common in legacy ECC landscapes. 4. Primary ownership data migration lead. 5. Supporting PM functional lead basis lead infrastructure architect. 6. Business ownership program sponsor. 7. Relevant SAP note. SAP note 2388483. Data volume management considerations.
How teams identified this issue. Diagnostic dashboard. Symptoms and evidence.
How ignored transactional data growth typically reveals itself during the program lifecycle. 1. Symptom: the sandbox database migration run takes significantly longer than expected during the data conversion steps. 2. Red flag: standard/SDF/HDB _ sizing reports reveal that high-volume PM transaction tables such as AUFK, AFIH, AFRU, and QMEL represent a significant portion of database growth. 3. Business impact: project budgets must be increased to accommodate much larger, more expensive cloud hosting instances or on-premise HANA hardware. 4. Detection: sizing assessments and readiness checks flag high-volume transactional data that has not been archived for over 5 to 10 years. 5. Technical proof: database analysis shows millions of closed, historically completed maintenance orders with TECO or CLSD system statuses sitting in the active database. Insight: treating historical transaction volume as a harmless data archive is a critical project cost risk in S4HANA.
Incident analysis and root cause why this happens.
1. Legacy organizations treat maintenance orders as permanent digital archives rather than active transactional data. 2. Project teams focus entirely on functional changes without running historical data volume profiling. 3. The business fears losing access to old maintenance history for audit purposes, blocking ECC archiving initiatives. 4. The infrastructure team sizes target hardware based on overall database size rather than running selective component-level scans. The root cause is treating transactional order history as a static database asset rather than an expensive in-memory liability.
Why this issue appears only during an ECC to S4HANA migration.
1. The issue becomes significantly more important during S4HANA migration because HANA memory sizing, conversion runtimes, and data volume management directly influence project cost, downtime, and infrastructure requirements. 2. Under traditional ECC database architectures, inactive master data typically has a lower operational cost impact than it does in an in-memory HANA environment. 3. Large volumes of historical maintenance orders increase database size, conversion runtimes, backup requirements, and overall HANA memory demand, making data volume management significantly more important than in traditional ECC environments. 4. S/4HANA migration processes perform extensive table conversion and optimization activities, which can experience significant runtime increases when processing millions of redundant historical records. ECC disk storage is cheap. HANA database memory is a premium resource that must be actively managed.
Business and program impact.
1. Program hardware and cloud hosting budgets escalate rapidly to accommodate massive database sizing. 2. Downtime windows during the deploy phase are elongated as millions of legacy orders are programmatically converted during cutover. 3. Post-go-live database backup and recovery times increase, impacting the overall system SLA and business continuity planning. 4. Remediation scope increases as custom analytics reports struggle to run efficiently over uncleansed historical datasets. Every gigabyte of unarchived transactional history directly increases the continuous licensing and hosting cost of S/4HANA.
Strategic decision. Evaluating transaction data storage paths.
Answer: managing legacy maintenance order volumes requires balancing history retention with target database storage cost. We must evaluate these 4 transactional data storage paths. 1. Active data archiving. Archive closed maintenance orders in ECC pre-conversion using standard archiving object PM_order to permanently shrink the target database footprint. 2. HANA hardware scale up. Accept the historical order footprint and increase target hardware specifications instead of reducing data volume through archiving. 3. S/4HANA data aging. Implement standard data aging, moving closed historical maintenance orders to the warm storage partition while keeping active records in memory. 4. Cold storage ILM partition. Offload historical PM transactional tables to an external cold storage archiving tier utilizing SAP Information Lifecycle Management. 5. Selective historical migration. Migrate only recent maintenance order history required for operations while archiving or retaining older records outside the active S/4HANA database. Pro tip: deferring data archiving to post-go-live is a critical mistake that permanently inflates your initial hardware contract commitments.
Transaction data retention matrix.
A standard analytical matrix to determine transaction data lifecycle steps during the discover phase. 1. Closed orders exceeding corporate retention requirements. Archive legacy maintenance orders to permanently reduce the database working memory footprint. 2. Closed notifications exceeding corporate retention requirements. Archive historical PM notifications using object PM_QMEL to clean up long text bloat. 3. Active orders. Retain active, open, and recently closed maintenance orders in memory to support daily operations. 4. Regulatory records. Retain compliance-critical calibration and safety-related transactional records or migrate them to an active ILM cold partition. Architect's rule: align with corporate compliance and audit leads before finalizing the PM archiving policy.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Data migration lead, the person who owns the custom archiving scope and gets fired if uncleansed order volumes blow up the conversion window. 2. Responsible. PM functional lead negotiates archiving retention thresholds with the business. 3. Consulted. Basis lead infrastructure architect. 4. Informed. Program sponsor. Steering committee, business process owners. Steering committees must establish clear data retention policies before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving database sizing issues requires structured evaluation and programmatic cleanup. 1. Data migration lead profiles the transactional data volume and calculates the target memory requirements. 2. PM functional lead reviews maintenance order history, notification history, and regulatory retention requirements to identify archiving candidates. 3. Basis lead configures and executes the archiving jobs in the legacy ECC environment. 4. Infrastructure architect maps the refined sizing requirements to the final hardware specification.
Who gets blamed versus who owns it?
1. Blamed. Basis team accused of miscalculating target database footprints or delaying the sandbox runs. 2. Blamed. Business process owners accused of blocking progress by demanding excessive historical data retention. 3. Actual owner. Data migration lead, accountable for assessing legacy transactional data and defining the archiving scope. 4. Root cause. Failure to perform a comprehensive data volume management assessment during the discover phase of the project. Do not blame the basis team for standard database bloat. The data migration lead must own the cleanup.
How this is actually fixed the right way by a role.
1. Data migration lead profiles the database to identify high-volume PM transactional tables such as AUFK, AFIH, AFRU, and QMEL. 2. PM functional lead collaborates with compliance, audit, and business process owners to identify maintenance orders and notifications eligible for archiving under corporate retention policies. 3. Basis lead configures the standard SAP archiving object PM_order in the legacy ECC system to programmatically archive closed orders. 4. Infrastructure architect recalculates the target HANA memory footprint using /SDF/HDB_sizing once the archiving runs are complete. Cleansing legacy transactional tables is the fastest way to shrink a database memory footprint.
Common mistakes to avoid what not to do.
1. Do not attempt to migrate 15+ years of active maintenance order history into RAM without executing a strict data archiving run. 2. Do not select data aging as a strategy without verifying that your custom PM analytics reports are compatible with aged-out records. 3. Do not delay the configuration of standard archiving object PM_order until the prepare or explore phases of the project. 4. Do not bypass regulatory and audit compliance guidelines when defining transaction archiving retention thresholds. Attempting to convert unarchived transactional history is the fastest way to stall a sandbox conversion.
Follow-up 1. How does archiving object PM_order optimize database sizing pre-conversion?
Answer. The standard SAP archiving object PM_order programmatically processes and permanently removes historically completed maintenance orders from active ECC database tables. This object identifies orders that meet the strict system status of CLSD or TECO and have exceeded the defined business retention period. It packages these transaction-heavy records into secure external archive files, freeing up massive physical storage space. Executing this step before the conversion significantly reduces the footprint of maintenance order-related tables such as AUFK, AFIH, AFRU, and associated status and settlement records, directly reducing the required RAM footprint on the target S/4HANA database.
Follow-up 2. What are the main functional risks of executing transaction archiving during the discover phase?
Answer. The primary functional risk of executing transaction archiving is the sudden loss of active online history for maintenance planners and supervisors. If the archiving retention threshold is set too aggressively, planners will lose standard search capabilities for older equipment breakdowns and historical maintenance costs. Additionally, active preventive maintenance plans might fail to schedule if they depend on historical order data for forecasting and call history. To mitigate this, the PM functional lead must balance database footprint reduction with operational business requirements, ensuring that at least 2 to 3 years of active order history remains completely available in the hot database tier.
Follow-up 3 curveball. Why is data aging highly suited for historical PM orders, but dangerous for technical objects?
Answer. Data aging is highly suited for historical PM orders because they represent closed, transactional records that are rarely accessed during daily operational planning. Moving these massive, high-volume transactional records to warm storage tables reduces active memory footprints while keeping them fully retrievable when needed. Conversely, applying data aging to PM master data represents a critical architectural mistake. Master data objects, such as active functional locations, equipment, and classifications, must remain in the hot, in-memory database layer to support daily planning, scheduling, and searching operations. If an organization attempts to age out inactive equipment records to save on hardware costs, planners will suffer from broken hierarchy navigation, missing search results, and failed work order creations.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization run data volume analysis and PM_order archiving simulations before finalizing sizing estimates. Recommendation 2. What successful projects do? Reliability perform archiving tests in a sandbox copy to validate retention policies and runtime reductions. Recommendation 3. What should be validated? Revalidation validate legal, audit, and maintenance history retention requirements before archiving historical orders. Recommendation 4. What should be governed? Responsibility require business process owners to formally approve maintenance order retention periods before conversion planning begins.
Migration Incident 5. GIS integration dependencies missed.
During the discover phase of an SAP ECC to SAP S/4HANA migration, organizations frequently overlook the deep dependencies between their legacy plant maintenance system and external geographical information systems (GIS). GIS integrations are critical for utility, pipeline, and linear asset-intensive companies, where functional locations and equipment are mapped directly to physical coordinates on Earth. Failing to catalog these integrations, geographical sync jobs, and custom coordinate mapping tables during early assessment workshops leads to a complete breakdown of spatial asset tracking and mapping functionalities when the system is converted.
Incident classification and relevant SAP note if applicable.
1. Complexity. High enterprise integration architecture failure. 2. Migration phase discover. 3. Frequency common in linear asset industries. 4. Primary ownership integration architect. 5. Supporting PM functional lead GIS specialist basis architect. 6. Business ownership program sponsor. 7. Relevant SAP note not applicable. Third-party GIS integration assessment gap.
How teams identify this issue. Diagnostic dashboard. Symptoms and evidence.
How missed geographical integration dependencies typically reveal themselves during the program lifecycle. 1. Symptom. Maintenance planners cannot view or plot technical objects on spatial maps inside the system, causing a complete stop in geographical planning. 2. Red flag. Finding legacy custom tables that link SAP technical object IDs to GIS shapefiles without any standard API documentation. 3. Business impact. Field technicians are dispatched to incorrect locations, leading to delayed repair times and increased operational safety risks. 4. Detection. Interface inventory workshops reveal GIS applications, middleware platforms, or map rendering services that were omitted from the original integration landscape documentation. 5. Technical proof. RFC connection test logs show failed pings, or web service logs show unmapped payload structures between SAP and the legacy GIS middleware. Insight. If geographical coordination jobs run silently in the background, they are often forgotten until they fail on the new database.
Incident analysis and root cause. Why this happens.
1. Silos between the SAP core team and the external GIS and operational technology engineering teams prevent integration touchpoints from being jointly analyzed. 2. Assessments focus entirely on standard SAP transactions, completely ignoring the background data synchronization jobs running in the middleware. 3. Organizations assume that standard S/4HANA features like the Geographical Enablement Framework (GEF) will natively consume legacy coordinate mappings without any redesign. 4. Legacy GIS interfaces were custom-built decades ago and lack active, up-to-date interface registry documentation. The root cause is treating GIS mapping as a local plant floor utility rather than a critical enterprise integration boundary.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migration because the underlying data model and API structures are modernized. 2. S/4HANA encourages modernization of GIS integrations through standard frameworks such as GEF, APIs, OData services, and SAP Business Technology Platform integration patterns. 3. Legacy GIS integrations that rely on direct table access, custom database updates, or unsupported interface techniques often require redesign to align with S/4HANA data models and integration standards. 4. Under normal ECC operations, legacy background sync jobs run without disruption, hiding the architectural debt until the database is converted. S/4HANA's modern API and security architecture strongly encourage migration away from direct table modifications towards supported integration patterns.
Business and program impact.
1. Project timelines expand significantly as development teams are forced to rebuild custom mapping middleware during UAT. 2. Costly post-conversion remediations are required to restore GIS integration sync jobs, blowing up the innovation budget. 3. High operational risk of dispatching emergency repair crews to the wrong geographic assets due to unmapped coordinates. 4. Planners lose real-time visibility into regional breakdown backlogs, directly impacting overall asset reliability metrics. A broken spatial integration represents a severe field safety hazard for heavy infrastructure operators.
Strategic decision. GIS integration modernization approach.
Answer: selecting the target GIS integration modernization approach requires balancing custom interface complexity, target data models, and long-term business goals. We must evaluate these 5 potential options. 1. Retain existing GIS integration subject to compatibility validation. Keep legacy interfaces and coordinate mappings, validating compatibility and performance on S/4HANA without altering integration architecture. 2. Modernize through APIs and OData. Redesign the spatial data exchange to utilize modern OData services and standard SAP APIs. 3. Introduce SAP BTP integration layer. Decouple the integration by utilizing standard SAP BTP integration flows as a secure translation proxy. 4. Adopt GEF-based architecture. Implement the standard SAP Geographical Enablement Framework to natively align business objects with spatial GIS registries. 5. Replace legacy GIS platform. Decommission the outdated spatial system completely in favor of a modern, enterprise-approved GIS cloud platform. Pro tip: if your legacy custom GIS integration is highly unstable, use the migration as a business case to rebuild it on BTP.
GIS integration decision matrix.
A standard analytical matrix to determine GIS integration modernization paths during the discover phase. 1. Standard GIS integration working. Retain and validate target interfaces on S/4HANA without altering functional patterns. 2. Custom RFC-based integration. Modernize using standard SAP APIs or secure OData services. 3. Unsupported middleware. Replace with a modern integration layer on SAP BTP or standard enterprise middleware. 4. Legacy direct table integration. Redesign to align with standard S/4HANA application logic and APIs. 5. No documentation exists. Reverse engineer active transport payloads, RFC destinations, and database triggers. Architect's rule: do not leave undocumented spatial interfaces. Reverse engineer them before the prepare phase begins.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Integration architect, the person who owns the system interface registry and gets fired if uninventoried GIS connections fail and freeze emergency maintenance operations. 2. Responsible. PM functional lead, maps technical object IDs to the corresponding geographical coordinates. 3. Consulted. GIS specialist, basis architect, lead ABAP developer. 4. Informed. Program sponsor, steering committee, business process owners. Integration architects must audit all standard and non-standard interface endpoints before the project exits the prepare phase.
Ownership, who actually fixes it.
Resolving spatial integration gaps requires joint technical and functional reassessment. 1. Enterprise solution architect reevaluates the target GIS integration strategy and defines the future state integration architecture. 2. PM functional lead validates the mapping between SAP technical objects and their corresponding GIS spatial identifiers and coordinate structures. 3. GIS specialist configures external spatial databases to align with S/4HANA specifications. 4. Basis team configures and tests the target security certificates and RFC endpoints.
Who gets blamed versus who owns it?
1. Blamed. PM functional team business blames PM consultants for failing to flag geographical mapping requirements during workshops. 2. Blamed. GIS specialists accused of making uncoordinated changes to spatial databases without notifying the core project. 3. Actual owner. Integration architect accountable for mapping out the complete interface registry, including all legacy third-party endpoints. 4. Root cause. Failure to invite GIS and spatial database specialists to the early discover phase architecture workshops. Do not blame the business for missing spatial interfaces. The integration architect must enforce a strict interface discovery process.
How this is actually fixed the right way by a role.
1. Integration architect maps every legacy GIS web service, RFC destination, and custom database trigger during a comprehensive interface assessment. 2. PM functional lead audits the legacy technical object registry to identify all GIS mapping repositories, custom coordinate tables, and spatial object relationships. 3. Lead ABAP developer reviews legacy GIS middleware code to identify custom data payload transformations that must be redesigned. 4. Basis lead configures and tests the target S/4HANA security certificates and RFC endpoints to establish a secure link with the GIS server. Standardizing your spatial interfaces on GEF is the only way to protect your GIS integration during future upgrades.
Common mistakes to avoid what not to do.
1. Do not assume that standard S/4HANA GEF will automatically convert your legacy custom GIS coordinate mappings without a functional redesign. 2. Do not delay the integration mapping of third-party GIS applications until the functional testing phase of the project. 3. Do not allow the core SAP migration team to operate in a silo without actively consulting your GIS engineering and mapping specialists. 4. Do not rely on legacy RFC endpoints without verifying that S/4HANA's modern security protocols support the target GIS server. Hoping that legacy mapping tables will magically work in S/4HANA is a critical project risk.
Follow-up 1. What is the SAP Geographical Enablement Framework, GEF, and how does S/4HANA utilize it?
Answer. The SAP Geographical Enablement Framework, GEF, is an SAP framework that helps integrate spatial GIS information with business objects such as equipment and functional locations. It provides a framework for linking SAP business objects with spatial information maintained within GIS platforms. Planners can plot, visualize, and dispatch work orders directly from an interactive map interface inside S/4HANA, eliminating the need for legacy custom mapping workarounds. Leveraging GEF ensures that all spatial coordinates are processed using standard SAP APIs, securing seamless compatibility with future system upgrades.
Follow-up 2. How do you identify hidden GIS interfaces during the discover phase if they are not documented?
Answer. Identifying undocumented GIS interfaces requires the integration architect to perform a deep semantic review of legacy system connection logs and background processes. The architect must audit transaction SM59 to analyze every active RFC destination, scanning for connections pointing to external spatial data servers like ESRI. Additionally, running background job audits via transaction SM37 helps locate any legacy ABAP programs executing hourly or nightly coordinate synchronization runs. Finally, tracing custom interface programs, middleware payloads, and updates to GIS-related custom tables can reveal hidden integration dependencies.
Follow-up 3 curveball. How would you handle a situation where a legacy GIS middleware cannot support S/4HANA's modern OData-based security standards?
Answer. If legacy GIS middleware cannot support S/4HANA's secure, modern OData, or REST-based communication, the integration architect must design a secure intermediate translation layer. Rather than compromising the security of the core S/4HANA system by downgrading TLS versions or Authentication protocols. The integration architect should implement a secure middleware translation layer, often using SAP BTP or another enterprise integration platform. The BTP middleware acts as a secure proxy, consuming modern OData payloads from S/4HANA, validating the security certificates, and translating them into legacy-compliant formats for the old GIS server. This side-by-side architecture isolates the legacy system's technical debt while keeping the core S/4HANA system clean, secure, and fully compliant with modern compliance standards.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete, standard interface audit across all legacy PM programs to map out every active external coordinate sync job before designing the target architecture. Recommendation 2. What successful projects do? Reliability elite projects establish a combined SAP GIS integration workgroup during the prepare phase, bringing together ERP and OT engineers to design unified interface payloads. Recommendation 3. What should be validated? Revalidation. Validate legacy coordinate mapping accuracy by running geographic rendering tests on a subset of critical equipment assets in a sandbox copy. Recommendation 4. What should be governed? Responsibility. Require formal architectural approval and sign off on the target GIS integration design from both the ERP program director and the GIS operations manager before starting build activities.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 6. External mobile applications excluded from scope.
During the discover phase of an SAP ECC to SAP S/4HANA migration, organizations often fail to include legacy external mobile maintenance applications in the initial transformation scope. Because these apps rely on highly complex middleware like SAP Mobile Platform or Agentry and direct table lookups on the legacy ECC database, excluding them from early scoping leads to a complete disruption of plant floor maintenance operations on day 1 of go-live, as technicians cannot retrieve or confirm work orders in the field.
Incident classification and relevant SAP, note if applicable.
1. Complexity, high mobility architecture scoping failure. 2. Migration phase, discover. 3. Frequency, common in asset-intensive industries. 4. Primary ownership, mobile solutions lead. 5. Supporting, PM functional lead, basis architect, enterprise solution architect, and integration architect for large programs. 6. Business ownership, VP of operations / plant manager. 7. Relevant SAP note, SAP note 2660361. SAP service and asset manager release information.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How ignored mobile integration dependencies typically reveal themselves during the program lifecycle. 1. Symptom. Field technicians are unable to download newly assigned maintenance orders or upload time confirmations on their mobile devices post-sandbox conversion. 2. Red flag. Finding legacy agentry or SMP SAP mobile platform sync ports mapped to the ECC environment without any corresponding S/4HANA upgrade plans. 3. Business impact. Maintenance backlogs spike dramatically as field crews are forced to revert to manual paper-based order distribution. 4. Detection. Architecture discovery workshops reveal active Cyclo or agentry database tables such as /Cyclo/ custom namespaces in the legacy ECC environment. 5. Technical proof. Middleware synchronization logs reveal failed backend calls, interface mapping errors, or unsupported data structures following sandbox conversion testing. Insight. If legacy mobile apps depend on direct database table selections, they will completely fail in S/4HANA.
Investigation tools and transactions used.
Use these tools and transactions to diagnose and trace legacy mobile interface synchronization issues. 1. SM59 RFC connections. Analyze active RFC connections pointing to the SAP Mobile Platform (SMP) or external mobile middleware servers. 2. /IWFND/error_log OData gateway error log. Investigate OData service failures and gateway mapping errors generated by mobile synchronization attempts. 3. Legacy Cyclo administration transactions. Audit legacy Cyclo agentry configurations, active user profiles, and synchronization logs directly inside the SAP backend. 4. SMP management cockpit. Check external middleware event logs and mobile endpoint connections to identify payload mismatch errors during migration dry runs. Architect's rule. Do not try to debug mobile connection failures in S4HANA without first checking /IWFND/error_log.
Incident analysis and root cause why this happens.
1. Project steering committees treat mobile applications as isolated, third-party add-ons rather than tightly integrated extensions of the core ERP. 2. The team assumes that legacy agentry, or SMP middleware, will remain compatible with the S4HANA data model without requiring redesign. 3. Functional architects overlook the direct database queries and custom /sci-close/tables that the legacy mobile apps depend on. 4. Silos between the core SAP migration team and local plant floor operations hide the true scale of mobile usage in the field. The root cause is treating field mobility as a non-critical utility rather than an active process extension.
Why this issue appears only during an ECC to S4HANA migration.
1. The issue becomes highly visible during S4HANA migration because organizations frequently re-evaluate legacy mobile architectures and integration approaches. 2. S4HANA encourages modernization of mobile applications through SAP Service and Asset Manager, SAP Mobile Services, standard APIs, and OData-based integration patterns. 3. Legacy Cyclo and agentry implementations that rely on custom database access patterns or obsolete integration designs frequently require redesign or modernization during S4HANA migrations. 4. Under normal ECC operations, legacy middleware sync jobs run without disruption, hiding the architectural debt until the core database is converted. S4HANA's modern gateway OData layer is incompatible with old direct table database updates.
Business and program impact.
1. Maintenance planning and scheduling efficiency can decline significantly during the initial post-go-live period. 2. Data integrity is severely compromised as technicians write manual notes on paper and upload batch data late. 3. Unbudgeted software licensing and consulting fees are incurred late in the project to replace or upgrade legacy mobile platforms. 4. Decline in safety compliance as supervisors fail to distribute critical hazard and work clearance documents in the field. A broken mobile maintenance platform directly results in immediate operational and scheduling backlogs.
Impact on technicians and maintenance teams.
How a failed mobile integration directly impacts the daily operations of field crews and planners. 1. Technicians cannot download work orders or view technical object attachments such as safety checklists or CAD drawings while working in offline plant zones. 2. Supervisors must manually print shop papers using transaction IW3D and physically distribute them, causing massive confusion and delay during shift changes. 3. Field crews must perform manual time and material tracking on paper, leading to significant transcription errors when uploading data later. 4. Technicians lose real-time visibility into urgent safety hazard alerts, increasing overall workplace safety risks. Forcing field technicians back to paper-based tracking destroys the user adoption of your new S4HANA system.
Strategic decision. Evaluating mobile maintenance strategy.
Answer: resolving the mobile maintenance scoping gap requires selecting a sustainable S4HANA compliant mobile platform. We must evaluate these 4 strategic options. 1. Adopt SAP Service and Asset Manager SSAM. Migrate to SAP's strategic mobile maintenance platform, accepting initial cloud enablement and licensing parameters. 2. Upgrade legacy SAP Work Manager. Retain the legacy agentry-based Work Manager platform, upgrading its backend integration to S4HANA-compatible agentry components. 3. Custom Fiori offline applications. Build custom, side-by-side offline Fiori applications on SAP BTP to replace legacy third-party mobile systems. 4. Retain third-party mobile apps. Keep the existing non-SAP mobile solution, completely redesigning its integration APIs to consume S4HANA standard OData services. Pro tip: if your legacy agentry work manager is heavily customized, do not waste money upgrading it. Migrate directly to SSAM on BTP.
Mobile integration decision matrix.
A standard architectural matrix to determine the correct mobile integration path during the discover phase. 1. Offline requirement critical. Prioritize SAP Service and Asset Manager SSAM or another proven offline-capable mobile platform, validating synchronization performance, attachment handling, and conflict resolution before finalizing the target architecture. 2. Standard SAP Work Manager Agentry. Upgrade to S/4HANA-compatible agentry components or strategically migrate to cloud-native SSAM. 3. Custom or Cyclo Agentry App. Rebuild as a cloud-native BTP extension to eliminate legacy agentry middleware dependencies. 4. Third-party mobile app. Redesign the integration APIs to consume S/4HANA standard OData services instead of legacy direct table reads. 5. Paper-based legacy process. Implement standard SAP Service and Asset Manager SSAM to drive mobile operational efficiency in the field. Architect's rule. Do not leave undocumented mobile interfaces. Evaluate and standardize them during the discover phase.
Governance and accountability, RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Mobile Solutions Lead, the person who owns the system interface registry and gets fired if legacy mobile connections fail on go-live day. 2. Responsible. PM Functional Lead maps technical object fields to the corresponding mobile OData services. 3. Consulted. Basis Architect, Integration Architect. 4. Informed. Program Sponsor, Steering Committee, Business Process Owners. The mobile solution lead must validate all standard and custom mobile endpoints before entering the prepare phase.
Ownership, who actually fixes it.
Resolving spatial integration gaps requires joint technical and functional reassessment. 1. Mobile solutions lead inventories mobile applications, synchronization mechanisms, offline capabilities, custom extensions, and backend integrations before designing the target mobility architecture. 2. PM Functional Lead audits legacy PM custom table fields to ensure standard S/4HANA OData services can support the required mobile data payloads. 3. Basis Architect configures secure communication protocols HTTPS or OData on the S/4HANA gateway and test environments. 4. Senior ABAP developer rebuilds any required legacy custom exit logic, for example, inside mobile enhancement spots using modern baddies.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of breaking mobile connections during the technical sandbox database conversion. 2. Blamed. PM Functional Team business blames consultants for not identifying critical mobile process dependencies. 3. Actual owner. Mobile Solutions Lead, accountable for assessing legacy mobile middleware and including them in the migration scope early. 4. Root cause. Failure to perform a comprehensive mobility architecture assessment during the discover phase of the project. Do not blame the basis team for broken mobile integrations. The mobility architecture assessment should have identified these dependencies much earlier.
How this is actually fixed the right way by a role.
1. Mobile Solutions Lead designs the target S/4HANA mobile architecture, mapping legacy SMP or agentry setups to cloud-native SSAM endpoints on SAP BTP. 2. PM Functional Lead audits legacy PM custom fields to ensure target S/4HANA OData services can support the required mobile data payloads. 3. Basis Architect configures the secure SAP gateway and tests standard OData endpoints such as CO_EAM_BUS2007_EX or any standard EAM OData services to establish a secure link. 4. Senior ABAP developer rebuilds any required legacy custom exit logic, for example, inside mobile enhancement spots using modern baddies. Scrubbing your legacy custom code repository can reduce your ABAP remediation scope by up to 60%.
Common mistakes to avoid what not to do.
1. Do not assume that legacy agentry or SMP mobile applications will run natively on S/4HANA without substantial integration upgrades. 2. Do not bypass security certificate and SSL validations on target mobile endpoints, as this invites severe cybersecurity risks. 3. Do not delay the deployment of S/4HANA mobile test environments, as offline synchronization can only be validated under real plant floor network conditions. 4. Do not allow local plant operations to revert to paper-based tracking permanently, as this destroys the data integrity of your new S/4HANA system. Ignoring mobile application dependencies is the fastest way to create operational disruption immediately after go live.
Follow-up 1. What is the main architectural difference between legacy SAP Work Manager and the new SAP Service and Asset Manager SSAM?
Answer: the legacy SAP Work Manager relies on agentry metadata-driven middleware, which requires proprietary local database synchronizations and direct backend table reads. Conversely, the new SAP Service and Asset Manager SSAM leverages SAP Mobile Services and SAP BTP capabilities, while consuming standard S/4HANA APIs and OData services. This modern architecture eliminates legacy middleware complexity, simplifies user provisioning, and natively supports real-time, side-by-side extensions. Transitioning to SSAM ensures that mobile maintenance processes are fully decoupled from the core ERP, protecting your mobile landscape during future upgrades.
Follow-up 2. Why is the /sci/clo/namespace critical to audit during an ECC/PM migration?
Answer: the custom namespace /sci/clo/ contains the entire backend configuration, mapping tables, and custom ABAP code of legacy SICLO or SAP Work Manager mobile applications. Auditing this namespace during the discover phase is critical because these legacy configurations are often supported by custom programs and integrations that contain direct database access logic and custom fields that are completely incompatible with the simplified S/4HANA data model. Failing to scan and remediate the /sci/clo/ repository leads to major gateway errors, broken RFC connections, and failed synchronization jobs. A thorough audit allows the mobile architect to identify which custom mobile fields must be systematically mapped to standard S/4HANA OData objects.
Follow-up 3 Curveball. How do you handle custom fields on the PM work order screen when migrating to standard SAP Asset Manager?
Answer: when migrating custom work order fields to the standard SAP Service and Asset Manager SSAM, we must utilize the standard S/4HANA OData extension framework. Rather than directly modifying standard SAP mobile tables or writing complex legacy custom code, we extend the standard SAP Asset Manager OData services using supported extension mechanisms on BTP. This involves extending the S/4HANA business entity in the backend, exposing the custom fields through the secure OData layer, and mapping them to the mobile UI using the SAP Mobile Services Editor. This side-by-side extension model keeps the core S/4HANA ERP clean, while ensuring that custom business-critical fields remain available on technicians' mobile screens.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization inventory every mobile application, middleware component, synchronization process, and field usage pattern during discover. Recommendation 2. What successful projects do? Reliability perform end-to-end mobile process testing in a sandbox environment before finalizing the target mobility strategy. Recommendation 3. What should be validated? Revalidation validate offline functionality, attachment synchronization, notification processing, and work order completion scenarios. Recommendation 4. What should be governed? Responsibility require business approval for the target mobile platform and mobile process design before entering the build phase.
Migration Incident 7. Third-party maintenance scheduling tools not identified.
During the discover phase of an SAP ECC to SAP S/4HANA migration, organizations often fail to identify third-party maintenance scheduling and planning tools during their interface inventory. Asset-intensive enterprises frequently rely on external planning boards to manage technician daily allocations and dispatch routines. Because these legacy scheduling systems integrate using custom RFC connections, iDocs, or direct selections from standard PM tables, omitting them from early scoping workshops results in a complete failure of the planning board interface when the core database is converted.
Incident classification and relevant SAP note if applicable.
1. Complexity. Medium interface architecture discovery failure. 2. Migration phase, discover. 3. Frequency, common in older ECC landscapes. 4. Primary ownership, integration architect. 5. Supporting, PM functional lead, basis architect, lead ABAP developer. 6. Business ownership, maintenance planning lead. 7. Relevant SAP note, not applicable, interface architecture discovery gap.
How teams identify this issue, diagnostic dashboard, symptoms and evidence.
How unrecognized maintenance scheduling integrations typically reveal themselves during the program lifecycle. 1. Symptom. Maintenance schedulers open their planning boards and find them completely empty, with no work orders or technician capacities displaying. 2. Red flag. Finding legacy background job logs that continuously attempt to push work order allocations to an unregistered external endpoint. 3. Business impact. Planners cannot assign work orders, leading to highly uncoordinated maintenance execution and delayed backlog resolution. 4. Detection. Interface inventory workshops or custom program scans reveal active RFC destinations pointing to non-SAP scheduling servers. 5. Technical proof. Outbound transactional RFC logs show failed synchronization payloads with connection failures, payload validation errors, or authentication failures. Insight. If legacy scheduling integrations run silently without proper documentation, they represent a severe go-live risk.
Incident analysis and root cause why this happens.
1. Steering committees assume that scheduling is a minor functional feature handled entirely within standard SAP plant maintenance transactions. 2. The third-party scheduling software was implemented locally by plant management years ago without central IT involvement or documentation. 3. The technical team scans only standard SAP interfaces, completely missing custom database triggers that push order updates to external schedulers. 4. The program team assumes existing scheduling functionality can be replaced or redesigned later, without fully understanding current third-party dependencies. The root cause is treating maintenance scheduling as a local plant utility rather than an active enterprise interface.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes highly visible during S/4HANA migration because organizations must reassess legacy integration methods, security models, and custom scheduling interfaces. 2. Legacy scheduling tools rely on direct database reads or obsolete API structures that are incompatible with S/4HANA's simplified database layout. 3. System conversion activities temporarily restrict system availability during migration testing and cutover events, exposing dependencies that were previously unnoticed. 4. Modern integration architectures often require stronger authentication, encrypted communication, and supported interface technologies, exposing weaknesses in legacy scheduling integrations. Legacy database shortcuts used by external planning boards will not execute on the S/4HANA simplified data model.
Business and program impact.
1. Project timelines expand during integration testing as developers are forced to rebuild custom scheduling interfaces. 2. Unexpected software consulting costs are incurred to upgrade third-party scheduling connectors late in the project. 3. Planners lose the ability to schedule urgent preventive or corrective maintenance orders, increasing the risk of equipment failure. 4. Decline in shop floor labor productivity as technicians receive unoptimized or conflicting daily work schedules. A broken scheduling interface directly results in immediate backlog accumulation and uncoordinated asset downtime.
Strategic decision. Scheduling tool modernization strategy.
Answer: managing external planning board integrations requires selecting a robust S/4HANA compatible scheduling platform. We must evaluate these 4 strategic options. 1. Retain and optimize third-party schedulers. Retain active third-party planning boards, refactoring custom RFC connections and database triggers to utilize S/4HANA standard APIs. 2. Adopt standard SAP resource scheduling RSH capabilities. Standardize scheduling operations entirely within the ERP core by adopting standard Fiori-based resource scheduling for maintenance planners. 3. Deploy SAP multi-resource scheduling MRS. Utilize standard MRS to handle highly complex technician capacity and constraint-based scheduling scenarios. 4. Rebuild on SAP BTP. Decouple the planning board from the core ERP by rebuilding custom dispatching utilities as side-by-side cloud extensions on SAP BTP. Pro tip: if legacy custom scheduling integrations are highly unstable, evaluate the business case for standard RSH or MRS solutions.
Scheduling tool decision matrix.
A standard analytical matrix to determine the correct scheduling integration path during the discover phase. 1. Highly customized scheduling logic. Retain specialized scheduling platform or redesign custom optimization algorithms before migrating to standard RSH or MRS. 2. Standard planning board working. Retain and validate target interfaces on S/4HANA without altering integration patterns. 3. Custom RFC-based scheduling. Modernize using standard SAP APIs or secure OData services. 4. Geographical dispatch scheduling required. Integrate advanced spatial planning tools via secure API layers to optimize local routing and crew dispatch. 5. Paper-based planning process. Adopt standard SAP resource scheduling RSH or MRS to establish digital scheduling controls in the core ERP. Architect's rule: do not leave undocumented scheduling interfaces. Evaluate and standardize them during the discover phase.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Integration architect, the person who owns the system interface registry and gets fired if uninventoried scheduling interfaces fail and paralyze the plant planning boards. 2. Responsible. PM functional lead maps technical object fields to the corresponding scheduling API payloads. 3. Consulted. Basis architect. Lead a BAP developer. 4. Informed. Program sponsor, steering committee, maintenance planning lead. Steering committees must establish clear interface discovery guidelines before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving spatial integration gaps requires joint technical and functional reassessment. 1. Integration architect audits the interface catalog and designs secure communication paths between S/4HANA and the scheduling tool. 2. PM functional lead maps work orders, operations, capacities, crews, and technical objects to target scheduling payloads. 3. Basis architect configures secure RFC connections and handles certificate exchanges between systems. 4. Senior ABAP developer remediates any obsolete custom interface triggers or synchronization programs.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of failing to identify the scheduling integrations during process scoping workshops. 2. Blamed. Planning board vendor accused of delivering an unstable interface that is incompatible with S/4HANA. 3. Actual owner. Integration architect accountable for identifying every interface endpoint, including local plant planning systems. 4. Root cause. Failure to enforce a rigorous interface discovery process and involve local planners and plant stakeholders during early scoping workshops. Do not blame the functional team for undocumented interfaces. The integration architect must own the registry.
How this is actually fixed the right way by a role.
1. Integration architect maps every legacy scheduling web service, RFC connection, and file-based data transfer during an interface discovery audit. 2. PM functional lead reviews the technical object and work order structure modifications to ensure the scheduling API payload remains valid. 3. Basis architect configures secure RFC destinations and validates connection protocols with the external scheduling server. 4. Senior ABAP developer refactors the legacy custom triggers, replacing obsolete direct database updates with standard S/4HANA APIs. Standardizing your planning board connections on modern APIs is the only way to protect your scheduling during future upgrades.
Common mistakes to avoid what not to do.
1. Do not assume that standard S/4HANA resource scheduling RSH will automatically replace third-party planning boards without a business transition plan. 2. Do not delay the validation of external scheduling interfaces until the system integration testing (SIT) phase of the project. 3. Do not allow local plant planners to operate on isolated spreadsheets or disconnected boards, as this destroys target data integrity. 4. Do not bypass standard SAP APIs to perform direct database updates on maintenance order tables from external schedulers. 5. Do not assume that a planning board is merely a reporting tool. Many scheduling systems actively update technician assignments, capacities, and work order priorities.
Follow-up 1. How does S/4HANA Resource Scheduling RSH compare to third-party scheduling tools?
Answer. Standard S/4HANA Resource Scheduling is a Fiori-based, in-memory tool designed to optimize maintenance order and operations scheduling directly within the core ERP database. Unlike legacy third-party scheduling tools, RSH does not require complex middleware synchronizations or custom data replication layers. It reads and writes live data in real time, eliminating latency and data mismatch risks. However, if a plant requires highly complex, constraint-based multi-resource scheduling or geographical dispatching, a specialized third-party tool remains the preferred choice.
Follow-up 2. What is the risk of using custom database triggers to sync maintenance orders with external schedulers?
Answer. Using custom database triggers represented a common workaround in ECC to push real-time order updates to external schedulers. In S/4HANA, this practice is highly dangerous because direct database updates bypass standard application logic, validation rules, status management, and integration processes, creating data consistency and supportability risks. If a trigger attempts to update core tables such as OFC or AFIH directly, it can create data inconsistencies, status synchronization issues, failed business validations, and unsupported system behavior that becomes difficult to troubleshoot after conversion. To secure system stability, developers must systematically replace these legacy triggers with standard, event-driven S/4HANA APIs or outbound OData services.
Follow-up 3 Curveball. How would you migrate a customer using legacy SAP multi-resource scheduling misses to S/4HANA?
Answer. Migrating a legacy SAP multi-resource scheduling customer to S/4HANA requires a strategic evaluation of their scheduling complexity. If the customer uses standard MISS functionalities, we can upgrade to S/4HANA compatible MISS components or transition to standard resource scheduling RSH. However, if they have built extensive custom enhancements on their legacy MISS planning board, we must systematically redesign those extensions. The integration architect must map legacy custom exits to standard S/4HANA APIs, ensuring that technician capacities and work order allocations synchronize without causing database lock conflicts.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization. Run a complete, standard interface audit across all plants during Discover to catalog every third-party planning board, custom RFC destination, and data transfer mechanism in use. Recommendation 2. What successful projects do? Reliability elite projects establish a combined EAM and scheduling integration team during the prepare phase, bringing together SAP functional leads and third-party software engineers to design unified API payloads. Recommendation 3. What should be validated? Revalidation. Validate the performance and data synchronization accuracy of the target scheduling interface by executing high-volume order load simulations in a sandbox environment. Recommendation 4. What should be governed? Responsibility. Require formal business sign-off and functional approval on the target scheduling integration design from both the plant maintenance director and the integration architect before entering the build phase.
Migration Incident 8. Custom PM notification workflows undocumented.
During the Discover phase of an SAP ECC to SAP S/4HANA migration, project teams often overlook undocumented custom plant maintenance notification workflows. Legacy organizations commonly configure custom workflows using SAP Business Workflow to trigger automated approvals, email notifications, and work order creation when critical equipment breakdown notifications are created. Because these legacy workflows are undocumented and rely on obsolete database triggers, custom container variables, and deprecated table joins, omitting them from early scoping leads to a complete failure of the notification approval process post-conversion.
Incident classification and relevant SAP note if applicable.
1. Complexity. Medium custom workflow architecture assessment failure. 2. Migration phase discover. 3. Frequency common in older ECC landscapes. 4. Primary ownership workflow architect. 5. Supporting PM functional lead ABAP developer. 6. Business ownership maintenance operations manager. 7. Relevant SAP note not applicable custom workflow assessment gap.
How teams identify this issue diagnostic dashboard, symptoms and evidence.
How unrecognized legacy custom workflows typically reveal themselves during the program lifecycle. 1. Symptom. Business users find that urgent breakdown notifications are created in the system, but no automated approvals or email alerts are dispatched to planners. 2. Red flag. Finding active custom event linkages in transaction SWE2 that point to obsolete PM business objects without any corresponding documentation. 3. Business impact. Critical breakdowns sit in the system unassigned, causing significant asset downtime and delayed maintenance execution. 4. Detection. Architecture discovery workshops or custom workflow audits reveal legacy custom tasks linked to standard PM business objects like BUS2038 or BUS2078. 5. Technical proof. Workflow runtime logs SWI1 show failed event executions, or Event Queue browser logs SWEQ ADM show a backlog of stuck notification events. Insight. If legacy custom workflows rely on direct database triggers, they will fail to execute in S/4HANA.
Investigation tools and transactions used.
Use these tools and transactions to diagnose, trace, and validate legacy workflow issues during workflow discovery and migration assessments. 1. SWE2 event type linkages. Audit active event linkages between PM business objects and workflow templates to identify undocumented workflow triggers. 2. SWI1 workflow log. Analyze workflow runtime history to identify failed work items, approval bottlenecks, and inactive workflow paths. 3. SWELS event trace switch. Enable workflow event tracing to capture and troubleshoot workflow triggering events during testing. 4. SWEL event trace display. Review captured workflow events and verify that business object events are being raised correctly. 5. SWEQ ADM event queue administration. Monitor queued workflow events, identify processing backlogs, and resolve stuck event executions. 6. SWDD workflow builder. Review workflow definitions, container bindings, approval logic, and custom workflow step configurations. 7. PFTC task maintenance. Audit standard and custom workflow tasks, agent assignments, and task-level configuration dependencies. Architect's rule. Never assume a workflow is inactive simply because users cannot see it. Always validate event linkages, workflow logs, and active task definitions before finalizing the migration scope.
Incident analysis and root cause why this happens.
1. Legacy workflows were built years ago by developers who left the organization without leaving process maps or documentation behind. 2. Assessment teams treat workflows as simple functional configuration elements, failing to scan the active technical event linkage tables. 3. The business assumes that standard S/4HANA Fiori notification apps will natively trigger legacy backend workflows without any redesign. 4. The technical team focuses entirely on custom ABAP program scans, completely ignoring background event receivers and workflow containers. The root cause is treating custom workflows as a standard functional setup rather than an active custom extension.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migrations because S/4HANA modernizes the core workflow engines and business objects. 2. S/4HANA introduces flexible workflow capabilities and modern workflow design patterns, requiring organizations to reassess existing SAP business workflow implementations, custom event linkages, container bindings, and approval processes. 3. Legacy ECC workflows rely on outdated direct table queries and direct event triggers that require complete refactoring. 4. Under normal ECC operations, the legacy background event triggers execute without issue, hiding the risk until the system is converted. S/4HANA's modernized workflow engine will not execute unremediate legacy containers.
Business and program impact.
1. Project timelines expand significantly as developers are forced to troubleshoot and rebuild broken approval paths during the build phase. 2. Maintenance response times increase as planners are unaware of urgent equipment breakdowns, leading to localized production stoppages. 3. Decline in business trust as users find that automated notification routing is completely broken after the sandbox conversion. 4. Increased operational risk during the transition period as emergency work order approvals are delayed by broken workflows. 5. Regulatory maintenance approvals may be delayed, creating audit and compliance exposure. A broken approval workflow directly leads to communication bottlenecks and delayed maintenance execution.
Governance and accountability, Ray C. model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Workflow architect, the person who owns the custom workflow assessment and gets fired if broken legacy workflows paralyze breakdown notifications. 2. Responsible. PM functional lead documents the required business approval steps and conditions. 3. Consulted. Lead ABAP developer business process owner. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must establish clear workflow ownership before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving spatial integration gaps requires joint technical and functional reassessment. 1. Workflow architect audits the legacy event linkages and maps the target S/4HANA workflow architecture. 2. PM functional lead documents the required business approval steps and designs the future state notification process. 3. Lead ABAP developer refactors legacy custom workflow tasks and configures modern container variables. 4. Basis lead validates workflow runtime services, background job execution, event queue processing, and notification infrastructure.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of failing to test notification processes properly during early sandbox conversion testing. 2. Blamed. Business process owners accused of demanding over complicated approval processes that are too difficult to build. 3. Actual owner. Workflow architect, accountable for performing a comprehensive workflow audit and documenting legacy event linkages. 4. Root cause. Failure to involve workflow specialists and run event linkage audits during the discover phase of the project. Do not blame the functional team for undocumented workflows. The workflow architect must own the audit.
How this is actually fixed the right way by a role.
Workflow architect executes a comprehensive event linkage audit in transaction SWE2 to inventory all active custom workflow triggers. 2. PM functional lead interviews maintenance planners to document the business approval steps, conditions, and email notification paths. 3. Lead ABAP developer refactors the legacy custom tasks, replacing obsolete direct database queries with standard S/4HANA API services. 4. Basis lead configures the standard SAP gateway and tests event processing to ensure notifications trigger workflow containers successfully. Standardizing your approval paths on flexible workflow is the only way to protect your processes during future upgrades.
Common mistakes to avoid what not to do.
1. Do not assume that standard S/4HANA flexible workflow will natively consume legacy ECC custom workflow containers without redesign. 2. Do not delay the audit of custom event linkage tables SWE2 until the system integration testing SIT phase of the project. 3. Do not allow development teams to remediate legacy workflows without formal, documented business approval processes from the plant managers. 4. Do not bypass standard SAP business objects to trigger workflows directly from custom database tables. Hoping that legacy containers will magically work in S/4HANA is a critical project risk.
Follow-up 1. What is the S/4HANA Flexible Workflow Framework, and how does it affect legacy PM workflows?
Answer. S/4HANA Flexible Workflow is a modern, Fiori-based framework designed to simplify business approval paths by allowing functional consultants to configure processes without custom ABAP coding. In legacy ECC systems, plant maintenance notifications relied on the complex SAP business workflow engine, which required extensive developer involvement and custom container configurations, while standard ECC business objects like BUS2038 are still supported in S/4HANA. The flexible workflow framework offers a cleaner, low-code alternative that is easier to maintain. Transitioning to this framework ensures that approvals are managed side by side, protecting your custom logic during future system upgrades.
Follow-up 2. How do you identify undocumented custom workflows during the discover phase?
Answer: identifying undocumented custom workflows requires the workflow architect to run a rigorous audit of active system event linkages in transaction SWE2. This transaction maps standard SAP PM business objects to custom receiver types and active workflow templates. By filtering this list for PM objects such as BUS2038 and BUS2078, the architect can immediately isolate every active custom background trigger. Additionally, auditing the workflow runtime database tables and running historical log analysis via transaction SWI1 reveals which custom templates are actively executing in the legacy production environment.
Follow-up 3. Curveball. Why is a legacy custom workflow container variable particularly prone to failing after S/4HANA conversion?
Answer: legacy custom workflow container variables often fail because they rely on direct database queries or obsolete data structures that are simplified or reorganized in S/4HANA. In ECC, developers frequently map container variables directly to standard database tables to pass maintenance order or notification data. During system conversion, S/4HANA simplifies these core logistics tables and replaces legacy direct access pathways with streamlined CDS views. If a custom workflow attempts to read a simplified or deprecated field, the runtime engine will generate container binding errors and fail to resolve the process. To prevent this, architects must refactor legacy containers to utilize standard S/4HANA compliant APIs.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete, standard event linkage audit in transaction SWE2 during discover to catalog every active custom workflow trigger in use. Recommendation 2. What successful projects do? Reliability elite projects establish a combined EAM and workflow integration team during the prepare phase, bringing together functional leads and workflow developers to design standard flexible workflows. Recommendation 3. What should be validated? Revalidation: validate the performance and data synchronization accuracy of the target workflow containers by executing high-volume notification load simulations in a sandbox environment. Recommendation 4. What should be governed? Responsibility: require formal business sign-off and functional approval on the target workflow process design from both the plant maintenance director and the workflow architect before entering the build phase.
Migration incident 9. Functional location hierarchy inconsistencies ignored.
During the discover phase of an SAP ECC to SAP S/4HANA conversion, organizations frequently ignore the poor data quality of their legacy functional location hierarchies. Over decades of operation, individual plants develop localized, inconsistent naming conventions, creating broken asset trees, orphan locations, and circular hierarchy loops. Failing to standardize structure indicators and cleanse these inconsistencies during early assessments leads to severe UI performance issues and broken analytical cost roll-ups in S/4HANA.
Incident classification and relevant SAP note if applicable.
1. Complexity: medium master data architecture failure. 2. Migration phase discover. 3. Frequency: very common in decentralized landscapes. 4. Primary ownership master data lead. 5. Supporting PM functional lead data migration lead. 6. Business ownership maintenance operations manager. 7. Relevant SAP note not applicable technical object data quality gap.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How uncleansed legacy asset hierarchies typically reveal themselves during the program lifecycle. 1. Symptom: Fiori asset hierarchy browsers and equipment tree applications fail to render or experience massive latency when loading plant structures. 2. Red flag: finding more than 10 different active structure indicators configured for a single unified business entity. 3. Business impact: Planners cannot accurately roll up maintenance costs from lower-level equipment to the parent functional location. 4. Detection. Master data profiling workshops reveal thousands of orphaned functional locations that lack a defined superior node. 5. Technical proof. Database analysis of table IFLOT reveals missing superior functional locations field TPLMA or circular hierarchy references. Insight. Messy hierarchies in legacy GUI are an eyesore. In S/4HANA Fiori, they completely break the user experience.
Investigation tools and transactions used.
Use these tools and transactions to identify hierarchy corruption and structural inconsistencies in functional location master data. 1. IH01 Functional Location Structure Display. Visualize the complete functional location hierarchy and identify missing or inconsistent parent-child relationships. 2. IL03 Display Functional Location. Validate structure indicators, superior functional locations, and labeling standards on individual records. 3. SE16H or SE16NIFLOT Table Analysis. Identify orphan records, invalid superior functional locations, and hierarchy anomalies using direct data profiling. 4. SAP Data Services or Migration Cockpit Profiling Reports. Analyze duplicate naming conventions, inconsistent structure indicators, and mass cleansing requirements. 5. SAP S/4HANA Migration Cockpit Analysis. Validate mapping rules, hierarchy transformation logic, and migration readiness. Architect's rule. Never begin functional location migration without first profiling hierarchy integrity and structure indicator consistency.
Incident analysis and root cause why this happens.
1. Decades of mergers, acquisitions, and plan expansions introduce conflicting asset naming conventions without subsequent data harmonization. 2. Legacy ECC systems lacked central master data governance, allowing local plan engineers to create functional locations freely. 3. Project teams treat master data as a simple lift and shift extraction task rather than a strategic data transformation opportunity. 4. Business stakeholders underestimate the strict hierarchical data prerequisites required by S/4HANA's embedded analytics.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes highly visible during S/4HANA migration because modernized Fiori UX and CDS views rely on strictly defined hierarchical relationships. 2. S/4HANA embedded analytics dynamically aggregate costs in real time using recursive hierarchy logic, which fails entirely when loops or orphan nodes exist. 3. Legacy ECC list reports like IH01 were highly forgiving of missing hierarchy links, masking the extent of the underlying data corruption. 4. Modern integration scenarios, such as pushing S/4HANA asset trees to SAP Asset Performance Management, strictly reject non-standardized structures. S/4HANA's real-time analytical power is useless if the underlying data hierarchy is fractured.
Business and program impact.
1. User acceptance testing UAT is delayed as business users reject the new system due to unreadable, disorganized asset trees. 2. Financial month-end close activities are delayed because maintenance costs cannot be accurately aggregated to parent cost centers. 3. Additional, unbudgeted data cleansing cycles are added to the critical path, delaying the overall cutover timeline. 4. Field technicians struggle to locate physical assets, increasing wrench time delays and negatively impacting equipment reliability metrics. Uncleansed asset hierarchies directly sabotage the operational efficiency expected from a S/4HANA transformation.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Master data lead, the person who owns the master data readiness milestone and gets fired if dirty hierarchies break UAT. 2. Responsible. PM functional lead defines the target structure indicators and renaming conventions. 3. Consulted. Maintenance operations manager, plant reliability engineers. 4. Informed. Program sponsor, enterprise solution architect, steering committee. Do not let the technical data migration team attempt to cleanse business master data without functional guidance.
Ownership, who actually fixes it.
Resolving hierarchical data corruption requires structured evaluation and programmatic cleanup. 1. Master Data Lead runs data profiling reports to isolate circular references, orphan nodes, and inconsistent structure indicators. 2. PM Functional Lead works with local plant engineers to standardize the enterprise-wide functional location naming convention. 3. Data Migration Lead executes programmatic transformation scripts using the S/4HANA Migration Cockpit to rename and reparent locations. 4. Maintenance Operations Manager formally approves the final cleansed hierarchy structure before it is loaded into the target system.
Who gets blamed versus who owns it?
1. Blamed. Fiori development team accused of building a slow or broken asset hierarchy application that fails to load. 2. Blamed. PM functional team business blames functional consultants for an unreadable equipment structure. 3. Actual owner. Master Data Lead accountable for assessing legacy data quality and enforcing mandatory cleansing cycles. 4. Root cause. Failure to prioritize master data profiling and harmonization during the early discover phase. Do not blame the UX developers when the underlying master data architecture is fundamentally broken.
How this is actually fixed the right way by a role.
1. Master Data Lead executes legacy transaction IH01 and custom database queries to extract the complete list of orphaned or disjointed functional locations. 2. PM Functional Lead consolidates redundant structure indicators TPLKZ and defines a unified enterprise standard asset hierarchy template. 3. Data Migration Lead utilizes alternative labeling functions or direct mapping files to systematically rename and reparent the extracted locations. 4. Maintenance Operations Manager visually validates the new cleansed hierarchy in the sandbox environment to ensure operational accuracy. Cleansing your asset hierarchy is a mandatory prerequisite for enabling real-time cost analytics in S/4HANA.
Common mistakes to avoid what not to do.
1. Do not migrate legacy functional location hierarchies, as is without verifying that every node connects to a valid superior location. 2. Do not allow individual plants to retain their highly localized structure indicators when implementing a unified global S/4HANA template. 3. Do not attempt to fix massive hierarchical loops manually during UAT. This must be resolved programmatically during the prepare phase. 4. Do not underestimate the impact of messy asset hierarchies on the performance of modern embedded analytics and Fiori tree applications.
Follow-up 1. Why are structure indicators so critical when migrating functional locations to S/4HANA?
Answer. Structure indicators define the strict edit masks and hierarchical levels for functional locations, dictating how an asset string is parsed by the system. In S/4HANA, standardizing these indicators is critical because Fiori-based analytical apps and real-time CDS views rely on uniform structural logic to perform rapid, dynamic cost roll-ups. If a migrated landscape contains 15 conflicting structure indicators, the recursive logic cannot uniformly traverse the asset tree, causing systemic reporting failures and degraded user experience.
Follow-up 2. How can alternative labeling help harmonize legacy functional locations during a migration?
Answer. Alternative labeling is an advanced configuration feature that allows organizations to physically rename a functional location's visible label without changing its underlying system database key. During a migration involving multiple legacy plants or recent M&A activities, this feature is invaluable. It enables the data migration team to impose a strictly harmonized, global naming convention across the enterprise while preserving historical maintenance records, measuring points, and equipment linkages tied to the original primary key.
Follow-up 3 Curveball. What causes a hierarchy loop in plant maintenance, and why is it dangerous in S/4HANA?
Answer. A hierarchy loop occurs when an asset structure contains a circular reference, such as functional location A being assigned as the parent of B, while B is incorrectly updated to be the superior of A. In legacy environments, these database anomalies were often ignored by flat list reports. In S/4HANA, modern embedded analytics use recursive CTE's common table expressions to traverse hierarchies in real time. If the database engine encounters a circular loop, the query will infinitely recurse, resulting in severe memory dumps, system timeouts, and application crashes.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run extensive data profiling routines during the discover phase to mathematically isolate circular references, orphan nodes, and conflicting structure indicators. Recommendation 2. What successful projects do? Reliability: elite projects force plant managers to align on a single, global structure indicator matrix before the first data extraction takes place. Recommendation 3. What should be validated? Revalidation: physically validate the cleansed hierarchy by testing deep cost roll-up scenarios within standard Fiori analytical dashboards in the sandbox environment. Recommendation 4. What should be governed? Responsibility: implement strict, centralized master data governance (MDG) protocols to prevent local plant users from creating non-compliant functional locations post-go live.
Migration Incident 10. Inactive technical objects not identified for archiving.
During the discover phase of an SAP ECC to SAP S/4HANA migration, assessment teams frequently fail to profile the system for obsolete or dismantled technical objects. Over decades, organizations accumulate hundreds of thousands of equipment records and functional locations that have been physically decommissioned but never purged from the database. Ignoring this inactive master data inflates the target HANA memory footprint, degrades Fiori search performance, and extends conversion runtimes during the system downtime window.
Incident classification and relevant SAP note if applicable.
1. Complexity: medium data volume management assessment failure. 2. Migration phase discover. 3. Frequency: very common in older ECC landscapes. 4. Primary ownership: data migration lead. 5. Supporting PM functional lead basis architect. 6. Business ownership: maintenance operations manager. 7. Relevant SAP note. SAP note 2234978 data volume management and archiving.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How unarchived technical objects typically reveal themselves during the program lifecycle. 1. Symptom: search applications and value helps may become cluttered with obsolete technical objects if archiving and retention strategies are not implemented. 2. Red flag: master data reports reveal a massive ratio of equipment records carrying inactive or deletion flag system statuses. 3. Business impact: infrastructure budgets are forced upwards to accommodate the unnecessary in-memory hosting of dead master data. 4. Detection: early data volume management DVM assessments flag tables EQUI and IFLOT as top contributors to overall database growth. 5. Technical proof: historical usage analysis reveals a significant percentage of technical objects have not participated in maintenance activity for several years. Insight: migrating dismantled assets into an expensive in-memory database is a massive waste of infrastructure budget.
Investigation tools and transactions used.
Use these tools and transactions to identify inactive master data and archiving candidates. 1. TAANA or DB15 table analysis and archiving space. Profile the exact row counts and storage footprints of master data tables prior to sizing. 2. SARA archive administration. Evaluate the configuration and historical execution logs of standard SAP archiving objects. 3. IL03 or IE03 display technical objects. Verify system statuses and dependent measuring points on individual obsolete records. 4. IH08 or IH06 equipment and location list edits. Mass scan technical objects filtered by inactive statuses to quantify the potential archiving scope. Architect's rule: profiling tables with TAANA provides the irrefutable mathematical proof needed to convince the business to archive.
Incident analysis and root cause why this happens.
1. The business operates under a keep everything mentality, fearing the loss of historical maintenance traceability for audit purposes. 2. Functional teams underestimate the complexity of archiving master data, which requires clearing all dependent transactional orders first. 3. Project scope is restricted strictly to technical conversion, deliberately excluding data cleanup to artificially compress the project timeline. 4. Assessment teams fail to run standard SAP data volume management DVM reports during the discover phase. The root cause: is a lack of executive data governance, forcing the business to release obsolete records.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes highly visible during S/4HANA migration because organizations shift from cheap disk storage to premium in-memory computing. 2. S/4HANA's real-time CDS view architecture constantly aggregates master data relationships in memory, slowing down when processing massive volumes of dead records. 3. Search applications and value helps may become cluttered with obsolete technical objects if archiving and retention strategies are not implemented. 4. In legacy ECC systems, inactive master data quietly rested on disk storage without materially impacting daily system performance or licensing costs. HANA memory optimization requires treating legacy master data as a curated asset, not a dumping ground.
Business and program impact.
1. Target cloud hardware sizing budgets escalate significantly to host millions of records that provide zero operational value. 2. Conversion runtimes during mock cutovers stretch beyond the acceptable business downtime window due to unnecessary table processing. 3. User adoption suffers post-go-live as field technicians struggle to locate active equipment amidst thousands of dismantled asset records. 4. Data migration leads are forced to scramble and design emergency archiving rules late in the prepare phase, increasing project risk. Migrating dead data directly cannibalizes the return on investment of your S/4HANA hardware.
Strategic decision. Technical object archiving strategy.
Answer: addressing massive volumes of inactive technical objects requires a firm governance decision, balancing project timelines against long-term hardware costs. We must evaluate these 4 options. 1. Pre-migration ECC archiving. Execute an aggressive data archiving project in the legacy system to physically delete and archive obsolete assets before S/4HANA sizing is finalized. 2. Post-migration ILM or cold storage. Migrate all data into S/4HANA and implement SAP Information Lifecycle Management ILM to systematically move obsolete master data to cold storage tiers. 3. Selective archiving strategy. Archive obsolete assets above agreed age and inactivity thresholds while retaining legally required historical technical objects. 4. Retain and scale up hardware. Accept the technical debt, migrate all data as is, and absorb the inflated HANA memory and cloud hosting costs indefinitely. Pro tip: do not defer archiving to the post-migration run phase. Business urgency for cleanup evaporates the moment the system goes live.
Archiving decision matrix.
A standard analytical matrix to determine the correct technical or business archiving action based on master data findings. 1. Inactive greater than 10 years plus no regulatory requirement. Archive the historical technical objects in ECC pre-conversion using standard archiving. 2. Inactive greater than 10 years plus regulatory requirement. Implement standard SAP ILM to enforce legally compliant destruction-free retention locks. 3. Inactive less than 5 years plus possible reuse. Retain the records in memory to support potential near-term operational reactivation. 4. Active maintenance history exists. Evaluate the complete transaction dependency chain open orders, notifications before attempting to archive. Architect's rule: prune and archive legacy technical objects before finalizing cloud hardware contract commitments.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Data migration lead, the person who owns the master data landscape footprint and gets fired if the sandbox database conversion timeframe blows out. 2. Responsible. PM functional lead negotiates data retention and deletion rules with plant stakeholders. 3. Consulted. Basis architect, enterprise solution architect. 4. Informed. Program sponsor, steering committee, business process owners. Steering committees must empower the data migration lead to enforce strict data retention policies against business resistance.
Ownership, who actually fixes it.
Resolving data volume bloat requires structured analysis and programmatic archiving execution. 1. Data migration lead executes table profiling and formally identifies the volume of inactive records eligible for archiving. 2. PM Functional Lead validates that the target equipment records have no open financial or logistical dependencies blocking their deletion. 3. Basis Architect configures the archiving storage paths, sets up archive administration, and schedules the background deletion jobs. 4. Maintenance Operations Manager formally signs off on the list of obsolete assets to be permanently purged.
Who gets blamed versus who owns it?
1. Blamed. Basis team accused of incorrectly sizing the target hardware or failing to optimize the conversion runtime. 2. Blamed. Business process owners accused of being unreasonable and refusing to part with useless historical data. 3. Actual owner. Data migration lead, accountable for assessing legacy data quality and enforcing mandatory cleansing cycles. 4. Root cause. Failure to position data volume management as a mandatory prerequisite to S/4HANA sizing and conversion. Do not blame the infrastructure team for hardware costs when the core issue is missing master data governance.
How this is actually fixed the right way by a role.
1. Data migration lead executes legacy transaction TAANA to profile table EQUI and identifies all records with DLFL or INAC statuses. 2. PM Functional Lead systematically executes archiving prerequisites, clearing open maintenance plans and measuring points tied to the inactive assets. 3. Basis Architect configures the relevant SAP archiving objects for equipment and functional locations in transaction SARA and routes the output to secure external storage. 4. Enterprise Solution Architect recalculates the S/4HANA target sizing report to secure the newly optimized hardware footprint. Archiving technical objects requires clearing all dependent transactional history first. It must be orchestrated carefully.
Common mistakes to avoid what not to do.
1. Do not attempt to archive a technical object without first archiving all of its historical maintenance orders and notifications. 2. Do not allow the business to indefinitely delay archiving decisions by promising to clean up the data after go live. 3. Do not delete technical objects using custom Z programs or direct table deletions. Always utilize standard SAP archiving objects. 4. Do not finalize your target cloud infrastructure contract before the archiving assessment has been formally reviewed.
Follow-up 1. Why is archiving technical objects harder than archiving transactional data?
Answer. Archiving technical objects requires archiving all dependent transactional data first. You cannot archive an equipment record if there are open maintenance orders, active measuring points, or unarchived historical notifications linked to it. This strict top-down dependency chain means archiving master data is a complex, multi-step project. It must begin months before the target conversion date to ensure all underlying logistics and financial dependencies are successfully cleared.
Follow-up 2. What system statuses indicate a technical object is ready for archiving?
Answer. To be eligible for standard archiving, a technical object must have the system status INAC inactive or DLFL deletion flag set. Additionally, the standard SAP archiving engine checks internal residence times and ensures no active logistical or financial dependencies exist. Organizations must systematically mass update these statuses using standard list edits or custom background jobs before initiating the actual archiving run via transaction SARA.
Follow-up 3 Curveball. How do you convince the business to archive equipment records when regulatory auditors require historical maintenance traceability?
Answer. To convince the business, the architect must demonstrate that archiving does not equal data destruction. Standard SAP archiving moves historical records from the active database into compressed archive files while preserving audit accessibility. These archived records remain searchable through standard SAP archive access mechanisms and transactions such as SARA and DB15. Furthermore, implementing SAP ILM allows the organization to enforce legally compliant destruction-free retention locks, satisfying audit requirements while permanently reducing the active database footprint. Presenting this clear distinction between active database cleanup and historical trace preservation is the key to overcoming operational resistance.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization. Run rigorous table profiling using TAANA early in the discover phase to mathematically quantify the exact volume of inactive technical objects. Recommendation 2. What successful projects do? Reliability. Execute a full end-to-end archiving simulation run in a recent production copy to validate retention policies and measure the exact impact on the target database footprint. Recommendation 3. What should be validated? Revalidation. Formally validate legal, audit, and maintenance history retention requirements with the compliance team before permanently purging technical objects. Recommendation 4. What should be governed? Responsibility. Implement centralized master data governance (MDG) protocols to ensure that dismantled assets are routinely flagged for deletion post-go live, preventing future database bloat.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, You can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 11. PM-specific batch jobs undocumented.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams often focus entirely on online dialogue transactions and Fiori apps, completely ignoring the landscape of scheduled background jobs. In plant maintenance, automated batch jobs run critical daily operations such as preventive maintenance deadline monitoring, mass order settlements, and custom material reservation interfaces. Failing to inventory, document, and remediate these undocumented batch jobs leads to silent, catastrophic failures post-go-live, where expected work orders simply fail to generate.
Incident classification and relevant SAP, note if applicable.
1. Complexity, medium operational readiness failure. 2. Migration phase, discover. 3. Frequency, very common in decentralized landscapes. 4. Primary ownership, PM functional lead. 5. Supporting, basis lead, lead ABAP developer, cutover manager. 6. Business ownership, maintenance planning lead. 7. Relevant SAP note, not applicable, operational assessment gap.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How missing operational batch jobs typically reveal themselves during the program lifecycle. 1. Symptom. Preventive maintenance plans stop generating new work orders automatically during sandbox integration testing. 2. Red flag. Finding hundreds of active background jobs in the legacy system scheduled under the user IDs of departed employees. 3. Business impact. Technicians arrive for their shifts without assigned preventive maintenance tasks, causing massive shop floor idle time. 4. Detection. Cutover simulation testing reveals that nightly maintenance plan scheduling runs were completely omitted from the converted system. 5. Technical proof. System dump logs show legacy custom Z programs executed in the background failing due to deprecated tables in the S/4HANA data model.
Investigation tools and transactions used.
Use these tools and transactions to identify undocumented background processes and batch schedules. 1. SM37 Background Job Overview. Audit the active and historical execution logs of all background jobs running in the legacy ECC production environment. 2. SM36 Define Background Job. Review the exact ABAP programs, dynamic variants, and user authorizations assigned to the scheduled PM jobs. 3. ST22 ABAP Runtime Errors. Trace short dumps triggered by legacy custom background programs failing against the S/4HANA database constraints. 4. Fiori Application Jobs App. Review application jobs that have been redesigned or exposed through modern S/4HANA application job frameworks. Architect's rule. Never assume a background job will successfully migrate just because the underlying ABAP program passed a syntax check.
Incident analysis and root cause why this happens.
1. Local plant users create dynamic background jobs independently over decades without logging them in a central IT interface registry. 2. Migration assessments focus entirely on user-facing transactions, assuming that background processing requires zero redesign. 3. Legacy custom programs scheduled in the background bypass standard ABAP test cockpit ATC scoping rules. 4. The program team fails to assign business ownership to background jobs, assuming they are purely technical operations managed by basis. The root cause is treating background jobs as invisible infrastructure rather than critical business processes.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes highly visible during migration because S/4HANA modernizes the data model, causing legacy custom background jobs to dump instantly. 2. Standard ECC performance optimizations used in custom batch programs are rendered obsolete by HANA's in-memory computing architecture. 3. S/4HANA introduces advanced application job tools, making the migration a strategic opportunity to evaluate and simplify operational background processing. 4. During technical downtime, background jobs must be systematically suspended and resumed. Untracked jobs may fail, generate unexpected processing results, or interfere with cutover activities. S/4HANA's strict database constraints break legacy batch logic that relied on direct, unoptimized table reads.
Business and program impact.
1. Cutover weekends are severely disrupted if unidentified background jobs activate unexpectedly and lock critical transaction tables. 2. Post-go-live maintenance compliance plummets as mandatory safety and calibration work orders are not generated by the system. 3. Planners are forced into reactive, manual administration, individually running scheduling transactions to compensate for broken automations. 4. Integration pathways fail silently as scheduled outbound data extractions to third-party scheduling boards never execute. A missed background job results in a silent failure. The business only realizes it when the work stops flowing.
Impact on technicians and maintenance teams.
How undocumented batch failures disrupt the physical maintenance workflow on the shop floor. 1. Technicians arrive for morning shifts to find their mobile devices or assignment boards completely empty because nightly scheduling jobs failed. 2. Routine preventive tasks are missed, directly increasing the likelihood of unscheduled breakdowns and hazardous equipment failures in the field. 3. Supervisors spend hours manually generating and dispatching work orders, delaying wrench time and reducing overall shift productivity. 4. Critical spare parts are not staged at the work center because automated material availability checks failed to run overnight. Automated background jobs are the invisible engine of plant floor productivity. When they stop, the technicians stop.
Governance and accountability. Ray C. model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. PM functional lead, the person who owns the maintenance business process and gets fired if skipped background jobs result in missed maintenance compliance post-go live. 2. Responsible. Basis lead extracts the technical system background job inventory. 3. Consulted. Lead ABAP developer cutover manager. 4. Informed. Program sponsor, steering committee, maintenance planning lead. Steering committees must enforce a strict policy. If a batch job lacks a documented business owner, it does not migrate.
Ownership. Who actually fixes it?
Resolving missing operational jobs requires a structured inventory and programmatic redesign. 1. PM functional lead evaluates the inventory of legacy background jobs and determines their active business necessity and process relevance. 2. Basis lead extracts the technical background job list from the legacy ECC environment and schedules the approved jobs in S/4HANA. 3. Lead ABAP developer remediates the custom batch programs, ensuring CDS view compatibility and HANA optimization. 4. Cutover manager designs the suspension and resumption sequence for all active jobs during the technical downtime bridge.
Who gets blamed versus who owns it?
1. Blamed. PM functional team accused of forgetting to configure the background jobs required to generate maintenance orders. 2. Blamed. Cutover team accused of losing configurations during the transport migration to production. 3. Actual owner. PM functional lead accountable for validating the operational readiness of all automated maintenance processes. 4. Root cause. Failure to actively profile legacy system background operations and treat them as formal business process requirements. Do not blame the technical teams for undocumented automations. PM process ownership must validate every background job.
How this is actually fixed the right way by a role.
1. Basis lead executes a mass extraction of transaction SM37 history to catalog every background program, variant, and frequency schedule. 2. PM functional lead formally reviews the list, decommissioning obsolete jobs, verifying process relevance, and mapping active jobs to standard S/4HANA catalogs. 3. Lead ABAP developer refactors legacy custom Z programs scheduled in the background to comply with S/4HANA syntax and CDS database structures. 4. Cutover manager utilizes standard programs like BTCTR NS1 or BTCTR NS2 to systematically suspend and resume batch operations during cutover. Standardizing your batch jobs on the Fiori application jobs framework ensures long-term visibility and process governance.
Common mistakes to avoid what not to do.
1. Do not migrate every legacy background job without validating business necessity. 2. Do not schedule production jobs using personal user IDs. 3. Do not assume a custom batch program is HANA compatible because it compiles successfully. 4. Do not enter cutover without a documented suspension and restart plan for all critical PM jobs.
Follow-up 1. Why do PM background scheduling jobs such as IP30 or IP30H stop generating work orders after migration?
Answer: during migration, background scheduling jobs like IP30 often fail to generate work orders due to obsolete variants, custom exits, authorization mismatches, or dependencies on deprecated custom tables and fields. If a legacy background job executes using unsupported selection criteria or outdated business logic, the system may trigger a silent execution failure or a runtime short dump. Additionally, organizations frequently evaluate HANA-optimized scheduling and deadline monitoring alternatives available within their target S/4HANA release, making it essential to validate legacy variants, execution methods, and scheduling approaches. Failing to review and remediate these dependencies, or failing to update the security authorizations of the system execution user, can result in a complete operational standstill post-go-live.
Follow-up 2. How do you determine the business value of an undocumented custom background job?
Answer: determining the value of an undocumented custom job requires the functional lead to analyze the spool outputs and variants generated in transaction SM37. By reviewing the output logs, the team can identify which database tables are being updated and trace the destination of the data. Furthermore, cross-referencing the execution schedule with system usage data helps determine if any active business users are actively consuming the generated reports or interfaces. If no business owner can justify the variance output, the job must be formally decommissioned before migration.
Follow-up 3. Curveball. What is the specific danger of allowing maintenance jobs to run during the technical cutover downtime window?
Answer: allowing background jobs to run during the technical cutover downtime window is extremely dangerous because the database is in an intermediate state of conversion. If a preventive maintenance job activates while the target S/4HANA tables are being restructured, it will create incomplete processing results, job failures, or lock conflicts that can potentially crash the active SUM migration tool. To prevent this, the cutover manager must execute programs like BTCTRNS1 to systematically suspend all background processing before downtime begins, and BTCTRNS2 to resume them safely only after business validation is complete.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: run comprehensive SM37 and SM36 audits during the discover phase to inventory every active background job running in the production environment. Recommendation 2. What successful projects do? Reliability elite projects. Review all legacy batch schedules and migrate suitable jobs to modern application job frameworks while retaining supported standard scheduling mechanisms where appropriate. Recommendation 3. What should be validated? Revalidation. Physically validate the execution of critical nightly batch runs like deadline monitoring during the mock cutover to ensure work orders generate correctly. Recommendation 4. What should be governed? Responsibility. Enforce a strict governance policy requiring a named business process owner and a valid functional justification for every background job migrated to the new system.
Migration Incident 12. Fiori impact not communicated to business users.
During the discover phase of an SAP ECC to SAP S/4HANA transformation, project teams often fail to communicate the massive impact of the SAP Fiori user experience to business users. Maintenance planners, supervisors, and technicians typically assume that standard SAP GUI transactions such as IW31, IL21, or IW38 will remain completely unchanged post-conversion. When the system is converted without a proactive organizational change management strategy, Users are suddenly forced onto a completely new web-based interface without prior training, leading to massive operational shock and an immediate collapse in system adoption.
Incident classification and relevant SOP, note if applicable.
1. Complexity. High change management and readiness failure. 2. Migration phase, discover. 3. Frequency, very common in older ECC landscapes. 4. Primary ownership, PM functional lead. 5. Supporting, change management lead, basis architect, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SOP note, not applicable, Fiori adoption and change management failure.
How teams identify this issue, diagnostic dashboard, symptoms and evidence.
How uncommunicated user interface changes typically reveal themselves during the program lifecycle. 1. Symptom. Planners and supervisors experience immediate confusion and operational slowdowns, complaining that they cannot find their standard work order screens. 2. Red flag. Project change management plans focus entirely on basic system training while completely omitting custom Fiori Launchpad role mappings. 3. Business impact. Maintenance teams revert to paper-based tracking sheets or offline spreadsheets, bypassing the new S/4HANA system entirely. 4. Detection. Business readiness assessments and early user surveys reveal that over 80% of plant floor workers have never seen a Fiori screen. 5. Technical proof. Fiori Launchpad usage logs reveal extremely low adoption rates for standard maintenance planning applications despite successful technical deployment.
Investigation tools and transactions used.
Use these tools to assess user readiness, role mappings, and Fiori adoption risks. 1. SU01 or PFCG. Review legacy and target user roles and authorization assignments. 2. Fiori Launchpad Content Manager. Validate role to app mappings and catalog assignments. 3. Cint03N. Analyze legacy transaction usage patterns to identify high-impact user groups. 4. SOP Readiness Check. Review Fiori recommendation outputs and UX-related simplification opportunities. Architect's Rule. Use SD03N transaction data to identify which legacy transactions are actually being used by your planners.
Incident analysis and root cause why this happens.
1. Project steering committees treat the S/4HANA transition as a purely technical database upgrade rather than a business-facing transformation. 2. The change management team operates in a silo, designing training materials without validating the actual daily workflows of the plant floor workers. 3. Legacy functional planners assume that keeping legacy SAP GUI shortcuts active indefinitely is a viable long-term support strategy. 4. The program fails to run a comprehensive role-to-app mapping assessment during the early discover phase of the project. The root cause is treating the user experience as a minor training task rather than a critical business process re-engineering stream.
Why this issue appears only during an ECC to S/4HANA migration.
1. The failure becomes highly visible during S/4HANA migration because organizations introduce Fiori as a new user experience layer, requiring users to adapt to role-based navigation, launchpads, and app-centric processes. 2. Under normal ECC operations, users have utilized the identical, stable SAP GUI interface for decades without needing any UX training. 3. The technical conversion forces a coexistence of legacy GUI and modern Fiori screens, exposing critical process and adoption gaps. 4. Legacy SAP systems did not feature the granular, role-based application catalog structure defined by the modern Fiori Launchpad. S/4HANA's modernized business processes require a matching modernization of the user interface.
Business and program impact.
1. Maintenance planning and scheduling efficiency can decline significantly during the initial post-go-live period. 2. Wrench time drops as technicians spend hours trying to navigate unfamiliar web-based app catalogs rather than performing active asset repairs. 3. Business trust in the new ERP platform collapses, leading to widespread user resistance and a high volume of emergency support tickets. 4. Long-term post-go-live optimization budgets are consumed by emergency change management and retraining campaigns. Ignoring user experience changes during discover, guarantees operational performance drops during hypercare.
Impact on technicians and maintenance teams.
How a failed user adoption strategy directly disrupts the daily operations of field crews and planners. 1. Technicians struggle to log daily time confirmations or search for spare parts because they are unfamiliar with the new Fiori navigation model and application catalog structure. 2. Planners are unable to release urgent breakdown orders because they cannot find the standard IW32 equivalent inside their unconfigured Fiori Launchpad catalogs. 3. Field crews revert to writing maintenance logs on paper, creating a massive data back-entry backlog that corrupts the integrity of asset history. 4. Plant floor supervisors lose real-time visibility into active work backlogs, leading to uncoordinated shift handovers and increased safety risks. Forcing field technicians back to paper-based tracking destroys the user adoption of your new S/4HANA system.
Governance and accountability, RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. PM functional lead, the person who owns the maintenance business process and gets fired if untrained business users reject Fiori, freeze order confirmations, and break plan operations. 2. Responsible. Change management lead executes training, communications, and user readiness audits. 3. Consulted. Basis architect. Maintenance operations manager. 4. Informed. Program sponsor, steering committee, business process owners. Steering committees must establish clear OCM ownership before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving user adoption and readiness gaps requires coordinated business, functional, and technical ownership. 1. PM functional lead maps legacy PMGUI transactions to standard S/4HANA Fiori applications. 2. Change management lead designs plant-specific training curricula and coordinates hand-holding sessions with local supervisors. 3. Fiori security engineer configures secure role-based Launchpad catalogs to ensure users see only relevant apps. 4. Basis architect configures the secure Fiori front-end gateway and troubleshoots active connection latency.
Who gets blamed versus who owns it.
1. Blamed. Basis team, accused of building a slow, broken, or completely inaccessible Fiori front-end portal. 2. Actual owner. PM functional lead, accountable for validating the business readiness of all automated maintenance user experiences. 3. Root cause. Failure to position Fiori user experience as a critical organizational change management stream during the early discover phase. Successful Fiori adoption is a business transformation responsibility, not a technical deployment activity.
How this is actually fixed the right way by a role.
1. PM functional lead maps every legacy PMGUI transaction code to its corresponding S/4HANA standard Fiori app. 2. Change management lead executes a plant-by-plant user adoption audit to measure baseline computer literacy and Fiori readiness. 3. Fiori security engineer configures standard Fiori Launchpad catalogs, groups, and roles to streamline user access profiles. 4. Basis architect validates gateway OData services and optimizes active network protocols to ensure crisp, sub-second screen rendering. Early role mapping, targeted training, and controlled Fiori adoption are the keys to long-term user acceptance.
Common mistakes to avoid what not to do.
1. Do not roll out the S/4HANA system without executing a dedicated, plant-specific organizational change management campaign. 2. Do not allow business users to retain unremediate legacy SAP GUI transactions as a workaround to avoid Fiori training. 3. Do not deploy uncustomized Fiori launchpads containing hundreds of irrelevant tiles, as this causes immediate user fatigue. 4. Do not delay Fiori security role mapping and catalog testing until the final cutover phase of the project.
Follow-up 1. Why is an exhaustive role-to-app mapping assessment critical during the discover phase?
Answer: a role-to-app mapping assessment is a critical discover best practice that aligns legacy job profiles with S/4HANA's target user experience. In ECC, maintenance planners, supervisors, and technicians utilized wide-ranging, unoptimized standard transactions that allowed arbitrary screen navigation. In S/4HANA, the Fiori Launchpad delivers a highly curated, role-specific app catalog designed to streamline daily tasks. Performing this mapping assessment early ensures that security leads can configure data-driven, decluttered catalogs containing only the exact apps a user needs, preventing role bloat and system adoption failures during go-live.
Follow-up 2. What is the risk of allowing business users to permanently bypass Fiori using legacy SAP GUI transactions in S/4HANA?
Answer: allowing users to bypass Fiori and remain on legacy SAP GUI represents a critical program risk that directly sabotages the business case of the migration. Many S/4HANA innovations are optimized for Fiori and deliver their best user experience through role-based applications. Operating on legacy GUI means the organization continues to run S/4HANA as a slightly faster version of ECC, completely missing out on real-time decision-making capabilities. Furthermore, many SAP innovations and user experience investments are focused on Fiori-based applications rather than expanding legacy GUI capabilities, increasing long-term supportability and custom enhancement costs.
Follow-up 3 Curveball. How do you handle Fiori adoption when migrating a highly remote plant with poor, low-bandwidth network connectivity?
Answer: for remote plant locations with poor network bandwidth, the architect must design a highly optimized, low-footprint user experience. Rather than deploying complex, graphics-heavy Fiori analytical apps, we should configure streamlined transactional apps and enforce strict browser caching policies. Additionally, we must leverage SAP Service and Asset Manager on secure mobile devices, which is built for completely offline operations, allowing technicians to sync data locally over Wi-Fi when back at the base. This hybrid architectural model ensures that field operations continue seamlessly without saturating the plant's limited satellite or cellular network bandwidth.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete, standard role-to-app mapping assessment during Discover to align legacy job descriptions with S/4HANA standard Fiori catalogs. Recommendation 2. What successful projects do? Reliability elite projects conduct hands-on Fiori pilot sessions with planners, supervisors, and technicians months before go-live to validate role mappings and build user confidence. Recommendation 3. What should be validated? Revalidation: physically validate Fiori launchpad responsiveness and rendering times in a sandbox environment over simulated low-bandwidth plant network connections during UAT. Recommendation 4. What should be governed? Responsibility: require the program director and the change management lead to formally sign off on the user readiness metrics of each plant before entering the deploy phase.
Migration Incident 13. Heavy Z table dependency for maintenance analytics discovered late.
During the Discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently fail to identify custom analytics architectures that are heavily dependent on custom database tables, commonly known as Z tables. Legacy organizations often build complex, custom reporting suites that read from custom tables populated by background jobs or custom user exits to track key maintenance performance metrics. Failing to identify these Z table dependencies during early scoping leads to a complete breakdown of maintenance reporting, executive dashboards, and operational KPI calculations when entering the sandbox testing phase.
Incident classification and relevant SAP note if applicable.
1. Complexity: high custom analytics architecture assessment failure. 2. Migration phase Discover. 3. Frequency common in legacy ECC landscapes. 4. Primary ownership enterprise solution architect. 5. Supporting lead ABAP developer PM functional lead analytics lead. 6. Business ownership maintenance operations manager. 7. Relevant SAP note not applicable custom analytics architecture assessment gap.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How unrecognized legacy custom analytics tables typically reveal themselves during the program lifecycle. 1. Symptom: legacy maintenance KPI dashboards and custom analytics reports are completely blank or crash with database error logs after sandbox conversion. 2. Red flag: Finding legacy custom database tables prefixed with Z or Y that store hundreds of thousands of historical maintenance records without any active data dictionary documentation. 3. Business impact. Maintenance leaders lose real-time visibility into plant floor performance, cost tracking, and technician resource utilization. 4. Detection. ABAP Test Cockpit ATC identifies incompatible syntax, direct database access, obsolete enhancement techniques, and HANA optimization issues. 5. Technical proof. Database lineage analysis reveals custom Z tables populated by background jobs, user exits, or custom enhancement logic reading legacy (ECC) tables that are simplified in S/4HANA.
Investigation tools and transactions used.
Use these tools and transactions to identify custom database tables and analytics report dependencies. 1. SE16N Table Browser. Analyze the structure and data volume of custom Z tables containing historical maintenance analytics records. 2. SD03N Workload and Performance Analysis. Identify which custom database tables are actively being read or updated by legacy reporting transactions. 3. ATC ABAP Test Cockpit. Identify custom code objects, SQL statements, and obsolete database access patterns impacted by S/4HANA simplification items. 4. SAP Readiness Check. Audit custom code recommendations to identify custom database tables that are impacted by S/4HANA simplified data models.
Incident analysis and root cause why this happens.
1. Legacy organizations built custom reporting databases over decades because traditional ECC/PM reports such as MCIP or MCJB lacked performance and flexibility. 2. Assessment teams focus entirely on standard SAP database structures, completely overlooking custom tables that are updated silently by background jobs. 3. Technical architects perform simple custom code counts, neglecting to run semantic code scans that evaluate database access paths and table dependencies. 4. Business analysts assume standard S/4HANA CDS views will natively replace legacy custom reporting structures without requiring a functional redesign. The root cause is treating custom reporting as a standard functional setup rather than an active custom database extension.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migrations because S/4HANA promotes virtual data models and embedded analytics, reducing the need for custom replicated reporting tables maintained through background synchronization jobs. 2. S/4HANA replaces legacy aggregate tables with standard CDS views that aggregate data on the fly using real-time database calculations. 3. Many legacy ECC analytics rely on custom database update techniques and background synchronization jobs that require redesign or remediation under S/4HANA's modernized extensibility framework. 4. Under normal ECC operations, legacy background sync jobs run without disruption, hiding the architectural debt until the database is converted. S/4HANA's modern virtual data models are incompatible with unremediate legacy database tables.
Business and program impact.
1. The transformation program faces unbudgeted remediation effort to redesign custom reports, CDS views, and executive dashboards during Realize. 2. Maintenance directors lose real-time visibility into active operational metrics, delaying strategic decision-making and backlog tracking. 3. Critical maintenance KPIs become unavailable during testing cycles, delaying business sign-off and increasing UAT defect volumes. 4. Business confidence in the new system declines during user acceptance testing, as standard dashboards return blank or incomplete values. A broken analytics interface directly results in delayed reporting and unoptimized operational scheduling.
Strategic decision. Analytics modernization strategy.
Answer: once heavy Z table dependencies are identified, the program must determine the future reporting architecture before entering Realize. We must evaluate these 4 options. 1. Retain and remediate. Keep the Z table architecture and modify the custom code for S/4HANA compatibility. 2. CDS view replacement recommended. Replace custom reporting tables with standard CDS views and embedded analytics wherever possible. 3. Hybrid reporting model. Retain only business-critical Z table logic while migrating the majority of reports to standard analytics. 4. External analytics platform. Rebuild reporting using SAP Analytics Cloud, Datasphere, or an enterprise BI platform. Architect's rule. Every retained Z table becomes future technical debt that must be justified by measurable business value.
Governance and accountability, RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target analytics architecture and gets fired if critical reporting capabilities fail during business validation. 2. Responsible. Lead ABAP developer executes system scans and performs code correction. 3. Consulted. PM functional lead, analytics lead, basis architect. 4. Informed. Program sponsor, steering committee, business process owners. Steering committees must establish clear data modeling guidelines before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving custom analytics dependencies requires coordinated functional, technical, and reporting architecture remediation. 1. Lead ABAP developer audits legacy PM custom tables and identifies candidates for standard CDS view replacement. 2. PM functional lead maps the custom business KPI requirements to standard S/4HANA analytical applications. 3. Enterprise solution architect designs the target S/4HANA analytics architecture, utilizing SAP Analytics Cloud or standard embedded CDS views. 4. Basis architect ensures the target reporting platforms, connectivity components, and transport landscape are properly configured and available.
Who gets blamed versus who owns it.
1. Blamed. BI development team accused of failing to configure the target reporting dashboards or standard analytics apps correctly. 2. Actual owner. Enterprise solution architect, accountable for identifying legacy custom database dependencies and Z table architectures early. 3. Root cause. Failure to perform a comprehensive custom database and reporting assessment during the discover phase of the project. Do not blame the reporting teams when the underlying custom analytics architecture was never assessed during discover.
How this is actually fixed the right way by a role.
1. Lead ABAP developer executes standard custom code and database scanners to locate every PM transaction code reading from custom Z tables. 2. PM functional lead reviews legacy KPI reports, identifying redundant fields and mapping active metrics to standard S/4HANA fields. 3. Enterprise solution architect designs standard virtual data models, replacing custom Z tables with real-time, standard S/4HANA CDS views. 4. Senior ABAP developer refactors legacy reporting code, configuring modern CDS view extensions to deliver optimized, real-time maintenance reporting. Replacing custom Z tables with modern CDS views is the only way to protect your reporting during future upgrades.
Common mistakes to avoid what not to do.
1. Do not attempt to migrate custom Z tables to S/4HANA as a simple storage lift and shift without evaluating modern CDS view alternatives. 2. Do not delay the audit of legacy custom reporting architectures until after the sandbox conversion is completed. 3. Do not allow development teams to write complex custom extraction programs that bypass standard S/4HANA virtual data models. 4. Do not assume that standard S/4HANA embedded analytics will natively replicate highly specific, custom legacy calculations without a functional redesign.
Follow-up 1. Why did legacy ECC plant maintenance systems rely so heavily on custom Z tables for analytics?
Answer. Legacy ECC systems relied on traditional disk-based databases that were optimized for transactional processing rather than analytical reporting. Running complex queries on standard tables like a fee or auth directly would lock the database, severely degrading online transaction performance in high-volume plants. To prevent this, developers created custom Z tables that were populated nightly by background jobs, allowing planners to run reports without locking active transactions. In S/4HANA's in-memory architecture, this redundant data replication layer is obsolete because Standard CDS views aggregate data on the fly without performance penalties.
Follow-up 2. How do you identify hidden Z table dependencies in legacy custom reports during the discover phase?
Answer: identifying these hidden dependencies requires the lead developer to execute a semantic database analysis of all legacy custom ABAP code. The developer can use ATC analysis, where used lists, SQL trace utilities, and custom code scans to locate ABAP programs referencing Z table namespaces. Additionally, auditing transaction SD03N allows the architect to identify which custom database tables are actively being read by custom PM transactions. This data-driven profiling ensures that the team catalogs every active custom data model, preventing reporting failures during sandbox testing.
Follow-up 3 Curveball. Why is migrating a legacy custom data extraction job to SAP Analytics Cloud particularly prone to failing after a S/4HANA conversion?
Answer: legacy extraction jobs frequently fail because they rely on direct database reads of legacy logistics tables that are simplified or deprecated in S/4HANA. During conversion, standard tables are replaced by dynamic CDS views, meaning the physical database fields referenced by the legacy extractor no longer contain active data. When the extractor executes, it returns blank files or generates system connection errors, breaking downstream business intelligence dashboards. To secure the integration, architects must refactor the extractor to consume standard S/4HANA compliant OData services rather than legacy database paths.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete, standard custom database and ABAP test cockpit ATC audit during the discover phase to catalog every active Z table, custom index, and background data synchronization job in use. Recommendation 2. What successful projects do? Reliability elite projects establish a combined PM and analytics team during the prepare phase, bringing together PM consultants and business intelligence architects to design modern CDS views. Recommendation 3. What should be validated? Revalidation: validate the performance and data accuracy of the target virtual data models by executing high-volume query stress tests in a sandbox environment during UAT. Recommendation 4. What should be governed? Responsibility: require formal architectural approval and sign off on the target analytics design from both the plant maintenance director and the custom code lead before starting build activities.
Migration incident 14. Unsupported PM add-ons identified late.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams often fail to inventory and validate the compatibility of legacy third-party plant maintenance add-ons. Older ECC landscapes frequently host industry-specific add-ons installed directly on the ABAP stack. If these add-ons are not certified by the vendor for S/4HANA or do not have an active deinstallation pathway, identifying this gap only after project kickoff creates a critical blocker, preventing the generation of the mandatory stack XML file and halting the conversion.
Incident classification and relevant SAP note if applicable.
1. Complexity: high critical software component block. 2. Migration phase discover. 3. Frequency common in older landscapes. 4. Primary ownership enterprise solution architect. 5. Supporting basis lead PM functional lead ABAP developer. 6. Business ownership program sponsor. 7. Relevant SAP note. SAP Note 2214409 SAP S/4HANA. Compatible add-ons.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How uninventoried third-party add-ons typically reveal themselves during the program lifecycle. 1. Symptom: the maintenance planner utility fails to generate the mandatory stack XML file, returning a critical blocking error stating that an active add-on has no valid upgrade path. 2. Red flag: finding third-party software components such as prefixes like /VES/ or /PROM/ in the system status list that do not appear in the standard S/4HANA compatibility catalog. 3. Business impact: the entire conversion project is forced into an unbudgeted pause immediately after kickoff, delaying the sandbox build. 4. Detection. Standard readiness check and maintenance planner scans flag incompatible third-party software components active on the legacy ABAP stack. 5. Technical proof. The Software Update Manager SUM logs or maintenance planner error outputs show block codes for specific third-party namespaces during metadata verification.
Investigation tools and transactions used.
Use these tools to identify active software components, release levels, and add-on compatibility status. 1. SAINT Add-on Installation Tool. Audit all installed third-party software components, release levels, and active namespaces on the legacy ABAP stack. 2. SPAM Support Package Manager. Verify support package levels and check for any unresolved imports or uncommitted add-on patches. 3. Maintenance Planner. Scan the legacy system's active component registry and attempt to generate the target stack XML file to identify blocking software. 4. /SDF/S4H_add-on_check S4HANA add-on compatibility check. Run the specialized SAP report to programmatically verify which active add-ons are formally certified for the target release. Architect's rule. Do not trust a vendor's verbal claim that their add-on is S4HANA compliant. Always verify it using /SDF/S4H_add-on_check.
Incident analysis and root cause why this happens.
1. Project managers assume all third-party add-ons installed on ECC will natively run on S4HANA or can be bypassed during the technical conversion. 2. Silos between the basis team and PM functional leads prevent third-party components from being formally cross-referenced against the S4HANA compatibility list. 3. Legacy add-on vendors have gone out of business or stopped supporting standard SAP integration upgrades, leaving the code orphaned on the stack. 4. The program team fails to execute standard software component scans during the early project preparation stages. The root cause is treating add-on compatibility as a minor upgrade step rather than a critical project milestone.
Why this issue appears only during an ECC to S4HANA migration.
1. The failure is unique to S4HANA migrations because S4HANA enforces a strict, standard architectural block via Maintenance Planner and Software Update Manager. 2. During many traditional ECC upgrade projects, organizations often encountered fewer compatibility enforcement checks and therefore deferred remediation of certain third-party components until later project phases. 3. S4HANA conversion readiness checks identify unsupported software components and can block conversion activities until compatibility issues are resolved through upgrade, replacement, or deinstallation strategies. 4. The database layer optimizations and streamlined data models in S4HANA strictly prevent legacy, unremediate add-ons from executing. S4HANA conversion readiness is governed by software component compatibility long before business testing ever begins.
Business and program impact.
1. The program faces severe delays immediately after kickoff, pushing out sandbox conversions by weeks or months. 2. Unbudgeted software licensing and consulting fees are incurred to purchase S4HANA certified add-on upgrades. 3. High risk of losing specialized plant floor functionalities if an unsupported add-on must be deinstalled without a functional replacement. 4. Decline in program momentum as the technical team scrambles to resolve metadata errors instead of executing build activities. An incompatible add-on represents a complete system blockage. It is the ultimate progress stopper.
Add-on criticality assessment matrix.
A standard framework used to determine the remediation path for unsupported third-party PM add-ons. 1. Business Critical Plus certified upgrade available. Upgrade to the supported S4HANA version. 2. Business Critical Plus no upgrade available. Rebuild functionality on SAP BTP or alternative architecture. 3. Business Critical Plus vendor end of life. Begin replacement architecture immediately and remove dependency from the S4HANA conversion path. 4. Low business value plus standard SAP alternative exists. Retire the add-on and migrate to standard functionality. 5. Unknown business value. Execute stakeholder workshops before committing to remediation funding. Architect's rule. Never spend millions upgrading an add-on before proving the business still needs it.
Strategic decision. Evaluating add-on compatibility options.
Answer: resolving the unsupported add-on blocker requires selecting a viable S/4HANA compliant application architecture. We must evaluate these four strategic options. 1. Upgrade to certified version. Secure the S/4HANA certified version of the third-party add-on from the vendor, accepting any upgrade and licensing fees. 2. Retire and standardize. Deinstall the incompatible add-on entirely and redesign the business processes to utilize standard S/4HANA Fiori applications. 3. Rebuild on SAP BTP. Decommission the unsupported add-on and rebuild its highly specialized PM features as side-by-side cloud extensions on SAP BTP. 4. Delay and redesign. Pause the conversion timeline to allow the vendor to complete their S/4HANA certification, or completely redesign the PM system landscape. Pro tip: if an add-on is orphaned by its vendor, use the migration as a business case to rebuild the capability on BTP.
Add-on compatibility decision matrix.
A standard analytical matrix to determine the correct add-on remediation path during the discover phase. 1. Vendor certified version exists. Purchase and apply the S/4HANA certified upgrade path before executing the conversion. 2. Legacy custom or SciClo app. Decommission the outdated agentry add-on and migrate users to cloud-native SAP Service and Asset Manager. 3. Standard PM functionality exists. Formally deinstall the legacy add-on using standard installation tools and adopt standard Fiori apps. 4. No S/4HANA certification planned. Rebuild the custom or third-party features as a side-by-side extension on SAP BTP to keep the core clean. Architect's rule: do not let uncertified software stall your migration. Utilize standard deinstallation paths to clear the stack.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect, the person who owns the target compatibility strategy and gets fired if legacy add-ons permanently block the stack XML generation. 2. Responsible, Basis Lead. 3. Consulted, PM Functional Lead, lead ABAP developer and software vendor. Collaborate to verify vendor release roadmaps and scan custom code dependencies. 4. Informed. Program sponsor, steering committee, business process owners.
Ownership, who actually fixes it.
Resolving unsupported add-ons requires coordinated software component assessment, vendor engagement, and architecture decision-making. 1. Basis Lead reviews SAINT, executes compatibility checks, and attempts to generate the stack XML. 2. PM Functional Lead coordinates with software vendors to verify S/4HANA certification roadmaps. 3. Lead ABAP developer identifies custom code dependencies on the legacy add-ons namespaces. 4. Enterprise Solution Architect evaluates whether the add-on should be upgraded, replaced with standard functionality, or rebuilt as an extension.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of failing to identify the technical blocking components before the project officially kicked off. 2. Actual owner. Enterprise Solution Architect, accountable for executing a comprehensive software component audit during the discover phase. 3. Root cause. Failure to run the standard SAP readiness check or consult the add-on compatibility matrix before signing the project SOW. Do not blame legacy developers for legacy code. Blame current architects for ignoring it during discovery.
How this is actually fixed the right way by a role.
1. Basis Lead runs the specialized report /SDF/S4H_add-on_check to identify every active legacy add-on namespace. 2. PM Functional Lead contacts the third-party software vendor to secure the official S/4HANA compatibility release statement and upgrade installation files. 3. Lead ABAP developer reviews the ABAP repository for any custom Z programs that reference legacy add-on namespaces to prevent custom code dumps. 4. Enterprise Solution Architect establishes the target migration strategy, validating whether the add-on should be upgraded, retired, or rebuilt. Every unsupported add-on must have a documented remediation strategy before the first sandbox conversion begins.
Common mistakes to avoid what not to do.
1. Do not attempt to execute a brownfield system conversion, without first generating and validating the target stack XML file. 2. Do not assume a third-party add-on is compatible with S/4HANA simply because the vendor claims their standard software is HANA-ready. 3. Do not manually delete or manipulate add-on namespace tables in the database to bypass maintenance planner blocks, as this permanently corrupts the dictionary. 4. Do not delay the audit of installed software components, SAINT, until after the project SOW has been signed and resources are mobilized.
Follow-up 1. Why is the generation of a stack XML file the ultimate gating blocker for a S/4HANA conversion?
Answer. The stack XML is a compulsory system metadata file generated exclusively by the maintenance planner that defines the exact target software component list, support packages, and database upgrade paths. The Software Update Manager SUM strictly requires this file as its core configuration blueprint during the uptime phase. If the legacy system hosts an active, incompatible third-party add-on, Maintenance Planner will refuse to generate the XML, completely blocking the technical conversion. Without a valid stack XML, standard S/4HANA conversion procedures cannot proceed through the normal SUM-driven migration path, making add-on compatibility a non-negotiable discover phase assessment task.
Follow-up 2. What is the process for formally deinstalling an unsupported add-on an ECC pre-conversion?
Answer. Formally deinstalling an unsupported add-on requires utilizing the standard SAP add-on installation tool, Transaction SAINT. The basis lead must verify if the specific add-on vendor has delivered an official deinstallation tool or package for that release. If supported, the deinstallation process removes the software component according to the vendor-supported procedure and updates the system component registry. The exact treatment of custom tables, historical data, and namespaces depends on the vendor's deinstallation package and retention strategy.
Follow-up 3 curveball. How would you handle a situation where a business-critical PM add-on is incompatible with S/4HANA and the vendor has gone out of business?
Answer. If a mission-critical add-on is completely orphaned and cannot be upgraded, the enterprise solution architect must design an immediate side-by-side transition. The team must first determine whether a supported deinstallation procedure exists. If no supported removal path is available, the organization may need to redesign the migration approach, isolate the functionality, or evaluate alternative implementation strategies before conversion can proceed. Before rebuilding, the PM functional lead must determine whether the capability still delivers measurable business value, or whether equivalent functionality already exists in standard S/4HANA. Once resolved, the development team rebuilds the specialized features as a secure, decoupled cloud extension on SAP BTP or standard Fiori apps, keeping the core ERP clean.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization run a complete, standard SAINT and support package manager audit during the discover phase to catalog every active third-party namespace and add on. Recommendation 2. What successful projects do? Reliability elite projects execute compatibility scans and preliminary stack XML validation exercises before finalizing scope, budget, and implementation contracts. Recommendation 3. What should be validated? Revalidation validate legacy custom code references against the target upgraded add-on namespaces in a sandbox environment to identify custom code breakage. Recommendation 4. What should be governed? Responsibility require formal commercial and technical commitment from the third-party add-on vendor regarding their S/4HANA release roadmap before cutover planning begins.
Migration Incident 15. No downtime estimation performed for PM-heavy environment.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently approve a migration strategy without performing a formal downtime estimation for the plant maintenance landscape. Asset-intensive organizations often operate around the clock and maintain extremely large volumes of maintenance orders, notifications, measurement documents, equipment history records, attachments, and mobile workforce transactions. When downtime planning is based on assumptions rather than data-driven simulations, the organization discovers late in the project that the required conversion outage exceeds the business-approved maintenance window, creating a major cutover risk and potentially forcing a redesign of the migration strategy.
Incident classification and relevant SOP, note if applicable.
1. Complexity. Very high cutover and downtime planning failure. 2. Migration phase, discover. 3. Frequency, common in asset-intensive industries. 4. Primary ownership, enterprise solution architect. 5. Supporting, basis lead, PM functional lead, cutover manager, infrastructure architect. 6. Business ownership, plant operations director. 7. Relevant SOP note, release-dependent SUM and downtime optimization guidance.
How teams identify this issue, diagnostic dashboard, symptoms and evidence.
How missing downtime estimation activities typically reveal themselves during the program lifecycle. 1. Symptom. Initial project plans assume a simple weekend outage without any supporting technical analysis. 2. Red flag. No formal downtime estimation workshop is conducted during discover or prepare. 3. Business impact. Plant leadership rejects the proposed outage window because it conflicts with production schedules and maintenance shutdown plans. 4. Detection. Sandbox conversion simulations reveal significantly longer runtimes than originally estimated. 5. Technical proof. SUM and DMO trial runs indicate database conversion durations exceeding approved business downtime thresholds.
Investigation tools and transactions used.
Use these tools and assessments to evaluate downtime risk and conversion duration. 1. SOP readiness check. Analyze data volumes, custom code impact, and technical readiness indicators. 2. Maintenance planner. Validate conversion paths and supporting technical requirements. 3. SUM software update manager. Execute trial conversions and measure actual processing durations. 4. DB02 database analysis. Review database growth, table sizes, and storage consumption. 5. ST03N workload analysis. Assess transaction volumes and operational activity patterns. 6. Sandbox DMO simulations. Perform production-scale conversion tests to generate realistic downtime estimates. Architect's rule. Never approve a cutover strategy using spreadsheet assumptions when simulation data is available.
Incident analysis and root cause why this happens.
1. Migration teams assume technical downtime scales predictably across all environments. 2. Historical PM transaction volumes are never analyzed before migration strategy approval. 3. Data archiving opportunities are ignored during the early planning stages. 4. Business outage constraints are not collected from plant operations leadership. 5. Technical teams commit to aggressive go-live timelines before validating actual conversion durations. The root cause is approving a migration strategy before understanding the true runtime characteristics of the system.
Why this issue appears only during an ECC to S/4HANA migration.
1. Under normal ECC operations, transaction volume rarely creates visible business concerns because the system remains online. 2. During S/4HANA conversion, millions of maintenance records must be validated, transformed, and processed during migration activities. 3. Large PM datasets directly influence database migration runtimes, consistency checks, and conversion processing windows. 4. The issue remains hidden until migration planning, simulation activities, or cutover design workshops begin. S/4HANA migration exposes operational data volumes that remained invisible during normal ECC operations.
Business and program impact.
1. Go-live schedules become unrealistic and require major replanning efforts. 2. Plant shutdown windows must be renegotiated with operations leadership. 3. Additional infrastructure, consulting, and testing costs are incurred to reduce downtime. 4. Executive confidence in the migration program declines as timeline commitments become unreliable. A poor downtime estimate becomes a program-level credibility problem long before go-live.
Impact on technicians and maintenance teams.
How inaccurate downtime planning directly impacts maintenance operations. 1. Maintenance planners lose access to work order management capabilities longer than expected. 2. Technicians are unable to create notifications, confirm work, or retrieve equipment history during extended outages. 3. Emergency maintenance activities must be tracked manually outside SOP. 4. Plant supervisors lose visibility into active maintenance backlogs and resource assignments. Every additional hour of outage increases operational disruption across the maintenance organization.
Strategic decision. Evaluating downtime strategy options.
Answer: resolving downtime risk requires selecting an appropriate migration execution strategy. We must evaluate these options. 1. Traditional weekend downtime. Accept a longer outage window and perform a standard conversion. 2. Downtime optimization strategy. Utilize available SUM downtime reduction capabilities and process improvements. 3. Near-zero downtime strategy. Invest in advanced downtime minimization approaches and supporting infrastructure. 4. Historical data reduction strategy. Archive eligible legacy data before conversion to reduce processing volumes. 5. Landscape transformation strategy. Separate historical and active data migration activities into controlled phases. The correct downtime strategy must be aligned with business outage tolerance, not technical preference.
Downtime assessment decision matrix.
A standard framework used to determine the appropriate conversion approach. 1. Approved outage window exceeds estimated downtime. Proceed with standard conversion planning. 2. Estimated downtime slightly exceeds business tolerance. Implement downtime optimization measures. 3. Estimated downtime significantly exceeds business tolerance. Evaluate near-zero downtime strategies. 4. Historical data volume drives runtime. Execute archiving and data reduction activities before migration. 5. Mission-critical 24/7 operations. Reassess migration architecture and cutover approach. Architect's rule. Downtime strategy decisions must be based on measured evidence rather than assumptions.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target migration strategy and gets fired if approved outage assumptions prove impossible to execute. 2. Responsible. Basis lead performs technical simulations and downtime estimation exercises. 3. Consulted. PM functional lead, infrastructure architect, cutover manager. 4. Informed. Program sponsor, plan operations director, steering committee. Executive approval of downtime assumptions must occur before entering realize.
Ownership. Who actually fixes it?
Resolving downtime estimation risks requires coordinated technical analysis and business planning. 1. Basis lead executes sandbox conversions and measures actual migration runtimes. 2. PM functional lead identifies operational outage constraints and maintenance scheduling dependencies. 3. Cutover manager designs the conversion timeline and outage execution model. 4. Enterprise solution architect evaluates alternative migration approaches when downtime exceeds business tolerance.
Who gets blamed versus who owns it?
1. Blamed. Basis team accused of underestimating technical conversion durations. 2. Blamed. Cutover team accused of creating unrealistic outage schedules. 3. Actual owner. Enterprise solution architect, accountable for approving migration strategy without validated downtime estimates. 4. Root cause. Migration strategy approved before transaction volume-based downtime analysis was completed. Do not blame execution teams for assumptions that were never validated during discover.
How this is actually fixed the right way by a role.
1. Basis lead performs production-size sandbox conversions and captures runtime metrics for each migration phase. 2. PM functional lead validates outage constraints against production schedules, maintenance shutdowns, and regulatory requirements. 3. Cutover manager builds multiple cutover scenarios and contingency plans based on measured conversion durations. 4. Enterprise solution architect selects the final migration strategy using simulation evidence rather than assumptions. Downtime estimates should be generated from repeated simulations, not optimistic planning workshops.
Common mistakes to avoid what not to do.
1. Do not approve a migration strategy before performing at least one realistic downtime estimation exercise. 2. Do not assume production runtimes will match vendor benchmark examples. 3. Do not ignore data archiving opportunities that could materially reduce conversion duration. 4. Do not commit to executive outage windows before validating technical feasibility. 5. Do not treat downtime estimation as a basis-only activity. It is a business-critical planning exercise.
Follow-up 1. Why can PM transaction volume dramatically increase S/4HANA conversion downtime?
Answer: PM-heavy environments often contain millions of maintenance orders, notifications, measurement documents, equipment records, attachments, and historical maintenance transactions. During conversion, these objects must be validated, transformed, and processed according to the target S/4HANA data model. As data volumes increase, migration runtimes, consistency checks, and database processing activities expand significantly. Organizations that underestimate PM transaction volumes frequently discover that actual conversion durations exceed business-approved outage windows.
Follow-up 2. How do you estimate downtime during the discover phase?
Answer: effective downtime estimation begins with collecting database size information, transaction volumes, growth projections, and infrastructure characteristics. The basis team then performs sandbox conversion simulations using representative production data volumes. Runtime metrics generated from SUM and migration exercises are analyzed alongside business outage requirements. Multiple simulation cycles are typically required to produce a realistic estimate that can support executive planning and migration strategy decisions.
Follow-up 3 curveball. The business only allows a 10-hour outage window, but your simulations predict 28 hours. What do you do?
Answer: the first step is to validate the simulation results and identify the primary runtime drivers. The team should evaluate data archiving opportunities, downtime optimization techniques, infrastructure improvements, and alternative migration approaches. If the projected runtime still exceeds business tolerance, the enterprise solution architect must present alternative strategies and associated costs to the steering committee. The objective is not to force the business to accept an unrealistic outage window, but to align migration architecture, budget, timeline, and operational requirements before execution begins.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: execute formal downtime estimation workshops before migration strategy approval and document all business outage constraints. Recommendation 2. What successful projects do? Reliability elite projects perform multiple production scale sandbox simulations and continuously refine estimates as new data becomes available. Recommendation 3. What should be validated? Revalidation: recalculate downtime projections after every major archiving activity, infrastructure change, or scope adjustment. Recommendation 4. What should be governed? Responsibility: require formal executive sign-off on outage assumptions and downtime targets before entering the realize phase.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 16. CVI impact on PM vendors underestimated.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently underestimate the impact of the customer-vendor integration CVI on plant maintenance operations. Maintenance departments rely heavily on external vendors for subcontracted repairs, equipment warranties, and external labor services. Because the PM team often assumes vendor data cleansing is exclusively a finance or procurement responsibility, legacy PM-specific vendors are omitted from early readiness checks. This oversight causes massive failures during sandbox testing, when maintenance orders attempt to trigger external services using unconverted or broken business partner records.
Incident classification and relevant SAP, note if applicable.
1. Complexity, high cross-module master data failure. 2. Migration phase, discover. 3. Frequency, very common in asset-intensive industries. 4. Primary ownership, enterprise solution architect. 5. Supporting, master data lead, PM functional lead, procurement lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. SAP note 2265093. SAP S/4HANA Business Partner Approach, or CVI.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How unconverted PM vendors typically reveal themselves during the program lifecycle. 1. Symptom 1. Equipment and functional location records lose manufacturer, supplier, or warranty partner assignments after conversion testing. 2. Symptom 2. PM03 external service operations fail to generate purchase requisitions during integration testing. 3. Red flag. Master data cleansing workshops exclusively target mainstream suppliers while completely ignoring PM-specific account groups and local contractors. 4. Business impact. External contractors cannot be dispatched, halting critical breakdown repairs and preventing the fulfillment of warranty claims. 5. Detection. CVI synchronization pre-checks flag hundreds of maintenance service vendors for missing mandatory fields like tax numbers and postal codes. 6. Technical proof. The MDS_load_cockpit synchronization logs display hard failures for legacy PM vendors, preventing them from becoming active business partners.
Investigation tools and transactions used.
Use these tools and reports to identify PM vendor data quality and synchronization failures. 1. CVI_pre-check readiness check. Run the standard program to identify missing mandatory fields across all legacy maintenance vendors. 2. MDS_load_cockpit synchronization cockpit. Execute and monitor the mass synchronization of legacy ECC vendors to the target business partner data model. 3. BP business partner. Validate whether converted maintenance vendors successfully receive the correct supplier and business partner roles such as FLVN00 and FLVN01 post-migration. 4. CVI_upgrade_check_resolve. Diagnose specific mapping conflicts and account group mismatch errors blocking the PM vendor synchronization. 5. SC16N table browser. Compare legacy vendor tables and business partner tables to identify failed synchronization records. Architect's rule. Do not trust standard procurement cleansing to cover local PM contractors. Audit the specific PM account groups directly.
Incident analysis and root cause why this happens.
1. Silos between the PM and finance and procurement teams lead to the assumption that vendor cleansing is entirely a finance responsibility. 2. Local plant managers historically created one-time or local maintenance vendors with extremely poor data quality, omitting mandatory tax or address fields. 3. Project teams fail to map PM-specific partner functions, such as manufacturer or service provider, to the new S/4HANA business partner roles. 4. The program team fails to perform a comprehensive cross-functional impact assessment during the discover phase of the project. The root cause is treating the business partner conversion as an isolated financial activity rather than a cross-modular operational requirement.
Why this is a migration-specific failure.
1. The issue becomes a critical blocker during S/4HANA migration because S/4HANA mandates the business partner model for all external entities. 2. In legacy ECC, incomplete vendor master records could still be used to trigger external PM operations if minimal purchasing data was present. 3. S/4HANA's CVI synchronization process strictly enforces mandatory data validation, actively blocking the creation of the target business partner if data is malformed. 4. Legacy partner function links on equipment and functional locations will break permanently if the underlying vendor fails to convert. S/4HANA's unified data model refuses to tolerate the localized, dirty vendor records that ECC permitted for decades.
Business and program impact.
1. Integration testing cycles are heavily delayed as PM orders cannot generate external purchase requisitions for third-party labor. 2. Data migration cutover windows blow out due to the need for emergency, manual deduplication of failed maintenance vendors. 3. Plant maintenance operations suffer compliance risks if certified external inspectors cannot be dispatched due to system errors. 4. The procurement team is forced to halt standard processing to manually enrich thousands of broken PM vendor records. A failure in vendor synchronization instantly breaks the procurement supply chain for external maintenance execution.
Impact on technicians and maintenance teams.
How failed vendor synchronizations directly disrupt the daily operations of field crews and planners. 1. Planners are unable to assign external service operations to work orders, paralyzing repairs that require specialized third-party contractors. 2. Technicians cannot view accurate manufacturer or supplier details on equipment records, delaying the sourcing of proprietary spare parts. 3. Supervisors are unable to process active warranty claims because the legacy vendor linked to the equipment master no longer exists in S/4HANA. 4. Shop floor crews experience extended asset downtime while waiting for procurement to manually bypass system errors and secure external labor. When external maintenance services are blocked, internal technicians are left waiting in front of broken equipment.
Strategic decision. Enterprise CVI transformation strategy.
Answer: selecting the target CVI transformation approach requires a firm architectural decision to prevent operational PM-dependent maintenance execution from stalling at go-live. 1. Enterprise-wide CVI program recommended. Treat vendor conversion as a cross-functional transformation initiative spanning PM, MM, finance, and customer service. 2. Procurement-owned approach. Allow procurement to manage conversion activities while PM validates only critical maintenance vendors. 3. PM critical vendor first. Prioritize vendors tied to maintenance execution, warranties, calibration services, and regulatory inspections. 4. Big Bang cleansing. Clean every vendor simultaneously regardless of business relevance, accepting high project overhead and manual cleansing cycles. Pro tip: do not let CVI be handled solely by the finance team. Without PM involvement, local maintenance vendors will be ignored.
CVI remediation decision matrix.
A standard analytical matrix to determine the correct technical or business action based on vendor assessment findings. 1. Active PM vendor with missing data. Execute manual data enrichment in ECC to populate missing postal codes, tax IDs, and bank details before running CVI. 2. Inactive PM vendor greater than 2 years. Flag the vendor for deletion and execute standard ECC archiving to remove it from the conversion scope. 3. Duplicate local contractors. Perform deduplication in ECC, merging redundant vendor records into a single surviving entity before S/4HANA synchronization. 4. Vendor is also a customer. Execute customer or vendor linkage in ECC, ensuring both records share identical address data to create a unified business partner. Architect's rule: prune and archive obsolete maintenance vendors before finalizing the CVI synchronization scope.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target migration strategy and gets fired if unsynchronized vendor records paralyze third-party maintenance operations. 2. Responsible. Master data lead coordinates CVI pre-checks and executes the mass synchronization. 3. Consulted. PM functional lead. Procurement lead. 4. Informed. Program sponsor steering committee. Steering committees must explicitly assign PM vendor cleansing tasks, otherwise both PM and procurement will assume the other is handling it.
Ownership, who actually fixes it.
Resolving spatial integration gaps requires joint technical and functional reassessment. 1. Master data lead executes the CVI pre-checks and distributes the error logs detailing which PM vendors failed validation. 2. PM functional lead validates the list of failed vendors, confirming which active local contractors require manual data enrichment. 3. Procurement lead coordinates with external vendors to collect missing tax numbers, addresses, and banking information. 4. Master data lead validates business partner role assignments such as supplier financial accounting and supplier purchasing after synchronization.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of building defective maintenance orders that failed to generate purchase requisitions. 2. Blamed. Procurement team accused of abandoning the plant maintenance department by failing to migrate local contractors. 3. Actual owner. Enterprise solution architect, accountable for approving migration strategy without validated business partner conversions. 4. Root cause. Failure to treat CVI as a holistic, cross-modular enterprise master data project during the discover phase. Do not blame PM or procurement when the migration strategy ignored business partner readiness.
How this is actually fixed the right way by a role.
1. Master data lead runs standard program CVI pre-check to extract the complete list of orphaned or incomplete maintenance vendors. 2. PM functional lead reviews the output, identifying obsolete vendors for archiving and active vendors for immediate address enrichment. 3. Procurement lead utilizes mass update tools like MAS or LSMW in the legacy ECC system to inject missing mandatory fields into the vendor records. 4. Master data lead executes the MDS_load_cockpit synchronization, verifying that all PM vendors successfully generate an active business partner ID. Cleansing your vendor master data in ECC before migration is a mandatory prerequisite for enabling external services in S/4HANA.
Common mistakes to avoid: what not to do.
1. Do not restrict your CVI readiness checks exclusively to standard procurement account groups. Always include local PM contractors. 2. Do not migrate obsolete or unused legacy maintenance vendors, as this dramatically increases the manual cleansing workload. 3. Do not attempt to fix massive CVI synchronization errors during UAT. This must be resolved programmatically during the prepare phase. 4. Do not bypass S/4HANA mandatory field configurations to force dirty vendor data through the synchronization cockpit.
Follow-up 1. Why do PM external service operations fail if the CVI synchronization is incomplete?
Answer: in S/4HANA, external service operations control key PM03 trigger a direct process chain. PM order to external operation PM03 leads to purchase requisition to vendor or business partner to purchase order. If the customer vendor integration CVI fails to synchronize the legacy vendor to a standard business partner with the required purchasing roles FLVN01, this entire integration chain breaks. The system cannot generate the automatic purchase requisition from the maintenance order, completely stalling subcontracted labor dispatch and halting critical asset repairs.
Follow-up 2. How does the CVI conversion impact equipment and functional location partner functions?
Answer: equipment and functional locations use partner functions to track critical relationships, such as the manufacturer, supplier, or external service provider. The CVI process converts these legacy vendor records into the unified business partner model. If the CVI synchronization fails for these specific vendors, the partner function links on the technical objects become orphaned or uneditable in S/4HANA. Consequently, maintenance planners are prevented from identifying who holds the active warranty or who to contact for proprietary equipment repairs.
Follow-up 3. Curveball. What happens if a legacy maintenance vendor is also a customer, but their data is inconsistent?
Answer: if a maintenance vendor is also a customer, for example, they supply maintenance labor but also purchase scrap equipment. S/4HANA requires merging both legacy records into a single, unified business partner. If the addresses, tax numbers, or banking details conflict between the customer and vendor records, the CVI synchronization will generate a hard failure. The master data team must execute a manual cleansing and customer or vendor linkage exercise in ECC to declare a surviving data set before the conversion can successfully process.
Real implementation tips and best practices: the 4 R's.
1. Recommendation 1. What should be done? Realization: execute the CVI_pre-check program early in the discover phase to mathematically isolate the volume of dirty PM vendor records. 2. Recommendation 2. What successful projects do? Reliability elite projects force plant managers to review their local contractor lists and approve the archiving of inactive vendors before the first synchronization run. 3. Recommendation 3. What should be validated? Revalidation: physically validate the CVI success rate by executing the complete PM03 to purchase requisition to purchase order process flow in the sandbox environment. 4. Recommendation 4. What should be governed? Responsibility: implement centralized business partner governance through MDG and prohibit local creation of maintenance vendors without mandatory validation controls.
Migration incident 17. IoT sensor integrations excluded from assessment.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently exclude legacy Internet of Things IoT and plant floor SCADA sensor integrations from the initial architecture assessment. Heavy industries rely on real-time sensor feeds to automatically trigger measurement documents and condition-based maintenance alerts in the ERP. Skipping this integration assessment during early scoping leads to a complete failure of predictive maintenance and automated breakdown warnings when the system is converted, directly impacting asset reliability.
Incident classification and relevant SOP, note if applicable.
1. Complexity. High third-party interface assessment failure. 2. Migration phase. Discover. 3. Frequency. Common in asset-intensive industries. 4. Primary ownership. Integration architect. 5. Supporting. PM functional lead. Basis architect. Lead ABAP developer. Enterprise solution architect. 6. Business ownership. Maintenance operations manager. 7. Relevant SOP note. Not applicable. IoT and asset intelligence assessment gap.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How unrecognized legacy real-time sensor integrations typically reveal themselves during the program lifecycle. 1. Symptom. Critical equipment operating parameters are updated on the physical plant floor, but fail to trigger automated measurement documents in S/4HANA. 2. Red flag. Finding legacy custom middleware scripts that push SCADA values into measuring point tables without any standard API registry. 3. Business impact. Maintenance teams miss critical predictive wear indicators, resulting in unexpected equipment breakdowns and high-cost emergency repairs. 4. Detection. Interface inventory workshops reveal SCADA platforms, data historians, edge gateways, or custom middleware services that were omitted from the original integration landscape documentation. 5. Technical proof. Database analysis reveals measuring points table, IMPT, and historical measurement documents table, IMRG, mapped to legacy custom RFC destinations, transaction, SM59. An active background scheduling jobs transaction SM37 without any corresponding API or cloud destination mappings.
Investigation tools and transactions used.
Use these tools and transactions to diagnose and trace legacy, IoT, SCADA, and sensor integrations. 1. IK17 measurement documents list. Audit table records to verify if real-time coordinate and parameter updates are actively being processed. 2. SLG1 application log. Investigate runtime interface logs and XML payload mapping errors generated by external sensor streams. 3. SM59 RFC connections. Check active RFC destinations pointing to legacy SCADA or plant floor data historian servers. 4. /AIF/ERR AIF error handling. Analyze transaction error logs in the SAP application interface framework to isolate failed cloud payloads. Architect's rule. Do not attempt to redesign sensor integrations before identifying every active SCADA endpoint, RFC destination, and middleware dependency.
Incident analysis and root cause why this happens.
1. Project steering committees treat SCADA and sensor integrations as isolated operational technology (OT) elements rather than core ERP transactions. 2. The program team fails to execute a comprehensive technical and functional inventory of all data historian interfaces during early scoping. 3. The business assumes that standard S/4HANA innovations like Predictive Asset Insights (PA) will natively consume legacy coordinate mappings without any redesign. 4. The technical team focuses entirely on custom ABAP program scans, completely ignoring background event receivers and workflow containers. The root cause is treating operational technology integrations as plant floor utilities instead of mission-critical ERP data sources.
Why this issue appears only during an ECC to S/4HANA migration.
1. The failure becomes highly visible during S/4HANA migration because organizations introduce modern OData APIs, SAP BTP Event Mesh, and SAP Predictive Asset Insights as the target real-time integration standards. 2. Legacy ECC systems relied on direct database reads or obsolete RFC structures that are incompatible with S/4HANA's secure, modernized API layer. 3. Legacy sensor integrations that depend on direct database updates, proprietary middleware, or unsupported RFC patterns often require significant redesign for S/4HANA compatibility. 4. Under normal ECC operations, legacy background sync jobs run without disruption, hiding the integration risk until the system conversion occurs.
Business and program impact.
1. Condition-based maintenance plans become purely reactive as automated measurement documents stop updating, destroying the predictive maintenance business case. 2. Critical health indicators and operational wear metrics do not trigger automated maintenance notifications, leading to sudden, high-cost equipment breakdowns. 3. Mean time between failure MTBF metrics and asset reliability tracking degrades severely due to missing operational sensor history. 4. Failure to identify legacy IoT integrations during the discover phase can invalidate predictive maintenance business cases worth millions in expected plant downtime reduction. 5. The projected ROI of predictive maintenance initiatives becomes impossible to validate because sensor-driven reliability metrics are no longer trusted.
IoT Integration Criticality Assessment Matrix.
A standard framework used to determine the correct target integration path based on legacy sensor findings. 1. Business Critical Plus Supported Interface. Retain and validate target interfaces on S/4HANA without altering integration patterns. 2. Business Critical Plus Unsupported Interface. Rebuild as a cloud-native BTP extension or standardize via OData APIs to eliminate direct database modification risks. 3. Low usage plus high maintenance cost. Retire integration and evaluate standard SAP measurement document entry processes. 4. Unknown usage or legacy custom trigger. Audit and reverse engineer active transport payloads, RFC destinations, and database triggers to establish functional relevance. Architect's rule. Do not commit to legacy database triggers. Audit and standardize them before the prepare phase begins.
Impact on technicians and maintenance teams.
How failed real-time sensor integrations directly disrupt the daily operations of field crews and planners. 1. Technicians must perform manual walk-downs and physically write measurement readings on paper, causing massive downtime and delayed maintenance logging. 2. Planners are unable to receive automated equipment wear alerts, preventing them from scheduling preventive maintenance before a catastrophic failure occurs. 3. Technicians lose automated condition alerts and must manually inspect equipment health, increasing manual inspection workloads and wrench time delays. 4. Plant floor supervisors lose real-time visibility into active work backlogs, leading to uncoordinated shift handovers and increased safety risks.
Strategic decision. Evaluating IoT integration strategy.
Answer: resolving the IoT integration scoping gap requires selecting a sustainable S/4HANA compliant data historian platform. We must evaluate these 4 strategic options. 1. Implement SAP Predictive Asset Insights PAI. Adopt SAP's standard cloud-based predictive maintenance platform on BTP, utilizing event-driven machine learning algorithms. 2. Retain legacy SCADA integrations. Preserve the business capability while redesigning the integration layer to consume supported APIs, event mesh, or middleware services. 3. Custom BTP Event Mesh Gateway. Build custom, side-by-side event-driven integrations on SAP BTP to decouple plant floor data from the core ERP. 4. Decommission real-time sensors. Revert to manual measuring point entries and schedule-based preventive maintenance to minimize architectural complexity. 5. Required Discover deliverable. Approved IoT and SCADA integration inventory containing every interface, middleware component, protocol, endpoint, payload owner, and target remediation strategy. Pro tip: if your legacy sensor integration architecture is highly customized and unsupported, use the migration as a business case to rebuild it on SAP BTP.
IoT and Asset Intelligence Decision Matrix.
A standard analytical matrix to determine the correct IoT integration path during the discover phase. 1. Standard SCADA integration working. Retain and validate target interfaces on S/4HANA without altering integration patterns. 2. Legacy custom or trigger-based sync. Rebuild as a cloud-native BTP extension to eliminate legacy database table modification risks. 3. Predictive maintenance strategic goal. Adopt standard SAP Predictive Asset Insights PAI and Asset Intelligence Network AIN to drive automated notifications. 4. Manual or paper-based measuring. Implement standard SAP Gateway OData services to enable mobile-based measurement document entries. Architect's rule: Do not leave undocumented mobile interfaces. Evaluate and standardize them during the discover phase.
Governance and accountability, RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Integration architect, the person who owns the system interface registry and gets fired if uninventoried IoT connections fail and paralyze the automated maintenance trigger systems. 2. Responsible. PM functional lead and lead ABAP developer collaborate to map and refactor legacy interface logic. 3. Consulted. Basis architect, enterprise solution architect. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must explicitly assign ownership for IoT and SCADA interface discovery. Otherwise, every team assumes someone else inventoried the integrations.
Ownership, who actually fixes it.
Resolving sensor integration failures requires coordinated assessment of operational technology and ERP integration architecture. 1. Integration architect audits the interface catalog and designs secure communication paths between S/4HANA and the external IoT middleware. 2. PM functional lead maps the legacy measuring point and technical object configurations to ensure the incoming payload remains valid. 3. Lead ABAP developer identifies custom code and database trigger dependencies on the legacy tables. 4. Basis architect configures secure communication protocols HTTPS and OData on the S/4HANA gateway and test environments. 5. Enterprise solution architect validates that the target integration strategy aligns with the broader S/4HANA extensibility and clean core architecture principles.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of failing to test automated measurement document generations properly during early sandbox conversion testing. 2. Actual owner. Integration architect accountable for identifying every interface endpoint, including local plant floor data historians. 3. Root cause. Failure to enforce a rigorous interface discovery process and involve local planners and plant stakeholders during early scoping workshops. Do not blame legacy developers for legacy code. Blame current architects for ignoring it during discovery.
How this is actually fixed the right way by a role.
1. Integration architect maps every legacy IoT web service, RFC connection, and file-based data transfer during an interface discovery audit. 2. PM functional lead reviews the legacy measuring point and technical object configurations to ensure the incoming payload remains valid. 3. Basis architect configures the standard SAP gateway and tests standard OData endpoints to establish a secure link. 4. Senior ABAP developer assesses custom interface logic and estimates remediation effort required for S/4HANA compatibility. Scrubbing your legacy custom code repository can reduce your ABAP remediation scope by up to 60%.
Common mistakes to avoid what not to do.
1. Do not assume that standard S/4HANA Predictive Asset Insights PAI will automatically replace third-party IoT integrations without a business transition plan. 2. Do not delay the validation of external IoT and SCADA interfaces until the system integration testing (SIT) phase of the project. 3. Do not allow local plant planners to operate on isolated spreadsheets or disconnected boards, as this destroys data integrity. 4. Do not bypass standard SAP APIs to perform direct database updates on maintenance order tables from external schedulers.
Follow-up 1. What is SAP Predictive Asset Insights PAI, and how does S/4HANA utilize it?
Answer: SAP Predictive Asset Insights PAI is a cloud-based application designed to optimize maintenance strategies using machine learning algorithms and real-time sensor data. It consumes active measuring points and technical object details from S/4HANA, analyzing equipment health, projecting failure dates, and automatically triggering PM notifications when wear thresholds are breached. Transitioning to PAI requires a secure, event-driven integration framework, transforming reactive plant operations into an automated, predictive maintenance environment.
Follow-up 2. How does the /AIF/ERR transaction help trace failed IoT sensor payloads?
Answer: the standard transaction /AIF/ERR acts as the central error handling console for the SAP application interface framework, allowing architects to monitor real-time message flows. When external IoT sensors attempt to push data to S/4HANA, the framework captures inbound and outbound payloads, records mapping failures, stores processing status, and enables message reprocessing without modifying source systems, validating the structure and mapping them to standard PM measuring points. If a payload contains a mismatch, the transaction isolates the specific field error, allowing developers to debug the integration without looking at raw database tables.
Follow up 3 Curveball. What is the specific danger of allowing legacy, direct database, updates on table, IMRG from external SCADA systems?
Answer: directly updating the measurement document table, IMRG, bypasses the standard SAP application logic, validation rules, and status management. In S/4HANA, these direct database modifications can cause severe inconsistencies in core data, as they bypass critical real-time calculations and dependent reporting streams. If a SCADA system pushes unvalidated entries directly into the database, it can corrupt technical object history and trigger uncoordinated background runs. Developers must systematically replace these legacy custom database updates with standard, secure APIs, or standard OData services.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete interface audit during Discover to catalog every active SCADA sensor, custom RFC destination, and data historian in use. Recommendation 2. What successful projects do? Reliability elite projects establish a joint EAM and OT integration team during the prepare phase, bringing together ERP architects and plant floor automation engineers to design unified API payloads. Recommendation 3. What should be validated? Revalidation: validate the real-time processing and data mapping accuracy of the target OData services by executing high-volume sensor load simulations in a sandbox environment. Recommendation 4. What should be governed? Responsibility: require formal business sign-off and functional approval on the target IoT integration design from both the plant maintenance director and the chief information officer before entering the build phase.
Migration Incident 18. Plant-wise data quality inconsistencies not identified.
During the Discover phase of an SAP ECC to SAP S/4HANA conversion, the project team often fails to assess and audit plant-wise master data inconsistencies across decentralized manufacturing sites. The central ERP team assumes that because all plants operate on the same legacy ECC instance, their technical objects share a unified data model. In reality, each plant operates as an autonomous silo, using vastly different classification characteristics, mismatched object types, and inconsistent maintenance planner groups. Failing to discover these plant-level discrepancies during the early assessment results in the complete collapse of the global S/4HANA template design during the Explore phase, forcing massive, unbudgeted local data cleansing cycles.
Incident classification and relevant SAP, note if applicable.
1. Complexity: high master data governance failure. 2. Migration phase, Discover. 3. Frequency, very common in older decentralized landscapes. 4. Primary ownership, enterprise solution architect. 5. Supporting, master data lead, PM functional lead, data migration lead. 6. Business ownership, plant operations director. 7. Relevant SAP note, not applicable, master data quality assessment gap.
How teams identified this issue: diagnostic dashboard, symptoms and evidence.
How unrecognized plant-wise data inconsistencies typically reveal themselves during the program lifecycle. 1. Symptom: blueprints for a unified S/4HANA global template are rejected during Explore workshops because local plant managers find that the proposed unified object types do not match their legacy daily tracking processes. 2. Red flag: finding that the same class of technical assets such as centrifugal pumps is mapped to entirely different catalog profiles and characteristics across different plant codes. 3. Business impact: the timeline to design and validate a global S/4HANA maintenance template slips because consolidated reporting cannot reconcile inconsistent plant data. 4. Detection: master data profiling workshops reveal a complete lack of global data standards, with each plant managing its own localized data sheets. 5. Technical proof. Database analysis of table EQUZ and table AFIH reveals that legacy planner groups and cost codes are mapped to inconsistent, non-existent, or obsolete cost codes. Cross-plan analysis of EQUI, EQUZ, IFLOT, and AFIH reveals identical asset classes mapped to different planner groups, catalog profiles, and maintenance classifications.
Investigation tools and transactions used.
Use these tools to assess plant-wise master data consistency, technical object standardization, and template harmonization readiness. 1. TAANA table analysis. Profile the raw variance of catalog profiles and planner groups across different plant codes in table EQUI. 2. IH08 equipment list edit. Mass extract technical object records across multiple plants to identify inconsistent naming lengths and mismatched object types. 3. SE16H or SE16N table browser. Directly analyze master data segment tables such as EQUZ and IFLOT to find orphan records and obsolete organizational links. 4. SAP readiness check. Audit the technical data consistency, reports, and data quality indicators prior to sizing. Architect's rule. Run table-level profiling across all plant codes before drafting your target global template blueprint.
Incident analysis and root cause why this happens.
1. The central program team treats the migration as a purely technical conversion, ignoring the operational silos that grew over decades. 2. Organizations lack a centralized master data governance (MDG) organization, leaving data maintenance entirely to local plant floor clerks. 3. Assessment teams perform simple row count scans in Discover, completely missing the deep semantic data variations between manufacturing sites. 4. The program team fails to assign business ownership to background data cleansing tasks, assuming they are purely technical operations. The root cause is treating master data as a local, site-specific utility rather than an active enterprise asset.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes highly visible during S/4HANA migration because organizations attempt to establish a single global template spanning multiple plants, exposing decades of local master data divergence that ECC previously tolerated. 2. S/4HANA's real-time CDS view architecture constantly aggregates master data relationships in memory, slowing down when processing massive volumes of dead records. 3. Search applications and value helps may become cluttered with obsolete technical objects if archiving and retention strategies are not implemented. 4. In legacy ECC systems, plants operated as decentralized, isolated silos, where data inconsistencies were tolerated because reporting was localized. S/4HANA's real-time analytical power is useless if the underlying data hierarchy is fractured.
Business and program impact.
1. The global template design stalls during the explore phase, adding months of unbudgeted design workshops. 2. Project costs escalate significantly as local consultants must be hired to execute plant-specific data cleansing. 3. Low user adoption post-go-live as local planners reject standard reports that display scrambled or incomplete information. 4. Data migration leads are forced to scramble and design emergency archiving rules late in the prepare phase, increasing project risk. 5. Executive leadership loses confidence in the global template strategy because every plant demands exceptions to the proposed standard design. Uncleansed asset hierarchies directly sabotage the operational efficiency expected from a S/4HANA transformation.
Impact on technicians and maintenance teams.
How failed real-time sensor integrations directly disrupt the daily operations of field crews and planners. 1. Technicians cannot find standard spare parts because different plants use inconsistent material to equipment catalog profiles. 2. Maintenance planners struggle to identify equivalent assets across plants because equipment classifications and catalog structures differ significantly. 3. Field supervisors are unable to log equipment breakdown history because the standard catalog codes do not match legacy plant terms, breaking asset traceability. 4. Planners spend hours manually validating and correcting tech object details in the office instead of dispatching active repair work.
Strategic decision. Technical Object Harmonization Strategy.
Answer: resolving plant-wise data discrepancies requires selecting an executive strategy for template standardization. We must evaluate these 4 paths. 1. Enforce global template harmonization. Mandate a strict, unified master data standard across all plants pre-conversion, accepting the high cost of manual data cleansing. 2. Retain localized data silos. Allow individual plants to retain their legacy naming conventions and structure indicators, accepting high long-term maintenance costs and broken central analytics. 3. Phased template harmonization. Migrate plants using a hybrid model, converting them to S/4HANA with legacy data as is, and executing data cleansing in post-go-live phases. 4. Hybrid harmonization program. Execute targeted pre-conversion harmonization for critical objects while allowing lower priority data domains to follow a phased governance roadmap. 5. Required discover deliverable. Plant-wise data quality assessment report containing classification variances, planner group inconsistencies, catalog profile deviations, hierarchy gaps, harmonization recommendations, and global template readiness status. Pro tip: if Legay custom codes are too heavily embedded, do not proceed with a legacy conversion. Pivot the project to Greenfield.
Data Quality Cleansing Decision Matrix.
A standard analytical framework used to determine the correct data cleansing action based on plant-wise assessment findings. 1. Unified global template approved. Execute strict, automated mass cleansing of legacy technical objects in ECC using standard tools before conversion. 2. Critical local naming inconsistencies. Deploy alternative labeling to map local plant terms to the global template without altering underlying keys. 3. High volume of obsolete or dismantled assets. Flag the legacy records for deletion and execute standard ECC archiving to remove them from the conversion scope. 4. No central governance structure exists. Establish a centralized master data governance organization to enforce data standards during the prepare phase. Architect's rule: standardizing legacy data parameters pre-conversion is the only way to protect your template during S/4HANA functional build phases.
Governance and Accountability RACI Model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect, the person who owns the target migration strategy and gets fired if unharmonized plant data collapses the global template design. 2. Responsible. Master Data Lead and PM Functional Lead, coordinate to execute data quality checks, profiling, and template mapping. 3. Consulted. Plant Operations Director, Data Migration Lead. 4. Informed. Program Sponsor, Steering Committee. Steering committees must establish clear data retention policies before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving plant-wise master data inconsistencies requires coordinated governance, profiling, harmonization, and template standardization activities across all manufacturing sites. 1. Enterprise Solution Architect defines the target master data standards and global template boundaries. 2. Master Data Lead coordinates with local plant managers to execute data quality checks and profiling. 3. PM Functional Lead maps legacy PM planner groups and technical object categories to the global standard. 4. Data Migration Lead executes programmatic transformation scripts using standard migration tools.
Who gets blamed versus who owns it.
1. Blamed. PM Functional Team, accused of creating inconsistent planner groups, catalog profiles, and technical object classifications. 2. Actual Owner. Enterprise Solution Architect, accountable for selecting a migration strategy without validating plant-level data readiness. 3. Root Cause. Failure to enforce a rigorous data quality assessment and establish global template boundaries during the discover phase. Successful global template adoption depends on business ownership of data standards, not technical migration activities.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect establishes the target master data standards and global template boundaries. 2. Master Data Lead executes mass profiling reports using TAANA to identify plant-wise database variants. 3. PM Functional Lead reviews legacy planner groups and technical object categories to map them to the global standard. 4. Data migration lead estimates transformation complexity and identifies cleansing rules required before migration execution begins. Standardizing your approval paths on flexible workflow is the only way to protect your processes during future upgrades.
Common mistakes to avoid what not to do.
1. Do not attempt to migrate legacy functional locations, as is without establishing a unified global structure indicator. 2. Do not allow local plant managers to bypass data cleansing tasks to avoid near-term operational workloads. 3. Do not delay the data quality profiling TAANA until the realization phase of the project. 4. Do not build custom, unoptimized ABAP views in S/4HANA to compensate for dirty legacy master data.
Follow-up 1. Why do inconsistent maintenance planner groups, INGRP, break S/4HANA analytical dashboards?
Answer: inconsistent maintenance planner groups, INGRP, directly sabotage the real-time reporting capabilities of S/4HANA's standard Fiori dashboards. S/4HANA's embedded analytical views dynamically aggregate costs and maintenance execution backlogs based on the assumption of a unified, enterprise-wide organizational structure. If Plant A uses numerical codes for planner groups, while Plant B uses alphanumeric strings, the central CDS views cannot perform standard, side-by-side performance comparisons. Consequently, executive dashboards return skewed or incomplete data, completely defeating the business value of real-time operational reporting.
Follow-up 2. How does the S/4HANA Migration Cockpit, LTMC, assist in programmatically cleansing plant-wise data during conversion?
Answer: the S/4HANA Migration Cockpit, LTMC, provides a robust, standard platform to programmatically cleanse and harmonize legacy plant data during the migration process. It utilizes built-in transformation rules that allow the data migration lead to map legacy, inconsistent plant values such as local equipment categories or planner groups to the new global template standards on the fly. Rather than manually editing millions of legacy records in ECC, the team can upload legacy extractions into LTMC and apply automated translation mappings. This standardized transformation layer ensures that only clean, compliant master data is loaded into the target S/4HANA database.
Follow-up 3 Curveball. How do you convince autonomous local plant managers to accept a standardized global template that changes their legacy daily processes?
Answer: overcoming local plant resistance requires the enterprise architect to shift the discussion from technical conformity to business value and operational efficiency. The architect must demonstrate that standardizing on a global S/4HANA template is a mandatory prerequisite to enabling advanced, high-value innovations like Predictive Asset Insights (PAI) or unified mobile applications. Additionally, by involving local planners early in the discover phase and establishing a joint EAM data council, plants are given an active voice in shaping the standard template. Presenting this clear roadmap of long-term operational benefits combined with structured governance is the only way to secure local business buy-in.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run extensive data profiling routines using TAANA during the discover phase to mathematically isolate circular references, orphan nodes, and conflicting structure indicators. Recommendation 2. What successful projects do? Reliability elite projects force plant managers to align on a single, global structure indicator matrix before the first data extraction takes place. Recommendation 3. What should be validated? Revalidation: physically validate the cleansed hierarchy by testing deep cost roll-up scenarios within standard Fiori analytical dashboards in the sandbox environment. Recommendation 4. What should be governed? Responsibility: implement centralized master data governance (MDG) protocols for technical objects and prohibit local creation of functional locations without mandatory validation controls.
Migration Incident 19. Duplicate equipment numbering ranges discovered late.
During the discover phase of an SAP ECC to SAP S/4HANA transformation, project teams often fail to analyze overlapping or duplicate equipment numbering ranges across decentralized legacy environments. In legacy ECC setups, different plants or acquired business units frequently maintained localized, Unharmonized number ranges, allowing duplicate equipment IDs to coexist across separate systems. When attempting to convert these systems into a single, unified S/4HANA global client, these overlapping numbers clash, causing critical primary key collisions and completely stalling the master data migration stream.
Incident classification and relevant SOP, note if applicable.
1. Complexity, high master data governance failure. 2. Migration phase, discover. 3. Frequency, common in older ECC landscapes. 4. Primary ownership, enterprise solution architect. 5. Supporting, basis lead, PM functional lead, lead ABAP developer. 6. Business ownership, program sponsor. 7. Relevant SOP note, not applicable, enterprise number range governance assessment.
How teams identified this issue, diagnostic dashboard, symptoms and evidence.
How unharmonized legacy equipment numbering ranges typically reveal themselves during the program lifecycle. 1. Symptom. Master data upload scripts during sandbox conversion runs fail with database primary key violation errors when importing equipment records. 2. Red flag. Finding legacy configuration tables that define identical intervals for different technical object categories with no central coordination. 3. Business impact. Data migration teams cannot complete basic technical object loads, completely halting integration testing and subsequent UAT phases. 4. Detection. Standard data profiling and duplication checks during the early assessment workshops reveal massive number range overlaps across legacy plants. 5. Technical proof. Cross-system profiling reveals identical EQUNR values, representing different physical assets across legacy source systems.
Investigation tools and transactions used.
Use these tools and reports to identify legacy number range intervals and duplicate technical objects. 1. SNRO number range object maintenance. Audit the active and historical interval configurations for the PM equipment object EQUIP_NR. 2. SE16N or SE16H equipment master analysis. Analyze EQUI records across legacy source systems to identify duplicate equipment IDs and conflicting asset attributes. 3. TAANA table analysis. Perform multi-plant database scans on table EQUI to quantify the volume of identical asset keys. 4. SOP readiness check. Analyze master data readiness indicators and identify technical object simplification requirements. Architect's rule. Never size a target HANA database before running SNRO interval checks across all legacy systems.
Incident analysis and root cause why this happens.
1. Legacy plants operated as autonomous silos for decades, creating and managing their own localized technical object numbering schemes. 2. Assessment teams treat equipment numbering as a simple configuration element, completely ignoring legacy number range configuration tables. 3. The organization lacks centralized master data governance MDG protocols to coordinate unique asset identification across the enterprise. 4. The business falsely assumes S/4HANA can natively segregate duplicate numbers by plant code without database primary key conflicts. The root cause is a lack of centralized data governance, allowing uncoordinated numbering ranges to coexist in the legacy landscape.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA system consolidations because the target architecture forces multiple legacy systems into a single global client. 2. In legacy ECC, duplicate equipment numbers could coexist without clashing because they resided in completely separate, disconnected databases. 3. The system consolidation into S/4HANA's unified database schema exposes these legacy numbering overlaps at the database table level. 4. S/4HANA's strict referential integrity rules prevent transactional records from being posted against technical objects with duplicate primary keys. Legacy database client isolation is eliminated in S/4HANA, requiring absolute primary key uniqueness across the enterprise.
Business and program impact.
1. Project timelines expand significantly as data migration leads are forced to design emergency equipment renumbering and mapping logic. 2. Additional custom development effort is incurred to rebuild dependent interfaces and historical links to the newly renumbered assets. 3. Business confidence declines as key users struggle to identify renamed or renumbered technical objects during user acceptance testing. 4. Downstream interface remediation costs escalate rapidly as external systems like SCADA, MES, or GIS must be modified to consume new asset keys. An unharmonized numbering range is a critical data blocker that directly stalls the build and testing phases of the project.
Impact on technicians and maintenance teams.
How failed user adoption and numbering collisions directly disrupt daily maintenance operations. 1. Field technicians struggle to identify assets in the field if physical equipment tags no longer align with renumbered S/4HANA records. 2. Maintenance planners lose historical work order traceability when legacy asset IDs are split or remapped during conversion. 3. Technicians lose confidence in the accuracy of the new system, resorting to manual tracking sheets outside standard ERP processes. 4. Dispatching processes are disrupted as supervisors cannot verify which physical asset matches the newly generated work order ID. Mismatches between physical asset tags and S/4HANA database keys destroy on the floor planner confidence.
Strategic decision. Evaluating S/4HANA asset renumbering paths.
Answer: selecting the target S/4HANA renumbering strategy requires balancing business disruption with the complexity of downstream interface mappings. We must evaluate these 4 options. 1. Enterprise asset renumbering. Execute a global, programmatic renumbering of all duplicate legacy equipment, establishing a unified naming convention. 2. Cross-reference mapping model. Maintain legacy equipment IDs as external references within S/4HANA while generating completely new, standardized global equipment numbers. 3. Prefix-based harmonization. Prefix legacy equipment keys with plant-specific identifier codes to quickly enforce uniqueness at the database level. 4. Global Asset Registry Model. Decouple physical asset identification entirely by mapping legacy IDs to standard global asset registry numbers. Pro tip: if legacy numbers are deeply embedded in downstream SCADA systems, use prefix-based harmonization to minimize integration redesign.
Asset renumbering decision matrix.
A standard analytical matrix used to determine the correct technical or business action based on master data findings. 1. Duplicate an active asset. Renumber the asset programmatically during data load using the S/4HANA migration cockpit to prevent primary key collisions. 2. Duplicate an obsolete asset. Flag the legacy asset for deletion and execute standard ECC archiving to remove it from the conversion scope. 3. Duplicate an interface dependency. Implement a dedicated mapping layer in SAP BTP to translate legacy IDs to new S/4HANA keys. 4. Duplicate an regulatory asset. Execute a controlled, audited renumbering plan to satisfy statutory and history tracking compliance. Architect's rule: prune and archive obsolete duplicate assets before committing to complex, manual renumbering runs.
Discover deliverables. Technical object numbering blueprint.
The mandatory architectural deliverables that must be signed off during the discover phase to mitigate numbering collisions. 1. Equipment number range assessment. Documented analysis of all active and inactive number ranges across all legacy systems. 2. Duplicate asset inventory. A comprehensive register identifying every duplicate equipment ID and its physical location. 3. Number range collision report. Impact analysis detailing which legacy plants are affected by overlapping intervals. 4. Renumbering complexity assessment. Cost and timeline estimates for modifying downstream systems like SCADA or GIS. 5. Global asset identification strategy. Approved architecture blueprint defining the unified S/4HANA numbering strategy.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target migration strategy and gets fired if unharmonized numbering ranges collide and freeze the migration. 2. Responsible. Data migration lead. 3. Consulted. Basis architect, lead ABAP developer. 4. Informed. Program sponsor, steering committee. Plant operations managers. Steering committees must establish clear data governance standards before the project enters the prepare phase.
Ownership, who actually fixes it.
Resolving duplicate equipment numbering conflicts requires coordinated governance, numbering standardization, and migration planning activities across all participating business units. 1. Enterprise Solution Architect defines the enterprise-wide numbering strategy and approves the target asset identification model. 2. PM Functional Lead partners with plant managers to design a unified enterprise standard equipment numbering scheme. 3. Basis Lead analyzes existing SNRO and NRIV configurations and documents collision risks. 4. Senior ABAP developer identifies custom programs, interfaces, and reports dependent on equipment number ranges and estimates remediation complexity.
Who gets blamed versus who owns it.
1. Blamed. Data migration team accused of building defective upload scripts that fail to import valid equipment records. 2. Blamed. PM functional team accused of failing to identify master data configurations during initial scoping workshops. 3. Actual owner. Enterprise Solution Architect, accountable for selecting the correct consolidated target numbering strategy. 4. Root cause. Failure to perform a comprehensive database and configuration audit of legacy number range tables during the discover phase. Do not blame the upload scripts when the underlying legacy numbering structure is fundamentally broken.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect establishes the final consolidated target numbering strategy and obtains formal executive steering committee approval. 2. PM Functional Lead audits the legacy equipment registries to identify and categorize active versus obsolete duplicate assets. 3. Integration Architect catalogs all dependent downstream interfaces such as SCADA, MES, or GIS that utilize the overlapping equipment numbers. 4. Basis Lead executes technical scans on transaction SNRO and table NRIV to mathematically map out all legacy interval overlaps. Resolving duplicate equipment numbering during discover requires solid, business-approved renumbering strategy blueprints, not code.
Common mistakes to avoid what not to do.
1. Do not attempt to migrate overlapping legacy equipment number ranges into a single global S/4HANA client without a prior renumbering strategy. 2. Do not assume that S/4HANA can natively distinguish duplicate equipment numbers by plant code without database primary key conflicts. 3. Do not delay the audit of legacy number range configuration, tables NRIV, until the final user acceptance testing phase of the project. 4. Do not allow local plants to continue creating technical objects using non-standardized, unbuffered number ranges post-go live.
Follow-up 1. Why is equipment numbering range harmonization so critical in an S/4HANA system consolidation?
Answer: equipment numbering range harmonization is a critical best practice because the primary key of the standard equipment table EQUI must be absolutely unique across the entire S/4HANA database client. In decentralized legacy landscapes, duplicate equipment numbers often coexist because they reside in completely separate system databases. During a system consolidation, forcing these overlapping records into a single global client triggers immediate primary key violations, completely stalling the data migration run. Standardizing these ranges pre-conversion is the only way to ensure database integrity and unblock the master data stream.
Follow-up 2. How do you identify overlapping technical object number ranges during the discover phase?
Answer: identifying these overlaps requires the data migration lead to perform a comprehensive configuration audit of transaction SNRO and table NRIV across all legacy environments. The lead must extract the active interval ranges fields from number and TONumber for the PM equipment object EQU IP_NR. By cross-referencing these intervals in a master spreadsheet, the team can mathematically identify every overlapping range. This proactive profiling ensures that the team designs the necessary renumbering and mapping logic long before the actual data conversion execution.
Follow-up 3 curveball. How do you remediate legacy custom interfaces that depend on hard-coded equipment number ranges?
Answer: Remediating legacy custom interfaces with hard-coded numbering dependencies requires a systematic code refactoring exercise driven by the integration architect. During the discover phase, the team must execute custom code scans to locate ABAP programs with hard-coded number intervals. These unoptimized hard-coded values must be systematically replaced with dynamic, table-driven parameters using standard TV/ARVC configurations or custom control tables. Decoupling the interface logic from the physical equipment numbering ranges ensures that the interface continues to execute flawlessly across dependent systems like MES, SCADA, or GIS, even after the assets are programmatically renumbered during the migration.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete standard audit of transaction SNRO and table NRIV during discover to catalog every active legacy number range interval in use. Recommendation 2. What successful projects do? Reliability elite projects establish a combined plant maintenance and data migration workgroup before discover sign-off, bringing together PM consultants and master data architects to design a unified global number range matrix. Recommendation 3. What should be validated? Revalidation: formally validate legacy numbering range overlaps by running collision reports and estimating the exact complexity of downstream interface modifications. Recommendation 4. What should be governed? Responsibility: require formal executive sign-off and steering committee approval on the target equipment numbering strategy before completing the discover phase.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 20. Business disruption during order freeze underestimated.
During the discover phase of an SAP ECC to SAP S/4HANA migration, executive leadership frequently underestimates the operational disruption caused by maintenance order freeze windows. A system freeze is required during the final cutover to prevent data delta inconsistencies, meaning no new work orders can be created and no confirmations can be posted. Failing to align this controlled transactional freeze window with physical plant maintenance cycles during early scoping leads to uncoordinated production stops, safety compliance risks, and massive backlogs that overwhelm the maintenance team immediately after go live.
Incident classification and relevant SAP, note if applicable.
1. Complexity. High program governance and readiness failure. 2. Migration phase, discover. 3. Frequency, common in 24/7 manufacturing environments. 4. Primary ownership, enterprise solution architect or program manager or business transformation lead. 5. Supporting, PM functional lead cutover manager OCM lead. 6. Business ownership, plant operations director. 7. Relevant SAP note, not applicable. Business readiness and change management gap.
How teams identified this issue. Diagnostic dashboard. Symptoms and evidence.
How underestimated operational freeze impacts typically reveal themselves during the program lifecycle. 1. Symptom. Plant supervisors express alarm during Discover workshops, stating that a 48-hour system freeze will halt critical inspections. 2. Red flag. The project master schedule defines a technical cutover window without any corresponding business blackout or manual workaround plan. 3. Business impact. Maintenance planners start building unauthorized shadow systems in Excel to track work during the predicted freeze window. 4. Detection. Readiness surveys reveal that maintenance crews have no procedure for handling emergency breakdowns during the transition period. 5. Technical proof. Historical transaction logs show that the target freeze window overlaps with a high-volume seasonal maintenance shutdown.
Incident analysis and root cause. Why this happens.
1. Executive leadership treats the migration as a technical IT upgrade rather than a physical operational transformation. 2. Project teams fail to collect plant-specific operational requirements during the early discover phase architecture sessions. 3. The program team fails to quantify the operational impact of maintenance order freezes on plant operations, assuming they are purely technical operations managed by basis. 4. The organization assumes that business as usual can be suspended without formal contingency planning or manual safety protocols. The root cause is a lack of operational empathy at the steering committee level regarding shop floor realities.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migrations because of the single point of truth cutover requirement, which typically requires a controlled transactional freeze window. 2. Under normal ECC operations, short maintenance outages are manageable. However, many S/4HANA conversions require extended windows depending on migration approach and landscape complexity for technical data restructuring. 3. System conversion activities temporarily restrict system availability during migration testing and cutover events, exposing dependencies that were previously unnoticed. 4. Legacy ECC systems were often highly localized, allowing plant-by-plant upgrades. S/4HANA consolidations remove this isolation and force a unified freeze.
Business and program impact.
1. Plant managers may refuse to grant system downtime, potentially forcing a high-cost postponement of the entire global go-live. 2. Severe safety risks emerge if technicians cannot access hazardous environment permits or technical drawings during the freeze. 3. Post-go-live data entry backlogs result in incorrect asset reliability reporting for the first quarter of the new system operations. 4. Decline in shop floor morale as maintenance crews perceive the new S/4HANA system as a hindrance to their physical work.
Impact on technicians and maintenance teams.
How underestimated freeze windows directly disrupt the daily operations of field crews. 1. Technicians cannot create emergency breakdown notifications, forcing them to rely on verbal or radio communication which is not auditable. 2. Manual permit-to-work processes increase safety risks as technicians lose real-time visibility into lockout-tagout isolations in SAP. 3. Maintenance crews accumulate a massive backlog of work confirmations on paper, which requires weeks of manual data entry after go-live. 4. Asset history becomes temporarily fragmented, making it impossible for field crews to reference previous repair notes during a breakdown.
Strategic decision. Evaluating cutover and freeze strategy.
Answer: selecting a viable cutover strategy requires balancing technical downtime with physical plant safety. We must evaluate these 4 strategic options. 1. Standard weekend cutover. Proceed with a 48 to -72-hour hard freeze, accepting the requirement for a complete manual workaround process during the blackout. 2. NZDT transformation strategy. Invest in advanced near-zero downtime technology to minimize the maintenance order freeze to a sub-4-hour window. 3. Staggered plant deployment. Reduce global business risk by migrating plants in smaller regional waves rather than a single big bang cutover. 4. Planned shutdown alignment. Delay the migration to align precisely with a pre-scheduled holiday or seasonal plant maintenance turnaround. Pro tip: if your plant runs 24/7 mission-critical safety operations, a standard weekend cutover is rarely a viable strategic option.
Discover deliverables. Operational readiness planning.
The following deliverables must be produced during the discover phase to mitigate freeze window risks. 1. Freeze impact assessment. A detailed report mapping the volume of maintenance transactions impacted by varying downtime durations. 2. Emergency workaround strategy. A documented safety protocol defining how breakdown work is authorized and tracked during the system blackout. 3. Plant cutover calendar. A unified schedule cross-referencing technical migration milestones with physical production and shutdown cycles. 4. Operational readiness sign-off. A formal confirmation from plant operations leadership accepting the proposed cutover window and manual process.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who defines the cutover framework and gets fired if the freeze window causes an unplanned plant shutdown. 2. Responsible. Cutover manager performs technical downtime estimation and identifies the physical freeze constraints. 3. Consulted. PM functional lead, plant operations director, OCM lead. 4. Informed. Program sponsor, steering committee, maintenance planners. The steering committee must formally approve the business disruption risk before the project enters the prepare phase.
Ownership. Who actually fixes it?
Resolving business disruption risks requires joint technical and functional assessment in the discover phase. 1. Enterprise solution architect assesses multiple technical cutover risk scenarios to determine the impact on asset availability. 2. PM functional lead identifies specific maintenance processes and regulatory inspections that cannot tolerate any downtime. 3. OCM Lead evaluates the workforce computer literacy and organizational readiness for a high-intensity manual workaround period. 4. Plant Operations Director validates operational blackout constraints and provides the physical maintenance shutdown schedules.
Who gets blamed versus who owns IT?
1. Blamed. Cutover team accused of demanding an impossible system freeze window that disrupts production. 2. Blamed. PM functional team accused of failing to protect the business from IT-driven downtime. 3. Actual owner. Enterprise solution architect accountable for approving a cutover strategy that was not operationally validated. 4. Root cause. Failure to treat the maintenance order freeze as a high-risk business continuity event during the discover phase. Do not blame the technical migration tools for the length of the freeze. Blame the lack of operational contingency planning.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect performs a formal freeze impact assessment by mapping transactional volumes to target cutover durations. 2. PM Functional Lead identifies every critical maintenance process that must continue manually during the system blackout. 3. Cutover Manager estimates multiple technical downtime options such as NZDT or ZDO to present to the steering committee. 4. OCM Lead evaluates organizational readiness risks and identifies the training effort required for manual contingency processes. Planning for the freeze is as important as planning for the go-live. Both must be operationally validated.
Common mistakes to avoid what not to do.
1. Do not communicate the system freeze window for the first time during the training phase. It must be scoped during discover. 2. Do not assume technicians will naturally find a way to manage maintenance without SAP. Always provide a formal manual toolkit. 3. Do not schedule a hard system freeze during a planned plant turnaround or peak production season. 4. Do not ignore the data entry effort required post-go-live to catch up on the work performed during the freeze period.
Follow-up 1. What are the specific risks of allowing shadow systems like Excel during a maintenance order freeze?
Answer. The primary risk of allowing planners to use unauthorized shadow systems like Excel is the inevitable loss of data integrity and the creation of a massive post-go-live reconciliation backlog. When work is tracked outside of SAP, critical maintenance history, safety permits, and spare part consumption records are often recorded inconsistently. This leads to transcription errors when the data is eventually backfilled into S/4HANA, directly corrupting the technical object history and making future failure analysis unreliable. To prevent this, the project must provide a single, controlled manual process kit rather than letting plants design their own workarounds.
Follow-up 2. How do you align a technical S/4HANA cutover with a physical plant maintenance cycle?
Answer. Aligning a technical cutover with a physical plant cycle requires the cutover manager to attend operational planning sessions at least 6 months before go-live. The goal is to identify low-activity windows where preventive maintenance volume is naturally reduced. Ideally, the migration should be scheduled between major turnaround events to ensure the maintenance team is not already overextended. If a conflict is unavoidable, the enterprise architect must evaluate advanced downtime reduction techniques, such as NZDT near zero downtime, to minimize the business disruption to a manageable duration.
Follow-up 3 curveball. How would you manage an emergency breakdown of a mission-critical asset during the system freeze period?
Answer. Managing a mission-critical breakdown during a system freeze requires a pre-approved safety-first manual contingency protocol. Technicians must utilize physical emergency repair packs that contain paper-based safety isolation permits and work logs to ensure no regulatory compliance is bypassed. Once the repair is complete and S/4HANA is back online, a dedicated data entry team must immediately post the notification and order confirmations. This ensures that the equipment downtime and repair costs are captured in the asset history, while the physical plant safety remains the absolute priority during the IT outage.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run an operational impact assessment during Discover to map out the must-have maintenance processes that cannot stop during a system freeze. Recommendation 2. What successful projects do? Reliability elite projects perform a baseline operational activity audit to identify peak maintenance windows and schedule cutover during natural low activity periods. Recommendation 3. What should be validated? Revalidation: validate estimated freeze durations and backlog volumes using historical maintenance transaction data. Recommendation 4. What should be governed? Responsibility: establish a business cutover lead role for each plant, accountable for managing on-site safety and manual workarounds during the migration blackout window.
Migration Incident 21. Finance simplification impact on PM settlement underestimated.
During the Discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently underestimate the impact of mandatory finance simplifications on the plant maintenance PM settlement process. The introduction of the Universal Journal and new asset accounting changes how maintenance costs are capitalized and settled to assets under construction AUC. Failing to assess these cross-module dependencies early leads to critical settlement failures, incorrect financial reporting, and the inability to close capital maintenance orders during early sandbox conversion cycles.
Incident classification and relevant SAP note if applicable.
1. Complexity: very high cross-module integration failure. 2. Migration phase, Discover. 3. Frequency, common in asset-intensive industries with capital projects. 4. Primary ownership, enterprise solution architect and FICO lead. 5. Supporting, PM functional lead, data migration lead. 6. Business ownership, financial controller. 7. Relevant SAP note. SAP Note 2206026, Settlement of Investment Measures in SAP S/4HANA.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How underestimated finance PM integration impacts typically reveal themselves during the program lifecycle. 1. Symptom: maintenance order settlement runs transaction K088 terminate with hard errors regarding inactive depreciation areas or missing GL accounts. 2. Red flag: PM functional workshops are conducted in a silo without the participation of the finance and asset accounting leads. 3. Business impact: capital maintenance costs are trapped in the PM module, preventing the timely capitalization of high-value asset improvements. 4. Detection: S/4HANA Readiness Check identifies multiple simplification items related to new asset accounting and Universal Journal integration. 5. Technical proof: database table, ACDOC. A Universal Journal shows missing or inconsistent secondary cost element postings from PM settlement activities.
Investigation tools and transactions used.
Use these tools and transactions to diagnose PM finance settlement and mapping inconsistencies. 1. KO03 display maintenance order. Review settlement rules and the status of investment profiles linked to capital maintenance orders. 2. AIAB AUC settlement. Analyze the distribution of costs from the asset under construction to the final fixed asset in the new S/4HANA ledger. 3. KO8G actual settlement. Selection variant. Investigate mass settlement failures and check the application logs for finance-driven validation errors. 4. SE16N table analysis. Validate entries in table ACDOC, A, and ANLC to identify discrepancies between PM order values and asset values.
Incident analysis and root cause why this happens.
1. Project teams fail to realize that S/4HANA merges finance and controlling into a single line item table, requiring a complete redesign of secondary cost elements. 2. Legacy settlement profiles in ECC often utilize unoptimized GL account structures that are no longer valid under new asset accounting rules. 3. The program team ignores the mandatory requirement to align PM investment measures with the new technical clearing account architecture. 4. The organization underestimates the effort required to remediate legacy PM settlement rules that point to decommissioned or merged cost centers. The root cause is treating maintenance settlement as a purely functional PM task rather than a core financial ledger integration.
Why this issue appears only during an ECC. to S4HANA migration.
1. The failure is unique to S4HANA migration because new asset accounting is a mandatory prerequisite that changes the data model of the PM to FI bridge. 2. In legacy ECC, PM settlement to AUC utilized a multi-table storage model GL, CO, and AA, which allowed for less rigid validation rules during the settlement run. 3. S4HANA's Universal Journal architecture enforces real-time reconciliation, meaning any mismatch in PM settlement rules triggers an immediate system block. 4. Standard ECC upgrade paths did not require the conversion of secondary cost elements into GL accounts, a change that now disrupts legacy PM reporting. S4HANA eliminates the separation between PM logistics and finance, exposing integration gaps that ECC quietly tolerated for years.
Business and program impact.
1. Project timelines are threatened as month-end close simulations fail, forcing emergency redesign of the PM and FICO integration during the build phase. 2. Inaccurate asset values on the balance sheet lead to compliance risks and potential audit findings during the first post-migration financial cycle. 3. Maintenance directors lose visibility into capital budget utilization, potentially leading to overspending on unmonitored plant turnaround projects. 4. Increased manual effort for the finance team who must manually journal and correct failed automated maintenance settlements.
Strategic decision. Settlement redesign strategy.
Answer: selecting the target PM and finance settlement strategy requires a firm governance decision to ensure financial compliance and operational continuity. 1. Standardized S4HANA account-based settlement recommended. Redesign all PM settlement profiles to align with the new account-based COPA and Universal Journal standards. 2. Legacy cost-based settlement retention. Attempt to retain legacy costing models, accepting the high risk of reconciliation errors and complex custom mapping workarounds. 3. Capitalized maintenance centralization. Shift the ownership of AUC settlement from the PM module to a centralized project systems PS or investment management IM architecture. 4. Phased ledger conversion. Implement the new settlement logic only for new capital orders, while managing legacy open orders through manual period-end adjustments. Pro tip: moving to account-based settlement is the only way to leverage S4HANA's real-time financial reporting power.
Discover deliverables. Finance integration readiness.
The following deliverables must be produced during the discover phase to mitigate PM and finance integration risks. 1. Settlement profile audit report. A comprehensive inventory of all legacy PM settlement profiles and their corresponding target GL accounts in S4HANA. 2. A UC mapping document. A technical map defining how maintenance order costs will flow to assets under construction under the new asset accounting rules. 3. Secondary cost element inventory. A list of all PM-specific secondary cost elements that must be converted into standard GL accounts in the Universal Journal. 4. Financial integration risk matrix. A prioritized list of high-value capital maintenance projects that are at risk of settlement failure during cutover.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target integration design and gets fired if failed settlements paralyze the financial month-end close. 2. Responsible. FICO lead assesses and validates the target asset accounting and settlement architecture. 3. Consulted. PM functional lead, asset accounting lead, data migration lead. 4. Informed. Program sponsor, chief financial officer, plan operations director. Settlement governance must be a joint venture between maintenance and finance leadership.
Ownership, who actually fixes it.
Resolving PM and finance integration gaps requires joint technical and functional assessment in the discover phase. 1. Enterprise solution architect assesses the impact of new asset accounting on legacy PM investment profiles and settlement rules. 2. FICO lead identifies decommissioned legacy GL accounts and maps them to the target S4HANA chart of accounts. 3. PM functional lead validates that the target maintenance order types are assigned to the correct settlement profiles and depreciation areas. 4. Data Migration Lead executes the extraction and enrichment of legacy settlement rules to ensure compatibility with the Universal Journal.
Who gets blamed versus who owns it?
1. Blamed. PM functional team accused of providing incorrect settlement rules that break the financial ledger postings. 2. Blamed. Finance team accused of implementing a rigid new system that prevents maintenance planners from closing work orders. 3. Actual owner. Enterprise solution architect, accountable for approving an architecture that failed to reconcile cross-module financial dependencies. 4. Root cause. Failure to treat PM settlement as a high-risk integration boundary between logistics and finance during the discover phase. Successful integration is an architectural responsibility, not a module-specific configuration task.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect performs a formal integration impact assessment, mapping legacy PM investment measures to the target S/4HANA financial ledgers. 2. FICO Lead evaluates the target accounting model and defines the technical clearing account requirements for maintenance to asset capitalization. 3. PM Functional Lead reviews the complete inventory of legacy settlement profiles to determine which structures are compatible with the new ledger design. 4. Data Migration Lead analyzes legacy maintenance order volumes to estimate the technical effort required for automated settlement rule conversion. In the discover phase, fixing the issue means identifying the gap and defining the target architecture, not performing the configuration.
Common mistakes to avoid what not to do.
1. Do not assume that ECC settlement rules will work as is in S/4HANA without validating the target GL account and depreciation area mappings. 2. Do not exclude asset accounting leads from PM blueprinting sessions, as they own the target ledger structure. 3. Do not delay the audit of secondary cost elements until the technical conversion phase, as this will stall the financial reconciliation runs. 4. Do not ignore legacy maintenance orders with incomplete settlement rules, as they will cause hard errors during the system conversion.
Follow-up 1. How does the introduction of the Universal Journal, ACDOCA, impact the PM settlement process?
Answer. The Universal Journal Table ACDOCA merges previously separate tables for GL, controlling, and asset accounting into a single source of truth. For the PM settlement process, this means that every cost posting from a maintenance order must now be fully reconciled in real time across all financial dimensions. Legacy, secondary cost elements must be converted into standard GL accounts, and the settlement logic must be redesigned to ensure that these accounts are correctly assigned to the appropriate ledger groups. Failing to adapt the PM settlement profiles to this new unified ledger structure results in immediate posting failures and broken financial reconciliation.
Follow-up 2. What is the risk of inconsistent depreciation area mapping during PM to AUC settlement?
Answer. In new asset accounting, every asset transaction must be posted to all relevant depreciation areas simultaneously according to the assigned accounting principles. If the PM settlement profile or the investment profile is not correctly aligned with these target depreciation areas, the system will block the settlement run to the asset under construction. This inconsistency prevents the organization from capitalizing maintenance costs for regulatory or tax purposes, directly leading to inaccurate balance sheet reporting. Architects must ensure that the PM and FICO bridge is validated for all parallel ledgers to avoid these critical financial blocks.
Follow-up 3 curveball. How would you handle a situation where a maintenance order must settle to multiple assets with different accounting principles?
Answer. Handling multiple target assets with conflicting accounting principles requires the architect to evaluate the technical clearing account architecture early in the project. The strategy involves designing a settlement profile that utilizes ledger group-specific posting logic or a neutral clearing account to distribute costs across diverse regulatory ledgers. During discover, the team must identify these complex scenarios to determine if standard S/4HANA functionality suffices, or if a custom settlement user exit must be refactored. This ensures that each asset is updated according to its specific regulatory requirements, while maintaining a single, transparent audit trail from the original maintenance work order.
Real implementation tips. and best practices the 4 Rs.
Recommendation 1. What should be done? Realization: execute a comprehensive cross-module audit of all PM investment profiles and settlement rules early in the discover phase. Recommendation 2. What successful projects do? Reliability elite projects. Establish a PM and finance integration task force that meets weekly during discover to align technical maintenance objects with the target S/4HANA ledger design. Recommendation 3. What should be validated? Revalidation: validate settlement architecture assumptions using representative PM capital order samples and cross-module financial reconciliation analysis. Recommendation 4. What should be governed? Responsibility: assign formal joint accountability to the FICO lead and PM functional lead for the sign-off of the target state settlement architecture.
Migration Incident 22. Material ledger impact on PM spares missed during discovery.
During the discover phase of an SAP ECC to SAP S/4HANA migration, project teams frequently overlook the mandatory activation of the material ledger ML. While often viewed as a purely financial requirement for manufacturing, the material ledger fundamentally changes how maintenance spare parts and MRO maintenance, repair, and operations inventories are valuated. Failing to assess the impact on PM spare parts valuation, price controls, and work order cost calculations early leads to critical posting errors, blocked material reservations, and distorted maintenance cost reporting during sandbox trials.
Incident classification and relevant SAP note if applicable.
1. Complexity: high critical finance logistics integration failure. 2. Migration phase discover. 3. Frequency: universal material ledger is mandatory in S/4HANA. 4. Primary ownership: enterprise solution architect. 5. Supporting: PM functional lead, FICO lead, MM lead. 6. Business ownership: inventory controller and maintenance manager. 7. Relevant SAP note. SAP note 2267835. Material ledger obligatory in SAP S/4HANA.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How unrecognized material ledger impacts reveal themselves during the program lifecycle. 1. Symptom: maintenance work orders for spare part heavy repairs fail to release, or goods movements MIGO are blocked by material ledger not active errors. 2. Red flag: maintenance cost reports in the sandbox environment show 0 or inconsistent values for consumed MRO spare parts. 3. Business impact: procurement of mission-critical spare parts is halted, directly threatening plant availability and production schedules. 4. Detection: S/4HANA readiness check flags the mandatory material ledger activation as a high-impact simplification item for all valuated materials. 5. Technical proof: financial posting logs show failures in the Universal Journal, a CDOC, due to missing currency or valuation types required by the material ledger.
Investigation tools and transactions used.
Use these tools to assess material ledger readiness and spare parts valuation consistency. 1. OMX1 or OMX2 material ledger configuration assessment. Analyze current ECC valuation areas and determine which maintenance plants are eligible for material ledger conversion. 2. CKM3N material price analysis. Investigate legacy spare part price histories to identify inconsistent price controls standard versus moving average. 3. MM03 display material. Audit accounting and costing views of high-volume PM spare parts to identify missing valuation data. 4. SAP readiness check. Review the material ledger section to identify specific material types and plants requiring data enrichment before conversion.
Incident analysis and root cause why this happens.
1. Project teams assume the material ledger is a finance-only feature, ignoring its impact on logistics-driven PM material consumption. 2. Legacy ECC maintenance plants often operate with multiple currencies or inconsistent valuation methods that ML does not support natively. 3. The program team fails to account for the mandatory actual costing versus price control decisions during the early architectural scoping phase. 4. Organizations overlook MRO spare parts during master data profiling, focusing only on finished goods and raw materials used in production. The root cause: is a lack of cross-modular understanding of how S/4HANA merges inventory valuation with the general ledger.
Why this is a migration-specific failure.
1. The failure is unique to S/4HANA migration because the material ledger is now the mandatory and only engine for inventory valuation. 2. In legacy ECC, the material ledger was optional. Many PM-heavy organizations managed spare parts through simple moving average prices without ML active. 3. The conversion process for S/4HANA requires every existing valuated material to be programmatically converted to the ML data model during the downtime window. 4. Legacy ECC systems allowed PM material reservations to exist without strict ledger reconciliation, a gap that S/4HANA's Universal Journal strictly prohibits.
Business and program impact.
1. Maintenance cost accuracy is compromised, as work order confirmations may reflect incorrect or zero costs for high-value spare parts. 2. Month-end financial closing is delayed if the material ledger cannot reconcile maintenance stock movements with the general ledger. 3. Plant supervisors lose budget control visibility when plan versus actual cost variances for maintenance projects become unreliable. 4. The project faces unbudgeted manual effort to cleanse and enrich thousands of spare part accounting views late in the prepare phase.
Strategic decision. Material ledger valuation strategy.
Answer: selecting the target inventory valuation model for spare parts requires a governance decision balancing reporting depth with process complexity. 1. Standard ML activation single currency. Activate material ledger for all PM plants using a single currency to satisfy S/4HANA prerequisites with minimal complexity. 2. Multi-currency or global valuation strategy. Implement ML with parallel currencies, for example, local and group, to support global maintenance cost transparency and tax compliance. 3. Actual costing for MRO. Enable actual costing for maintenance spares to capture exact price variances, accepting the high month-end processing overhead. 4. Standard price versus moving average alignment. Force a global policy to standardize price control S or V for all technical spare parts before migration begins. Pro tip: for most PM-heavy organizations, activating ML without actual costing for MRO spares is the most pragmatic strategic path.
Discover deliverables. Material ledger scoping.
Following deliverables must be produced during the discover phase to mitigate PM and ML integration risks. 1. ML scoping and activation report. A comprehensive map of every maintenance plant and its corresponding target valuation model in S/4HANA. 2. MRO valuation impact analysis. A detailed assessment of how moving to the material ledger will impact the valuation of existing high-value spare part inventories. 3. Spare part master data cleanse plan. A prioritized list of materials with inconsistent price controls or missing accounting data requiring enrichment. 4. Cross-functional ML governance map. A documented agreement defining ownership of ML configuration between the PM, MM, and finance teams.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target state integration and gets fired if blocked material ledgers paralyze maintenance goods movements. 2. Responsible. FICO lead evaluates the target material ledger configuration and currency settings for maintenance plants. 3. Consulted. PM functional lead. MM lead inventory controller. 4. Informed. Program sponsor, chief financial officer, plant operations director.
Ownership. Who actually fixes it.
Resolving PM and ML integration gaps requires joint technical and functional assessment in the discover phase. 1. Enterprise solution architect assesses the impact of mandatory ML activation on existing PM business processes and material reservations. 2. FICO lead evaluates the target currency and valuation model, ensuring it supports both financial and maintenance reporting requirements. 3. PM functional lead assesses the impact of material ledger valuation changes on maintenance planning, reservations, and spare part consumption processes. 4. Lead analyzes the volume of valuated materials in legacy maintenance plants to estimate the data migration and enrichment effort.
Who gets blamed versus who owns it?
1. Blamed. Finance team accused of imposing complex accounting rules that prevent technicians from withdrawing parts for repairs. 2. Blamed. Team accused of failing to maintain the material master data correctly before the conversion. 3. Actual owner. Enterprise solution architect, accountable for failing to assess the cross-modular impact of the material ledger during discover. 4. Root cause. Failure to treat the material ledger as a mandatory logistics financial integration boundary rather than a siloed finance task. Do not blame the finance team for standard S/4HANA prerequisites. Integration is an architectural responsibility.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect performs a formal integration impact assessment, identifying every maintenance plant affected by mandatory ML activation. 2. FICO Lead evaluates the target valuation and currency model, defining the mandatory ML settings required to support PM spare parts consumption. 3. PM Functional Lead reviews the inventory of MRO spare parts to determine if legacy price controls and valuation types require standardization. 4. Lead analyzes the valuated material master repository to estimate the technical effort required for automated data enrichment during conversion. In the discover phase, fixing means identifying the cross-module dependencies and defining the target valuation strategy.
Common mistakes to avoid what not to do.
1. Do not assume the material ledger is only for manufacturing. It is mandatory for every valuated material, including maintenance spares. 2. Do not delay the material ledger scoping until the technical conversion phase, as it requires complex master data enrichment. 3. Do not allow PM functional workshops to proceed without a formal alignment session with the FICO and integration leads. 4. Do not activate ML actual costing for MRO spare parts without first validating that the maintenance team can support the high administrative overhead.
Follow-up 1. Why is the material ledger mandatory for PM spare parts, even if actual costing is not used?
Answer. In S/4HANA, the material ledger is the underlying data architecture for all inventory valuation, regardless of whether an organization chooses to use actual costing. It allows the system to support multiple currencies and parallel valuation methods within the Universal Journal. For PM, this ensures that every spare part issued to a work order is valuated with absolute precision and real-time reconciliation with the financial ledgers. Even without actual costing, ML activation is required to unblock goods movements and enable standard maintenance order settlement processes.
Follow-up 2. What is the risk of having inconsistent price control S versus V for PM spare parts during ML activation?
Answer. Maintenance spare parts often carry inconsistent price controls, with some using standard price S and others using moving average price V. While S/4HANA supports both, the material ledger strictly enforces how variances and price changes are handled during the period end close. If the PM team does not standardize these controls early, the organization may experience massive, uncoordinated price variances in maintenance cost centers after go live. Architects must define a clear pricing strategy during discover to ensure that maintenance budgets remain predictable and audit-ready in the new system.
Follow-up 3 curveball. How would you handle valuated PM spare parts that are shared between a manufacturing plant and a distribution center?
Answer. Sharing valuated spare parts between different plant types requires the architect to evaluate the valuation area settings early in the discover phase. Each plant may have different functional requirements for the material ledger, such as different parallel currencies or actual costing settings. The strategy involves designing a unified ML configuration that satisfies both the high-volume transactional needs of the distribution center and the precision costing needs of the maintenance plant. If requirements conflict, the team may need to evaluate separate valuation types or split valuation strategies to ensure financial compliance without disrupting maintenance availability.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete audit of evaluated MRO spare parts across all maintenance plants early in Discover to identify inconsistent price controls. Recommendation 2. What successful projects do? Reliability elite projects conduct a joint MRO valuation workshop involving PM, MM, and finance to define a unified global pricing strategy for S/4HANA. Recommendation 3. What should be validated? Revalidation: validate material ledger architecture assumptions using representative samples of high-value spare parts and valuation impact analysis. Recommendation 4. What should be governed? Responsibility: assign a single cross-module master data steward accountable for the consistency of accounting and costing views across the manufacturing and maintenance plants.
Discover phase conclusion. Mitigating architectural uncertainty.
The Discover phase is where organizations learn the truth about their SAP landscape. Across the Discover phase incidents, we observed a consistent pattern. Migration programs rarely struggle because of technical conversion activities alone. They struggle because critical information was never identified, documented, analyzed, or challenged during the earliest stages of the transformation. Migration strategy mistakes: undocumented integrations, unsupported add-ons, poor master data quality, excessive custom code, hidden technical debt, obsolete technologies, and governance gaps all originate long before the first conversion system is built. The Discover phase exists to expose these risks, while remediation is still relatively inexpensive and manageable. Successful organizations treat Discover as an architectural investigation rather than a project kickoff exercise. They invest time in understanding their business processes, technical landscape, data quality, interfaces, custom developments, operational dependencies, and future state objectives before committing to migration decisions. Every risk identified during Discover lowers the probability of disruption later in the migration lifecycle. Every risk ignored during Discover eventually reappears in Prepare, Explore, Realize, Deploy, or Run, usually with significantly higher cost, complexity, and business impact. A successful SAP S/4HANA migration is not built on conversion tools. It is built on discovery quality.
Transition. Moving from strategy to execution readiness.
At the conclusion of the Discover phase, organizations should understand what must be migrated, why it must be migrated, what risks exist, and which strategic direction the program will follow. However, understanding the landscape is not the same as being ready to migrate it. The Prepare phase transforms assessment findings into execution readiness. During Discover, teams identify risks. During Prepare, teams eliminate them. During Discover, teams assess migration feasibility. During Prepare, teams establish migration readiness. The focus now shifts from strategy and assessment toward technical validation, remediation planning, conversion preparation, infrastructure readiness, data cleansing, compatibility analysis, security preparation, and migration execution planning. Most Prepare phase incidents occur when organizations assume that identifying a problem automatically means the problem has been solved. The Prepare phase exists to ensure that every critical dependency, remediation activity, and technical prerequisite has been addressed before conversion activities begin. This is where migration programs move from planning to preparation. Let's deep dive into Prepare phase migration incidents. Prepare phase overview. Establishing system conversion readiness. The Prepare phase converts migration strategy into migration readiness. During this phase, organizations execute detailed readiness activities designed to remove technical blockers, validate assumptions, prepare environments, remediate defects, optimize data, assess integrations, and establish the foundation required for successful SAP S/4HANA conversion execution. The primary objective of the Prepare phase is not to migrate the system. The primary objective is to ensure that the system is capable of being migrated. Organizations perform extensive technical validation activities during this phase, including readiness check remediation, simplification item resolution, custom code analysis, Unicode validation, master data cleansing, infrastructure preparation, security assessments, interface validation, archiving analysis, integration readiness reviews, and conversion rehearsal preparation. Most Prepare phase incidents occur because organizations underestimate the effort required to convert assessment findings into actual remediation activities. Problems identified during Discover frequently remain unresolved, creating blockers that surface during sandbox conversions, technical validations, and migration rehearsals. The Prepare phase serves as the final quality gate before conversion activities begin. Failures here are significantly less expensive than failures during deploy or production cutover.
Prepare phase, functional readiness activities.
Typical business and functional activities performed during the Prepare phase include 1. Migration scope validation, validating legacy functional and process migration scope assumptions. 2. Master data cleansing, cleansing functional location and equipment master data to eliminate data quality issues. 3. Order history review, reviewing maintenance order history quality to prepare for archiving. 4. Transaction integrity, validating notification and measurement document data integrity. 5. Planning and scheduling alignment, reviewing maintenance planning and scheduling configurations. 6. Fiori application readiness, assessing PM and Fiori application readiness and layout catalog profiles. 7. Authorization mapping, reviewing legacy transaction codes and future state authorization requirements. 8. Integration ownership, validating technical interface ownership across connected external systems. 9. Retention governance, defining historical data retention requirements with compliance teams. 10. Analytics dependencies, reviewing legacy reporting and analytics dependencies. 11. Cleansing participation, participating actively in master data remediation and cleansing activities.
Prepare phase, technical readiness activities.
Typical technical activities performed during the Prepare phase include 1. Readiness check remediation, executing SAP readiness check technical remediation steps. 2. Simplification item resolution, resolving pre-conversion simplification item findings. 3. Custom code analysis, running custom code analysis and ATC assessments. 4. Add-on compatibility, performing third-party add-on compatibility validation. 5. Unicode and database verification, executing Unicode and database consistency checks. 6. Infrastructure prep, preparing and provisioning the target migration infrastructure. 7. HANA sizing validation, validating HANA memory sizing assumptions using actual data footprints. 8. Interface validation, reviewing legacy interfaces and RFC destinations. 9. Fiori sizing assessment, performing Fiori front-end gateway and application sizing assessments. 10. Duration risk analysis, analyzing conversion duration risks and DMO phase runtimes. 11. Archiving execution, implementing archiving strategies to shrink the database payload. 12. Security and auth reviews, performing security and authorization reviews. 13. Sandbox environment prep, preparing sandbox conversion environments. 14. Rehearsal planning, conducting migration rehearsal planning and downtime scheduling.
Critical business stakeholders and their roles.
Technical and functional leaders manage the execution of readiness tasks during the Prepare phase. 1. Enterprise Solution Architect, owns the overall migration readiness strategy and technical governance. 2. Basis Lead, owns technical readiness, conversion preparation, and infrastructure validation. 3. PM Functional Lead, owns PM process readiness, master data quality, and business validation activities. 4. Data Migration Lead, owns cleansing, transformation, validation, and migration readiness activities. 5. Security Lead, owns authorization redesign and Fiori access readiness. 6. Compliance and audit teams, approve retention policies, archiving strategies, and regulatory obligations. 7. Maintenance operations manager, validates operational readiness and business continuity requirements. 8. Program sponsor, provides governance oversight and remediation funding decisions.
Key deliverables produced.
These readiness assessments and plans must be compiled during the Prepare phase. These deliverables certify system and hardware readiness before conversion activities begin. 1. Migration Readiness Assessment, documents the overall system compatibility status. 2. Readiness Check Remediation Plan, details the technical correction steps for switch framework blockers. 3. Simplification Item Resolution Plan, outlines the customizing remediations required for standard data tables. 4. Custom Code Remediation Plan, establishes the prioritization and refactoring roadmap for custom ABAP objects. 5. Data Cleansing Strategy, Outlines the master data and transaction data cleanup rules. 6. Archiving and retention strategy. Defines the standard archiving objects and business retention thresholds. 7. Interface readiness assessment. Documents the target state interface configurations. 8. Infrastructure readiness certification. Confirms that hardware has been provisioned and optimized. 9. Security readiness assessment. Outlines target role assignments and catalog mappings. 10. Fiori readiness assessment. Validates launching and transactional speed on the target front-end server. 11. Conversion rehearsal plan. Establishes the sequence and timing of mock conversions. 12. Migration risk register updates. Consolidates all open risks and active mitigations. 13. Cutover preparation plan. Outlines the detailed business blackout and technical execution schedule. 14. Sandbox conversion readiness approval. The formal sign-off allowing technical execution to begin.
Here are the key integration touchpoints validated.
S/4HANA preparation requires technical validation of these key PM integration boundaries. 1. External maintenance systems must be inventoried, documented, and technically validated before conversion. 2. Mobile maintenance platforms require compatibility verification and Fiori alignment assessments. 3. GIS platforms require validation of hierarchy, spatial, and asset integrations. 4. Procurement and vendor systems require readiness validation for maintenance service execution. 5. IoT and SCADA platforms require interface compatibility assessments and technical validation. 6. Analytics platforms require assessment of reporting dependencies and obsolete structures. 7. Middleware platforms require RFC, IDOC, API, and messaging validation before conversion.
Why incidents occur and warning signs.
Most prepare phase incidents occur due to incomplete planning and assessment oversights. These critical warning signs indicate major project risks months before cut over. 1. Siloed scoping. Missing cross-functional planning, procurement, and financial settlement dependencies. 2. Undocumented integrations. Legacy interfaces operating silently without centralized governance or ownership. 3. Data cleansing delays. Postponing master data and transactional data cleanup until conversion testing begins. 4. Unresolved discover findings. Discover phase compatibility blockers and security gaps left unaddressed. 5. Ignored add-ons. Third-party add-on compatibility ignored until maintenance planner blocks are hit. 6. Postponed security redesign. Authorization role remediation and Fiori Launchpad catalog mappings delayed. 7. Large numbers of unresolved SAP readiness check findings and simplification items remain unassigned. 8. Data cleansing activities and sandbox conversion tests are repeatedly postponed. 9. Third-party add-on compatibility remains unknown during the system prep window. 10. Fiori sizing assumptions are based on estimates rather than actual load testing measurements. 11. Undocumented RFC destinations continue to appear during integration dry runs. 12. Migration duration estimates continue increasing due to ignored historical data volumes. 13. Business owners are unable to approve archiving decisions or locate technical owners for custom integrations.
Here is the key message to the prepare phase.
The discover phase identifies migration risks. The prepare phase removes them. Most conversion failures that occur later in the program can be traced back to unresolved readiness issues that should have been addressed during prepare. A migration environment is not ready because assessments have been completed. It is ready only when assessment findings have been remediated, validated, tested, and formally approved. The purpose of the prepare phase is to ensure that conversion activities begin with confidence, not assumptions.
Prepare phase, readiness and preparation incidents.
We systematically analyze the next 22 core technical and functional readiness blockers in the prepare phase. These incidents also represent critical data cleansing, mapping, and technical integration blocks. 23. SAP readiness check identified unsupported PM business functions. 24. Simplification item check failed due to inconsistent PM customizing. 25. Business partner CVI pre-checks fail because PM vendors lacked mandatory fields. 26. Custom PM enhancements caused ATC failures. 27. Maintenance Planner Stack XML generation failed due to incompatible add-ons. 28. Unicode inconsistencies found in long text maintenance notifications. 29. Equipment classification data contained invalid characters blocking migration. 30. Historical maintenance order tables excessively large causing migration duration concerns. 31. Archiving strategy rejected because compliance teams required historical retention. 32. PM interfaces using obsolete IDOC structures identified. 33. Fiori sizing underestimated for maintenance technician usage. 34. RFC destinations for external maintenance systems undocumented. 35. Custom PM authorization roles incompatible with Fiori architecture. 36. Measurement document inconsistencies detected during data validation. 37. Equipment serial number duplication detected across plants. 38. PM order statuses inconsistent due to years of custom updates. 39. Large backlog of failed PM IDOCs discovered. 40. Custom maintenance cost reports dependent on deprecated ECC tables. 41. Maintenance plan scheduling inconsistencies found during cleanup. 42. Technical object hierarchy loops caused validation failures. 43. Plant maintenance LIS obsolescence ignored, breaking legacy PM analytics readiness. 44. MRP live impacts on maintenance component planning undocumented. Let's deep dive into prepare phase migration incidents with Migration Incident 23.
Migration Incident 23. SAP Readiness Check identified unsupported PM business functions.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams must run the SAP Readiness Check to evaluate the legacy landscape against target system constraints. In legacy environments, organizations often activated specific plant maintenance PM and industry solution business functions via the switch framework to enable specialized features. If the SAP Readiness Check identifies any of these active legacy extensions as always off in the target S/4HANA release, the entire technical conversion is strictly hard blocked until a strategic process redesign is established.
Incident classification and relevant SAP note if applicable.
1. Complexity. High critical technical conversion blocker. 2. Migration phase, prepare. 3. Frequency, common in heavily customized or industry-specific landscapes. 4. Primary ownership, enterprise solution architect. 5. Supporting PM functional lead, basis lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. SAP Note 2240359 SAP S/4HANA. Always off business functions.
How teams identify this issue diagnostic dashboard, symptoms and evidence.
How unsupported business functions typically reveal themselves during the program lifecycle. 1. Symptom. The initial SAP Readiness Check dashboard displays a critical red status under the Active Business Functions analytical tile. 2. Red flag. Legacy functional consultants admit to activating experimental switch framework features years ago without documenting actual business usage. 3. Business impact. The project cannot proceed to the sandbox conversion phase, causing immediate timeline delays and forcing unbudgeted process redesign workshops. 4. Detection. The execution of the SAP Readiness Check data collection programs flags specific PM-related extensions as fundamentally incompatible. 5. Technical proof. Transaction SFW5 shows active business functions that are not supported in the target S/4HANA release.
Investigation tools and transactions used.
Use these tools to diagnose business function conflicts and transition paths. 1. RC_collect_analysis_ data. Execute the master data collection program in ECC to generate the payload for the SAP Readiness Check Cloud dashboard. 2. SFW5 switch framework. Audit the legacy ECC environment to definitively confirm which enterprise extensions and industry solutions are actively switched on. 3. Simplification item catalog. Cross-reference the flagged business function against S/4HANA documentation to locate successor functionalities. 4. /SDF/RC_start_check. Run the localized simplification item check to validate the exact technical block preventing the SUM execution. Architect's rule: never assume a business function can be deactivated. Always validate SAP-supported deactivation and remediation options first.
Incident analysis and root cause why this happens.
1. Legacy plant operations teams requested localized industry solutions years ago, which central IT activated without evaluating long-term architectural impacts. 2. Administrators occasionally activated business functions in production just to test features, permanently altering the underlying data dictionary. 3. The program team treats the SAP readiness check as a mere technical formality rather than a strategic business blueprinting prerequisite. 4. Functional leads assume S/4HANA contains a one-to-one mapping for every single legacy ECC feature, completely ignoring SAP's code-based simplification strategy. The root cause is treating irreversible switch framework activations as harmless configuration toggles.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue becomes a hard block during S/4HANA migration because SAP intentionally deprecated legacy redundant features to enforce the simplified digital core. 2. During traditional ECC upgrade projects, organizations often encountered fewer compatibility enforcement checks and therefore deferred remediation of certain third-party components until later project phases. 3. S/4HANA conversion readiness checks identify unsupported software components and can block conversion activities until compatibility issues are resolved through upgrade, replacement, or deinstallation strategies. 4. Legacy ECC systems tolerated a massive footprint of overlapping industry solutions that S/4HANA now natively consolidates or entirely replaces. S/4HANA conversion requires all active business functions to align with supported target state compatibility rules.
Business and program impact.
1. The entire system conversion timeline is suspended, preventing the technical team from building the first S/4HANA sandbox environment. 2. Maintenance operations face the sudden realization that highly specialized legacy features will not exist in the target S/4HANA system. 3. Significant unbudgeted consulting effort is required to re-engineer core maintenance processes to align with standard S/4HANA capabilities. 4. Business trust is damaged early in the program as stakeholders feel they are losing critical functionality rather than gaining modern innovations.
Strategic decision. Evaluating business function mitigation options.
Answer: resolving an always-off compatibility block requires a firm architectural pivot. We must evaluate these 4 strategic options. 1. Standard successor adoption recommended. Redesign the legacy maintenance process to utilize the designated successor functionality defined in the simplification item catalog. 2. Side-by-side extensibility. Relocate the required specialized functionality outside the core ERP by building a custom cloud extension on SAP BTP. 3. Formal SAP assessment. Engage SAP and implementation partners to validate supported remediation and transition options for the identified business function. 4. Greenfield pivot. Abandon the system conversion approach entirely and pivot to a greenfield implementation to cleanly escape the irreversible legacy metadata. Pro tip: do not attempt to bypass the check technically. You must functionally adapt to the new digital core.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target architecture and gets fired if the project stalls indefinitely at the readiness check. 2. Responsible. PM functional lead maps the legacy business process to the new S/4HANA successor functionalities. 3. Consulted. Basis lead SAP consulting services. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must empower the architect to enforce process changes when legacy functions are fundamentally unsupported.
Ownership, who actually fixes it.
Resolving a business function blocker requires structured evaluation and functional process redesign. 1. Basis lead analyzes SAP readiness check findings and identifies incompatible switch framework activations requiring remediation. 2. Enterprise Solution Architect consults the SAP Simplification Item Catalog to identify alternative architectural paths. 3. PM Functional Lead conducts emergency blueprinting workshops with the business to redesign the impacted maintenance workflows. 4. Lead ABAP developer evaluates if any side-by-side extensibility builds are required to bridge the lost functionality.
Who gets blamed versus who owns it?
1. Blamed. Basis team accused of misconfiguring the SAP readiness check or failing to execute the system scan correctly. 2. Blamed. PM functional team accused of failing to identify master data configurations during initial scoping workshops. 3. Actual owner. Enterprise solution architect, accountable for interpreting the compatibility blocks and defining the strategic remediation path. 4. Root cause. Failure to review the S/4HANA simplification item catalog before finalizing the program budget and timeline. Do not blame the basis administrators for delivering the bad news. Functional deprecation is an architectural reality.
How this is actually fixed the right way by a role.
1. Basis lead generates the comprehensive SAP readiness check dashboard to isolate the exact always-off business functions halting the conversion. 2. Enterprise Solution Architect cross-references the blocked functions with standard SAP notes to locate the designated successor capabilities. 3. PM Functional Lead formally deprecates the legacy operational process and documents the new S/4HANA compliant maintenance workflow. 4. Basis Lead executes SAP-supported remediation activities and reruns validation checks to confirm the blocker has been resolved. Clearing an always-off block requires accepting functional change, not applying a technical band-aid.
Common mistakes to avoid what not to do.
1. Do not attempt to manipulate the core database tables to forcibly deactivate a business function. This will permanently corrupt the dictionary. 2. Do not ignore the SAP readiness check results under the false assumption that the Software Update Manager (SUM) will bypass the warnings. 3. Do not promise the business that custom development can perfectly recreate a massive, deprecated industry solution from scratch. 4. Do not delay the execution of the SAP readiness check until the prepare phase is nearly over. It is a day-one necessity.
Follow-up 1. Why are business functions in SFW5 generally irreversible in SAP ECC?
Answer. Many business functions introduce structural and application-level changes that are not designed for standard deactivation after activation. When activated in transaction SFW5, they generate new database tables, append fields to standard structures, and permanently activate background code logic. Attempting to deactivate them manually breaks the core application logic, which is exactly why S/4HANA conversion checks strictly block systems with incompatible active functions.
Follow-up 2. What happens if the SAP readiness check flags a business-critical PM function as always off?
Answer. If an actively used plant maintenance business function is flagged as always off, the technical conversion is completely hard blocked and cannot proceed via the standard Software Update Manager. The Enterprise Solution Architect must perform a deep functional gap analysis to map the legacy process to new, standard S/4HANA capabilities, or design a custom side-by-side extension. The project cannot move into the realize phase until a formal workaround or process redesign is fully validated and signed off by the business.
Follow-up 3 curveball. Can a basis administrator manually manipulate the database to deactivate the business function and bypass the check?
Answer. Manipulating core system tables to forcibly deactivate a business function would place the system outside SAP-supported remediation paths and introduce significant technical and supportability risks. Doing so can leave orphan data structures and active system calls pointing to unsupported logic, creating significant conversion and supportability risks. Architects must strictly prohibit this dangerous shortcut and enforce proper functional remediation to clear the SAP readiness check block legally.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization run the RC_collect_analysis_data program on your production environment immediately upon project kickoff to generate the definitive SAP readiness check dashboard. Recommendation 2. What successful projects do? Reliability elite projects execute simplification item checks early and prepare to identify and prioritize hard conversion blockers before remediation planning begins. Recommendation 3. What should be validated? Revalidation. Physically validate the functionality of the designated S/4HANA successor processes with the business to ensure no critical operational gaps remain. Recommendation 4. What should be governed? Responsibility. Enforce a strict governance freeze on the legacy ECC environment, preventing unauthorized activation of new SFW5 business functions during the migration program.
Migration Incident 24. Simplification item check failed due to inconsistent PM customizing.
During the prepare phase of an SAP ECC to SAP S/4HANA conversion, project teams execute the simplification item check (SI check) via report/SDF/RC_ start_ check to identify compliance errors before conversion. A major blocker occurs when the check fails due to inconsistent or unremediate plant maintenance PM customizing, particularly around maintenance order settlement profiles and investment measures. If legacy ECC configurations contain obsolete settlement-related configuration or unsupported accounting assignments, the SI check can trigger a conversion blocker requiring remediation.
Incident classification and relevant SAP note if applicable.
1. Complexity. High critical technical conversion blocker. 2. Migration phase. Prepare. 3. Frequency. Common in older landscapes. 4. Primary ownership. Enterprise solution architect. 5. Supporting PM functional lead, FICO lead, basis lead. 6. Business ownership. Maintenance planning lead or financial controller. 7. Relevant SAP note. SAP Note 2399707 Simplification Item Check.
How teams identified this issue. Diagnostic dashboard. Symptoms and evidence.
How inconsistent PM customizing typically reveals itself during the program lifecycle. 1. Symptom. The simplification item check report returns a hard red return code equals 7 for the EAM and PM functional area during execution. 2. Red flag. Finding legacy PM order types that are still assigned to obsolete cost elements or merged general ledger accounts. 3. Business impact. The basis team cannot generate the target stack XML in Maintenance Planner, completely halting the conversion schedule. 4. Detection. Standard pre-conversion scans flag configuration inconsistencies in the PM settlement profiles or investment parameters. 5. Technical proof. The /SDF/RC_ start_ check results identify PM settlement or investment measure configuration inconsistencies requiring remediation before conversion.
Investigation tools and transactions used.
Use these tools and transactions to identify PM customizing inconsistencies and mapping blocks. 1. /SDF/RC_ start_ check simplification item check. Run the master pre-conversion check report to identify and isolate specific EAM customizing blocks. 2. OK07 define settlement profile. Audit legacy PM settlement profiles to verify if their allocation structures point to deprecated cost elements. 3. OIOA define PM order types. Review investment profile assignments and settlement-related parameters used by capital maintenance orders. 4. SPRO SAP reference IMG. Navigate the legacy customizing path to locate and remediate the inconsistent PM and FICO integration parameters.
Incident analysis and root cause why this happens.
1. Decades of custom PM configuring resulted in ghost or inactive order types that are no longer used by the business, but remain active in configuration. 2. The FICO team merged or decommissioned general ledger accounts in ECC without updating the corresponding PM settlement profiles. 3. Functional architects treat the SI check as a purely technical basis task, ignoring their module-specific configuration cleansing duties. 4. The program team fails to remediate PM and FICO configuration inconsistencies identified during readiness assessments. The root cause is treating custom PM customizing as an isolated functional setup rather than an active cross-modular integration.
Why this issue appears only during an ECC to S/4HANA migration.
1. The failure is unique to S/4HANA migrations, because S/4HANA conversion requires legacy customizing to comply with simplification item validation rules before technical conversion can proceed. 2. Traditional ECC upgrades generally involved fewer simplification-specific compatibility validations. 3. Legacy ECC environments often retained inactive or outdated PM configuration that becomes visible during S/4HANA readiness validation. 4. S/4HANA conversion requires remediation of unsupported or inconsistent customizing before upgrade execution. S/4HANA conversion requires remediation of incompatible PM customizing before technical conversion can proceed.
Business and program impact.
1. The entire system conversion timeline is suspended, preventing the technical team from building the first S/4HANA sandbox environment. 2. Significant unbudgeted consulting effort is required to re-engineer core maintenance processes to align with standard S/4HANA capabilities. 3. Decline in program momentum as functional leads are pulled away from standard process mapping to troubleshoot legacy customizing errors. 4. Increased risk of post-go-live processing errors if configuration inconsistencies are not remediated before conversion.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise solution architect, the person who owns the target architecture and gets fired if legacy configuration blocks the build phase. 2. Responsible. PM functional lead assesses and remediates PM settlement and investment measure configuration inconsistencies. 3. Consulted. FICO lead basis lead. 4. Informed. Program sponsor, steering committee, maintenance planning lead. Steering committees must empower the architect to enforce process changes when legacy functions are fundamentally unsupported.
Ownership. Who actually fixes it?
Resolving PM customizing inconsistencies requires structured remediation and cross-functional validation. 1. Enterprise solution architect evaluates the target integration architecture and defines the required PM customizing remediation parameters. 2. PM functional lead audits legacy PM order types, identifies inconsistent settlement profiles, and executes the required customizing cleanup. 3. FICO lead maps legacy PM profiles to S/4HANA compliant account assignments and settlement structures. 4. Basis lead executes validation checks and confirms remediation of all reported simplification item findings.
Who gets blamed versus who owns it?
1. Blamed. Basis team accused of misconfiguring the SAP readiness check or failing to execute the system scan correctly. 2. Blamed. PM functional team. Business blames functional PM consultants for failing to identify configuration inconsistencies during remediation activities. 3. Actual owner. Enterprise solution architect, accountable for interpreting the compatibility blocks and defining the cross-functional PM and FICO remediation path. 4. Root cause. Failure to treat the PM and FICO integration boundaries as a critical migration prerequisite during early scoping workshops. Configuration blockers require cross-functional remediation, not blame assignment.
How this is actually fixed the right way by a role.
1. Enterprise solution architect performs a formal integration impact assessment, mapping legacy PM investment measures to target S/4HANA financial ledgers. 2. PM functional lead reviews the inventory of legacy settlement profiles and validates their alignment with the new S/4HANA chart of accounts. 3. FICO lead remediates settlement-related accounting assignments and validates compatibility with S/4HANA financial structures. 4. Basis lead reruns simplification checks and validates closure of all PM-related findings. Clearing SI check blockers requires configuration remediation and validation before conversion.
Common mistakes to avoid. What not to do.
1. Do not ignore legacy PM order types that are no longer used by the business. If they remain active in configuration, the check will still validate their deprecated settlement profiles. 2. Do not attempt to bypass SI check blocks by manually editing system tables in transaction SE16N, as this violates standard SAP support policies. 3. Do not delay the alignment of PM settlement profiles with the new FICO chart of accounts until the build phase begins. 4. Do not assume that a standard ECC settlement profile will natively run in S/4HANA without verifying its compatibility with new asset accounting.
Follow-up 1. What is the main architectural purpose of the S/4HANA Simplification Item Check (SI check?
Answer: the standard simplification item check is a pre-conversion check report designed to verify whether a legacy ECC system's customizing and transactional data are fully compatible with S/4HANA's simplified codebase. It executes multiple automated checks across various functional areas, including plant maintenance and asset accounting, to identify any inconsistencies that would cause data corruption or system dumps during the technical conversion. The check generates a detailed, red-flagged log of hard blocks that must be systematically resolved before the Software Update Manager (SUM) is permitted to initiate the actual upgrade.
Follow-up 2. How can an inconsistent PM order settlement profile cause the SI check to fail?
Answer: an inconsistent PM order settlement profile causes the SI check to fail because it references settlement-related accounting assignments that are no longer valid for the target S/4HANA configuration model. The SI check identifies these inconsistencies as conversion blockers requiring remediation before upgrade execution. Common examples include obsolete settlement profiles, unsupported investment measure assignments, or legacy account mappings that no longer align with the target S/4HANA design. Remediation requires the PM functional lead and FICO lead to review the affected configuration and align it with the approved target state architecture.
Follow-up 3. Curveball. How would you handle a situation where a legacy PM order type points to an investment profile that is no longer supported in new asset accounting?
Answer: if a legacy PM order type is assigned to an unsupported investment profile, the PM functional lead must work with the FICO lead to assess the incompatibility and determine its impact on the target S/4HANA settlement architecture. The team must define a S/4HANA compliant replacement investment profile and include its remediation in the conversion preparation plan. They should then validate that the proposed replacement supports the required settlement and capitalization processes before conversion activities proceed. This ensures the simplification item check findings are resolved without introducing settlement issues later in the migration lifecycle.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run the standard pre-conversion check report /SDF/RC_. Start check early in the prepare phase to identify all EAM-specific customizing blocks. Recommendation 2. What successful projects do? Reliability elite projects conduct recurring PM and FICO remediation reviews to resolve simplification item findings before sandbox conversion. Recommendation 3. What should be validated? Revalidation: validate S/4HANA customizing compatibility assumptions using representative PM order samples and cross-module financial reconciliation analysis. Recommendation 4. What should be governed? Responsibility: require formal sign-off of PM settlement and investment measure remediation before entering the build phase.
Migration Incident 25. Business Partner CV projects failed for PM vendors.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the data migration team executes the mandatory business partner customer vendor integration (CVI) checks. A major crisis occurs when the ProCheck report fails because legacy plant maintenance PM vendors lack mandatory fields required by the target business partner data model. Legacy maintenance departments commonly created local contractors, calibration vendors, and one-time service providers with incomplete master data, omitting postal codes, tax IDs, and country keys. This data debt creates significant CVI remediation requirements that must be addressed before the conversion can proceed through the planned migration path.
Incident classification and relevant SAP note if applicable.
1. Complexity: high technical data quality blocker. 2. Migration phase prepare. 3. Frequency common in older ECC landscapes. 4. Primary ownership enterprise solution architect. 5. Supporting basis lead PM functional lead procurement lead master data lead. 6. Business ownership maintenance operations manager. 7. Relevant SAP note. SAP Note 22659093, SAP S/4HANA Business Partner Approach, or CVI.
How teams identify this issue diagnostic dashboard, symptoms and evidence.
How unconverted PM vendors typically reveal themselves during the program lifecycle. 1. Symptom. The CVI ProCheck report returns hard error logs, stating that hundreds of legacy PM-specific vendors cannot be synchronized with the business partner model. 2. Red flag. Finding legacy maintenance vendor master records with incomplete address structures and missing tax identification numbers. 3. Business impact. Conversion planning activities are delayed while critical vendor master data issues are analyzed and remediated. 4. Detection. Executing the standard CVI ProCheck reports in the legacy ECC system reveals critical validation errors across the PM vendor account groups. 5. Technical proof. Error logs in the CVI upgrade check cockpit show that mandatory business partner fields are missing for active PM vendors in table LFA1.
Investigation tools and transactions used.
Use these tools and transactions to identify PM vendor data quality and synchronization failures. 1. CVI_PreCheck CVI ProCheck report. Run the master validation report to identify specific data gaps across all active maintenance vendors. 2. MDS_load_cockpit synchronization cockpit. Monitor the real-time execution and error logs of the background vendor to partner synchronization runs. 3. BP business partner. Validate whether converted maintenance vendors successfully receive the correct supplier and business partner roles post-migration. 4. SE16N table browser. Query the legacy vendor master table LFA1 to identify records with missing postal codes, tax details, or inconsistent name structures.
Incident analysis and root cause why this happens.
1. Legacy maintenance departments historically operated with decentralized vendor creation privileges, bypassing corporate data standards. 2. The change management and data profiling activities did not validate local PM-specific vendors during the initial discover phase assessments. 3. The technical team assumes that CVI is a purely financial task, ignoring the critical dependence of PM external service operations on vendor masters. 4. Legacy ECC configurations allowed PM material reservations and service purchase orders to execute using incomplete vendor records. The root cause is treating the business partner conversion as an isolated financial activity rather than a cross-modular operational requirement.
Why this issue appears only during an ECC to S/4HANA migration.
1. The issue is exclusive to S/4HANA migrations because S/4HANA mandates the business partner model, removing the legacy separate customer and vendor tables. 2. In legacy ECC, incomplete vendor master records were tolerated by the database, allowing standard PM03 external service operations to execute. 3. S/4HANA conversion preparation includes CVI validation activities that identify vendor master data issues requiring remediation before business partner synchronization and production conversion activities can be completed successfully. 4. Legacy partner function relationships should be validated during business partner conversion to ensure they remain correctly represented in the target S/4HANA environment. S/4HANA's unified data model refuses to tolerate the localized, dirty vendor records that ECC permitted for decades.
Business and program impact.
1. Project timelines expand significantly as critical vendor master data issues delay conversion readiness and sandbox validation activities. 2. Significant unbudgeted manual effort is spent by the procurement and maintenance teams to enrich thousands of legacy vendor records. 3. Maintenance response times increase during integration testing, as automated PM03 external service purchase requisitions fail to trigger. 4. Stakeholder confidence may decline if data quality issues are discovered late in the migration lifecycle. Unresolved vendor synchronization issues can disrupt external maintenance procurement processes and increase operational risk during migration.
Impact on technicians and maintenance teams.
How failed business partner conversions directly disrupt the daily operations of field crews and planners. 1. Planners may encounter issues assigning external service operations to work orders when required vendor relationships are not successfully synchronized, paralyzing repairs that require specialized third-party contractors. 2. Technicians cannot view accurate manufacturer or supplier details on equipment records, delaying the sourcing of proprietary spare parts. 3. Warranty management processes may require additional remediation if vendor-related partner relationships are not correctly represented after conversion. 4. Shop floor crews experience extended asset downtime while waiting for procurement to manually bypass system errors and secure external labor. When external maintenance services are blocked, internal technicians are left waiting in front of broken equipment.
Strategic decision. CVI data cleansing strategy.
Answer: selecting the target CVI transformation approach requires a firm architectural decision to prevent operational PM-dependent maintenance execution from stalling at go-live. 1. Enterprise-wide CVI program recommended. Treat vendor conversion as a cross-functional transformation initiative spanning PM, MM, finance, and customer service. 2. Procurement-owned approach. Allow procurement to manage conversion activities while PM validates only critical maintenance vendors. 3. PM critical vendor first. Prioritize vendors tied to maintenance execution, warranties, calibration services, and regulatory inspections. 4. Big Bang cleansing. Clean every vendor simultaneously regardless of business relevance, accepting high project overhead and manual cleansing cycles. Pro tip: do not let CVI be handled solely by the finance team. Without PM involvement, local maintenance vendors will be ignored.
CVI remediation decision matrix.
A standard analytical matrix to determine the correct technical or business action based on vendor assessment findings. 1. Active PM vendor with missing data. Execute manual data enrichment in ECC to populate missing postal codes, tax IDs, and bank details before running CVI. 2. Inactive PM vendor greater than 2 years. Flag the vendor for deletion and execute standard ECC archiving to remove it from the conversion scope. 3. Duplicate local contractors. Perform deduplication in ECC, merging redundant vendor records into a single surviving entity before S/4HANA synchronization. 4. Vendor is also a customer. Execute customer or vendor linkage in ECC, ensuring both records share identical address data to create a unified business partner. Architect's rule: prune and archive obsolete maintenance vendors before finalizing the CVI synchronization scope.
Governance and accountability RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect owns the target state architecture and overall conversion readiness strategy. 2. Responsible. Master Data Lead coordinates CVI pre-checks and executes the mass synchronization. 3. Consulted PM Functional Lead Procurement Lead. 4. Informed. Program Sponsor Steering Committee. Maintenance Operations Manager. Steering committees must explicitly assign PM vendor cleansing tasks. Otherwise, both PM and procurement will assume the other is handling it.
Ownership: who actually fixes it.
Resolving CVI-related master data validation failures requires joint technical, business, and data governance remediation during the prepare phase. 1. Enterprise Solution Architect assesses the impact of CVI validation blocks on legacy PM-dependent processes and designs the remediation strategy. 2. Master Data Lead analyzes CVI pre-check error logs to isolate which specific maintenance vendors failed validation and validates business partner role assignments such as supplier financial accounting and supplier purchasing after synchronization. 3. PM Functional Lead evaluates the active maintenance vendor list, identifying which local contractors must be retained. 4. Procurement Lead plans the manual data enrichment process, coordinating with external vendors to collect missing tax and address details.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of building defective maintenance orders that failed to generate purchase requisitions. 2. Blamed. Procurement team accused of abandoning the plant maintenance department by failing to migrate local contractors. 3. Actual owner. Enterprise Solution Architect, accountable for approving migration strategy without validated business partner conversions. 4. Root cause. Failure to treat CVI as a holistic, cross-modular enterprise master data project during the discover phase. Business partner conversion success depends on data governance, business ownership, and cross-functional remediation, not just technical execution.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect performs a formal integration impact assessment, identifying every maintenance plant and vendor account group affected by CVI. 2. Master Data Lead analyzes the legacy vendor master repository to isolate the exact data blocks in transaction CVI_pre-check. 3. PM Functional Lead reviews the legacy PM vendor list, identifying obsolete records for archiving and active records for immediate address enrichment. 4. Procurement Lead plans the mass update campaign utilizing standard tools like MASS in the legacy ECC system to enrich the missing data. Clearing CVI pre-check blockers requires data cleansing and functional validation before conversion begins.
Common mistakes to avoid what not to do.
1. Do not restrict your CVI readiness checks exclusively to standard procurement account groups. Always include local PM contractors. 2. Do not migrate obsolete or unused legacy maintenance vendors, as this dramatically increases the manual cleansing workload. 3. Do not attempt to fix massive CVI synchronization errors during UAT. This must be resolved programmatically during the prepare phase. 4. Do not bypass S/4HANA mandatory field configurations to force dirty vendor data through the synchronization cockpit.
Follow-up 1. Why do PM external service operations fail if the CVI synchronization is incomplete?
Answer. External service operations in plant maintenance rely on purchasing info records and active vendor masters to determine external labor costs and routing. In S/4HANA, if the business partner is not fully synchronized with the underlying vendor role due to a CVI failure, the PM process may experience issues generating or processing the required purchase requisition until the underlying business partner synchronization issues are resolved. Consequently, this can prevent the procurement team from issuing purchase orders, potentially stalling critical maintenance tasks, and delaying the dispatch of third-party contractors.
Follow-up 2. How does the CVI conversion impact equipment and functional location partner functions?
Answer. Equipment and functional locations use partner functions to maintain relationships with manufacturers, suppliers, contractors, and service providers. During the CVI process, vendor records are converted into the business partner model required by S/4HANA. If vendor records contain data quality issues or cannot be successfully synchronized, the associated partner function relationships may require remediation before they can be fully utilized in the target system. Project teams should therefore validate maintenance-related partner assignments during the prepare phase and resolve identified business partner conversion issues before conversion activities proceed.
Follow-up 3 Curveball. What happens if a legacy maintenance vendor is also a customer, but their data is inconsistent?
Answer. When a maintenance vendor also exists as a customer, the CVI process evaluates both records as part of the business partner conversion approach. If address information, tax identifiers, banking details, or other key attributes are inconsistent across the related records, the conversion team must assess and remediate the discrepancies before synchronization activities can be completed successfully. The master data lead should coordinate a customer or vendor harmonization exercise in ECC to establish an approved target data set and validate the relationship before executing the final business partner conversion.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization. Run the CVI_pre-check program early in the prepare phase to identify and quantify PM vendor master data quality issues. Recommendation 2. What successful projects do? Reliability elite projects execute recurring PM procurement master data remediation workshops to resolve CVI-related vendor issues before sandbox conversion begins. Recommendation 3. What should be validated? Revalidation. Validate S/4HANA customizing compatibility assumptions using representative PM order samples and cross-module financial reconciliation analysis. Recommendation 4. What should be governed responsibility implement centralized business partner governance through MDG and prohibit local creation of maintenance vendors without mandatory validation controls.
Migration Incident 26. Custom PM enhancements caused ATC failures.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams run the ABAP Test Cockpit ATC to analyze the compatibility of custom code. A major blocker occurs when custom plant maintenance PM enhancements, such as custom user exits in legacy enhancement spots or direct database reads on simplified tables, cause critical ATC check failures. Because these custom enhancements contain legacy database calls, obsolete programming patterns, or S/4HANA compatibility issues, significant remediation may be required before production conversion activities can proceed safely.
Incident classification and relevant SAP note if applicable.
1. Complexity. High critical custom code remediation risk. 2. Migration phase, prepare. 3. Frequency, very common in older ECC landscapes. 4. Primary ownership. Custom code lead custom code remediation workstream. 5. Supporting. Lead ABAP developer PM functional lead enterprise solution architect basis lead. 6. Business ownership. Maintenance operations manager. 7. Relevant SAP note. SAP note 1912445. ABAP custom code migration for SAP S/4HANA.
How teams identified this issue. Diagnostic dashboard. Symptoms and evidence.
How incompatible legacy custom enhancements typically reveal themselves during the program lifecycle. 1. Symptom. The custom code remediation workstream is blocked as standard target readiness variant runs fail to complete or return thousands of hard syntax errors. 2. Red flag. Finding legacy user exits that manipulate database fields directly instead of using standard object-oriented baddies. 3. Business impact. Sandbox conversion runs are delayed as developers spend weeks manually refactoring legacy ABAP code blocks. 4. Detection. The ABAP Test Cockpit ATC execution flags critical red alert syntax violations in custom EAM and PM packages. 5. Technical proof. ATC findings identify custom PM objects that reference obsolete database structures, deprecated function modules, unsupported modification techniques, or inefficient database access patterns that require remediation for S/4HANA readiness.
Investigation tools and transactions used.
Use these tools to identify incompatible custom code, modifications, and S/4HANA remediation requirements. 1. ATC ABAP Test Cockpit. Run the master quality check using the target readiness check variant to identify incompatible custom PM code. 2. SCI SAP Code Inspector. Execute detailed code inspections on specific custom PM packages to analyze syntax quality, performance risks, and remediation requirements identified during ATC analysis. 3. SE80 ABAP Development Workbench. Navigate legacy user exits and custom program code to locate and refactor deprecated database calls. 4. SPAU Repository Objects Modification. Monitor and adjust standard PM objects that were customized via direct modifications in the legacy system. Architect's rule. Prioritize ATC findings based on business usage and S/4HANA impact before allocating remediation effort.
Incident analysis and root cause why this happens.
1. Developers built custom PM enhancements over decades using direct database hacks and obsolete user exits to bypass standard SAP validation layers. 2. Assessment teams treat code compatibility as a simple compilation check, neglecting to run comprehensive semantic readiness scans. 3. Functional leads fail to align custom enhancements with standard S/4HANA extensibility patterns during early scoping. 4. The program team fails to establish a functional owner for each custom enhancement, leading to blind remediation of unused code. The root cause is treating custom code as a simple migration task rather than a strategic technical debt cleanup.
Why this issue appears only during an ECC to S/4HANA migration.
1. While custom code quality issues can exist in any SAP transformation initiative, S/4HANA migration introduces additional compatibility requirements that expose previously hidden technical debt. 2. Many legacy reporting and data access patterns require reassessment because S/4HANA introduces compatibility views, CDS-based consumption models, and simplified application structures. 3. Syntax and database operations that executed successfully on ECC frequently require redesign or optimization to comply with HANA and S/4HANA development standards. 4. S/4HANA enforces a completely new extensibility concept, making direct modification techniques completely obsolete. S/4HANA database optimizations will not tolerate legacy database shortcuts.
Business and program impact.
1. Custom code remediation costs escalate rapidly as ABAP teams spend months rewriting legacy code. 2. The overall S/4HANA program timeline slips, delaying downstream functional testing and training. 3. High risk of post-go-live processing errors, performance issues, or functional disruptions if incompatible custom code is not remediated. 4. Decline in program momentum as technical debt consumes resources meant for functional innovations. Unremediated custom code can become a major source of production defects, performance issues, and support challenges after go-live.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect owns the target state architecture and overall conversion readiness strategy. 2. Responsible. Custom code lead ABAP developer collaborate to analyze, prioritize, and execute custom code remediation. 3. Consulted PM functional lead basis lead. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must fund custom code remediation early. Technical debt discovered late becomes one of the largest sources of S/4HANA delays.
Ownership. Who actually fixes it?
Resolving custom code issues requires structured evaluation and programmatic cleanup. 1. Enterprise Solution Architect defines the target state custom code remediation strategy and approves process standardizations. 2. Custom code lead categorizes all custom objects based on standard ATC findings and actual system usage logs. 3. Lead ABAP developer refactors legacy custom code, replacing legacy database selections with standard APIs. 4. PM functional lead validates whether legacy custom enhancements remain business relevant or can be replaced by standard S/4HANA functionality.
Who gets blamed versus who owns it?
1. Blamed. ABAP developers accused of writing over complicated legacy custom programs that are too difficult to remediate. 2. Blamed. PM functional team business blames functional consultants for an unreadable equipment structure. 3. Actual owner. Enterprise Solution Architect, accountable for interpreting the compatibility blocks and defining the strategic remediation path. 4. Root cause. Failure to treat custom code remediation as a strategic technical debt cleanup during the discover phase of the project. Legacy custom code challenges require proactive governance, ownership, and remediation planning across technical and business teams.
How this is actually fixed the right way by a role.
1. Custom code lead runs a comprehensive ABAP test cockpit scan with the S/4HANA readiness check variant in the early sandbox. 2. PM functional lead reviews legacy PM enhancements like custom logic and user exit IW010009 to verify if standard functionality can replace them. 3. Lead ABAP developer refactors custom enhancements, replaces obsolete APIs, remediates ATC findings, and executes unit testing. 4. Custom code lead reruns ATC readiness checks and validates closure of all PM-related custom code findings before conversion testing begins. Successful custom code remediation requires prioritization, refactoring, testing, and business validation before conversion.
Common mistakes to avoid what not to do.
1. Do not assume legacy custom PM code will run on HANA just because it compiles without errors in ECC. 2. Do not attempt to remediate legacy Z programs that have not been executed in transaction SD03N for over 12 months. 3. Do not directly modify standard database tables. Always utilize standard BADIs or BTP side-by-side extensions. 4. Do not delay custom code remediation activities. until functional user acceptance testing begins.
Follow-up 1. How does the ABAP Test Cockpit ATC identify S/4HANA custom code incompatibilities?
Answer: the ABAP Test Cockpit ATC executes automated static code scans using specialized S/4HANA readiness variants to identify syntax obsolescence and database access violations. It parses the custom Z namespace for deprecated statements, direct table reads on simplified structures, and legacy function module calls. The tool generates a prioritized, red-flagged log of findings, isolating the exact line of code that requires modification. Leveraging ATC early ensures that developers have a precise, structured remediation roadmap before beginning active system conversion.
Follow-up 2. What is the risk of keeping legacy user exits like IW010009 during an S/4HANA conversion?
Answer: legacy user exits inside standard enhancements like IW010009 frequently rely on tightly coupled assumptions about ECC data structures, enhancement frameworks, and processing logic that may require redesign during S/4HANA migration. During migration, changes to application structures, enhancement frameworks, and data access patterns can cause legacy user exits to behave differently than they did in ECC, creating processing errors, unexpected behavior, or long-term supportability challenges. To mitigate these risks, developers must systematically refactor these legacy enhancements into standard baddies to ensure long-term stability and upgrade compatibility.
Follow-up 3. Curveball. Why must custom PM database access patterns be reviewed during an S/4HANA migration?
Answer: custom PM programs often contain database access logic that was optimized for legacy ECC data models. During an S/4HANA migration, developers must review these access patterns because application structures, compatibility views, performance characteristics, and recommended access methods may differ from ECC. Even when the underlying tables continue to exist, custom code should be validated against SAP simplification guidance and ATC findings to ensure performance, supportability, and long-term compatibility with the target S/4HANA release.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run a complete, standard custom database and ABAP Test Cockpit ATC audit during the discover phase to catalog every active Z table, custom index, and background data synchronization job in use. Recommendation 2. What successful projects do? Reliability elite projects cross-reference ABAP Test Cockpit ATC findings with SD03N transaction usage statistics to systematically eliminate unused custom objects. Recommendation 3. What should be validated? Revalidation: formally validate whether each legacy custom enhancement still provides unique business value in S/4HANA before committing development budget. Recommendation 4. What should be governed? Responsibility: require local plant business process owners to formally approve and justify the retention of every single custom object before migration development begins.
Migration Incident 27. Maintenance Planner Stack XML generation failed.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the technical team runs the maintenance planner to generate the compulsory target stack metadata file. A critical failure occurs when the maintenance planner refuses to generate the stack XML due to incompatible or unsupported third-party plant maintenance add-ons installed on the legacy ABAP stack. This technical blockage represents a hard stop for the system conversion, completely preventing the software update manager from initiating the upgrade execution.
Incident classification and relevant SAP note if applicable.
1. Complexity: high critical software component block. 2. Migration phase prepare. 3. Frequency: common in older landscapes. 4. Primary ownership: enterprise solution architect. 5. Supporting basis lead, PM functional lead, lead ABAP developer. 6. Business ownership, program sponsor. 7. Relevant SAP note. SAP note 2214409 SAP S/4HANA. Compatible add-ons.
How teams identify this issue. Diagnostic dashboard. Symptoms and evidence.
How uninventoried third-party add-ons typically reveal themselves during the program lifecycle. 1. Symptom: The Maintenance Planner utility fails to generate the mandatory stack XML file, returning a critical blocking error stating that an active add-on has no valid upgrade path. 2. Red flag. Finding third-party software components such as prefixes like /VES/ or /PROM/ in the system status list that do not appear in the standard S/4HANA compatibility catalog. 3. Business impact. Conversion planning and sandbox activities are delayed while incompatible software components are assessed and remediation strategies are defined. 4. Detection. Standard readiness check and maintenance planner scans flag incompatible third-party software components active on the legacy ABAP stack. 5. Technical proof. The Software Update Manager SUM logs or maintenance planner error outputs show block codes for specific third-party namespaces during metadata verification.
Investigation tools and transactions used.
Use these tools to identify active software components, release levels, and add-on compatibility status. 1. SAINT Add-on Installation Tool. Audit all installed third-party software components, release levels, and active namespaces on the legacy ABAP stack. 2. SPAM Support Package Manager. Verify support package levels and check for any unresolved imports or uncommitted add-on patches. 3. Maintenance Planner. Scan the legacy system's active component registry and attempt to generate the target stack XML file to identify blocking software. 4. /sdf/s4h_add-on_check S/4HANA add-on compatibility check. Run the specialized SAP report to programmatically verify which active add-ons are formally certified for the target release. Architect's rule. Do not trust a vendor's verbal claim that their add-on is S/4HANA compliant. Always verify it using /sdf/s4h_add-on_check.
Incident analysis and root cause why this happens.
1. Project managers assume all third-party add-ons installed on ECC will natively run on S/4HANA or can be bypassed during the technical conversion. 2. Silos between the basis team and PM functional leads prevent third-party components from being formally cross-referenced against the S/4HANA compatibility list. 3. Legacy add-on vendors have gone out of business or stopped supporting standard SAP integration upgrades, leaving the code orphaned on the stack. 4. The program team fails to execute standard software component scans during the early project preparation stages. The root cause is treating add-on compatibility as a minor upgrade step rather than a critical project milestone.
Why this issue appears only during an ECC to S/4HANA migration.
1. The failure is unique to S/4HANA migrations because S/4HANA conversion readiness checks identify unsupported software components and can block conversion activities until compatibility issues are resolved through upgrade, replacement, or deinstallation strategies. 2. During many traditional ECC upgrade projects, organizations often encountered fewer compatibility enforcement checks and therefore deferred remediation of certain third-party components until later project phases. 3. Maintenance Planner validates the target software stack against SAP's compatibility repository and refuses to generate the required stack XML when unsupported add-ons lack an approved conversion path. 4. Unsupported add-ons may contain technical dependencies that are incompatible with the target S/4HANA release, requiring upgrade, replacement, or removal before conversion activities can proceed. S/4HANA conversion tooling enforces software component compatibility checks to ensure that unsupported add-ons are addressed before system conversion begins.
Business and program impact.
1. The program faces significant delays as incompatible add-ons must be assessed, remediated, upgraded, or replaced before sandbox conversion activities can proceed. 2. Unbudgeted software licensing and consulting fees are incurred to purchase S/4HANA certified add-on upgrades. 3. High risk of losing specialized plant floor functionalities if an unsupported add-on must be deinstalled without a functional replacement. 4. Decline in program momentum as the technical team scrambles to resolve metadata errors instead of executing build activities. An incompatible add-on represents a complete system blockage. It is the ultimate progress stopper.
Strategic decision. Evaluating S4HANA add-on mitigation paths.
Answer: resolving the unsupported add-on blocker requires selecting a viable S4HANA compliant application architecture. We must evaluate these four strategic options. 1. Upgrade to certified version. Secure the S4HANA certified version of the third-party add-on from the vendor, accepting any upgrade and licensing fees. 2. Retire and standardize. Deinstall the incompatible add-on entirely and redesign the business processes to utilize standard S4HANA Fiori applications. 3. Rebuild on SAP BTP. Decommission the unsupported add-on and rebuild its highly specialized PM features as side-by-side cloud extensions on SAP BTP. 4. Delay and redesign. Pause the conversion timeline to allow the vendor to complete their S4HANA certification, or completely redesign the PM system landscape. Pro tip: if an add-on is orphaned by its vendor, use the migration as a business case to rebuild the capability on BTP.
Add-on compatibility decision matrix.
A standard analytical matrix to determine the correct add-on remediation path during the discover phase. 1. Vendor certified version exists. Purchase and apply the S4HANA certified upgrade path before executing the conversion. 2. Legacy custom or SciClo app. Decommission the outdated agentry add-on and migrate users to cloud-native SAP Service and Asset Manager. 3. Standard PM functionality exists. Formally deinstall the legacy add-on using standard installation tools and adopt standard Fiori apps. 4. No S4HANA certification planned. Rebuild the custom or third-party features as a side-by-side extension on SAP BTP to keep the core clean. Architect's rule: do not let unsupported software components stall your migration. Identify, assess, and remediate them during the discover phase.
Governance and accountability, RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect owns the target state architecture and overall conversion readiness strategy. 2. Responsible. Basis lead and lead ABAP developer collaborate to analyze software component compatibility, validate vendor upgrade paths, and identify custom code dependencies on unsupported add-ons. 3. Consulted. PM functional lead, software vendor. 4. Informed. Program sponsor, steering committee, business process owners. Steering committees must assign clear ownership for add-on compatibility assessment early in the program because unsupported software components can halt conversion activities before the first sandbox build begins.
Ownership, who actually fixes it.
Resolving add-on compatibility blockers requires coordinated technical analysis, vendor engagement, and architecture decision-making before conversion activities can continue. 1. Basis lead reviews SAINT, executes compatibility checks, and attempts to generate the stack XML. 2. PM functional lead coordinates with software vendors to verify S4HANA certification roadmaps. 3. Lead ABAP developer identifies custom code dependencies on the legacy add-ons namespaces. 4. Enterprise Solution Architect evaluates whether the add-on should be upgraded, replaced with standard functionality, or rebuilt as an extension.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of failing to identify the technical blocking components before the project officially kicked off. 2. Actual owner. Enterprise Solution Architect, accountable for approving the migration strategy without validated add-on compatibility check results. 3. Root cause. Failure to run standard pre-conversion checks or consult the S4HANA compatibility matrix during the early scoping phase. Add-on compatibility failures are governance problems, not basis problems, because unsupported software should be identified and addressed during early migration planning.
How this is actually fixed the right way by a role.
1. Basis lead runs the specialized report /SDF/S4H_add-on_ check to identify every active legacy add-on namespace. 2. PM functional lead contacts the third-party software vendor to secure the official S4HANA compatibility release statement and upgrade installation files. 3. Lead ABAP developer reviews the ABAP repository for any custom Z programs that reference legacy add-on namespaces to prevent custom code dumps. 4. Enterprise Solution Architect establishes the target migration strategy, validating whether the add-on should be upgraded, retired, or rebuilt. Every unsupported add-on must have a documented remediation strategy before the first sandbox conversion begins.
Common mistakes to avoid: what not to do.
1. Do not attempt to execute a brownfield system conversion without first generating and validating the target stack XML file. 2. Do not assume a third-party add-on is compatible with S/4HANA simply because the vendor claims their standard software is HANA-ready. 3. Do not manually delete or manipulate add-on namespace tables in the database to bypass maintenance planner blocks, as this permanently corrupts the dictionary. 4. Do not delay the audit of installed software components, SAINT, until after the project SOW has been signed and resources are mobilized.
Follow-up 1. Why is the generation of a stack XML file the ultimate gating blocker for a S/4HANA conversion?
Answer: the stack XML is a compulsory system metadata file generated exclusively by the maintenance planner that defines the exact target software component list, support packages, and database upgrade paths. The Software Update Manager (SUM) strictly requires this file as its core configuration blueprint during the uptime phase. If the legacy system hosts an active, incompatible third-party add-on, Maintenance Planner will refuse to generate the XML, completely blocking the technical conversion. Attempting to bypass this gating step is impossible, making add-on compatibility a non-negotiable discover phase assessment task.
Follow-up 2. What is the process for formally deinstalling an unsupported add on an ECC pre-conversion?
Answer: formally deinstalling an unsupported add-on requires utilizing the standard SAP add-on installation tool, Transaction SAINT. The basis lead must verify if the specific add-on vendor has delivered an official deinstallation tool or package for that release. If supported, the deinstallation process removes the software component according to the vendor-supported procedure and updates the system component registry. The exact treatment of custom tables, historical data, and namespaces depends on the vendor's deinstallation package and retention strategy.
Follow-up 3. Curveball. How would you handle a situation where a business-critical PM add-on is incompatible with S/4HANA and the vendor has gone out of business?
Answer: if a mission-critical add-on is completely orphaned and cannot be upgraded, the enterprise solution architect must design an immediate side-by-side transition. The team must first determine whether a supported deinstallation procedure exists. If no supported removal path is available, the organization may need to redesign the migration approach, isolate the functionality, or evaluate alternative implementation strategies before conversion can proceed. Once resolved, the development team rebuilds the specialized features as a secure, decoupled cloud extension on SAP BTP or standard Fiori apps, keeping the core ERP clean.
Real implementation tips and best practices: the 4 R's.
Recommendation 1. What should be done? Realization run a complete, standard SAINT and support package manager audit during the discover phase to catalog every active third-party namespace and add on. Recommendation 2. What successful projects do? Reliability elite projects execute early target stack XML generation tests in Maintenance Planner before signing the final partner statement of work. Recommendation 3. What should be validated? Revalidation validate legacy custom code references against the target upgraded add-on namespaces in a sandbox environment to identify custom code breakage. Recommendation 4. What should be governed? Responsibility require formal commercial and technical commitment from the third-party add-on vendor regarding their S/4HANA release roadmap before cutover planning begins.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, We will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 28. Unicode and CodePage inconsistencies detected in PM long text data.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams must run Unicode validation checks against database tables. A major blocker occurs when legacy plant maintenance PM notification long texts, stored in compressed cluster table STXL under text object QMEL, contain inconsistent CodePage indicators or invalid characters. If left unremediated, the conversion process will experience significant database migration runtime increases, or output corrupted, unreadable safety instructions to the plant floor post-migration.
Incident classification and relevant SAP note if applicable.
1. Complexity. Medium database data integrity failure. 2. Migration phase, prepare. 3. Frequency, common in older ECC landscapes. 4. Primary ownership, basis lead. 5. Supporting, PM functional lead, data migration lead, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. SAP note 11222341. Report UMG underscore adjust underscore STXL to adjust long texts in STXL table.
How teams identify this issue. Diagnostic dashboard, symptoms and evidence.
How legacy long text inconsistencies typically reveal themselves during the program lifecycle. 1. Symptom. Legacy maintenance notification long text display corrupted characters when loaded in sandbox test systems. 2. Red flag. Database preparation reports flag table STXL for having non-Unicode characters in fields assigned to Unicode-only languages. 3. Business impact. Planners and safety leads cannot read historical notification descriptions, potentially bypassing critical equipment hazard warnings. 4. Detection. Executing pre-conversion database consistency checks identifies raw binary formatting corruption in the compressed text clusters of table STXL. 5. Technical proof. Database analysis of standard table STXL using table verification utilities reveals invalid codepage keys.
Investigation tools and transactions used.
Use these tools to identify active software components, legacy modifications, and S/4HANA database level requirements. 1. UMG underscore adjust underscore STXL. Run the specialized database utility to programmatically repair and adjust codepage inconsistencies in compressed text clusters. 2. I18N internationalization screen. Review and configure active system codepages, language packs, and character set parameters on the legacy system. 3. SE16N table browser. Query standard text header table STXH and text cluster table STXL to isolate corrupted notification objects. 4. SARA archive administration. Verify if legacy notification archiving runs can permanently decommission obsolete records to reduce the table repair scope. Architect's rule. Identify and remediate Unicode inconsistencies early because corrupted long text data can significantly delay database conversion activities and impact business-critical historical records.
Incident analysis and root cause. Why this happens.
1. Historical data entered through legacy interfaces, external uploads, multiple language environments, and inconsistent codepage configurations introduce text encoding irregularities into long text records over time. 2. The legacy database is configured on a single code page SCP architecture, which allowed inconsistent binary bytes to be saved without validation. 3. Database administrators focus entirely on table space sizes and system memory during preparation, ignoring the contents of compressed cluster tables like STXL. 4. The custom data loading utilities bypass standard SAP script APIs and attempt to inject unvalidated text payloads directly into the system. The root cause is failing to identify and remediate legacy codepage inconsistencies and corrupted long text data before conversion preparation activities begin.
Why this issue appears only during an ECC to S/4HANA migration.
1. While data quality issues can exist in any SAP transformation initiative, S/4HANA migration introduces mandatory Unicode and data consistency requirements that expose previously hidden long text encoding problems. 2. Many legacy ECC systems accumulated long text records across multiple languages, codepages, and historical data entry methods that require validation before Unicode-compliant conversion processing can occur. 3. System conversion activities perform extensive table conversion and optimization activities, which can experience significant runtime increases when processing millions of redundant historical records. 4. Modern Fiori-based text viewers rely on standard web rendering engines that will output unreadable gibberish or crash if legacy codepage variables are inconsistent. S/4HANA conversion activities require Unicode-compliant data structures and can expose long-standing text encoding inconsistencies that remained hidden in legacy ECC systems.
Business and program impact.
1. Project timelines expand significantly as the technical team is forced to pause sandbox dry runs to execute emergency database repairs on table STXL. 2. Maintenance directors lose access to decades of valuable notification history and equipment repair notes, crippling active reliability engineering. 3. Additional, unbudgeted consulting costs are incurred to hire senior basis and database specialists to manually reconstruct corrupted text clusters. 4. Stakeholder confidence may decline if data quality issues are discovered late in the migration lifecycle. Unremediated Unicode inconsistencies can compromise historical maintenance records, increase conversion effort, and create long-term data quality risks in S/4HANA.
Impact on technicians and maintenance teams.
How failed Unicode conversions directly disrupt the daily operations of field crews and planners. 1. Technicians open urgent breakdown work orders and find that the safety instructions and hazard warnings display as unreadable garbage characters. 2. Planners cannot review previous shift notes or equipment failure descriptions, forcing them to duplicate diagnostic efforts from scratch. 3. Field crews lose real-time visibility into historical repair notes on mobile screens, increasing overall operational and safety risks. 4. Plant floor supervisors are forced to spend hours manually verifying safety procedures on paper, reducing overall shift wrench time and productivity.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Enterprise Solution Architect owns the target state architecture and overall conversion readiness strategy. 2. Responsible. Basis lead extracts profiles and runs UMG_adjust_STXL database repairs. 3. Consulted. PM Functional Lead Data Migration Lead. 4. Informed. Program Sponsor. Steering Committee. Maintenance Operations Manager. Steering committees must fund Unicode remediation activities early because unresolved long text inconsistencies can delay database conversion and testing activities.
Ownership. Who actually fixes it?
Resolving Unicode inconsistencies requires structured database analysis, data remediation, and business validation before conversion activities proceed. 1. Enterprise Solution Architect defines the target state Unicode conversion and database cleansing strategy. 2. Basis lead analyzes the SAP readiness check findings, executes table scans, and runs UMG_adjust_STXL in transaction SC38. 3. PM Functional Lead validates whether legacy long texts are functionally critical or can be archived using standard archiving. 4. Data Migration Lead coordinates the manual data cleanup for highly critical, corrupted assets.
Who gets blamed versus who owns it?
1. Blamed. PM Functional Team, accused of building defective maintenance notifications that fail to display text on screen. 2. Actual Owner. Enterprise Solution Architect, accountable for approving the migration strategy without validating database Unicode and CodePage compatibility. 3. Root Cause. Failure to treat Unicode and long text database preparation as a critical, mandatory technical prerequisite in the discover phase. Do not blame maintenance users for corrupted long texts when the underlying Unicode and CodePage inconsistencies were never assessed during migration preparation.
How this is actually fixed the right way by a role.
1. Basis lead executes report UMG_adjust_STXL in the legacy ECC environment to analyze and programmatically repair corrupted text blocks. 2. PM Functional Lead identifies active maintenance notifications to prioritize the repair of active operational text. 3. Lead ABAP developer analyzes custom programs that directly read or process long text data and remediates any logic that is incompatible with Unicode-compliant text handling standards. 4. Basis Lead reruns the database consistency check and validates that table STXL has 0 remaining CodePage inconsistencies. Successful Unicode remediation requires data correction, validation, testing, and business sign-off before database conversion activities begin.
Common mistakes to avoid. What not to do.
1. Do not attempt to execute a system conversion into S/4HANA without first validating database Unicode and CodePage consistency. 2. Do not manually delete rows in table STXL using direct database updates. Always utilize standard SAP repair utilities like UMG_adjust_STXL. 3. Do not assume that all historical notifications must be migrated into memory. Utilize standard archiving to shrink the table size. 4. Do not allow users to copy-paste unvalidated rich text formatting into standard text editors without implementing modern security controls.
Follow-up 1. Why does S/4HANA strictly require a Unicode database environment, and how does this affect plant maintenance?
Answer: S/4HANA is built on a single, modernized codebase that strictly supports only Unicode-compliant database architectures to enable real-time, global multi-language processing. In legacy ECC systems running on non-Unicode single-code page SCP setups, text was represented using localized single-byte characters. For plant maintenance, this transition is critical because long texts for technical objects and notifications are heavily prone to encoding corruption if they contain special symbols or multi-byte characters. Ensuring Unicode compatibility pre-conversion is non-negotiable to prevent data conversion crashes during the downtime window.
Follow-up 2. What is table STXL, and how does the report UMG_adjust_STXL remediate it?
Answer: Table STXL is a standard SAP script cluster table that stores compressed long text associated with numerous SAP business objects, including maintenance notifications and work orders. The specialized repair utility UMG_adjust_STXL scans the raw compressed clusters, identifies legacy codepage inconsistencies, and programmatically adjusts the text headers to align with standard Unicode structures. Executing this report prevents the system from triggering severe read errors or outputting corrupted text on screen. This is a critical technical database preparation task that must be executed weeks before the target conversion date.
Follow-up 3 Curveball. Why is a legacy non-Unicode direct table extraction of long texts completely broken after an S/4HANA conversion?
Answer: In legacy non-Unicode ECC systems, developers frequently wrote custom ABAP utilities that bypass standard function modules like read_text to extract long text directly from the compressed raw data in table STXL. After an S/4HANA conversion, these legacy direct access programs frequently fail or produce incorrect results because they rely on assumptions about non-Unicode text structures that no longer hold true after conversion. When the legacy code executes, the text interpretation logic may return unreadable characters, incomplete text output, or runtime errors because the underlying encoding assumptions are no longer valid. To resolve this, architects must systematically refactor these legacy extractions to consume standard SAP script APIs or modern S/4HANA compliant OData services.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: run the standard Unicode consistency check and pre-conversion reports early in the prepare phase to identify codepage anomalies in table STXL. Recommendation 2. What successful projects do? Reliability elite projects execute Unicode readiness assessments and remediation activities early in the migration lifecycle to isolate database-level risks before conversion execution begins. Recommendation 3. What should be validated? Revalidation: validate long text readability assumptions using representative samples of historical PM notifications containing multi-language and special characters. Recommendation 4. What should be governed? Responsibility: enforce strict, centralized data entry guidelines and browser-based standard editors to prevent users from introducing unvalidated, corrupted formatting characters post-go-live.
Migration Incident 29. Equipment classification data contained invalid characters blocking migration.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams often run into major roadblocks when legacy equipment classification data contains invalid, non-printable, or corrupted hexadecimal characters. Over decades, legacy ECC environments accumulate millions of characteristics and classes assigned to technical objects stored in tables like AUSB and KSSK. When executing pre-conversion checks, these unvalidated special characters in classification fields trigger severe data consistency failures, completely halting the S/4HANA pre-conversion preparation.
Incident classification and relevant SOP, note if applicable.
1. Complexity. High critical master data cleansing risk. 2. Migration phase, prepare. 3. Frequency, common in older ECC landscapes. 4. Primary ownership, data migration lead. 5. Supporting, PM functional lead, basis architect, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SOP note. SOP note 2470720 classification. Consistency check for classification tables.
How teams identify this issue, diagnostic dashboard, symptoms and evidence.
How legacy classification data quality issues typically reveal themselves during the program lifecycle. 1. Symptom. Classification consistency checks identify equipment or functional location characteristics containing invalid, non-printable, or unsupported character values. 2. Red flag. Characteristic values contain unexpected symbols, unreadable text strings, or invalid hexadecimal characters that do not conform to approved business value standards. 3. Business impact. The overall database pre-conversion readiness remains incomplete, blocking the basis team from completing the final sandbox prep runs. 4. Detection. Standard classification consistency checks and data quality profiling activities identify invalid values stored within equipment and functional location classification records. 5. Technical proof. Analysis of classification tables AUSP and KSSK reveals characteristic values containing invalid characters, corrupted text strings, or inconsistent formatting patterns.
Investigation tools and transactions used.
Use these tools and transactions to identify classification data corruption and inconsistent characteristics. 1. RC class_check consistency check for classification. Run the standard SOP validation report to scan, analyze, and isolate invalid characters in active classification tables. 2. CL02 class manager. Audit class definitions, structure parameters, and characteristic assignments associated with PM technical objects. 3. CL20N assign class to object. Validate individual equipment or functional location class allocations and characteristic value consistency. 4. SE16N table browser. Query standard classification tables AUSP and KSSK directly to identify orphaned records or invalid hex data bytes. Architect's rule. Never begin classification data migration without first validating characteristic value quality and eliminating invalid character records from active classifications.
Incident analysis and root cause why this happens.
1. PM technical object characteristics allowed unvalidated manual text entries where users entered special characters or local symbols. 2. Legacy interfaces or custom upload programs pushed raw, unsanitized external data streams directly into standard classification tables. 3. The organization lacked active master data governance MDG rules to restrict and validate characteristic values at the database entry point. 4. Project teams treat classifications as secondary transactional attributes, failing to perform deep database profiling during the discover phase. The root cause is failing to enforce classification data quality controls and characteristic value validation standards across legacy systems.
Why this issue appears only during an ECC to S4HANA migration.
1. The issue becomes highly visible during S4HANA migration because pre-conversion validation activities perform deeper consistency checks against classification and master data structures than are typically executed during daily ECC operations. 2. Legacy ECC systems often contain invalid characteristic values that remain undetected because standard business transactions continue to function despite underlying data quality issues. 3. Migration readiness checks and data cleansing activities analyze classification records at scale, exposing invalid characters, formatting inconsistencies, and corrupted values that must be corrected before conversion. 4. S4HANA migration programs require higher master data quality standards, making historical classification data defects significantly more visible than they were in legacy ECC environments.
Business and program impact.
1. Project schedules are delayed during the prepare phase, as the data team is forced to resolve classification data validation failures before continuing sandbox conversions. 2. Maintenance schedulers experience operational gaps as standard equipment search helps in Fiori applications fail to return critical technical object characteristic values. 3. Unbudgeted manual cleansing and validation cycles must be added to the project path to address extensive classification defects. 4. Data integration pipelines to external technical databases or asset performance networks are compromised by unremediate special characters.
Governance and accountability. RACI model.
Migration strategy decisions require clear ownership because they influence every subsequent workstream. 1. Accountable. Data migration lead, the person who owns the final master data readiness milestone and gets fired if unremediate classification records stall the conversion runs. 2. Responsible. PM functional lead reviews the flagged invalid equipment classifications and identifies the correct business values. 3. Consulted. Basis lead. Lead ABAP developer. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must fund classification data remediation activities early because unresolved characteristic value inconsistencies can delay migration readiness validation and conversion activities.
Ownership. Who actually fixes it?
Resolving classification data quality issues requires coordinated data cleansing, business validation, and migration governance before conversion activities can proceed. 1. Data migration lead extracts the complete list of corrupted classification records from tables AUSP and KSSK. 2. PM functional lead reviews the invalid characteristic values and defines the correct business values or mapping rules. 3. Lead ABAP developer develops controlled remediation utilities and validation programs to identify, correct, and revalidate invalid classification values in accordance with SAP-supported practices. 4. Basis lead supports classification data validation activities and assists with execution of standard consistency check and remediation utilities where required.
Who gets blamed versus who owns it?
1. Blamed. PM functional team accused of failing to validate equipment characteristic structures during early scoping. 2. Blamed. Data migration team accused of building defective upload scripts that failed to import valid classification records. 3. Actual owner. Data migration lead, accountable for assessing classification data quality and ensuring that invalid characteristic values are remediate before migration execution. 4. Root cause. Failure to prioritize classification data profiling and quality validation during the early discover phase of the project. Do not blame maintenance users for invalid classification values when the underlying data quality controls and validation processes were never enforced across legacy systems.
How this is actually fixed the right way by a role.
1. Data migration lead executes standard validation report RC class _ check in the legacy ECC system to identify all active classification errors. 2. PM functional lead reviews the output, identifying obsolete classes for archiving and defining the valid character mappings for active equipment. 3. Lead ABAP developer utilizes database repair programs like RMCLRECO or custom SQL scripts to programmatically purge non-printable characters. 4. Basis lead reruns the database consistency check and validates that table AUSP has 0 remaining corrupt characters. Successful classification data remediation requires cleansing, validation, testing, and business sign-off before migration execution activities begin.
Common mistakes to avoid. What not to do.
1. Do not attempt to migrate legacy PM classifications without first running a comprehensive consistency check RC class _ check. 2. Do not manually delete rows in table AUSP using unsupported direct database queries, as this permanently corrupts the standard SAP class indices. 3. Do not assume that all legacy characteristic values are accurate simply because they display without errors in legacy GUI transactions. 4. Do not delay the cleanup of legacy classification tables until after the sandbox conversion is completed.
Follow-up 1. Why is legacy classification data particularly prone to corruption in older SAP ECC landscapes?
Answer: legacy ECC landscapes often lacked centralized data entry controls, allowing users to manually enter free text values into characteristic fields. Additionally, legacy data load scripts often injected raw data directly into table AUSP without using standard SAP APIs like BAPI_OBJCL_create. This allowed non-printable control characters, unescaped delimiters, and invalid hexadecimal values to be stored in the database. While traditional ECC systems could tolerate these corrupt data bytes, migration validation and conversion activities frequently identify them as data quality defects that must be remediated before conversion can proceed successfully.
Follow-up 2. What is the report RC_check, and how does the data migration team utilize it?
Answer: the standard utility RC_check is a pre-conversion database consistency check designed specifically to identify errors in SAP's classification tables. The data migration lead executes this report to scan tables AUSP and KSSK, isolating orphan allocations, invalid characteristic records, and corrupted characters. The report outputs a detailed list of error logs, allowing the technical team to prioritize their cleanup activities. Running this check early in the prepare phase ensures that all database-level inconsistencies are resolved before executing the technical conversion.
Follow-up 3. Curveball. Why must invalid classification values be remediated before S/4HANA migration execution begins?
Answer: invalid classification values must be remediated before migration execution because they can cause consistency check failures, data load interruptions, reporting inaccuracies, and downstream application errors during conversion activities. While legacy ECC transactions may continue to function despite underlying data quality issues, migration readiness checks analyze classification records more rigorously and expose corrupted or unsupported values. Resolving these defects before conversion reduces migration risk and improves long-term master data quality in the target S/4HANA environment.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization run standard validation report RC_check early in the prepare phase to identify and quantify legacy equipment classification errors. Recommendation 2. What successful projects do reliability, execute, approved SAP consistency check, and remediation utilities in a sandbox environment to identify and correct corrupted classification records before conversion. Recommendation 3. What should be validated? Revalidation validate classification data accuracy by running end-to-end PM class searches in standard Fiori apps within the sandbox system to ensure no performance lag exists. Recommendation 4. What should be governed? Responsibility implement centralized master data governance MDG protocols to ensure that all future PM classifications are validated against strict business rules before saving.
Migration incident 30. Historical maintenance order tables causing migration duration concerns.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams execute their first sandbox conversion and frequently discover that decades of historical plant maintenance transactional data cause the conversion runtime to drastically exceed the approved downtime window. Massive volumes of completed maintenance orders, confirmations, and status records bottleneck the software update manager (SUM) during database migration. If not remediated through advanced table splitting or pre-conversion archiving, this prolonged processing duration creates critical concerns regarding cutover viability.
Incident classification and relevant SAP note if applicable.
1. Complexity. High data volume management and migration duration risk. 2. Migration phase, prepare. 3. Frequency, very common in mature ECC landscapes. 4. Primary ownership, enterprise solution architect or data migration lead. 5. Supporting, PM functional lead, basis lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, SAP note 20400002. System conversion downtime optimization for large tables.
How teams identified this issue diagnostic dashboard, symptoms and evidence.
How excessive historical maintenance order data typically reveals itself during migration preparation activities. 1. Symptom. Initial sandbox migration duration estimates indicate that conversion processing times significantly exceed approved project timelines and technical rehearsal objectives. 2. Red flag. Data volume assessments reveal tens of millions of completed maintenance orders and status records retained for purely historical purposes. 3. Business impact. The business rejects the proposed production cutover schedule because the required system blackout window is too long to sustain operations. 4. Detection. The Software Update Manager SUM stalls for hours on specific PM transaction tables during the DMOPARC-ONV_UPG execution phase. 5. Technical proof. SUM downtime evaluation logs identify tables such as AUFK, AFIH, AFRU, and JEST as massive single-table bottlenecks requiring advanced splitting.
Investigation tools and transactions used.
Use these tools to identify historical data bottlenecks, archiving opportunities, and migration duration risks. 1. SUM downtime evaluation logs. Analyze the phase-by-phase execution times in the Software Update Manager to identify exactly which PM tables caused the conversion bottleneck. 2. DB02 Database Performance Monitor. Review table sizes, growth trends, and storage consumption across maintenance order history tables before sandbox runs. 3. SARA Archive Administration. Assess available PM archiving objects and identify completed business records eligible for immediate removal. 4. RSTBHFS3 Table Splitting Tool. Evaluate the feasibility of generating table splitting rules for massive PM tables to optimize R3 load parallel processing. Architect's Rule. Measure actual conversion runtimes in SUM logs before deciding whether to archive data or scale up the migration hardware.
Incident analysis and root cause why this happens.
1. Organizations retain decades of completed maintenance orders because no formal data retention or archiving policy was ever enforced. 2. Basis teams execute the initial sandbox conversion using default SUM parameters without pre-configuring table splitting for massive PM tables. 3. Project teams focus purely on functional configuration, postponing data volume management decisions until sandbox runtimes force the issue. 4. Legacy ECC environments continue accumulating maintenance status history table JEST for years without periodic data cleansing. The root cause is failing to proactively manage historical data growth and migration duration risks before conversion testing begins.
Why this issue appears only during an ECC to S/4HANA migration.
1. Large data volumes can exist for years without creating visible business disruption or latency in daily ECC operations. 2. System conversion activities must sequentially process, validate, and migrate historical records, transforming a benign storage issue into a critical runtime bottleneck. 3. The SUMDMO engine processes tables row by row or via parallel background jobs, extremely large. Unsplit tables throttle the entire database migration engine. 4. Migration rehearsal schedules, cutover planning, and environment refresh activities become significantly more difficult when conversion runtimes expand uncontrollably. Migration programs transform historical data volume from a cheap storage concern into a critical conversion duration risk.
Business and program impact.
1. Migration rehearsal cycles require significantly longer execution windows, delaying overall project progress and exhausting the basis team. 2. Additional infrastructure and database resources must be rapidly provisioned to support optimized, parallel conversion testing activities. 3. Project schedules become volatile because conversion duration estimates fluctuate heavily based on table processing constraints. 4. Executive stakeholders lose confidence in migration timelines when projected cutover runtimes exceed previously approved blackout assumptions. Excessive historical data directly increases migration effort, testing duration, and overall program complexity?
Strategic decision. Evaluating conversion duration optimization.
Answer: reducing migration duration concerns requires selecting an appropriate technical management strategy before the next sandbox cycle. 1. SUM table splitting configuration. Implement advanced R3 load table splitting rules for massive PM tables to optimize parallel conversion processing. 2. Aggressive pre-migration archiving. Execute an immediate ECC archiving project using transaction SARA to permanently remove historical orders before conversion. 3. Downtime optimized DMO strategy. Invest in advanced near-zero downtime NZDT approaches and upscale migration server hardware. 4. Accept increased conversion duration. Retain all historical records natively, accept longer processing timelines, and renegotiate the production blackout window. The most successful programs combine aggressive table splitting with deep pre-migration archiving to slash conversion runtimes.
Conversion duration optimization matrix.
A standard framework used to evaluate and resolve maintenance history conversion bottlenecks. 1. Huge table bottleneck detected in SUM. Implement SUM table splitting RSTBHFS3 and increase R3 load parallel background processes. 2. Obsolete historical data. Execute aggressive pre-conversion archiving via SARA to physically shrink the conversion payload. 3. Required for regulatory compliance. Retain according to legal obligations but isolate into specific storage partitions if supported. 4. Mission-critical 24/7 operations. Reassess migration architecture and evaluate advanced downtime minimization approaches NZDT or ZDO. Technical conversion runtimes must be governed by mathematical optimization, not hardware scaling alone.
Governance and accountability RACI model.
Historical data decisions require clear accountability because they affect migration timelines, compliance requirements, and reporting capabilities. 1. Accountable. Enterprise Solution Architect owns the target state migration readiness strategy and gets fired if the downtime window blows out. 2. Responsible. Basis lead executes sandbox conversions, analyzes SUM downtime logs, and configures table splitting optimization. 3. Consulted. Data migration lead, PM functional lead, compliance stakeholders. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Steering committees must formally approve historical data retention decisions because they directly influence migration duration and program cost.
Ownership, who actually fixes it.
Resolving migration duration concerns requires coordinated technical analysis and business retention decisions. 1. Data migration lead assesses data volume reduction opportunities and quantifies migration duration impacts. 2. Basis lead analyzes SUM downtime logs, calculates optimal R3 load processing parameters, and configures table splitting for massive tables. 3. Data migration lead performs detailed table size analysis in DB02 and identifies historical records eligible for archiving. 4. PM functional lead validates operational retention requirements and confirms which historical records remain business critical. 5. Enterprise Solution Architect approves the target state historical data strategy and updates the cutover schedule.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of failing to provision adequate hardware to run the conversion at an acceptable speed. 2. Blamed. PM functional team accused of retaining excessive historical maintenance records that throttle the database engine. 3. Actual owner. Enterprise Solution Architect, accountable for ensuring that data volume management and table splitting are incorporated into migration readiness planning. 4. Root cause. Failure to assess historical data growth, retention requirements, and conversion duration impacts during early migration planning activities. Historical data accumulation is a governance issue, but conversion processing speed is a basis optimization responsibility.
How this is actually fixed the right way by a role.
1. Basis lead analyzes SUM downtime logs and generates table splitting rules for bottleneck tables AUFK, JEST to maximize R3 load parallel processing. 2. Data migration lead quantifies the migration duration impact of historical records and defines a targeted ECC archiving scope. 3. PM functional lead validates legal, operational, and warranty requirements for historical maintenance data retention before archiving execution. 4. Basis lead executes approved archiving objects through transaction SARA to physically shrink the conversion payload before the next sandbox cycle. Successful remediation combines business retention decisions, controlled archiving, and advanced SUM table splitting.
Common mistakes to avoid what not to do.
1. Do not execute sandbox conversion cycles using default SUM parameters when dealing with massive legacy PM data volumes. 2. Do not begin conversion testing before understanding the migration duration impact of large maintenance history tables. 3. Do not execute mass archiving activities without validating regulatory, audit, and operational retention requirements. 4. Do not postpone table splitting and downtime optimization discussions until cutover planning has already started.
Follow-up 1. How does SUM table splitting specifically reduce S/4HANA migration downtime for PM tables?
Answer. During an S/4HANA conversion, the Software Update Manager SUM extracts, validates, and imports database tables into the target HANA structure. If a massive PM table like AUFK or JEST is processed as a single block, it throttles the conversion engine to a single active thread, creating a massive runtime bottleneck. By configuring SUM table splitting, the basis lead instructs the R3 load engine to break the table into smaller, equally sized packages. This allows the system to process the historical data in parallel across multiple background jobs, dramatically shrinking the overall migration downtime window.
Follow-up 2. Why is transaction SARA frequently utilized to rescue failing migration schedules?
Answer. Transaction SARA is SAP's standard archive administration tool used to execute approved data archiving processes. When initial sandbox conversions reveal unacceptable runtimes, migration teams utilize SARA to systematically identify and permanently archive historical PM records like closed maintenance orders in ECC before the next conversion cycle. Removing millions of obsolete rows physically shrinks the database payload, directly reducing the required validation and import times during the SUM downtime phase.
Follow-up 3 curveball. Why should maintenance history retention decisions be treated as a business decision rather than a technical decision?
Answer. Maintenance history retention decisions must be treated as business decisions because only stakeholders can determine the ongoing operational, warranty, and regulatory value of historical records. While technical teams can quantify storage consumption and execute table splitting, they cannot independently delete records to optimize migration durations. Effective migration programs combine technical runtime analysis with formal business retention approvals, ensuring the organization does not sacrifice critical audit traceability just to shorten a weekend cutover window.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization. Perform detailed SUM downtime log analysis immediately after the first sandbox conversion to quantify processing bottlenecks on massive PM tables. Recommendation 2. What successful projects do? Reliability. Successful programs configure advanced R3 load table splitting rules for tables like JEST and AUFK before executing subsequent mock conversion cycles. Recommendation 3. What should be validated? Revalidation. Validate historical data retention requirements with compliance, audit, maintenance, and reporting stakeholders before executing emergency pre-conversion archiving. Recommendation 4. What should be governed? Responsibility. Establish formal information lifecycle management policies to prevent uncontrolled historical data growth from sabotaging the final cutover schedule.
Migration incident 31. Archiving strategy rejected because compliance teams required historical retention.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the project team identifies historical plant maintenance PM data archiving as the primary method for reducing database size and improving migration duration. However, the proposed archiving initiative is halted when compliance, audit, and records management stakeholders reject the historical data reduction scope. Because no formally approved enterprise retention policy exists, stakeholders disagree on which maintenance orders, notifications, technical history records, and asset maintenance documents can legally be archived. As a result, migration duration optimization activities stall and the program enters a governance deadlock.
Incident classification and relevant SOP, note if applicable.
1. Complexity. High data retention governance failure. 2. Migration phase, prepare. 3. Frequency, common in highly regulated industries. 4. Primary ownership, enterprise solution architect. 5. Supporting, compliance lead, data migration lead, PM functional lead, basis lead. 6. Business ownership, records management officer. 7. Relevant SOP note, not applicable, governance and compliance retention policy conflict.
How teams identify this issue, diagnostic dashboard, symptoms and evidence.
How data retention governance conflicts typically reveal themselves during migration preparation activities. 1. Symptom. The proposed historical data archiving initiative is suspended after compliance stakeholders reject the recommended retention scope. 2. Red flag. Different business units provide conflicting requirements regarding maintenance order retention, notification history, equipment records, and audit evidence. 3. Business impact. Migration duration reduction activities cannot proceed because no approved historical data retention policy exists. 4. Detection. Steering committee reviews identify unresolved disagreements between technical, operational, legal, and compliance stakeholders. 5. Technical proof. Historical maintenance records that have not been accessed for years remain active because no approved archival disposition decision has been authorized.
Investigation tools and documentation used.
Use these tools and governance artifacts to evaluate historical data retention requirements. 1. SARA Archive Administration. Assess archivable maintenance records and estimate potential database volume reduction. 2. SOP Information Lifecycle Management, ILM. Evaluate retention rule enforcement and legal hold requirements. 3. Corporate Records Retention Policy. Review enterprise record retention obligations and disposal procedures. 4. Regulatory and audit documentation. Validate legal, compliance, environmental, safety, and operational retention requirements. Architect's Rule. Never archive business records solely to improve migration performance without approved retention authorization from compliance stakeholders.
Incident analysis and root cause why this happens.
1. The organization never established a formally approved enterprise retention policy covering maintenance history records. 2. Business units independently define historical data requirements without centralized governance or legal review. 3. Migration teams prioritize conversion duration optimization, while compliance teams prioritize regulatory defensibility and audit readiness. 4. Data retention requirements are discovered late in the migration lifecycle after archiving proposals have already been developed. The root cause is failing to establish an approved enterprise data retention policy before migration data volume reduction activities begin.
Why this issue appears only during an ECC to S/4HANA migration.
1. Historical data retention disagreements can remain hidden for years while legacy systems continue operating normally. 2. S/4HANA migration introduces data volume reduction initiatives that force organizations to formally decide what historical information must remain active. 3. Migration duration optimization activities frequently require archiving discussions that expose unresolved governance and compliance gaps. 4. The program must balance migration efficiency, regulatory obligations, audit requirements, and operational reporting needs before conversion can proceed. Migration programs transform historical data retention from an administrative concern into a strategic governance decision.
Business and program impact.
1. Migration duration optimization initiatives are delayed while retention requirements are reviewed and approved. 2. Additional project costs are incurred as larger databases require more extensive testing, infrastructure, and conversion processing. 3. Executive stakeholders lose confidence in migration planning assumptions when key governance decisions remain unresolved. 4. Project timelines become increasingly difficult to predict because historical data reduction activities cannot proceed. Unresolved retention governance issues can delay migration programs even when the technical archiving solution is already available.
Strategic decision. Evaluating historical data retention options.
Answer: resolving the governance deadlock requires selecting an approved enterprise approach for managing historical maintenance information. 1. Archive according to approved retention rules. Define and approve retention periods before executing historical data archiving activities. 2. Retain all historical records. Preserve all legacy maintenance history and accept increased migration duration and infrastructure requirements. 3. Implement SAP Information Lifecycle Management. Apply retention controls, legal holds, and governed archival processes using SAP ILM. 4. Establish a historical reporting repository. Retain historical information outside operational processing while preserving audit and reporting accessibility. The best migration strategy is the one that satisfies regulatory obligations while maintaining acceptable conversion timelines.
Historical data retention decision matrix.
A standard framework used to evaluate maintenance history retention requirements. 1. Required by law or regulation. Retain according to documented statutory obligations. 2. Required for active operations. Retain because the information supports ongoing maintenance decision-making. 3. Required for audit or investigation support. Retain according to approved governance requirements. 4. No demonstrated business or compliance value. Archive according to approved retention and disposition procedures. Retention decisions must be based on documented business and compliance requirements rather than personal preference.
Governance and accountability RACI model.
Historical data retention decisions require clear accountability because they directly affect compliance exposure and migration planning. 1. Accountable. Enterprise Solution Architect owns the target state data retention strategy and migration readiness plan. 2. Responsible. Compliance lead evaluates regulatory obligations and approves historical data retention requirements. 3. Consulted. Data Migration Lead, PM Functional Lead. Legal Counsel. 4. Informed. Program Sponsor, Steering Committee, Maintenance Operations Manager. Migration programs cannot proceed with large-scale archiving activities until compliance ownership and retention approval are formally established.
Ownership, who actually fixes it.
Resolving retention governance conflicts requires coordinated business, legal, and migration decision-making. 1. Enterprise Solution Architect establishes the target state historical data strategy and facilitates stakeholder alignment. 2. Compliance lead evaluates statutory obligations, audit requirements, and retention risk exposure. 3. Data Migration Lead quantifies migration duration impacts and estimates the benefits of approved archiving activities. 4. PM Functional Lead validates which maintenance history records remain operationally relevant to the business.
Who gets blamed versus who owns it.
1. Blamed. Data migration team accused of failing to reduce database size and migration duration. 2. Blamed. Compliance team accused of unnecessarily blocking migration optimization activities. 3. Actual owner. Enterprise Solution Architect, accountable for ensuring that retention requirements are defined and approved before migration planning assumptions are finalized. 4. Root cause. Failure to establish an approved enterprise data retention policy before historical data reduction initiatives began. Governance deadlocks occur when organizations attempt to archive data before defining who owns retention decisions.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect establishes a cross-functional retention governance working group and defines decision authority. 2. Compliance lead reviews regulatory, audit, environmental, safety, and legal obligations affecting maintenance history retention. 3. Data Migration Lead presents migration duration forecasts for multiple retention scenarios and quantifies conversion impacts. 4. PM Functional Lead validates operational reporting and maintenance analysis requirements before retention decisions are finalized. Successful remediation requires governance alignment before technical archiving execution begins.
Common mistakes to avoid what not to do.
1. Do not archive maintenance history records solely to improve migration duration without approved retention authorization. 2. Do not assume that historical records lacking recent usage automatically qualify for disposal. 3. Do not allow individual departments to define retention requirements independently without enterprise governance review. 4. Do not postpone retention policy discussions until migration testing and archiving activities have already begun.
Follow-up 1. Why do compliance teams frequently reject archiving proposals during S/4HANA migration programs?
Answer. Compliance teams frequently reject archiving proposals because migration teams focus on reducing database size and conversion duration, while compliance stakeholders focus on preserving records required for legal, audit, regulatory, environmental, safety, and contractual obligations. Without documented retention rules, compliance organizations often reject broad archiving initiatives to prevent accidental destruction of records that may be required in the future.
Follow-up 2. What is SAP Information Lifecycle Management, ILM, and how does it help?
Answer. SAP Information Lifecycle Management, ILM, is a governance framework that helps organizations manage data retention rules, legal holds, archiving controls, and information disposal processes. During migration programs, ILM enables organizations to align technical archiving activities with approved compliance requirements, reducing the risk of unauthorized record deletion while supporting controlled data volume reduction initiatives.
Follow-up 3 Curveball. Why can retaining all historical maintenance records sometimes be a valid business decision despite increasing migration duration?
Answer. Retaining all historical maintenance records can be a valid business decision when regulatory obligations, litigation exposure, audit requirements, safety investigations, or asset traceability needs create greater business risk than increased migration duration. Organizations must balance technical optimization goals against legal and operational accountability requirements rather than making retention decisions based solely on migration efficiency.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization. Establish enterprise retention requirements during the discover phase before data volume reduction planning begins. Recommendation 2. What successful projects do? Reliability. Successful programs create formal retention governance workshops involving compliance, legal, audit, and operational stakeholders before defining archiving scope. Recommendation 3. What should be validated? Revalidation. Validate every proposed archiving category against documented retention requirements before execution approval is granted. Recommendation 4. What should be governed? Responsibility. Maintain formal ownership, approval workflows, and retention policy governance for all historical maintenance records.
Migration Incident 32. PM interfaces using obsolete IDOC structures identified.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the integration assessment team discovers that multiple plant maintenance PM interfaces rely on legacy IDOC message types, custom Z segments, obsolete process codes, and ECC-specific data structures. While these interfaces continue functioning in the legacy ECC landscape, readiness validation activities reveal that several integrations contain dependencies that require remediation before conversion. If left unresolved, maintenance notifications, work orders, equipment updates, and third-party maintenance provider transactions may fail after go-live, creating significant operational disruption.
Incident classification and relevant SAP note if applicable.
1. Complexity. High legacy integration architecture failure. 2. Migration phase. Prepare. 3. Frequency. Common and mature ECC landscapes. 4. Primary ownership. Integration architect. 5. Supporting PM functional lead, basis lead, middleware lead, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. Not applicable, legacy interface compatibility assessment required.
How teams identify this issue. Diagnostic dashboard. Symptoms and evidence.
How obsolete PM integration structures typically reveal themselves during migration preparation activities. 1. Symptom: integration testing identifies PM transactions failing to transfer correctly between SAP ECC and external maintenance systems. 2. Red flag: large numbers of custom Z segments, custom function modules, and undocumented IDOC enhancements are discovered during interface inventory workshops. 3. Business impact: maintenance notifications, equipment updates, and work order status changes risk failing after cutover. 4. Detection: SAP readiness check, interface inventory assessments, and ATC reviews identify custom integration dependencies tied to legacy ECC structures. 5. Technical proof: IDOC processing logs reveal dependencies on obsolete fields, custom mappings, or unsupported enhancement logic requiring remediation.
Investigation tools and transactions used.
Use these tools and transactions to assess PM integration readiness and identify obsolete interface structures. 1. WE02 display IDOCs. Analyze historical inbound and outbound PM IDOC traffic and identify active message types. 2. WE05 IDOC list. Review processing status, interface volumes, and recurring integration failures. 3. WE20 partner profiles. Audit partner profile configurations supporting external maintenance integrations. 4. WE30 IDOC development. Review custom IDOC definitions and identify obsolete extensions requiring remediation. 5. WE31 segment development. Analyze custom Z segments and determine whether they remain compatible with the target state architecture. 6. WE60 IDOC documentation. Generate technical documentation for active IDOC structures and message types. 7. BD87 status monitor for ALE messages. Reprocess failed IDOCs and validate interface behavior during migration testing. 8. ATC ABAP test cockpit. Identify custom code dependencies embedded within IDOC processing logic. Architect's rule: every active PM interface must be inventoried, documented, and tested before the first sandbox conversion begins.
Incident analysis and root cause why this happens.
1. Legacy PM interfaces were implemented many years ago using custom IDOC enhancements and undocumented integration patterns. 2. Organizations accumulated custom Z segments to satisfy business requirements without maintaining proper interface governance documentation. 3. External maintenance vendors continued consuming legacy ECC payload structures without periodic architecture reviews. 4. Project teams assumed that existing IDOC integrations would automatically remain compatible after migration. 5. No formal integration readiness assessment was executed during the discover phase. The root cause is treating integration architecture as a technical afterthought rather than a critical migration workstream.
Why this issue appears only during an ECC to S/4HANA migration.
1. Legacy PM interfaces often function successfully for years without any visible operational issues in ECC. 2. S/4HANA migration programs force organizations to inventory, validate, and test every active integration point. 3. Readiness assessments expose hidden dependencies on obsolete structures, custom enhancements, and unsupported access methods. 4. Integration testing frequently reveals that external systems rely on undocumented assumptions embedded within historical ECC payloads. Migration programs expose integration debt that daily ECC operations often conceal.
Business and program impact.
1. Critical maintenance transactions may fail to reach external maintenance providers after cutover. 2. Project schedules expand as teams perform emergency interface remediation and retesting activities. 3. Additional middleware and development effort is required to redesign unsupported integration patterns. 4. Business confidence declines when integration testing repeatedly exposes undocumented interface dependencies. An undocumented PM interface can become a production-critical outage immediately after go-live.
Strategic decision. Evaluating PM integration remediation options.
Answer: resolving obsolete IDOC dependencies requires selecting an integration strategy aligned with the target S/4HANA architecture. 1. Retain standard IDOC architecture. Remediate custom dependencies and continue utilizing supported standard IDOC processing. 2. Extend existing interfaces. Redesign custom segments and mappings to align with target state business requirements. 3. Adopt API-based integration. Replace selected IDOC interfaces with modern API-based integration patterns where appropriate. 4. Hybrid coexistence approach. Retain critical IDOC interfaces while gradually modernizing high-value integrations. The best strategy balances operational stability with long-term integration modernization.
PM Integration Remediation Matrix.
A standard framework used to determine the correct remediation path for obsolete PM interfaces. 1. Standard IDOC with no custom enhancements. Retain and validate through end-to-end testing. 2. Custom Z segments present. Review business justification and redesign where required. 3. Unsupported ECC dependency detected. Refactor integration logic to supported target state methods. 4. Strategic digital integration initiative. Evaluate migration toward modern API and event-driven integration models. Every integration should have a documented target state ownership model before cutover.
Governance and Accountability RACI Model.
Integration readiness requires clear ownership because failures often impact multiple business functions simultaneously. 1. Accountable. Integration architect owns overall integration readiness and target state architecture decisions. 2. Responsible. Middleware lead and lead ABAP developer analyze interface logic mappings and remediation requirements. 3. Consulted. PM functional lead, basis lead, external integration partners. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Unknown interfaces become migration risks because nobody formally owns them.
Ownership, who actually fixes it.
Resolving obsolete PM interfaces requires coordinated technical analysis, business validation, and integration redesign. 1. Integration architect inventories active interfaces and defines the target state integration strategy. 2. Middleware lead analyzes mappings, routing rules, and external system dependencies. 3. Lead ABAP developer reviews custom IDOC enhancements, exits, and processing logic. 4. PM functional lead validates business-critical transaction flows and testing scenarios.
Who gets blamed versus who owns it.
1. Blamed. Middleware team accused of failing to maintain interface documentation. 2. Blamed. ABAP team accused of introducing unsupported custom enhancements. 3. Actual owner. Integration architect, accountable for ensuring complete interface readiness before migration execution. 4. Root cause. Failure to perform comprehensive integration inventory and dependency assessment during the discover phase. Interface failures are usually governance failures long before they become technical failures.
How this is actually fixed the right way by a role.
1. Integration architect establishes a complete inventory of all PM-related interfaces and prioritizes remediation efforts. 2. Middleware lead validates mappings, routing logic, and external system dependencies against target state requirements. 3. Lead ABAP developer remediates obsolete custom IDOC enhancements and unsupported processing logic. 4. PM functional lead executes end-to-end integration testing to confirm successful business process execution. Successful interface remediation requires inventory, remediation, testing, and governance, not emergency fixes during cutover.
Common mistakes to avoid what not to do.
1. Do not assume that working ECC interfaces are automatically compatible with S/4HANA. 2. Do not migrate undocumented custom IDOC structures without formal assessment. 3. Do not postpone interface testing until user acceptance testing begins. 4. Do not allow external integration dependencies to remain owned exclusively by third-party vendors.
Follow-up 1. Why can an IDOC interface appear healthy in ECC but fail after S/4HANA migration?
Answer: an interface may operate successfully in ECC because its custom logic was designed around legacy assumptions, data structures, and field lengths that remain unchanged in the source environment. However, S/4HANA introduces significant data model simplifications, such as extending the material number field length from 18 to 40 characters. During migration testing, these hidden dependencies, deprecated tables, and unsupported enhancements break the IDOC payload mapping, causing silent failures that only become visible upon execution.
Follow-up 2. What is the difference between a standard IDOC segment and a custom Z segment during migration planning?
Answer. Standard IDOC segments are SAP-delivered structures supported through standard lifecycle management processes, ensuring native compatibility during an S/4HANA conversion. Custom Z segments are organization-specific extensions developed to pass unique business fields to external systems. During migration planning, these Z segments present significantly higher risk because they frequently rely on direct database reads of legacy ECC tables that may be simplified or deprecated in S/4HANA. Consequently, custom segments require detailed ABAP test cockpit compatibility assessments.
Follow-up 3 Curveball. When should an organization retire PM IDOC interfaces and move to API-based integrations instead?
Answer. Organizations should evaluate API-based integrations when they require real-time processing, simplified integration architecture, enhanced monitoring capabilities, cloud-native connectivity, or broader digital transformation objectives. However, migration projects should prioritize business continuity first and modernization second, ensuring operational stability remains the primary decision criterion. Planners often retain reliable legacy IDOC interfaces for non-critical, asynchronous data exchanges, while reserving modern API event-driven architecture for real-time SCADA or predictive maintenance feeds.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization. Create a complete PM interface inventory before the first sandbox conversion begins. Recommendation 2. What successful projects do? Reliability. Execute dedicated integration testing cycles separate from functional testing activities. Recommendation 3. What should be validated? Revalidation. Validate every inbound and outbound maintenance transaction against representative business scenarios. Recommendation 4. What should be governed? Responsibility. Establish formal integration ownership and lifecycle governance for every production interface.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 33. Fiori sizing underestimated for maintenance technician usage.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, infrastructure sizing assumptions are validated through performance modeling and early testing activities. A significant issue emerges when the project discovers that the expected volume of plant maintenance PM technicians using SAP Fiori applications was severely underestimated during architecture planning. Initial sizing calculations were based primarily on office-based planners and supervisors, while thousands of field technicians, contractors, and mobile users were omitted from concurrency estimates. As testing progresses, the Fiori front-end server, application servers, and supporting infrastructure exhibit resource constraints that threaten system performance and go-live readiness.
Incident classification and relevant SAP, note if applicable.
1. Complexity. High infrastructure capacity planning failure. 2. Migration phase, prepare. 3. Frequency, common in large maintenance-intensive organizations. 4. Primary ownership, enterprise solution architect. 5. Supporting, basis lead infrastructure architect, PM functional lead Fiori architect. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, not applicable. Fiori capacity planning and sizing assessment required.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How underestimated Fiori usage volumes typically reveal themselves during migration preparation activities. 1. Symptom. Performance testing reveals slow Fiori launchpad response times and delayed transaction execution during peak maintenance periods. 2. Red flag. Concurrent user estimates exclude large populations of maintenance technicians, contractors, and mobile field users. 3. Business impact. Technicians experience delays accessing work orders, notifications, and equipment information required for daily operations. 4. Detection. Load testing exercises identify CPU, memory, and application server utilization levels significantly higher than projected design assumptions. 5. Technical proof. Performance monitoring tools reveal infrastructure bottlenecks within Fiori, Gateway, and application server components during simulated production workloads.
Investigation tools and transactions used.
Use these tools and utilities to analyze Fiori adoption assumptions, system sizing, and performance bottlenecks. 1. SAP Quick Sizer. Validate user populations, workload assumptions, and infrastructure sizing requirements. 2. ST03N workload analysis. Analyze user workloads, transaction volumes, and peak utilization periods. 3. ST06 operating system monitor. Monitor CPU memory and operating system resource consumption during testing. 4. STAD statistics records. Review response times and resource utilization for business transactions. 5. SAP Early Watch Alert. Evaluate system capacity indicators and infrastructure health metrics. 6. Load Runner or equivalent load testing tool. Simulate realistic technician workloads and concurrent usage scenarios. Architect's rule. Size the landscape based on actual concurrent business users, not named user license counts.
Incident analysis and root cause why this happens.
1. Project teams underestimate the volume of field technicians expected to access Fiori applications simultaneously. 2. Sizing exercises focus on planners, supervisors, and office users while excluding contractors and mobile workers. 3. Business stakeholders fail to provide accurate workforce concurrency assumptions during architecture planning. 4. Infrastructure sizing models are copied from previous projects that had fundamentally different user populations. 5. Mobile maintenance adoption rates are significantly higher than originally projected. The root cause is inaccurate concurrency modeling rather than insufficient hardware procurement.
Why this issue appears only during an ECC to S/4HANA migration.
1. ECC environments often relied heavily on SAP GUI access patterns that generated different infrastructure consumption profiles. 2. S/4HANA migration programs frequently introduce large-scale Fiori adoption across maintenance organizations. 3. Mobile-first maintenance processes increase the number of concurrent application requests generated throughout the day. 4. Modern user experience initiatives expand system adoption to workforce segments that previously had limited SAP access. Migration programs often transform occasional SAP users into daily Fiori users.
Business and program impact.
1. Technicians experience slow application performance during critical maintenance activities. 2. Work order execution efficiency declines due to delays accessing operational information. 3. Additional infrastructure procurement costs emerge late in the migration program. 4. Go-live readiness is threatened if performance targets cannot be achieved before deployment. 5. Business confidence declines when performance testing results fail to meet expectations. Poor sizing decisions become highly visible the moment thousands of technicians start using the system simultaneously.
Impact on technicians and maintenance teams.
How insufficient Fiori capacity directly affects daily maintenance operations. 1. Technicians experience slow Fiori launchpad response times when attempting to access work orders, notifications, equipment records, and maintenance history. 2. Mobile users encounter delays loading task lists, spare part information, and technical object details while working in the field. 3. Supervisors struggle to receive real-time maintenance updates because work order confirmations and status changes are processed slowly during peak usage periods. 4. Contractors and temporary maintenance personnel experience intermittent access issues during shift change periods when user concurrency is highest. 5. Field crews lose confidence in the new S/4HANA platform and often revert to manual workarounds, paper notes, spreadsheets, or phone calls to complete operational activities. Poor Fiori performance is not perceived by technicians as an infrastructure issue. It is perceived as an inability to perform maintenance work efficiently.
Strategic decision. Evaluating Fiori capacity expansion options.
Answer: resolving Fiori sizing concerns requires selecting an infrastructure strategy capable of supporting long-term maintenance operations. 1. Scale existing infrastructure. Add additional application server capacity and supporting resources. 2. Optimize Fiori usage patterns. Reduce unnecessary workloads and improve application performance efficiency. 3. Phase user adoption. Introduce technician populations in controlled deployment waves. 4. Redesign architecture. Reassess infrastructure architecture and expand platform capacity before go live. Successful organizations address capacity risks before production adoption rather than after go live.
Fiori capacity planning matrix.
A standard framework used to evaluate and resolve Fiori sizing concerns. 1. Minor resource constraints. Tune application performance and optimize workload distribution. 2. Moderate capacity shortfall. Expand application server infrastructure and retest. 3. Major concurrency underestimation. Recalculate sizing assumptions and redesign capacity plans. 4. Massive workforce expansion. Execute phased deployment and controlled adoption strategies. Capacity planning decisions should be driven by measured workloads rather than assumptions.
Governance and accountability, RACI model.
Capacity planning decisions require clear ownership because they directly influence production stability. 1. Accountable. Enterprise Solution Architect owns overall platform capacity strategy and target state architecture. 2. Responsible. Infrastructure Architect and Basis Lead execute sizing validation, performance testing, and remediation planning. 3. Consulted. PM Functional Lead, Fiori Architect, business stakeholders. 4. Informed. Program Sponsor, Steering Committee, Maintenance Operations Manager. Performance issues are often business volume problems disguised as technical problems.
Ownership, who actually fixes it.
Resolving Fiori sizing concerns requires coordinated technical analysis and workforce planning validation. 1. Enterprise Solution Architect validates target state adoption assumptions and infrastructure strategy. 2. Infrastructure Architect recalculates capacity requirements based on actual workforce volumes. 3. Basis Lead executes performance testing and validates remediation effectiveness. 4. PM Functional Lead confirms technician usage patterns and operational workload assumptions. 5. Fiori Architect optimizes application deployment and user experience performance.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of building an underpowered landscape. 2. Blamed. Infrastructure team accused of failing to procure adequate capacity. 3. Actual owner. Enterprise Solution Architect, accountable for validating workforce sizing assumptions and architecture decisions. 4. Root cause. Failure to accurately model maintenance technician concurrency during planning activities. Most sizing failures originate from bad assumptions rather than bad technology.
How this is actually fixed the right way by a role.
1. Enterprise Solution Architect revalidates workforce adoption assumptions and target state capacity requirements. 2. Infrastructure Architect recalculates hardware sizing and develops an expansion roadmap. 3. Basis Lead executes repeatable load testing exercises and validates performance improvements. 4. PM Functional Lead provides accurate technician concurrency and business usage forecasts. 5. Fiori Architect optimizes Launchpad, application deployment, and user access patterns. Successful remediation combines accurate business forecasting with disciplined performance engineering.
Common mistakes to avoid what not to do.
1. Do not size infrastructure solely using named user counts. 2. Do not assume technician concurrency will mirror ECC usage patterns. 3. Do not postpone load testing until immediately before go live. 4. Do not ignore contractor and third-party maintenance users during sizing exercises. 5. Do not treat performance issues as purely technical problems without reviewing business assumptions.
Follow-up 1. Why are maintenance technicians often excluded from initial Fiori sizing calculations?
Answer. Many sizing exercises focus on office-based users because they are easier to quantify and traditionally represented the primary SAP user population. However, S/4HANA and Fiori adoption frequently expand SAP usage to field technicians, contractors, and mobile workers. If these populations are excluded from concurrency estimates, infrastructure requirements can be significantly underestimated.
Follow-up 2. What is the difference between named users and concurrent users in SAP sizing exercises?
Answer. Named users represent the total number of individuals authorized to access the system, while concurrent users represent the number actively using the platform at the same time. Infrastructure sizing should primarily focus on concurrent usage patterns because they directly determine resource consumption and performance requirements.
Follow-up 3. Curveball. Why can a technically healthy landscape still fail performance testing?
Answer. A landscape may be technically healthy from an infrastructure perspective, yet still fail performance testing if business volume assumptions are incorrect. If concurrency estimates, transaction volumes, or user adoption rates are significantly underestimated. The platform may experience performance degradation even when all technical components are functioning exactly as designed.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: validate workforce concurrency assumptions using actual maintenance shift data rather than estimates. Recommendation 2. What successful projects do? Reliability: execute realistic performance tests that simulate technician, planner, and contractor workloads simultaneously. Recommendation 3. What should be validated? Revalidation: recalculate infrastructure sizing whenever deployment scope or user populations change. Recommendation 4. What should be governed? Responsibility: establish formal ownership for capacity planning, workforce forecasting, and performance validation activities.
Migration Incident 34. RFC destinations for external maintenance systems undocumented.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams discover that numerous plant maintenance PM integrations rely on remote function call RFC destinations that were never formally documented. Over years of enhancements, interfaces were created between SAP PM and external maintenance applications, mobile workforce systems, GIS platforms, calibration systems, contractor portals, and condition monitoring solutions. When migration readiness assessments begin, the team cannot determine which RFC destinations are still active, which business processes depend on them, or who owns them. This creates a major migration risk because critical integrations may fail after conversion, resulting in operational disruptions and unplanned business outages.
Incident classification and relevant SAP note if applicable.
1. Complexity: high integration architecture and interface governance failure. 2. Migration phase prepare. 3. Frequency: very common in mature ECC landscapes. 4. Primary ownership, integration architect. 5. Supporting PM functional lead, basis lead, enterprise solution architect. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note not applicable. Legacy interface compatibility assessment required.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How undocumented RFC dependencies typically reveal themselves during migration preparation activities. 1. Symptom: migration workshops uncover interfaces whose technical owners, business owners, and operational purpose cannot be clearly identified. 2. Red flag: large numbers of RFC destinations exist in transaction SM59 with descriptions that provide little or no business context. 3. Business impact: critical maintenance integrations may stop functioning after migration because connection dependencies were never captured in the migration scope. 4. Detection: interface discovery exercises reveal active RFC traffic flowing between SAP PM and external maintenance platforms that are absent from architecture documentation. 5. Technical proof: ST03N workload statistics, RFC traces, and interface monitoring logs show ongoing usage of RFC destinations that are missing from the official interface inventory.
Investigation tools and transactions used.
Use these tools to identify undocumented RFC destinations and integration dependencies. 1. SM59 RFC destination configuration. Inventory all configured RFC destinations and identify associated technical connection parameters. 2. ST03N workload analysis. Analyze historical RFC usage statistics and identify actively utilized destinations. 3. ST22 ABAP dump analysis. Review historical integration-related failures that may expose undocumented interfaces. 4. SMGW gateway monitor. Monitor active RFC communication channels and gateway activity. 5. Solution Manager or SAP ALM interface monitoring. Correlate technical interfaces with business process ownership and operational usage. Architect's rule: every RFC destination must have a documented business owner, technical owner, purpose, source system, target system, and migration strategy before conversion begins.
Incident analysis and root cause: why this happens.
1. Interfaces were implemented years earlier by project teams that are no longer with the organization. 2. No centralized interface repository or integration governance process existed to maintain RFC documentation. 3. Business departments requested tactical integrations that bypass standard architecture review processes. 4. System upgrades and support projects introduced new RFC destinations without updating enterprise architecture records. 5. Organizations focused on application functionality while neglecting integration lifecycle management. The root cause is weak interface governance discipline combined with years of undocumented integration growth.
Why this issue appears only during an ECC to S/4HANA migration.
1. Undocumented RFC destinations can operate for years without attracting attention as long as integrations continue functioning. 2. S/4HANA migration requires comprehensive interface inventory, testing, cutover planning, and dependency validation activities. 3. Migration programs force organizations to identify every inbound and outbound integration that could be impacted by infrastructure, security, or application changes. 4. Technical conversion activities frequently modify host names, security certificates, middleware routes, and connectivity patterns, exposing undocumented dependencies. Migration readiness exercises often become the first time the organization fully understands its integration landscape.
Business and program impact.
1. Migration schedules are delayed while teams perform emergency interface discovery and dependency mapping exercises. 2. Additional consulting effort is required to reverse engineer undocumented integrations and identify business ownership. 3. Cutover risks increase because unknown interfaces cannot be adequately tested before production deployment. 4. Business stakeholders lose confidence when critical operational integrations are discovered late in the migration lifecycle. Unknown interfaces create unknown migration risks, and unknown risks become executive-level concerns.
Impact on technicians and maintenance teams.
How undocumented RFC integrations directly affect maintenance operations after migration. 1. Technicians stop receiving maintenance tasks originating from external planning or workforce management systems. 2. Mobile maintenance applications fail to synchronize work order updates, forcing crews to manually re-enter field information. 3. Equipment condition monitoring alerts are no longer transferred into SAP notifications, reducing proactive maintenance visibility. 4. Contractor maintenance activities become difficult to coordinate because external systems cannot exchange status updates with SAP. 5. Supervisors lose real-time visibility into maintenance execution progress when integration-dependent dashboards stop receiving operational data. Technicians rarely know what an RFC destination is, but they immediately notice when the systems feeding their daily work stop communicating with SAP.
Strategic decision. Managing undocumented RFC integrations.
Answer: resolving undocumented RFC dependencies requires selecting an integration governance strategy before migration execution. 1. Inventory and retain. Identify all active RFC destinations and formally onboard them into the migration scope. 2. Consolidate and simplify. Retire duplicate interfaces and standardize integration architecture before conversion. 3. Modernize through middleware. Replace direct point-to-point RFC integrations with governed middleware-based integration patterns. 4. Retire obsolete integrations. Decommission inactive RFC destinations and eliminate unnecessary technical debt. The best migration programs treat interface discovery as a business transformation activity rather than a technical cleanup exercise.
RFC Integration Assessment Matrix.
A standard framework used to evaluate undocumented RFC destinations during migration preparation. 1. Actively used and business critical. Retain, document, test, and include in all migration rehearsals. 2. Actively used but poorly governed. Assign ownership and redesign according to enterprise integration standards. 3. Inactive for extended periods. Validate with business stakeholders and decommission if no longer required. 4. Duplicate or redundant integration. Consolidate into strategic middleware and eliminate unnecessary connectivity. Every undocumented RFC destination must end up documented, modernized, or retired.
Governance and accountability, Ray C model.
Integration discovery decisions require clear accountability because undocumented interfaces can disrupt mission-critical maintenance operations. 1. Accountable. Integration architect owns interface inventory completeness and migration readiness validation. 2. Responsible. Basis lead and PM functional lead identify RFC usage patterns, business dependencies, and testing requirements. 3. Consulted. Enterprise solution architect, middleware team, external system owners. 4. Informed. Program sponsor, steering committee, maintenance operations manager. If nobody owns the interface inventory, the migration team inherits the risk by default.
Ownership, who actually fixes it.
Resolving undocumented RFC dependencies requires structured interface discovery and governance. 1. Integration architect establishes the enterprise-wide interface inventory and dependency map. 2. Basis lead inventories RFC destinations and validates technical connectivity requirements. 3. PM functional lead identifies the business processes dependent on external maintenance integrations. 4. Enterprise solution architect defines the target state integration strategy and modernization roadmap.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of not knowing where RFC destinations connect. 2. Blamed. PM functional team accused of failing to identify dependent business processes. 3. Actual owner. Integration architect accountable for maintaining interface governance and dependency visibility. 4. Root cause. Years of unmanaged integration growth without ownership, documentation, or lifecycle controls. Undocumented integrations are governance failures, not technical failures.
How this is actually fixed the right way by a role.
1. Basis lead inventories every RFC destination in SM59 and collects usage statistics from workload monitoring tools. 2. PM functional lead identifies which maintenance processes rely on each integration and validates business criticality. 3. Integration architect builds a complete interface inventory, ownership matrix, and migration test strategy. 4. Enterprise solution architect decides which interfaces should be retained, modernized, consolidated, or retired. Successful remediation requires complete interface visibility before the first integration test cycle begins.
Common mistakes to avoid what not to do.
1. Do not assume unused documentation means an interface is inactive. 2. Do not migrate RFC configurations without understanding their business purpose and ownership. 3. Do not wait until integration testing to discover undocumented dependencies. 4. Do not decommission RFC destinations without formal business validation and approval.
Follow-up 1. Why are undocumented RFC destinations considered one of the most dangerous migration risks?
Answer. Undocumented RFC destinations create unknown dependencies that cannot be properly tested, validated, or included in cutover planning. Because business users often do not realize which external systems depend on SAP integrations, these silent connections are easily missed during standard blueprinting. When the core database is converted, these forgotten interfaces break, and failures may remain completely invisible until production maintenance operations are suddenly disrupted after go live.
Follow-up 2. Why is transaction SM59 critical during migration preparation?
Answer. Transaction SM59 contains the technical definitions for RFC destinations used throughout the entire SAP landscape. Reviewing SM59 allows migration teams to systematically inventory legacy integrations, identify external third-party dependencies, and validate payload connectivity requirements. By cross-referencing these destinations with actual usage data from ST03N, architects can determine exactly which interfaces require rigorous migration testing and which can be safely decommissioned.
Follow-up 3 curveball. Why do organizations often discover undocumented integrations only during S/4HANA migration programs?
Answer. Many point-to-point RFC interfaces continue operating reliably for years in the background without attracting any IT attention. S/4HANA migration programs introduce structured discovery activities, strict security certificate enforcements, and mandatory network hostname changes that immediately break these fragile legacy connections. These modernization prerequisites force organizations to finally execute the deep dependency assessments that expose tactical plant-level integrations that were never formally documented.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: create a complete RFC inventory and ownership register during the discover phase rather than waiting until integration testing. Recommendation 2. What successful projects do? Reliability: successful programs correlate RFC usage statistics with business process maps to identify genuinely critical interfaces. Recommendation 3. What should be validated? Revalidation: validate every retained RFC destination during sandbox, integration, and cutover rehearsals. Recommendation 4. What should be governed? Responsibility: establish long-term interface governance standards that require ownership, documentation, and lifecycle reviews for every integration.
Migration Incident 35. Custom PM authorization roles incompatible with Fiori architecture.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams discover that many legacy plant maintenance PM authorization roles were designed exclusively for SAP GUI transactions and do not align with the Fiori authorization architecture. Years of custom role development, transaction-based security design, and direct authorization object assignments create significant challenges when maintenance processes are transitioned to Fiori applications. If not remediated before testing begins, technicians, planners, supervisors, and maintenance managers may be unable to access critical applications, resulting in widespread business disruption during user acceptance testing and post-go-live operations.
Incident classification and relevant SAP note if applicable.
1. Complexity: high security architecture and authorization redesign risk. 2. Migration phase, prepare. 3. Frequency, very common in mature ECC landscapes. 4. Primary ownership, security lead. 5. Supporting PM functional lead, basis lead, Fiori architect. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, not applicable, Fiori authorization concept, and role redesign assessment required.
How teams identified this issue: diagnostic dashboard, symptoms and evidence.
How Fiori authorization incompatibilities typically reveal themselves during migration preparation activities. 1. Symptom: technicians and planners can log into the Fiori Launchpad but cannot access applications required for their daily maintenance activities. 2. Red flag: large numbers of custom ECC roles contain transaction code authorizations but no corresponding Fiori catalogs, groups, or business roles. 3. Business impact: critical maintenance processes fail during testing because users cannot create notifications, process work orders, or record confirmations. 4. Detection: security testing identifies authorization errors, missing application tiles, and access denied messages during business process validation. 5. Technical proof: authorization traces reveal that required Fiori applications lack corresponding catalog assignments and business role mappings.
Investigation tools and transactions used.
Use these tools to identify authorization gaps and Fiori security incompatibilities. 1. SUIM User Information System: analyze legacy role assignments, authorization objects, and user access patterns. 2. SU53 Authorization Check Analysis: capture and analyze authorization failures experienced by end users. 3. PFCG Role Maintenance: review legacy PM roles and redesign them for Fiori business role requirements. 4. Fiori Launchpad Content Manager: validate catalogs, spaces, pages, and application assignments. 5. STAUTH Trace Authorization Trace: capture detailed authorization failures during business process execution. Architect's rule: never assume that a user who can execute a transaction code in ECC automatically has access to the equivalent Fiori application.
Incident analysis and root cause why this happens.
1. Legacy security models were designed around transaction codes rather than role-based business applications. 2. Organizations accumulated hundreds of custom PM roles over many years without standardization. 3. Project teams underestimate the effort required to redesign security roles for the Fiori architecture. 4. Authorization remediation activities are deferred until testing phases when business users begin reporting access failures. 5. The organization lacks a formal role rationalization strategy before migration preparation begins. The root cause is attempting to migrate a transaction-centric security model into an application-centric Fiori environment without redesign.
Why this issue appears only during an ECC to S/4HANA migration.
1. ECC users often access functionality through traditional SAP GUI transactions without relying on Fiori business catalogs. 2. S/4HANA introduces role structures that incorporate catalogs, spaces, pages, launchpad content, and application-specific authorizations. 3. Migration programs expose gaps between legacy transaction-based security models and modern Fiori authorization requirements. 4. Business process testing immediately reveals missing permissions because users interact through a fundamentally different user experience. S/4HANA does not simply modernize the interface. It fundamentally changes how application access is delivered and governed.
Business and program impact.
1. User acceptance testing schedules are delayed while security teams redesign and retest authorization models. 2. Large volumes of authorization defects consume project resources that were allocated to business process validation. 3. Business stakeholders lose confidence when basic maintenance transactions become inaccessible through Fiori applications. 4. Go-live risk increases because unresolved authorization defects directly affect day one operational readiness. A technically successful migration can still fail operationally if users cannot access the applications required to perform their jobs.
Impact on technicians and maintenance teams.
How Fiori authorization failures directly affect maintenance operations. 1. Technicians are blocked from downloading work orders or processing confirmations on mobile devices due to unconfigured OData service authorizations. 2. Plant floor supervisors lose real-time safety visibility because they lack access to modern Fiori Work Clearance Management WCM permit dashboards. 3. External maintenance contractors experience immediate system lockouts during shift change periods when user concurrency and security checks are highest. 4. Planners are forced to revert to manual, paper-based order tracking and offline spreadsheets because they cannot edit standard work order details in Fiori. Users judge the success of a migration by whether they can perform their daily work, not by whether the technical conversion completed successfully.
Strategic decision. Evaluating authorization remediation options.
Answer: resolving authorization incompatibilities requires selecting an enterprise security strategy before testing begins. 1. Role rationalization program. Consolidate and redesign legacy PM roles into standardized Fiori business roles. 2. Lift and shift security approach. Retain existing role structures with minimal adaptation and accept increased testing risk. 3. Business role redesign. Rebuild security using standard S/4HANA business role concepts and Fiori best practices. 4. Hybrid transition model. Maintain critical legacy access paths while gradually transitioning users to modern Fiori roles. The most successful programs treat role redesign as a business transformation initiative rather than a technical security task.
Fiori Authorization Assessment Matrix.
A standard framework used to evaluate PM security readiness before migration. 1. Field Service Mobile Technicians. Map directly to cloud-native mobile roles FLVN01 and prioritize standard OData security profiles pre-conversion. 2. Highly customized maintenance planners. Execute a full role rationalization program in PFCG to consolidate redundant transaction-centric roles. 3. External maintenance contractors. Deploy standardized, restricted Fiori business role templates to secure third-party data segregation. 4. Safety and work clearance supervisors. Build custom, high-security authorization roles specifically aligned with Fiori WCM safety permit applications. Role simplification before migration usually costs less than large-scale authorization remediation after go-live.
Governance and accountability, RACI model.
Authorization decisions require clear accountability because they directly influence user productivity and operational continuity. 1. Accountable. Security lead owns authorization readiness and role redesign strategy. 2. Responsible. PM functional lead and security team validate business access requirements and execute role remediation. 3. Consulted. Fiori architect, basis lead, enterprise solution architect. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Security defects discovered during testing are often symptoms of earlier governance and design failures.
Ownership, who actually fixes it.
Resolving authorization incompatibilities requires coordinated security, functional, and user experience validation. 1. Security lead inventories existing PM roles and identifies redesign requirements. 2. PM functional lead maps business activities to required Fiori applications and permissions. 3. Fiori architect validates catalogs, spaces, pages, and Launchpad configuration requirements. 4. Basis lead supports testing, tracing, and authorization troubleshooting activities.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of deploying incorrect technical configurations. 2. Blamed. PM functional team accused of failing to communicate user requirements clearly. 3. Actual owner. Security lead accountable for ensuring that authorization models support the target state operating environment. 4. Root cause. Failure to redesign transaction-centric ECC roles for Fiori-based business processes. Most authorization failures originate from design decisions made months before users ever begin testing.
How this is actually fixed the right way by a role.
1. Security lead performs role analysis and identifies authorization gaps between ECC and Fiori business processes. 2. PM functional lead validates required maintenance activities and maps them to application-level permissions. 3. Fiori architect configures catalogs, spaces, pages, and Launchpad content required by each business role. 4. Security team executes end-to-end testing, resolves authorization defects, and validates production readiness. Successful remediation requires business process validation, security redesign, and repeated user testing.
Common mistakes to avoid what not to do.
1. Do not assume ECC transaction authorizations automatically provide equivalent Fiori access. 2. Do not postpone role redesign activities until user acceptance testing begins. 3. Do not create excessive emergency access roles to compensate for poor authorization planning. 4. Do not allow business users to validate security models only after cutover rehearsals are complete.
Follow-up 1. Why cannot organizations simply reuse their ECC PM roles in S/4HANA Fiori?
Answer. Legacy ECC roles were primarily designed around transaction codes and SAP GUI navigation patterns. Fiori introduces an application-centric authorization model that depends on catalogs, business roles, Launchpad content, and application-specific permissions. While some authorization objects may still be relevant, the overall access model is fundamentally different. As a result, organizations must validate and often redesign roles to ensure users can perform their maintenance activities through the new Fiori experience.
Follow-up 2. Why do authorization issues often explode during user acceptance testing?
Answer. Authorization defects frequently remain hidden during early technical testing because only a limited set of scenarios is executed. User acceptance testing introduces real business users performing complete maintenance processes across multiple applications and roles. This broader coverage exposes missing permissions, incorrect catalog assignments, and role design flaws that were not previously visible. The result is often a sudden surge in security defects that must be remediated before go live.
Follow-up 3 Curveball. Why should role redesign be treated as a business transformation activity rather than a security exercise?
Answer. Authorization models directly influence how users perform their daily responsibilities, access information, and execute maintenance processes. A poorly designed role structure can slow operations, increase support tickets, and create productivity issues even when the technology functions correctly. Treating role redesign as a business initiative ensures that security decisions align with operational requirements, user experience goals, and long-term governance objectives. This approach typically produces far better outcomes than viewing authorization work as a purely technical task.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: perform a complete PM role inventory and authorization gap assessment before the first integration test cycle. Recommendation 2. What successful projects do? Reliability: successful programs establish standardized business role templates rather than migrating hundreds of custom ECC roles individually. Recommendation 3. What should be validated? Revalidation: validate every technician, planner, supervisor, and manager role using realistic end-to-end maintenance scenarios. Recommendation 4. What should be governed? Responsibility: implement ongoing role governance processes to prevent uncontrolled authorization growth after go live.
Migration Incident 36. Measurement document inconsistencies detected during data validation.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams execute data quality and consistency validation activities against plant maintenance PM measurement history. A major issue emerges when historical measurement documents contain inconsistent readings, duplicate entries, invalid counter values, incorrect units of measure, or chronology violations. Because measurement documents are heavily used for preventive maintenance planning, counter-based maintenance strategies, and asset performance analysis, these inconsistencies trigger migration readiness concerns and data validation failures that must be remediated before conversion activities proceed.
Incident classification and relevant SAP note if applicable.
1. Complexity: high technical object data integrity failure. 2. Migration phase prepare. 3. Frequency common in asset-intensive industries. 4. Primary ownership data migration lead. 5. Supporting PM functional lead basis lead lead ABAP developer. 6. Business ownership maintenance operations manager. 7. Relevant SAP note not applicable. SAP PM measurement document validation and data quality management best practices.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How measurement document inconsistencies typically reveal themselves during migration preparation activities. 1. Symptom: validation reports identify measurement readings that conflict with expected counter progression or maintenance history records. 2. Red flag: historical measurement documents contain duplicate readings, negative counter jumps, invalid units of measure, or impossible date sequences. 3. Business impact: counter-based maintenance plans become unreliable because future scheduling calculations are based on questionable historical data. 4. Detection: data profiling exercises and PM master data validation activities identify inconsistent measurement histories across technical objects. 5. Technical proof: tables such as IMRG and associated measurement point records reveal anomalies, duplicate values, invalid counter progression patterns, or uncoordinated counter overflows.
Investigation tools and transactions used.
Use these tools to identify measurement history inconsistencies and validation failures. 1. IK17 measurement document list. Review historical measurement documents and identify suspicious readings or chronology issues. 2. IK18 change measurement document. Analyze and correct measurement document inconsistencies where permitted by governance policies. 3. IK03 display measurement point. Validate measurement point configuration, counter settings, and historical trends. 4. SE16N table browser. Analyze measurement-related tables such as IMRG for duplicate or invalid historical entries. 5. SAP data services or data profiling tools. Execute bulk consistency analysis against large measurement document populations. Architect's rule: never assume measurement history is trustworthy simply because maintenance plans are currently running without visible failures.
Incident analysis and root cause why this happens.
1. Field personnel manually entered measurement readings without sufficient validation controls. 2. Legacy mobile applications and third-party interfaces occasionally transmitted duplicate measurement documents. 3. Counter rollovers, unit conversion errors, and historical data corrections were not consistently governed. 4. Data quality assessments were neglected because measurement history was viewed as operational data rather than migration-critical master data. 5. Organizations accumulated decades of measurement records without periodic cleansing or validation initiatives. The root cause is a long-term absence of measurement data governance and quality control processes.
Why this issue appears only during an ECC to S/4HANA migration.
1. Measurement inconsistencies can remain hidden for years because daily maintenance operations often focus only on recent readings. 2. Migration programs perform large-scale validation activities that analyze historical data across the entire asset population. 3. Readiness assessments expose chronology violations, counter anomalies, and duplicate records that were never previously investigated. 4. Business stakeholders become concerned because poor quality measurement history can compromise future maintenance planning and reporting accuracy. Migration projects often become the first enterprise-wide audit of maintenance measurement quality.
Business and program impact.
1. Migration timelines are delayed, while historical measurement anomalies are investigated and remediated. 2. Maintenance planning teams lose confidence in counter-based maintenance schedules derived from inconsistent data. 3. Additional cleansing and validation activities increase project effort and consulting costs. 4. Asset performance reporting becomes unreliable when historical measurements contain significant quality issues. Poor measurement quality creates both migration risk and long-term operational risk.
Impact on technicians and maintenance teams.
How measurement document inconsistencies directly affect maintenance operations. 1. Technicians receive maintenance orders at incorrect intervals because counter-based plans rely on inaccurate readings. 2. Planners struggle to determine true equipment utilization when historical measurements contain anomalies. 3. Supervisors lose confidence in reliability reports generated from questionable measurement histories. 4. Field crews spend additional time manually validating readings before performing maintenance activities. 5. Critical equipment may become over-maintained or under-maintained because scheduling calculations are based on flawed historical data. Measurement data drives maintenance decisions, making data quality an operational necessity rather than a technical concern.
Strategic decision. Evaluating measurement data remediation.
Answer: resolving measurement document inconsistencies requires selecting an appropriate remediation strategy before conversion activities continue. 1. Full historical cleansing. Correct all identified anomalies before migration execution. 2. Risk-based remediation. Focus only on measurement histories associated with critical assets and maintenance plans. 3. Archive obsolete measurement history. Remove inactive historical records that no longer provide business value. 4. Governed exception acceptance. Retain known anomalies with documented business approval and mitigation controls. The most successful programs prioritize critical assets while maintaining rigorous data quality standards.
Measurement data assessment matrix.
A standard framework used to evaluate measurement history remediation requirements. 1. Critical asset with counter-based maintenance. Perform full validation and correction before migration. 2. Minor asset with limited maintenance impact. Apply risk-based remediation and monitoring controls. 3. Duplicate historical records. Cleanse and consolidate before conversion testing begins. 4. Inactive or retired equipment. Evaluate archival opportunities before investing in remediation effort. Not all measurement defects carry equal risk. Prioritize remediation according to business impact.
Governance and accountability RACI model.
Measurement data decisions require clear ownership because they directly influence maintenance planning and operational reliability. 1. Accountable. Data migration lead owns measurement data readiness and validation outcomes. 2. Responsible PM functional lead validates business accuracy of historical measurements and maintenance impacts. 3. Consulted. Basis lead ABAP developer reliability engineering team. 4. Informed. Program sponsor. Steering committee, maintenance operations manager. Data quality issues become migration issues when ownership is unclear.
Ownership, who actually fixes it.
Resolving measurement data inconsistencies requires coordinated business and technical remediation efforts. 1. Data migration lead performs profiling, anomaly identification, and remediation planning. 2. PM functional lead validates the accuracy and business relevance of historical measurement records. 3. Lead ABAP developer develops controlled correction utilities where large-scale remediation is required. 4. Basis lead supports extraction, validation, and migration readiness verification activities.
Who gets blamed versus who owns it?
1. Blamed. Maintenance technicians accused of entering inaccurate readings over many years. 2. Blamed. PM functional team accused of failing to establish measurement data controls. 3. Actual owner. Data migration lead accountable for identifying and managing data quality risks before migration execution. 4. Root cause. Long-term absence of measurement data governance, validation controls, and periodic quality reviews. Migration teams inherit historical data problems, but they still own remediation planning.
How this is actually fixed the right way by a role.
1. Data migration lead executes profiling activities to identify duplicate, inconsistent, and invalid measurement documents. 2. PM functional lead validates anomaly reports and determines the correct business values for critical assets. 3. Lead ABAP developer develops controlled correction utilities and mass validation reports where required. 4. Basis lead re-executes validation activities and confirms that measurement data quality standards have been achieved. Successful remediation combines technical correction, business validation, and governance oversight.
Common mistakes to avoid what not to do.
1. Do not assume active maintenance plans guarantee measurement data quality. 2. Do not execute mass corrections without functional validation and approval. 3. Do not ignore duplicate or chronology conflicting measurement records during readiness assessments. 4. Do not postpone measurement data remediation until user acceptance testing begins.
Follow-up 1. Why can measurement document inconsistencies remain hidden for years in ECC systems?
Answer. Most maintenance teams focus primarily on current readings and near-term maintenance activities, rather than analyzing decades of historical measurement data. As a result, duplicate readings, chronology violations, and incorrect counter values may never be investigated unless they cause an obvious operational issue. Migration programs perform large-scale data quality assessments that review historical records across the entire asset population. This broader analysis frequently exposes defects that remained unnoticed during normal day-to-day operations.
Follow-up 2. Why are measurement documents important for maintenance planning and reliability analysis?
Answer. Measurement documents provide the historical operating data used to calculate equipment utilization, counter progression, and condition-based maintenance requirements. Counter-based plans heavily rely on tracking total running hours or cycle counts via measuring points in table, IMPT, to calculate accurate call horizons. If legacy measurement documents contain massive negative jumps or uncoordinated counter overflows, the scheduling engine calculates incorrect intervals, leading to either premature preventive maintenance or catastrophic delayed interventions.
Follow-up 3. Curveball. Why should organizations treat measurement data governance as a long-term operational discipline rather than a migration task?
Answer. Migration projects may identify measurement data defects, but they rarely create the underlying quality problems. These issues typically accumulate over many years through weak validation controls, inconsistent processes, and insufficient governance. Without sustainable controls, new inaccuracies will continue appearing after go-live regardless of how much cleansing occurs before migration. Strong governance ensures that measurement quality remains reliable long after the conversion project is complete.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization, execute measurement history, profiling early in the prepare phase to identify anomalies before conversion testing begins. Recommendation 2. What successful projects do? Reliability successful programs prioritize critical assets and counter-based maintenance plans when allocating remediation effort. Recommendation 3. What should be validated? Revalidation validate corrected measurement histories against maintenance schedules and reliability reports before migration approval. Recommendation 4. What should be governed responsibility? Establish long-term measurement data governance controls to prevent recurrence of historical data quality issues.
Migration Incident 37. Equipment serial number duplication detected across plants.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the data cleansing team discovers that equipment serial numbers are duplicated across multiple plants and company codes. Years of decentralized equipment creation practices, acquisitions, and inconsistent governance have allowed identical serial numbers to be assigned to different technical objects. During migration preparation and master data harmonization activities, these duplicates create significant identification, integration, and reporting concerns that must be resolved before conversion and business validation activities can proceed.
Incident classification and relevant SAP note if applicable.
1. Complexity. High technical object master data governance failure. 2. Migration phase, prepare. 3. Frequency, common in large multi-plant ECC landscapes. 4. Primary ownership, data migration lead. 5. Supporting, PM functional lead, master data governance lead, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, not applicable. SAP master data governance MDG and technical object data harmonization best practices.
How teams identify this issue. Diagnostic dashboard, symptoms and evidence.
How serial number duplication issues typically reveal themselves during migration readiness activities. 1. Symptom. Data quality reports identify identical serial numbers assigned to multiple equipment records across different plants. 2. Red flag. Multiple technical objects share the same manufacturer serial number but represent completely different physical assets. 3. Business impact. Maintenance planners lose confidence in equipment traceability and asset history reporting. 4. Detection. Data profiling activities and master data reconciliation workshops identify duplicate serial number populations. 5. Technical proof. Analysis of tables EQUI and OBJK reveals multiple equipment records containing identical serial numbers without approved business justification.
Investigation tools and transactions used.
Use these tools to identify, analyze, and remediate duplicate serial number records. 1. IQ03 display serial number. Validate the serial number master record and its integration with underlying equipment and materials. 2. IE03 display equipment. Review equipment master records and validate serial number assignments. 3. IH08 equipment list. Execute large-scale equipment reporting and duplicate serial number analysis. 4. SE16N table browser. Query equipment master data tables and perform duplicate value analysis. 5. SAP information steward or data profiling tools. Identify duplicate serial number populations and generate cleansing reports. Architect's rule. Treat duplicate serial numbers as a master data governance issue first, not merely a migration issue.
Incident analysis and root cause why this happens.
1. Different plants created equipment independently without global serial number validation controls. 2. Acquired companies imported legacy assets into ECC without harmonizing serial number standards. 3. Master data teams relied on manual spreadsheet-based asset onboarding processes. 4. The organization lacked enterprise-wide governance rules preventing duplicate technical object identifiers. The root cause is decentralized technical object governance, combined with weak asset master data controls.
Why this issue appears only during an ECC to S/4HANA migration.
1. Duplicate serial numbers can remain hidden for years because individual plants operate independently within established business processes. 2. Migration programs force enterprise-wide data harmonization and expose inconsistencies that were previously tolerated. 3. Data cleansing activities require a trusted and unique asset identification strategy before business validation can begin. 4. Enterprise reporting, analytics, and future digital manufacturing initiatives depend on reliable technical object identification. Migration programs expose technical object inconsistencies that often remain invisible during day-to-day ECC operations.
Business and program impact.
1. Migration timelines are delayed while duplicate equipment records are investigated and reconciled. 2. Asset history reporting becomes unreliable because maintenance records may be associated with the wrong physical asset. 3. Additional data cleansing effort and business workshops increase project costs. 4. Future predictive maintenance and reliability engineering initiatives are compromised by poor asset traceability. Technical object identity is foundational to maintenance, reliability, and asset management processes.
Impact on technicians and maintenance teams.
How duplicate serial numbers affect day-to-day maintenance operations. 1. Technicians may review maintenance history belonging to the wrong physical asset. 2. Spare parts recommendations become less reliable due to incorrect equipment associations. 3. Warranty and manufacturer support claims become difficult to validate. 4. Field teams lose confidence in the accuracy of equipment records and historical maintenance data.
Strategic decision. Resolving duplicate serial numbers.
Answer: the organization must establish a standardized asset identification strategy before migration execution. 1. Retain valid record. Identify the authoritative equipment record and retire duplicates. 2. Introduce global standards. Establish enterprise-wide serial number governance policies. 3. Merge asset histories. Consolidate historical maintenance records where business approved. 4. Implement MDG controls. Enforce duplicate prevention during future equipment creation. Successful programs solve duplicate assets permanently rather than performing one-time migration cleanup.
Governance and accountability. RACI model.
Asset master data decisions require clear ownership because they affect operations, reporting, and compliance. 1. Accountable. Data migration lead owns technical object data readiness before conversion. 2. Responsible PM functional lead validates correct equipment ownership and business mappings. 3. Consulted. Master data governance lead ABAP developer. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Data ownership must be clearly assigned before duplicate asset remediation begins.
Ownership. Who actually fixes it?
Resolving duplicate serial numbers requires coordinated business and technical validation. 1. Data migration lead identifies all duplicate serial number populations and drives remediation planning. 2. PM functional lead validates which equipment records represent the correct physical assets. 3. Master data governance lead defines future asset governance standards. 4. Lead ABAP developer supports automated duplicate detection and cleansing activities.
Who gets blamed versus who owns it?
1. Blamed. Maintenance teams accused of creating duplicate equipment records. 2. Blamed. Data migration team accused of discovering the issue too late. 3. Actual owner. Data migration lead accountable for identifying and resolving duplicate technical object data before migration execution. 4. Root cause. Years of weak asset master data governance and decentralized equipment management processes. Duplicate serial numbers are typically the result of governance failures accumulated over many years.
How this is actually fixed the right way by a role.
1. Data migration lead executes duplicate analysis reports and produces a complete reconciliation inventory. 2. PM functional lead validates the authoritative equipment records and approves business mappings. 3. Lead ABAP developer develops automated cleansing and duplicate detection utilities where necessary. 4. Master data governance lead implements preventive controls to stop future duplicate creation. The objective is not merely removing duplicates, but establishing trusted asset identity across the enterprise.
Common mistakes to avoid. What not to do.
1. Do not arbitrarily delete equipment records without business validation. 2. Do not assume identical serial numbers always represent duplicate physical assets. 3. Do not postpone serial number reconciliation until user acceptance testing. 4. Do not migrate duplicate technical object records into S/4HANA without remediation.
Follow-up 1. Why do duplicate serial numbers become a major concern during migration preparation?
Answer: migration preparation forces organizations to perform enterprise-wide data harmonization activities that expose inconsistencies hidden within legacy systems. Duplicate serial numbers undermine asset traceability, maintenance history accuracy, and reporting integrity. What may appear to be a minor master data issue can quickly become a major business validation problem when multiple plants depend on trusted equipment records. Resolving these conflicts early reduces migration risk and improves long-term asset governance.
Follow-up 2. How do successful migration programs typically resolve duplicate equipment records?
Answer: successful programs combine automated data profiling with business-led validation workshops. The technical team identifies duplicate populations, while maintenance and asset management stakeholders determine which records are authoritative. Historical maintenance data is then reconciled according to approved governance rules. This structured approach ensures that duplicate cleanup improves data quality without compromising operational history.
Follow-up 3. Curveball. Why is this issue often a symptom of broader master data governance weaknesses?
Answer: duplicate serial numbers rarely occur in isolation. They often indicate missing governance controls, inconsistent onboarding processes, weak validation rules, and decentralized ownership of asset master data. Organizations that discover widespread duplication frequently uncover additional quality issues involving functional locations, classes, characteristics, and equipment hierarchies. Migration projects simply expose governance weaknesses that have accumulated over many years.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: execute enterprise-wide serial number profiling before beginning technical conversion activities. Recommendation 2. What successful projects do? Reliability: establish authoritative equipment ownership and reconciliation governance before data cleansing execution. Recommendation 3. What should be validated? Revalidation: validate maintenance history, warranty records, and equipment relationships after duplicate remediation. Recommendation 4. What should be governed? Responsibility: implement MDG controls that prevent duplicate serial number creation across all plants going forward.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 38. PM order statuses inconsistent due to years of custom updates.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams discover that thousands of historical plant maintenance PM orders contain inconsistent system and user statuses. Over many years, custom ABAP programs, direct status update utilities, legacy interfaces, and unsupported mass correction activities modified PM order statuses outside standard SAP business logic. As migration readiness checks and business validation exercises begin, these inconsistencies create reporting discrepancies, process control failures, and data quality concerns that must be resolved before conversion activities can proceed safely.
Incident classification and relevant SAP, note if applicable.
1. Complexity. High business process integrity and master data consistency failure. 2. Migration phase, prepare. 3. Frequency, common in highly customized ECC landscapes. 4. Primary ownership, PM functional lead. 5. Supporting, data migration lead, lead ABAP developer basis lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, not applicable. PM order status data consistency and status management validation required.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How PM order status inconsistencies typically reveal themselves during migration preparation activities. 1. Symptom. Completed maintenance orders appear simultaneously in conflicting business states such as technically completed, open, or awaiting confirmation. 2. Red flag. Historical orders contain status combinations that are impossible under standard SAP PM business processes. 3. Business impact. Maintenance reporting, KPI calculations, backlog analysis, and audit reporting become unreliable. 4. Detection. Data quality reviews and PM process validation workshops identify mismatches between actual order history and recorded status values. 5. Technical proof. Analysis of PM order status tables JEST and JCDS reveals inconsistent status combinations and unsupported status transitions.
Investigation tools and transactions used.
Use these tools to identify, analyze, and remediate PM order status inconsistencies. 1. IW33 display maintenance order. Review maintenance order history and status progression. 2. SE16N table browser. Analyze status management tables and identify inconsistent status records. 3. BS23 display system status. Review standard SAP status definitions and allowable status transitions. 4. Custom data profiling reports. Identify invalid status combinations and quantify remediation scope. Architect's rule. Never assume historical status values are trustworthy when custom update programs have existed for years.
Incident analysis and root cause why this happens.
1. Legacy custom ABAP utilities updated PM order statuses directly rather than following standard SAP business processes. 2. Mass correction activities were executed during audits, acquisitions, or reporting projects without proper governance. 3. Interfaces integrated with external maintenance systems bypass standard status management logic. 4. Organizations prioritized operational continuity over long-term process and data integrity. The root cause is years of unsupported status manipulation outside standard SAP status management controls.
Why this issue appears only during an ECC to S/4HANA migration.
1. Daily ECC operations often continue successfully despite historical status inconsistencies. 2. Migration programs require deep business process validation and data quality assessment that expose hidden process defects. 3. Historical PM orders become subject to extensive reconciliation and reporting validation exercises. 4. S/4HANA transformation programs place greater emphasis on trusted analytics, process transparency, and data integrity. Migration activities expose process inconsistencies that may have remained hidden for many years.
Business and program impact.
1. Migration timelines expand, while business users validate and reconcile historical maintenance order records. 2. Maintenance KPI calculations become unreliable due to incorrect status populations. 3. Audit and compliance reporting may contain inaccurate maintenance process metrics. 4. Additional data cleansing and business validation workshops increase overall project costs. Untrusted order statuses create operational, reporting, and compliance risks far beyond the migration itself.
Impact on technicians and maintenance teams.
How inconsistent PM order statuses affect maintenance operations. 1. Technicians struggle to determine whether maintenance work was actually completed. 2. Planners receive inaccurate backlog and work completion reports. 3. Supervisors lose confidence in maintenance performance metrics. 4. Historical troubleshooting activities become more difficult because order life cycles cannot be trusted.
Governance and accountability. RACI model.
Status remediation decisions require clear ownership because they affect reporting, audits, and operational processes. 1. Accountable. PM functional lead owns PM process integrity and order status governance. 2. Responsible. Data migration lead coordinates status analysis, cleansing, and reconciliation activities. 3. Consulted. Lead ABAP developer basis lead maintenance operations manager. 4. Informed. Program sponsor. Steering committee, audit stakeholders. Status integrity is fundamentally a business process issue supported by technical remediation.
Ownership. Who actually fixes it.
Resolving PM order status inconsistencies requires coordinated business and technical validation. 1. PM functional lead validates proper business process status progression and exception handling. 2. Data migration lead identifies affected order populations and coordinates remediation activities. 3. Lead ABAP developer analyzes custom update programs and interface logic responsible for status corruption. 4. Basis lead supports data validation, transport management, and remediation execution.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of defining poor maintenance processes. 2. Blamed. Development team accused of creating unreliable custom update programs. 3. Actual owner. PM functional lead accountable for ensuring process integrity and status governance before migration execution. 4. Root cause. Years of uncontrolled custom updates, unsupported interfaces, and weak status governance practices. Status corruption is usually the result of governance failures accumulated over many years.
How this is actually fixed the right way by a role.
1. Data migration lead identifies all orders containing invalid or conflicting status combinations. 2. PM functional lead validates the correct business status for each affected order population. 3. Lead ABAP developer remediates custom programs and interfaces responsible for unsupported status updates. 4. PM functional lead performs final business validation to ensure that reporting and operational processes produce trusted results. The objective is not only correcting historical data, but also preventing future status corruption.
Common mistakes to avoid what not to do.
1. Do not migrate inconsistent PM order statuses without business validation. 2. Do not correct status records using unsupported direct database updates. 3. Do not assume historical reports remain accurate when status corruption exists. 4. Do not ignore the custom programs and interfaces that originally created the issue.
Follow-up 1. Why can inconsistent PM order statuses remain hidden in ECC for many years?
Answer: most daily maintenance activities focus on current operational orders rather than validating decades of historical process records. As a result, invalid status combinations can accumulate without triggering major business disruption. Custom reports often work around these inconsistencies, further masking the problem. Migration readiness activities finally expose the issue because they evaluate process integrity across the entire historical data population.
Follow-up 2. Why is correcting status values alone often insufficient?
Answer: correcting historical records addresses the symptom but not the source of the problem. If the custom programs, interfaces, or unsupported update processes responsible for the corruption remain active, new inconsistencies will continue to appear. Successful remediation requires both data correction and process control improvements. Governance, validation controls, and technical remediation must work together.
Follow-up 3. Curveball. Why do auditors care about historical PM status integrity during migration programs?
Answer: maintenance order statuses are often used to demonstrate compliance, work completion, safety execution, and asset management performance. If historical statuses are unreliable, audit findings and management reports may become questionable. Auditors therefore view status integrity as both a data quality issue and a governance issue. Migration programs provide an opportunity to restore confidence in historical maintenance records.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: perform enterprise-wide PM order status profiling before executing migration rehearsals. Recommendation 2. What successful projects do? Reliability: trace every invalid status population back to the custom programs or interfaces that created it. Recommendation 3. What should be validated? Revalidation: validate backlog reporting, work completion metrics, and maintenance KPIs after remediation. Recommendation 4. What should be governed? Responsibility: establish strict controls preventing unsupported status updates outside standard SAP business logic.
Migration incident 39. Large backlog of failed PM iDocs discovered.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the integration assessment team discovers a large backlog of failed plant maintenance PM iDocs that have accumulated over several years. Many of these failed iDocs originate from external maintenance systems, mobile workforce applications, GIS platforms, warehouse systems, and third-party asset management solutions. Because these failures were never fully investigated or reprocessed, critical maintenance transactions and master data updates may never have reached their intended target systems. Before migration activities can continue, the organization must determine the operational and business impact of these unresolved integration failures.
Incident classification and relevant SAP note if applicable.
1. Complexity: high integration data integrity and interface governance failure. 2. Migration phase: prepare. 3. Frequency: common and mature ECC landscapes with multiple external integrations. 4. Primary ownership: integration architect. 5. Supporting: PM functional lead, basis lead, lead ABAP developer. 6. Business ownership: maintenance operations manager. 7. Relevant SAP note. SAP note 1575857. iDoc processing. General performance and error analysis recommendations.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How unresolved PM interface failures typically reveal themselves during migration readiness activities. 1. Symptom: thousands of PM-related iDocs remain in failed, error, or unprocessed status within the ECC system. 2. Red flag: external systems contain maintenance data that does not match the corresponding records in SAP ECC. 3. Business impact: Maintenance history, technical object updates, and transactional records may be incomplete or inaccurate. 4. Detection. Integration assessment workshops identify unusually high volumes of historical IDOC processing failures. 5. Technical proof. IDOC monitoring transactions reveal large populations of PM-related IDOCs in error statuses requiring investigation.
Investigation tools and transactions used.
Use these tools to identify, analyze, and remediate failed PM IDOC populations. 1. WE02 IDOC list. Analyze failed PM IDOCs and identify recurring error patterns. 2. WE05 IDOC monitoring. Perform large-scale monitoring and filtering of interface failures. 3. BD87 IDOC reprocessing. Reprocess failed IDOCs after underlying issues are corrected. 4. SM58 transactional RFC monitor. Investigate RFC-related transmission failures associated with IDOC processing. Architect's rule. Never assume failed IDOCs are harmless historical artifacts. They may represent years of missing business transactions.
Incident analysis and root cause why this happens.
1. Integration support teams focused on resolving urgent operational incidents rather than eliminating historical interface backlogs. 2. External systems change message formats without corresponding SAP interface updates. 3. Failed IDOCs accumulated because monitoring and governance processes were inconsistent across support teams. 4. Organizations lacked formal ownership and escalation procedures for long-term interface failures. The root cause is weak interface governance, combined with years of unresolved integration exceptions.
Why this issue appears only during an ECC to S/4HANA migration.
1. Daily ECC operations often continue despite unresolved IDOC failures because users develop manual workarounds. 2. Migration programs require comprehensive interface inventories and integration health assessments. 3. Historical interface failures become highly visible when data reconciliation activities begin. 4. S/4HANA migration programs require trusted master data and transaction integrity across all connected systems. Migration readiness activities expose integration defects that may have remained hidden for many years.
Business and program impact.
1. Migration timelines expand, while integration teams investigate historical interface failures and missing transactions. 2. Additional reconciliation workshops are required to determine which business data was never successfully transmitted. 3. Operational reporting may be inaccurate due to years of incomplete synchronization between systems. 4. Project risk increases because unknown integration defects could reappear after migration. Unresolved interface failures create uncertainty regarding the completeness and reliability of operational data.
Impact on technicians and maintenance teams.
How failed PM IDOCs directly affect maintenance operations. 1. Technicians may be working with incomplete maintenance histories because external updates never reached SAP. 2. Planners may not see the latest asset information originating from connected maintenance systems. 3. Maintenance reporting becomes less reliable due to synchronization gaps between applications. 4. Supervisors lose confidence in operational dashboards when different systems report conflicting information.
Strategic decision. Resolving historical IDOC backlogs.
Answer: the organization must determine the appropriate treatment strategy for historical integration failures before migration execution. 1. Reprocess historical IDOCs. Correct underlying issues and attempt controlled reprocessing of failed messages. 2. Perform business reconciliation. Validate affected business data manually and correct discrepancies directly. 3. Retire obsolete interfaces. Decommission interfaces that no longer provide business value. 4. Accept documented exceptions. Formally document low-risk historical failures that cannot be economically remediated. The objective is not merely clearing technical queues but restoring trust in enterprise data flows.
Failed IDOC remediation matrix.
A common framework used to determine the appropriate treatment path for historical IDOC failures. 1. Business-critical transactions missing. Reprocess IDOCs and validate resulting business records. 2. Master data synchronization failures. Execute targeted reconciliation and data correction activities. 3. Obsolete legacy interfaces. Retire and document the integration before migration. 4. Low-risk historical failures. Evaluate business impact and formally approve exception handling. Not every failed IDOC deserves reprocessing, but every failed IDOC deserves business impact assessment.
Governance and accountability, RACI model.
Interface remediation decisions require clear ownership because they affect data integrity across multiple systems. 1. Accountable. Integration architect owns enterprise interface readiness and migration integration strategy. 2. Responsible. PM functional lead validates business impact and data completeness for affected maintenance processes. 3. Consulted. Basis lead ABAP developer external system owners. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Every unresolved interface failure must have an identified owner before migration readiness can be approved.
Ownership, who actually fixes it.
Resolving historical IDOC failures requires coordinated business and technical investigation. 1. Integration architect analyzes the overall interface landscape and prioritizes remediation efforts. 2. PM functional lead validates missing transactions and determines business impact. 3. Lead ABAP developer investigates custom IDOC processing logic and interface enhancements. 4. Basis lead supports RFC, middleware, and technical communication troubleshooting.
Who gets blamed versus who owns it.
1. Blamed. Basis team accused of allowing interface failures to accumulate. 2. Blamed. External system owners accused of sending invalid messages. 3. Actual owner. Integration architect accountable for ensuring interface governance and end-to-end integration visibility. 4. Root cause. Years of weak monitoring, poor ownership, and unresolved integration exceptions. Failed IDOCs are rarely a technical problem alone. They are usually governance problems disguised as technical issues.
How this is actually fixed the right way by a role.
1. Integration architect categorizes failed IDOCs by interface, business process, and business criticality. 2. PM functional lead determines which missing transactions require remediation or reconciliation. 3. Lead ABAP developer corrects custom mapping logic, validation rules, or processing enhancements responsible for recurring failures. 4. Basis lead validates RFC connectivity, middleware integration, and successful reprocessing execution. The goal is restoring trusted integration flows rather than simply reducing the number of failed messages.
Common mistakes to avoid what not to do.
1. Do not delete failed IDOCs without first understanding their business impact. 2. Do not assume historical interface failures are irrelevant to migration readiness. 3. Do not mass reprocess thousands of IDOCs without validating downstream consequences. 4. Do not proceed with migration until critical interface backlogs have been assessed and resolved.
Follow-up 1. Why do large IDOC backlogs often remain undiscovered for years?
Answer. Many organizations focus on keeping current operations running rather than investigating historical interface exceptions. Over time, users develop manual workarounds that mask the underlying integration failures. As a result, failed IDOCs accumulate without attracting management attention. Migration readiness assessments finally expose these hidden backlogs because they require end-to-end data integrity validation.
Follow-up 2. Why should not all failed IDOCs simply be reprocessed?
Answer. Some failed IDOCs represent obsolete business transactions, retired interfaces, or outdated master data that no longer exists. Blindly reprocessing them can create duplicate records, trigger unexpected business events, or corrupt current data by processing transactions out of their proper chronological sequence. Successful programs first classify failures by business impact before determining the appropriate remediation strategy. Business validation must always precede technical reprocessing.
Follow-up 3. Curveball. Why is this issue often considered a governance problem rather than an integration problem?
Answer. The technology typically provides mechanisms for monitoring, alerting, and correcting interface failures. The real problem arises when organizations fail to assign ownership, enforce escalation procedures, and regularly review integration health. Over time, unresolved failures accumulate because nobody is accountable for addressing them. Migration programs simply expose governance weaknesses that have existed for years.
Real implementation tips. and best practices the 4 Rs.
Recommendation 1. What should be done? Analyze failed IDOC populations early in the prepare phase rather than waiting for integration testing. Recommendation 2. What successful projects do? Reliability. Categorize IDOC failures by business criticality and interface ownership before remediation planning. Recommendation 3. What should be validated? Revalidation. Reconcile business transactions between SAP and connected systems after any large-scale IDOC cleanup effort. Recommendation 4. What should be governed? Responsibility. Establish formal interface ownership, monitoring, and escalation processes for every PM integration.
Migration Incident 40. Custom maintenance cost reports dependent on deprecated ECC tables.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the Custom Code Assessment Team discovers that numerous plant maintenance PM cost analysis reports directly read legacy ECC database tables and structures that are no longer recommended, simplified, or exposed in the same way within the target S/4HANA environment. Many of these reports were developed years ago to provide equipment-level maintenance cost breakdowns, work order analytics, and lifecycle asset cost reporting. If not remediated before conversion, these custom reports may fail, produce incorrect financial results, or create significant performance issues after go live.
Incident classification and relevant SAP note if applicable.
1. Complexity. High custom code and reporting architecture failure. 2. Migration phase, prepare. 3. Frequency, very common in mature ECC landscapes. 4. Primary ownership, lead ABAP developer. 5. Supporting PM functional lead, enterprise solution architect, data migration lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. SAP note 2270689. SAP S/4HANA simplification item checks.
How teams identify this issue. Diagnostic dashboard, symptoms and evidence.
How custom maintenance cost reporting dependencies typically reveal themselves during migration preparation. 1. Symptom. Custom PM cost reports fail ATC validation checks and are flagged for S/4HANA compatibility remediation. 2. Red flag. Custom reports contain direct select statements against legacy ECC financial, controlling, or maintenance order value tables such as PMCO. 3. Business impact. Asset maintenance cost reporting may become unavailable or inaccurate after go live. 4. Detection. ATC analysis identifies obsolete database access patterns and custom programs impacted by S/4HANA simplifications. 5. Technical proof. Simplification analysis and code scans reveal direct dependencies on deprecated ECC data structures like PMCO, requiring redirection to modern compatibility views.
Investigation tools and transactions used.
Use these tools to identify custom reporting dependencies and S/4HANA compatibility risks. 1. ATC ABAP Test Cockpit. Identify custom code objects affected by S/4HANA simplifications and obsolete database access patterns. 2. SYCM Simplification Database. Analyze impacted custom developments against relevant simplification items. 3. SE80 Object Navigator. Review report logic, function modules, classes, and custom reporting frameworks. 4. SQL Monitor SQLM. Identify frequently executed database statements and reporting performance bottlenecks. Architect's rule. Every custom report that reads ECC tables directly must be treated as a potential S/4HANA remediation candidate.
Incident analysis and root cause why this happens.
1. Custom maintenance cost reporting solutions were developed years before S/4HANA simplification principles existed. 2. Developers frequently bypass standard APIs and reporting frameworks to read ECC database tables directly. 3. Business stakeholders continuously requested reporting enhancements without considering long-term architecture implications. 4. Organizations rarely maintain documentation showing which reports depended on specific ECC tables. The root cause is uncontrolled growth of custom reporting solutions built tightly around legacy ECC database structures.
Why this issue appears only during an ECC to S4HANA migration.
1. ECC custom reports often function successfully for years because underlying table structures remain stable. 2. S4HANA introduces simplifications, compatibility views, and modern consumption models that expose legacy reporting assumptions. 3. Migration readiness activities systematically analyze custom code against the target architecture for the first time. 4. Performance expectations in S4HANA require developers to adopt optimized CDS-based reporting approaches rather than legacy table access patterns. Migration exposes reporting technical debt that remained hidden throughout the ECC lifecycle.
Business and program impact.
1. Critical maintenance cost reports may fail immediately after go-live if remediation is incomplete. 2. Finance and maintenance organizations may lose visibility into equipment lifecycle costs and repair spending trends. 3. User acceptance testing expands significantly as hundreds of custom reports require validation. 4. Additional development effort and budget are required to redesign legacy reporting solutions. A reporting failure may not stop the migration, but it can severely undermine business confidence after go-live.
Impact on technicians and maintenance teams.
How broken maintenance cost reporting affects operational users. 1. Maintenance planners lose visibility into equipment repair cost trends used for replacement decisions. 2. Reliability engineers struggle to identify high-cost assets requiring preventive maintenance optimization. 3. Supervisors cannot accurately compare labor, material, and contractor costs across maintenance programs. 4. Management decisions become less data-driven when historical cost analytics are unavailable or inaccurate.
Strategic decision. Remediate, replace, or retire custom cost reports.
Answer: every impacted maintenance cost report must be evaluated against business value, technical complexity, and long-term supportability. 1. Remediate existing reports. Refactor custom code to consume S4HANA compatible structures and APIs. 2. Rebuild using CDS views. Replace legacy reporting logic with modern S4HANA analytical models. 3. Adopt standard analytics. Replace custom reports with standard Fiori analytical applications where feasible. 4. Retire low-value reports. Eliminate reports that provide minimal business value or duplicate existing functionality. Migration is often the best opportunity to reduce custom reporting complexity rather than simply carrying it forward.
Custom report remediation matrix.
A common framework used to determine the future of legacy maintenance cost reports. 1. Business critical and frequently used. Refactor and modernize for S4HANA compatibility. 2. Available in standard Fiori. Replace custom report with standard analytics. 3. Low usage and low value. Retire and remove from scope. 4. Strategic reporting requirement. Rebuild using CDS views and modern reporting architecture. Not every custom report deserves migration investment. Business value must drive remediation decisions.
Governance and accountability RACI model.
Reporting remediation decisions require clear ownership because they affect both technical architecture and business operations. 1. Accountable. Enterprise Solution Architect owns the target state reporting architecture strategy. 2. Responsible. Lead ABAP developer analyzes remediates and validates impacted custom reports. 3. Consulted PM functional lead data migration lead reporting stakeholders. 4. Informed. Program sponsor. Steering committee. Maintenance operations manager. Every business critical custom report should have an approved remediation decision before the first production cutover rehearsal.
Ownership, who actually fixes it.
Resolving custom report dependencies requires coordinated technical and business assessment. 1. Lead ABAP developer identifies impacted reports and performs code remediation activities. 2. PM functional lead validates report outputs and confirms business reporting requirements. 3. Enterprise Solution Architect approves modernization, replacement, or retirement decisions. 4. Data Migration Lead validates historical data availability and reporting consistency after conversion.
Who gets blamed versus who owns it.
1. Blamed. ABAP development team accused of creating reports that no longer function after migration. 2. Blamed. PM functional team accused of requesting excessive custom reporting over the years. 3. Actual owner, enterprise solution architect accountable for ensuring reporting architecture readiness for S/4HANA. 4. Root cause. Years of custom report growth without governance, modernization planning, or architectural standards. Broken reports are usually symptoms of accumulated technical debt, rather than isolated development mistakes.
How this is actually fixed the right way by a role.
1. Lead ABAP developer executes ATC and simplification checks to identify impacted reporting objects. 2. PM functional lead prioritizes reports based on business criticality and operational dependency. 3. Enterprise solution architect approves modernization, replacement, or retirement decisions for each reporting solution. 4. Lead ABAP developer refactors reporting logic using CDS views, APIs, compatibility views, or approved S/4HANA reporting patterns. Successful remediation focuses on long-term reporting architecture rather than short-term technical workarounds.
Common mistakes to avoid what not to do.
1. Do not assume custom ECC reports will automatically function after migration. 2. Do not postpone custom code remediation until user acceptance testing. 3. Do not replicate every legacy report without validating current business value. 4. Do not bypass ATC and simplification analysis during migration preparation.
Follow-up 1. Why are maintenance cost reports particularly vulnerable during S/4HANA migration?
Answer. Maintenance cost reports often combine data from plant maintenance, controlling, materials management, and financial accounting. Many legacy reports were built using direct database reads against specific value tables like PMCO that were optimized for ECC. During migration, S/4HANA's Universal Journal merges these ledgers, exposing these direct dependencies and requiring them to be validated against the target data model. As a result, cross-modular cost reporting is frequently one of the largest custom code remediation workstreams.
Follow-up 2. Why are CDS views frequently recommended instead of direct table access?
Answer. CDS views provide a supported, performance-optimized, and semantically rich way to consume business data in S/4HANA. They abstract underlying database complexity and help shield custom developments from future structural changes. By using CDS views, developers align reporting solutions with SAP's strategic architecture direction. This significantly improves maintainability, performance, and long-term supportability.
Follow-up 3 curveball. Why can a technically working report still be considered a migration defect?
Answer. A report may execute successfully yet still produce inaccurate, incomplete, or misleading business results after migration. Technical execution alone does not guarantee functional correctness. Migration teams must validate calculations, data sources, reconciliation logic, and business outputs against expected results. A report that runs but delivers incorrect maintenance cost information represents a critical business defect.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization, execute ATC and simplification analysis on all custom PM reporting objects during the early prepare phase. Recommendation 2. What successful projects do? Reliability, create a formal inventory ranking custom reports by business criticality and remediation complexity. Recommendation 3. What should be validated? Revalidation, reconcile report outputs between ECC and S/4HANA sandbox environments using representative business scenarios. Recommendation 4. What should be governed? Responsibility, establish reporting architecture standards that prioritize CDS views, APIs, and standard analytics over direct database access.
Migration Incident 41. Maintenance plans scheduling inconsistencies found during cleanup.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, the data cleansing team discovers significant inconsistencies within plant maintenance PM maintenance plan scheduling records. Over years of operational use, maintenance plans were manually adjusted, cycle definitions were modified without governance, scheduling parameters became inconsistent, and obsolete maintenance items remained active. During migration readiness validation, these inconsistencies surface as scheduling conflicts, overdue call anomalies, incorrect maintenance forecasts, and inaccurate preventive maintenance projections. If left unresolved, the target S/4HANA system may generate incorrect maintenance calls, creating operational and compliance risks immediately after go live.
Incident classification and relevant SOP, note if applicable.
1. Complexity. Medium preventive maintenance data quality failure. 2. Migration phase, prepare. 3. Frequency, common and mature PM landscapes. 4. Primary ownership, PM functional lead. 5. Supporting, data migration lead, basis lead, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SOP note. Not applicable, maintenance plan scheduling data consistency validation required.
How teams identified this issue diagnostic dashboard, symptoms and evidence.
How maintenance plan scheduling inconsistencies typically reveal themselves during migration preparation activities. 1. Symptom. Maintenance plans generate unexpected scheduling dates, duplicate calls, or overdue preventive maintenance forecasts during validation exercises. 2. Red flag. Large volumes of maintenance plans contain manually overridden scheduling parameters, obsolete cycles, or inactive maintenance items that remain linked to active plans. 3. Business impact. Maintenance planners cannot reliably forecast future work, increasing operational risk and reducing confidence in preventive maintenance schedules. 4. Detection. Data cleansing workshops and maintenance plan validation exercises identify discrepancies between expected and system-generated scheduling dates. 5. Technical proof. Analysis of maintenance plans and scheduling histories reveals inconsistent cycle definitions, incorrect call horizons, and outdated scheduling parameters.
Investigation tools and transactions used.
Use these tools and transactions to identify scheduling inconsistencies and maintenance plan defects. 1. IP03 Display Maintenance Plan. Review maintenance plan configuration, scheduling parameters, and historical scheduling behavior. 2. IP10 Schedule Maintenance Plans. Execute scheduling simulations and validate future maintenance call generation logic. 3. IP15 Maintenance Plan List. Analyze maintenance plan populations and identify plans requiring remediation. 4. SE16 N-Table Browser. Review maintenance plan scheduling records and historical scheduling data for inconsistency analysis. Architect's Rule. Never assume that historical maintenance plan schedules are accurate simply because work orders were generated successfully in ECC.
Incident analysis and root cause why this happens.
1. Maintenance planners manually adjusted scheduling dates over many years without updating underlying maintenance plan logic. 2. Preventive maintenance cycles evolved as equipment strategies changed, but legacy plans were never fully restructured. 3. Organizations lacked governance controls to periodically review inactive maintenance items and obsolete scheduling definitions. 4. Migration programs often prioritize transactional data quality while overlooking preventive maintenance master data. The root cause is years of unmanaged maintenance plan evolution without systematic scheduling governance controls.
Why this issue appears only during an ECC to S/4HANA migration.
1. Maintenance plan defects can remain hidden for years because planners compensate manually for scheduling inaccuracies. 2. Migration readiness activities force organizations to validate preventive maintenance data at scale for the first time. 3. Data cleansing exercises expose scheduling anomalies that were previously masked by operational workarounds. 4. S/4HANA programs place significantly greater emphasis on data quality, automation, and schedule reliability. Migration preparation often reveals preventive maintenance defects that daily operations have quietly tolerated for years.
Business and program impact.
1. Migration timelines expand as maintenance plans must be reviewed, corrected, and revalidated before conversion. 2. Preventive maintenance forecasts become unreliable, increasing operational planning uncertainty. 3. Maintenance organizations risk generating duplicate, premature, or missed maintenance activities after go live. 4. Additional workshops are required to reconcile maintenance strategies with actual scheduling configurations. Poor maintenance plan quality creates operational risk long after the technical migration has been completed.
Impact on technicians and maintenance teams.
How maintenance plan scheduling defects affect field operations. 1. Technicians receive work orders at incorrect intervals, reducing preventive maintenance effectiveness. 2. Maintenance planners spend excessive time manually adjusting schedules instead of optimizing maintenance strategies. 3. Supervisors lose confidence in maintenance forecasts used for labor and shutdown planning. 4. Critical assets may become over-maintained or under-maintained due to inaccurate scheduling logic.
Governance and accountability RACI model.
Maintenance plan remediation requires clear ownership because scheduling quality directly affects operational reliability. 1. Accountable. PM functional lead owns preventive maintenance process integrity and maintenance plan readiness. 2. Responsible. PM functional lead and data migration lead identify, correct, and validate scheduling inconsistencies. 3. Consulted. Maintenance operations manager basis lead. 4. Informed. Program sponsor, steering committee, plant leadership. Preventive maintenance scheduling quality is a business process responsibility supported by migration governance.
Ownership, who actually fixes it.
Resolving maintenance plan scheduling inconsistencies requires both functional validation and data cleansing activities. 1. PM functional lead reviews maintenance strategies, cycle definitions, and scheduling logic. 2. Data migration lead identifies affected maintenance plans and coordinates remediation activities. 3. Maintenance operations manager validates future scheduling outputs against operational requirements. 4. Basis lead supports testing and scheduling simulations during migration validation cycles.
Who gets blamed versus who owns it.
1. Blamed. Maintenance planners accused of maintaining inaccurate preventive maintenance schedules. 2. Blamed. Data migration team accused of introducing scheduling discrepancies during cleansing activities. 3. Actual owner. PM functional lead, accountable for validating maintenance plan logic and scheduling integrity. 4. Root cause. Failure to govern maintenance plan lifecycle management and scheduling data quality over time. Scheduling inconsistencies are usually the result of years of process drift, rather than a single migration activity.
How this is actually fixed the right way by a role.
1. PM functional lead reviews maintenance strategies, maintenance items, and scheduling parameters for all affected plans. 2. Data migration lead identifies inconsistent scheduling records and coordinates cleansing activities. 3. Maintenance operations manager validates future maintenance call projections against real operational requirements. 4. PM functional lead executes scheduling simulations and confirms that corrected plans generate expected maintenance calls. Successful remediation requires schedule validation, business sign-off, and repeated simulation testing before conversion.
Common mistakes to avoid what not to do.
1. Do not migrate maintenance plans without validating future scheduling outputs. 2. Do not assume historical scheduling behavior reflects correct preventive maintenance logic. 3. Do not postpone maintenance plan cleansing until user acceptance testing. 4. Do not rely solely on technical validation without maintenance planner review and approval.
Follow-up 1. Why do maintenance plan scheduling defects often remain hidden for years in ECC environments?
Answer. Maintenance organizations frequently compensate for scheduling inaccuracies through manual intervention and planner experience. As a result, underlying maintenance plan defects remain undetected because operational work continues successfully. Over time, manual overrides become accepted practice, and the original scheduling logic is rarely reviewed. Migration readiness activities finally expose these hidden inconsistencies through systematic validation and simulation exercises.
Follow-up 2. Why is maintenance plan validation considered a business activity rather than a technical activity?
Answer. Technical teams can verify that scheduling records are complete and system logic executes correctly, but they cannot determine whether generated maintenance calls align with operational requirements. Only maintenance planners and business stakeholders understand the intended maintenance strategy for each asset. Therefore, schedule validation requires business ownership and formal operational sign-off. Technical correctness alone does not guarantee maintenance effectiveness.
Follow-up 3 curveball. Why can a technically successful migration still fail due to maintenance plan issues?
Answer. A migration may complete successfully from a technical perspective while still introducing major operational disruption. If maintenance plans generate incorrect call dates, technicians may perform work too early, too late, or not at all. These issues can affect asset reliability, compliance obligations, and maintenance productivity. Consequently, maintenance plan quality is often as important as technical conversion success.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: execute comprehensive maintenance plan validation and scheduling simulations early in the prepare phase. Recommendation 2. What successful projects do? Reliability: successful programs review high-risk maintenance plans with planners before executing sandbox conversions. Recommendation 3. What should be validated? Revalidation: validate future maintenance call forecasts against expected business schedules using representative assets. Recommendation 4. What should be governed? Responsibility: establish ongoing governance processes for maintenance plan lifecycle management and scheduling quality.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Migration Incident 42. Technical Object Hierarchy Loops caused validation failures.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, data validation activities identify circular references within the technical object hierarchy. Over many years, organizational restructuring, plant consolidations, mass uploads, and manual master data maintenance introduced invalid parent-child relationships between functional locations and equipment records. As migration readiness checks intensify, these hierarchy loops trigger validation failures because technical objects cannot logically be both descendants and ancestors of one another. If left unresolved, hierarchy-dependent applications, reporting structures, maintenance planning processes, and asset navigation functions may fail after migration.
Incident Classification and Relevant SAP, note if applicable.
1. Complexity, high technical object master data integrity failure. 2. Migration phase, prepare. 3. Frequency, common in older and decentralized PM landscapes. 4. Primary ownership, PM functional lead. 5. Supporting, data migration lead, basis lead, lead ABAP developer. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note, not applicable. Technical object, hierarchy, integrity validation required.
How teams identified this issue. Diagnostic dashboard, symptoms and evidence.
How technical object hierarchy loops typically reveal themselves during migration preparation activities. 1. Symptom. Hierarchy validation reports fail and identify technical objects that recursively reference themselves through parent-child relationships. 2. Red flag. Functional locations appear multiple times within the same hierarchy path or indirectly reference themselves through subordinate objects. 3. Business impact. Maintenance planners lose confidence in asset hierarchies used for planning, reporting, and cost roll-ups. 4. Detection. Data cleansing and hierarchy validation exercises identify circular references and orphan technical object structures. 5. Technical proof. Hierarchy analysis reveals recursive parent-child chains that prevent successful hierarchy traversal and validation.
Investigation tools and transactions used.
Use these tools and transactions to identify hierarchy corruption and circular references. 1. IH01 structure display. Analyze technical object hierarchies and identify abnormal parent-child relationships. 2. IL03 display functional location. Review functional location hierarchy assignments and superior location references. 3. SE16N table browser. Analyze hierarchy-related tables such as IFLOT for circular references and orphan records. 4. Data validation reports. Execute hierarchy consistency analysis to identify recursive and invalid hierarchy paths. Architect's rule. Never migrate technical object hierarchies without validating structural integrity and eliminating circular references.
Incident analysis and root cause why this happens.
1. Years of manual hierarchy restructuring introduced invalid superior object assignments without comprehensive validation. 2. Legacy mass upload utilities created parent-child relationships without enforcing hierarchy integrity controls. 3. Plant reorganizations merged technical object structures while leaving obsolete hierarchy references active. 4. Organizations lacked periodic master data audits to identify and correct hierarchy inconsistencies. The root cause is long-term degradation of technical object hierarchy governance and validation controls.
Why this issue appears only during an ECC to S/4HANA migration.
1. Hierarchy loops can remain hidden for years because daily maintenance transactions may only access small portions of the hierarchy. 2. Migration readiness activities force organizations to validate the entire technical object structure as a single integrated hierarchy. 3. Data cleansing exercises expose structural defects that were previously masked by operational workarounds. 4. Modern reporting Fiori applications and hierarchy-driven analytics depend on accurate and traversable asset structures. Migration validation often exposes technical object hierarchy defects that accumulated unnoticed over many years.
Business and program impact.
1. Migration activities are delayed while hierarchy defects are investigated and corrected. 2. Asset reporting structures become unreliable due to incorrect hierarchy relationships. 3. Maintenance cost roll-ups and equipment performance reporting may produce inaccurate results. 4. Additional master data cleansing cycles increase project duration and resource requirements. Hierarchy integrity is foundational to maintenance planning, reporting, and asset management processes.
Impact on technicians and maintenance teams.
How hierarchy loops directly affect maintenance operations. 1. Technicians struggle to navigate equipment structures because hierarchy paths become confusing or incomplete. 2. Maintenance planners cannot accurately identify parent-child asset relationships during planning activities. 3. Supervisors lose visibility into equipment populations located beneath specific functional locations. 4. Reliability teams encounter difficulties performing hierarchy-based analysis and reporting.
Governance and accountability RACI model.
Hierarchy remediation requires clear ownership because technical object structures support multiple business processes. 1. Accountable. PM functional lead owns technical object hierarchy integrity and maintenance master data quality. 2. Responsible. PM functional lead and data migration lead identify, analyze, and remediate hierarchy defects. 3. Consulted. Maintenance operations manager basis lead. 4. Informed. Program sponsor, steering committee, plant leadership. Technical object hierarchy quality is ultimately a business data responsibility supported by migration governance.
Ownership, who actually fixes it.
Resolving hierarchy loops requires detailed analysis of technical object relationships and business validation. 1. PM functional lead reviews hierarchy structures and determines the correct parent-child relationships. 2. Data migration lead identifies affected technical objects and coordinates remediation activities. 3. Maintenance operations manager validates the corrected hierarchy against operational reality. 4. Basis lead supports hierarchy validation testing and migration readiness activities.
Who gets blamed versus who owns it.
1. Blamed. Data migration team accused of creating hierarchy issues during cleansing activities. 2. Blamed. Maintenance planners accused of maintaining inaccurate technical object structures. 3. Actual owner. PM functional lead, accountable for technical object hierarchy integrity and validation. 4. Root cause. Failure to govern hierarchy maintenance and periodically validate structural consistency. Hierarchy loops are usually the result of years of accumulated master data drift, rather than a single migration activity.
How this is actually fixed the right way by a role.
1. Data migration lead executes hierarchy validation analysis and identifies all circular references and structural anomalies. 2. PM functional lead reviews affected technical objects and defines the correct hierarchy relationships. 3. Maintenance operations manager validates the corrected hierarchy against actual plant structures and operational requirements. 4. PM functional lead re-executes hierarchy validation and confirms that all technical object structures pass integrity checks. Successful remediation requires technical correction, business validation, and repeated hierarchy consistency testing.
Common mistakes to avoid what not to do.
1. Do not migrate technical object hierarchies without performing comprehensive integrity validation. 2. Do not manually restructure hierarchy relationships without business review and approval. 3. Do not assume hierarchy defects are harmless simply because daily maintenance transactions continue to function. 4. Do not postpone hierarchy remediation until user acceptance testing.
Follow-up 1. Why can technical object hierarchy loops remain undetected for many years?
Answer: most operational users interact with only a small subset of the overall asset hierarchy during their daily work. As a result, circular references may never become visible during normal maintenance activities. Over time, manual workarounds and localized knowledge compensate for hierarchy issues. Migration readiness validation is often the first activity that systematically evaluates the entire hierarchy structure.
Follow-up 2. Why are hierarchy loops considered a serious master data issue?
Answer: asset hierarchies support maintenance planning, reporting, cost roll-ups, reliability analysis, and navigation across technical objects. Circular references break the logical structure of these hierarchies and can prevent systems from correctly traversing parent-child relationships. This impacts both operational processes and analytical reporting. As a result, hierarchy integrity is a fundamental master data quality requirement.
Follow-up 3. Curveball. Why can a technically successful migration still fail operationally because of hierarchy defects?
Answer: the technical conversion may complete successfully while underlying hierarchy defects remain unresolved. After go live, planners, technicians, and reliability engineers may struggle to navigate asset structures or generate accurate reports. Incorrect hierarchies can also affect maintenance planning and performance analysis. Therefore, operational success depends on hierarchy quality as much as technical migration success.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization: execute comprehensive hierarchy integrity validation across all functional locations and equipment before sandbox conversion activities. Recommendation 2. What successful projects do? Reliability successful programs conduct dedicated technical object hierarchy workshops with maintenance planners before migration testing begins. Recommendation 3. What should be validated? Revalidation: validate corrected hierarchy structures using real maintenance planning, reporting, and asset navigation scenarios. Recommendation 4. What should be governed? Responsibility: establish ongoing governance controls that prevent future hierarchy corruption and circular reference creation.
Migration Incident 43. Plant maintenance LIS obsolescence ignored, breaking legacy PM analytics readiness.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams discover that a significant portion of plant maintenance reporting relies on legacy logistics information system LIS structures such as S061 through S065. Over many years, planners, reliability engineers, and maintenance managers have become dependent on LIS-based reports for backlog analysis, equipment history trending, order analytics, and maintenance performance monitoring. During migration readiness activities, the team fails to assess these dependencies and assumes that the reports will continue functioning unchanged after conversion. As S/4HANA shifts reporting strategies toward embedded analytics, CDS views, and Fiori analytical applications, the organization faces a major analytics readiness gap that threatens business reporting continuity.
Incident classification and relevant SAP, note if applicable.
1. Complexity: high reporting architecture modernization failure. 2. Migration phase, prepare. 3. Frequency, common and mature ECC landscapes. 4. Primary ownership, enterprise solution architect. 5. Supporting PM functional lead, analytics lead, lead ABAP developer, basis lead. 6. Business ownership, maintenance operations manager. 7. Relevant SAP note. SAP note 226934. SAP S/4HANA simplification item information for logistics information system.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How hidden LIS reporting dependencies typically reveal themselves during migration preparation. 1. Symptom: key maintenance reports used by planners and managers are missing, incomplete, or unsupported in early S/4HANA sandbox demonstrations. 2. Red flag: business users identify heavy reliance on LIS information structures S061, S062, S063, S064, and S065 during reporting workshops. 3. Business impact: maintenance leadership loses visibility into backlog trends, equipment reliability metrics, and historical maintenance performance indicators. 4. Detection: Readiness assessments and custom code scans reveal extensive usage of LIS transactions, custom LIS extractors, and Z reports reading information structures directly. 5. Technical proof. SQL analysis and usage statistics show custom programs executing direct reads against LIS information structures and associated update tables.
Investigation tools and transactions used.
Use these tools to identify legacy reporting dependencies and determine analytics modernization requirements. 1. MCJB or MCI7 or MCIS or MCI8. Identify actively used PMLIS reports and determine business reporting dependencies. 2. SCMON usage and procedure logging. Capture actual report execution patterns and identify frequently used LIS-dependent custom programs. 3. SQL monitor. Detect custom reports reading directly from LIS information structures or update tables. 4. ABAP test cockpit. Identify custom analytics programs that require redesign for S/4HANA compatibility and optimization. Architect's rule. Inventory every business report before conversion. Unknown reporting dependencies become executive escalations after go live.
Incident analysis and root cause why this happens.
1. Organizations continue using LIS reports for decades because they reliably support operational reporting requirements. 2. Project teams focus heavily on transactional process conversion while overlooking reporting architecture modernization. 3. Business users often cannot distinguish between standard ECC reports and LIS-based reporting frameworks. 4. Custom PM analytics evolve around LIS structures, creating hundreds of undocumented reporting dependencies. The root cause is treating reporting as a secondary workstream rather than a critical business continuity requirement.
Why this issue appears only during an ECC to S/4HANA migration.
1. Legacy ECC environments continue operating successfully because LIS structures remain available and business processes have evolved around them. 2. S/4HANA encourages a fundamentally different analytics strategy centered around CDS views, embedded analytics, Fiori applications, and real-time reporting models. 3. Migration readiness assessments expose historical reporting dependencies that were never formally documented. 4. Business users frequently assume that legacy reporting functionality will automatically exist in S/4HANA without redesign or replacement. S/4HANA migration is often the first time organizations fully discover the true scope of their reporting architecture.
Business and program impact.
1. Critical maintenance KPI reporting becomes unavailable or significantly delayed after conversion. 2. Additional project effort is required to redesign reports, dashboards, and management analytics late in the migration lifecycle. 3. User acceptance testing experiences significant disruption as business stakeholders discover missing reporting capabilities. 4. Executive confidence declines when operational reporting continuity cannot be demonstrated during sandbox and rehearsal activities. Loss of reporting visibility can create more business concern than transactional process changes.
Strategic decision. Evaluating PM analytics modernization options.
Answer: resolving LIS obsolescence requires selecting an analytics architecture that aligns with the organization's future reporting strategy. 1. Embedded analytics strategy. Rebuild legacy PM reporting using CDS views and Fiori analytical applications. 2. SAP Analytics Cloud strategy. Migrate executive dashboards and KPI monitoring into SAP Analytics Cloud. 3. Hybrid reporting model. Retain selected legacy reports temporarily while modernizing critical business analytics in phases. 4. Custom analytics redevelopment. Re-engineer heavily customized LIS reports using S/4HANA compliant reporting frameworks. The best migration programs replace reporting dependencies before go live rather than after user complaints emerge.
PM Analytics Modernization Decision Matrix.
A structured framework for determining the appropriate modernization path. 1. Low LIS usage. Replace directly with standard embedded analytics content where available. 2. Operational planner reporting. Rebuild using CDS views and Fiori analytical applications. 3. Executive KPI dashboards. Transition to SAP Analytics Cloud and Enterprise Reporting Platforms. 4. Heavy custom LIS dependency. Conduct full reporting redesign and establish a formal analytics modernization project. Not every LIS report should be rebuilt. Many can be retired through business process simplification.
Governance and accountability, RACI model.
Reporting modernization requires governance because analytics affect every business stakeholder. 1. Accountable. Enterprise Solution Architect owns the future state analytics architecture and reporting strategy. 2. Responsible. Analytics lead and PM functional lead inventory reports identify business requirements and define replacement solutions. 3. Consulted. Lead a BAP developer basis lead reporting governance team. 4. Informed. Program sponsor, steering committee, maintenance operations manager. Organizations that govern reporting early avoid emergency dashboard rebuilds near cutover.
Ownership, who actually fixes it.
Resolving reporting architecture risks requires collaboration across business, analytics, and technical teams. 1. Enterprise Solution Architect defines the target analytics architecture and modernization roadmap. 2. PM Functional Lead inventories business reporting requirements and validates replacement reporting capabilities. 3. Analytics Lead maps legacy LIS reports to CDS views, Fiori Analytics, SAC dashboards, or custom solutions. 4. Lead a BAP developer remediates custom reporting programs and eliminates unsupported reporting dependencies.
Who gets blamed versus who owns it.
1. Blamed. PM functional team accused of failing to identify critical reporting requirements during workshops. 2. Blamed. Analytics team accused of not rebuilding reports before testing began. 3. Actual owner. Enterprise Solution Architect, accountable for ensuring reporting architecture assessment was included in migration readiness planning. 4. Root cause. Failure to inventory and modernize legacy reporting dependencies before initiating conversion activities.
How this is actually fixed the right way by a role.
1. Analytics lead inventories all active LIS reports, information structures, dashboards, and custom reporting programs. 2. PM functional lead prioritizes business-critical reports and validates future state reporting requirements. 3. Lead a BAP developer remediates custom reporting logic and develops replacement CDS-based reporting solutions where necessary. 4. Enterprise Solution Architect approves the modernization roadmap and validates reporting readiness before production cutover. Successful migrations modernize analytics before business users discover missing information after go live.
Common mistakes to avoid what not to do.
1. Do not assume legacy LIS reports will continue functioning unchanged after conversion. 2. Do not postpone reporting inventory activities until user acceptance testing begins. 3. Do not rebuild every historical report without first validating actual business usage. 4. Do not ignore executive reporting requirements while focusing exclusively on transactional processes.
Follow-up 1. Why are LIS dependencies frequently discovered late in S/4HANA migration programs?
Answer. LIS dependencies are often discovered late because reporting workstreams typically receive less attention than transactional conversion activities. Many business users have relied on the same reports for years without understanding the underlying technical architecture. During readiness assessments, teams focus heavily on master data, integrations, and custom code, while reporting dependencies remain undocumented. The issue usually surfaces only when business users attempt to execute familiar reports in a sandbox environment.
Follow-up 2. Why should CDS views be considered when replacing PM/LIS reporting?
Answer. CDS views are a core reporting foundation in S/4HANA because they provide real-time access to operational data without relying on traditional aggregate structures. They support embedded analytics, Fiori applications, and modern reporting frameworks while remaining aligned with SAP's strategic architecture direction. Rebuilding reporting on CDS views improves maintainability, performance, and long-term compatibility with future S/4HANA releases.
Follow-up 3 curveball. Why is reporting continuity often more visible to executives than transactional readiness?
Answer. Executives typically consume dashboards, KPI, and management reports rather than executing maintenance transactions directly. Even when transactional processes function correctly, missing analytics can create the perception that the migration failed because decision makers lose operational visibility. Reporting outages become highly visible immediately after go live, making analytics readiness a critical business adoption factor. Successful migration programs, therefore, treat reporting continuity as a core readiness milestone.
Real implementation tips and best practices, the 4 Rs.
Recommendation 1. What should be done? Realization: perform a complete inventory of all LIS reports, dashboards, and custom PM analytics during the discover phase. Recommendation 2. What successful projects do? Reliability leading programs establish a dedicated reporting modernization workstream separate from transactional conversion activities. Recommendation 3. What should be validated? Revalidation: validate every critical maintenance KPI and management report in the sandbox environment before user acceptance testing begins. Recommendation 4. What should be governed? Responsibility: establish formal analytics governance to ensure all future reporting solutions align with the target S/4HANA architecture.
Migration Incident 44. MRP Live impacts on maintenance component planning undocumented.
During the prepare phase of an SAP ECC to SAP S/4HANA migration, project teams discover that the organization's maintenance component planning process relies heavily on legacy MRP behaviors that were never formally documented. As migration workshops progress, the PP and PM teams realize that MRP Live introduces different planning logic, performance optimization mechanisms, and material planning execution paths compared to traditional ECC MRP processing. Because no impact assessment was performed, planners cannot determine whether maintenance order reservations, spare part procurement triggers, stock planning assumptions, and shutdown material availability will behave as expected after conversion.
Incident classification and relevant SAP note if applicable.
1. Complexity: high cross-functional planning architecture risk. 2. Migration phase: prepare. 3. Frequency: common in PM-intensive manufacturing and asset-intensive industries. 4. Primary ownership: enterprise solution architect. 5. Supporting: PM functional lead, PP functional lead, supply chain lead, basis lead. 6. Business ownership: maintenance operations manager. 7. Relevant SAP note. SAP note 1914010 MD01N. Restrictions for planning in MRP Live on HANA.
How teams identify this issue: diagnostic dashboard, symptoms and evidence.
How undocumented MRP Live dependencies typically reveal themselves during migration readiness activities. 1. Symptom: maintenance planners observe different procurement proposals, shortage calculations, or material availability results during sandbox testing. 2. Red flag: business workshops reveal that no formal documentation exists describing how maintenance components are planned, reserved, or replenished today. 3. Business impact: planned shutdowns and preventive maintenance activities face increased risk because spare part availability assumptions cannot be validated. 4. Detection: integrated PP and PM testing identifies differences between ECC planning outputs and S/4HANA MRP Live planning results. 5. Technical proof: simplification item checks and planning simulations produce different exception messages, procurement recommendations, or classic MRP fallback behaviors compared to legacy ECC runs.
Investigation tools and transactions used.
Use these tools and transactions to identify planning dependencies and validate maintenance component planning behavior. 1. MD01N MRP Live. Execute HANA-based planning runs and compare planning outcomes against legacy ECC expectations. 2. MD04 stock or requirements list. Analyze material demand, reservations, shortages, and procurement proposals associated with maintenance orders. 3. IW32 change maintenance order. Review component reservations, plan materials, and maintenance order planning dependencies. 4. MD_MRP_force_classic. Validate planning triggers and identify materials that require fallback to classic MRP processing due to unsupported MRP Live parameters. Architect's rule: Never assume that maintenance component planning behaves identically after migration. Validate it through end-to-end planning simulations.
Incident analysis and root cause why this happens.
1. Organizations focus heavily on transactional PM processes while overlooking the planning engines that supply maintenance materials. 2. Legacy ECC planning behaviors evolve over many years through custom settings, planning parameters, and undocumented operational workarounds. 3. PP and PM teams often operate independently, creating a lack of visibility into cross-functional planning dependencies. 4. Migration readiness programs prioritize technical conversion activities and delay planning validation until integrated testing begins. The root cause is failing to treat maintenance material planning as a critical business capability, requiring formal migration assessment.
Why this issue appears only during an ECC to S/4HANA migration.
1. Traditional ECC environments continue operating successfully because existing planning assumptions have been embedded into daily operational processes for years. 2. S/4HANA introduces MRP Live, which leverages HANA-based planning execution and may alter planning performance, execution paths, and optimization behavior. 3. Migration readiness testing exposes planning dependencies that were never formally documented in legacy environments. 4. Integrated testing frequently reveals that maintenance planners rely on historical planning outcomes rather than documented planning rules. Migration programs often expose hidden planning assumptions that were never visible during routine ECC operations.
Business and program impact.
1. Critical maintenance activities face increased risk due to uncertainty around spare part availability and replenishment timing. 2. Integrated testing cycles expand significantly as PP and PM teams investigate planning discrepancies. 3. Project timelines are extended while planning rules, material strategies, and reservation processes are validated. 4. Business confidence declines when maintenance planners cannot reliably predict future material availability after migration. Even when maintenance orders function correctly, planning uncertainty can undermine operational readiness.
Impact on technicians and maintenance teams.
How undocumented planning impacts directly affect maintenance operations. 1. Technicians arrive at scheduled maintenance activities only to discover that required spare parts were never procured or reserved correctly. 2. Maintenance planners spend excessive time manually validating stock availability instead of focusing on reliability planning. 3. Shutdown and turnaround schedules become vulnerable to unexpected material shortages. 4. Field teams lose confidence in automated planning recommendations and revert to manual inventory verification processes.
Strategic decision. Evaluating maintenance planning readiness.
Answer: resolving MRP Live uncertainty requires selecting a structured validation and planning modernization strategy before cutover activities begin. 1. Full MRP Live adoption. Validate all maintenance material planning scenarios and transition completely to MRP Live processing. 2. Phased planning transition. Gradually move selected material groups and planning scenarios to MRP Live while maintaining controlled business oversight. 3. Classic MRP fallback configuration. Strategically configure specific complex spare parts to process via classic MRP while standardizing the broader inventory on MRP Live. 4. Planning redesign initiative. Reassess planning parameters, procurement strategies, and maintenance material governance processes. The most successful programs validate planning outcomes rather than assuming functional equivalence between ECC and S/4HANA.
Maintenance component planning decision matrix.
A structured framework used to determine the correct planning readiness approach. 1. Simple maintenance inventory environment. Execute standard MRP Live validation and proceed with adoption. 2. Heavy shutdown planning dependency. Conduct extensive simulation cycles and business validation before cutover approval. 3. Large number of critical spare parts. Review planning parameters and establish enhanced governance controls. 4. Complex PP and PM integration landscape. Launch a dedicated planning readiness workstream before migration execution. Planning accuracy should be measured through business outcomes, not technical configuration completion.
Governance and accountability, Ray C. model.
Planning readiness requires governance because inventory availability directly impacts maintenance execution. 1. Accountable. Enterprise Solution Architect owns the end-to-end planning architecture readiness strategy. 2. Responsible. PM Functional Lead and PP Functional Lead validate planning outcomes and document cross-functional planning dependencies. 3. Consulted. Supply Chain Lead, Basis Lead, Data Migration Lead. 4. Informed. Program Sponsor, Steering Committee, Maintenance Operations Manager. Organizations that govern planning readiness early avoid costly operational surprises after go-live.
Ownership, who actually fixes it.
Resolving planning uncertainty requires technical validation and business process alignment. 1. Enterprise Solution Architect defines the planning readiness framework and migration validation strategy. 2. PM Functional Lead validates maintenance order component planning, reservations, and spare part requirements. 3. PP Functional Lead analyzes MRP live behavior and confirms planning outputs align with business expectations. 4. Supply Chain Lead validates procurement lead times, inventory policies, and replenishment strategies.
Who gets blamed versus who owns it.
1. Blamed. PM Functional Team accused of failing to identify material shortages before testing activities. 2. Blamed. Supply Chain Team accused of creating planning parameters that no longer generate expected procurement recommendations. 3. Actual Owner. Enterprise Solution Architect, accountable for ensuring that planning readiness assessments were included in migration scope. 4. Root Cause. Failure to document and validate maintenance component planning behavior before migration testing began. Planning failures are usually architecture and governance failures rather than isolated configuration defects.
How this is actually fixed the right way by a role.
1. PM Functional Lead identifies critical maintenance orders and validates component planning outcomes across representative business scenarios. 2. PP Functional Lead executes MRP live simulations and compares planning outputs against ECC baseline results. 3. Supply Chain Lead validates procurement proposals, inventory strategies, and replenishment assumptions. 4. Enterprise Solution Architect approves the final planning readiness assessment before production cutover authorization. Successful remediation requires simulation, validation, documentation, and business sign-off before migration execution.
Common mistakes to avoid what not to do.
1. Do not assume that maintenance material planning outcomes will automatically match historical ECC behavior. 2. Do not limit testing to maintenance order execution while ignoring planning and replenishment processes. 3. Do not postpone MRP live validation until user acceptance testing. 4. Do not approve production cutover without documented planning readiness sign-off from both PP and PM stakeholders.
Follow-up 1. Why is MRP live assessment important for maintenance operations during an S/4HANA migration?
Answer. Maintenance execution depends heavily on timely availability of spare parts, consumables, and repair materials. While maintenance orders may migrate successfully, planning issues can still disrupt operations if procurement recommendations and replenishment calculations behave differently after conversion. MRP live assessment helps identify these risks before go live. This allows organizations to validate planning outcomes and avoid unexpected maintenance material shortages.
Follow-up 2. Why should PP and PM teams jointly participate in migration readiness testing?
Answer. Maintenance planning often relies on processes that span multiple functional domains, including production planning, procurement, inventory management, and maintenance execution. PP teams understand planning engine behavior, while PM teams understand operational maintenance requirements. Joint testing ensures that planning recommendations support real-world maintenance activities. This significantly reduces the risk of post-go-live operational disruptions.
Follow-up 3 curveball. Why can a technically successful migration still fail from a planning perspective?
Answer. A migration can be technically successful if systems convert correctly, interfaces function, and data migrates without errors. However, the business may still experience operational failures if planning outcomes no longer support maintenance execution. Missing spare parts, delayed procurement recommendations, or inaccurate replenishment logic can disrupt critical maintenance schedules. Planning readiness is therefore just as important as technical readiness.
Real implementation tips and best practices, the 4 R's.
Recommendation 1. What should be done? Realization, execute, end. To end maintenance material planning simulations during the prepare phase and document all planning dependencies. Recommendation 2. What successful projects do? Reliability leading organizations establish dedicated PP and PM planning readiness workshops before integrated testing begins. Recommendation 3. What should be validated? Revalidation, validate procurement proposals, shortages, reservations, and replenishment recommendations using representative maintenance scenarios. Recommendation 4. What should be governed? Responsibility, establish formal planning governance and sign-off procedures to ensure business ownership of planning outcomes before cut over.
Category 2, key takeaways. Prepare phase migration incidents conclusion.
That wraps up Category 2, prepare phase incidents. The overarching lesson is that technical readiness does not equal business readiness. Passing your ABAP test cockpit scans, resolving simplification item check blocks, and getting green lights on your readiness dashboard are only half the battle. If your master data is corrupt, your business partner conversions are inconsistent, and your team lacks a clear data cleansing strategy, the conversion will inevitably stall. The prepare phase is where you must ruthlessly clean your legacy technical debt.
Part 1, key takeaways. Discover and prepare migration incidents mastery.
As we conclude our analysis of incidents 1 through 44, keep these 4 architectural rules at the center of your readiness strategy. 1. Strategy decisions must be data-driven. Never select a system conversion path based on SI estimates or timeline assumptions without running full sizing and custom code scans first. 2. Data cleansing is not an IT task. The PM functional team, operations leads, and business stakeholders must actively own the cleansing of obsolete technical objects, duplicate serial numbers, and inaccurate measuring points. 3. CVI is a cross-functional lifecycle boundary. Business partner conversion is not an isolated finance task. If PM-specific contractors are ignored during pre-checks, external maintenance execution will paralyze at go-live. 4. Downtime is your ultimate gating risk. Run production-scale downtime simulations early to validate whether your historical transactional data volume requires aggressive pre-migration archiving.
Part 1, conclusion. Discover and prepare phase migration incidents conclusion.
We have covered all 44 critical incidents across the discover and prepare phases of the project. If there is one golden rule to take away, it is this. Migration failures are rarely born during the cutover window. They are born during discover and prepare. Selecting an incorrect migration strategy, underestimating custom code, or failing to run detailed sizing assessments guarantees a delayed go-live. Mastering these early-stage incidents proves that you think like a true enterprise solution architect, not just a configuration consultant.
The 6-part series overview. The 6-part EAM and PM migration incidents roadmap.
This video concludes part 1 of our exhaustive 6-part migration masterclass. Here is what we are covering across the entire series. This comprehensive series covers the entire SAP Asset Management migration lifecycle across 275 real-world incidents. Part 1 incidents 1 to 40 for this video. Discover and prepare phases related migration incidents strategic planning, readiness checks, CVI, and pre-conversion cleansing. Part 2 incidents 45 to 85. Explore and early realize phases related migration incidents sandbox conversions, SPDD and SPAU adjustments, and technical build failures. Part 3 incidents 86 to 127. Realize phase-related migration incidents UX custom code remediation, Fiori security, Launchpad architectures, and user acceptance testing. Part 4 incidents 128 to 175. Realize phase-related migration incidents data complex integrations with EWM, Ariba, BTP, Data Migration Cockpit, and UAT execution. Part 5 incidents 176 to 222. Deploy phase-related migration incidents mock cutover rehearsals, production downtime, and early hypercare incidents. Part 6 incidents 223 to 275. Run phase-related migration incidents, HANA database optimizations, post-go-live CDS view performance, and critical production outages.
The ultimate goal.
This 275 incident series is designed to bypass abstract theory. By the end, you will understand how real S/4HANA programs succeed, why they fail, who owns the risks, and how experienced architects resolve incidents before they become multi-million-dollar production disasters.
Links in the description.
For all parts Part 1 through Part 6, please check the links provided in the video description below. Save this video and subscribe to continue the journey. Do not forget to subscribe, and I will see you in Part 2 where we dive into the sandbox and technical conversion incidents.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.